Hello everyone and welcome to this AP Chemistry virtual lesson. This is the first lesson in a series of lessons on AP Chemistry. The lessons will be presented daily, Monday through Friday. We begin today, March 25th, and this series of lessons will run through Friday, May 1st. My name is Michael Faribault, and I teach chemistry, AP Chemistry at Albemarle High School. Go Patriots. My school is located in Charlottesville, Virginia. Good morning to you. It is 10 o'clock in the morning where I live, which is on the east coast of the United States. I know that there are people who are watching this video. I assume most of them are studying AP Chemistry. They may live in other parts of the US or in other countries around the world. Even though some of you may be watching this video live right now, we want to remind you that each of these lessons will be recorded and available on demand on this YouTube channel for students to watch at any time. This is a virtual lesson, and as such, it will be a different experience from what I would normally do in my own classroom. In my class, I would be able to walk around the room and check on student work. Students would be able to ask me questions during the lesson. During these virtual lessons, I will make every effort to present the information clearly, and I will give you examples and diagrams and practice problems that will hopefully help you to better understand the content and the skills in the AP Chemistry curriculum. Today's lesson will cover topic 8.1, which is an introduction to acids and bases. During today's lesson, I will pause at different times during the instruction after I've asked a question. Now, this pause will give students a chance to process what I have just asked and to think about the answer to the question. In future lessons, you may find that I have so much to present, and there may be a lot of material in a 45-minute lesson, and I might be going too fast for you to keep up with all the information. But remember, each of these lessons is being recorded and will be available on demand. So what I'm saying is that sometimes I will be pausing to give you time to think, and there may be times in future lessons where you will need to pause the video. So for example, if you're in the middle of solving a problem and I, your teacher, start moving on to explain the answer to the problem before you are finished, feel free to pause the video to give yourself the time you need to complete the problem. And then when you're ready, you can click play to see if your answer is correct. Now, I'd like to make a few brief comments about the AP Chemistry exam for this year, 2020. For more information about AP exams, you can visit the following website, apcentral.collegeboard.org. Now, at the top of the page, you can click on the link that will give you more information about how the College Board is supporting schools that may be closed right now. And all of the details are there on the website for you to read on your own. But let me highlight a few important details. Traditional face-to-face exam administrations will not take place. Students will take a 45-minute online free response exam at home. Now, some students may want to take the exam sooner rather than later, while the content is still fresh, and other students may want more time to practice. For each AP subject, there are two different testing dates. The full exam schedule, specific free response question types that will be on each AP exam, and additional testing details will be available by April 3rd. Any relevant free response questions in AP Classroom will be available for digital use, so students can access all practice questions of the type that will appear on the exam. In AP Chemistry, the AP exam this year will only cover the material in units 1 through 7 from the course and exam description. Now, that being said, people watching this lesson might be asking the following question. Well, only content from units 1 through 7 will be tested on the AP exam this year. Why do the first three lessons that are scheduled for this week include topics 8.1, which is on acids and bases, 8.2, which is on pH and pOH of strong acids and strong bases, and 8.3, which is on weak acids and weak bases in equilibrium? Well, today, the topic that we are covering, topic 8.1, is one that colleges have asked that all AP students study, even if it is not tested on the exam in 2020. And colleges are supporting AP students this year by allowing a more flexible approach to the exam, where it will focus on a lesser amount of content than in other years. To make this relevant to your upcoming AP exam, today and in all lessons, we will include AP exam practice questions. And I'll be making connections today between topic 8.1 and selected topics from earlier units that will be included on the AP exam. Eventually, the full schedule of review topics for the remainder of this course will be available to you so that you, the student, can choose which topics you want to prioritize for review, and thus which virtual lessons you'll want to watch. So again, on AP Central, you can find a link to the information about these live AP review courses. And so, for example, right now, you're watching the lesson on chemistry. But as you can see, there are a variety of classes available and review on YouTube Live. All right, I'm going to begin with an overview of today's lesson. As I mentioned, in this lesson, you will learn about the following topics and skills. So the topic is 8.1, Introduction to Acids and Bases. In this lesson, we'll talk about how to calculate the values of pH and pOH. We'll talk about the Kw expression, which is the equilibrium constant for the autoionization of water. And we'll talk about what species are present in a neutral solution of water. The science practice or the skill that goes along with this topic is to identify an appropriate theory, definition, or mathematical relationship to solve a problem. There are some other topics from the AP Chemistry curriculum that are relevant to today's lesson, in which you should already be familiar with. So from Unit 4, which is on chemical reactions, topic 4.8 is an introduction to acid-base reactions. So today we'll talk about how to identify a Bronsted-Lowry acid and base. We'll talk about conjugate acid-base pairs and proton transfer in an acid-base reaction. The appropriate science practice or skill, describe the components of and quantitative information from models and representations that illustrate both particulate level and macroscopic level properties. Here are some other topics that are relevant to today's lesson. In Unit 7, which is on equilibrium, topic 7.9 is an introduction to Le Châtelier's principle. Identify the response of a system at equilibrium to an external stress using Le Châtelier's principle, and the appropriate science practice or skill, explain the connection between experimental results and chemical concepts, processes, or theories. Now, the specific stress we'll talk about with respect to Le Châtelier's principle is a change in temperature. So therefore, it's important that you understand from thermodynamics, which is Unit 6, endothermic and exothermic processes. So explain the relationship between experimental observations and energy changes associated with a chemical or physical transformation. The science practice or skill provide reasoning to justify a claim using chemical principles or laws or using mathematical justification. So as you can see, even though the official title of this lesson is 8.1, there are many other topics that are relevant to today's lesson. So give you an overview. We'll talk about the definition of pH and pOH today. I'll talk about the difference between the H+ ion and the hydronium ion or HCl+. We'll talk about the reaction of water with itself, the autoionization of water, relationship between pH and pOH in a pure water sample, and then the effect of changes in temperature on the value of Kw, which is the water equilibrium constant, as well as the pH of pure water, how that can change with changes in temperature. So here I'm going to start with a warm-up problem for you, and I pulled this problem from the 2014 AP Chemistry free response section. So what you're looking at on the screen is a reaction between propanoic acid and water. So it says propanoic acid is a carboxylic acid, CH3, CH2, COOH, and it reacts with water according to the equation above. Now, part A of this question is to identify a Bronsted-Lowry conjugate acid-base pair in the reaction. Clearly label which is the acid and which is the base. Now, while you are trying to answer this question, I'm going to go ahead and do some drawing on the screen. So I'm going to draw the formula of propanoic acid, and I'd like to highlight what is the specific structural feature about this molecule that makes it an acid. Now, so far I've drawn 5 hydrogens and 3 carbons, but we actually haven't gotten to the most important part of this molecule with respect to it being an acid, and that is this final hydrogen that's on the right. So that particular hydrogen is the hydrogen that is going to be donated. This is an acid, and it is a proton donor, or an H+ donor. Now, what is it reacting with? Well, it's going to react with a water molecule in this reaction, so I'm going to go ahead and draw a water molecule. And as you can see, the water molecule also has hydrogens. But in this particular reaction, the water is behaving as a Bronsted-Lowry base. So the acid is the proton donor. That means that the base is the proton acceptor. So in this particular example, we're looking at proton transfer, so the transfer of an H+, and it always is transferred in acid-base reactions from the acid to the base. Now, what do we have on the other side of the equation? Well, after this particular transfer has occurred, we're going to produce a molecule of water that has now accepted H+. This now becomes a polyatomic ion that has a positive charge. So that is the hydronium ion, HCl+, that you can see on the right side of the equation. And after this particular bond here breaks, then the propanoic acid will turn into the following ion. This is called the propanoate ion. So it has all of the atoms except for that final hydrogen. So the propanoate ion is considered the conjugate base. I'm just going to put CB here for short. And the hydronium ion in this case is the conjugate acid of water. All right, let's take a look at the official answers from the scoring guidelines for this question. It said identify a Bronsted-Lowry conjugate acid-base pair in the reaction. Clearly label which is the acid and which is the base. So as you can see, there were 2 acceptable answers to this question. So students could either have chosen this pair, which is the propanoic acid, and then the corresponding ion. Now again, don't forget, if you're writing these types of things down on your paper, don't forget to include include charges. There is a difference between a molecule and a polyatomic ion, so that charge is important. And in a similar way, we have this conjugate acid-base pair. Don't forget to include H3O plus, include that charge. All right, well, that was an example of conjugate acid-base pairs. Again, to remind you of this definition, which comes from Unit 4, Topic 4.8. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So we'll come to another problem. This will give you some more practice with conjugate acid-base pairs. So what you're looking at now are 4 different examples of acid-base reactions. Each of these reactions contains a water molecule. So I'd like you to focus on the water. In each reaction, decide if water is acting as a Bronsted-Lowry acid, in other words, as a proton donor, or as a Bronsted-Lowry base. So here is one of those moments I had mentioned earlier, in which I'm going to go ahead and give you a minute. I'm going to pause, give you a chance to work on this problem. You can either just think about it and imagine what the different properties are of the water in each of the 4 reactions, or if you're writing this down, it's be a good time to try to write this answer down. So again, each reaction, decide if water is acting as an acid or a base. All right, you might still be working on this question, and that's fine. I'm going to go ahead and start talking about the answers here. So again, if you need a little more time to process, feel free to pause the video. And the first reaction I'm going to take a look at is this one involving HCl. And many chemistry students already know that this particular chemical, which is called hydrochloric acid, is an acid. So that means it definitely is a proton donor. You can tell it's a proton donor because on the right side of the equation, we see a chloride ion, which means that this HCl has lost H+. That H+ has been transferred to the water, and you can see the hydronium ion on the right side of the equation. So in this first example, the correct answer is that water is behaving as a proton acceptor, as a base. Now, moving on to this equation down below, we have something called NH3, which is ammonia. And you might not be sure necessarily if ammonia is an acid or a base because it does contain hydrogens, and so on its own, you might not be sure what's happening. But it turns out, as you can look on the right side of the equation, that NH3, ammonia, has been transformed into NH4+, which is the ammonium polyatomic ion. So therefore, if the NH3 has acquired H+, it must have got the H+ from the water molecule. So in this reaction, water is behaving as an acid. It is a proton donor, and the ammonia is behaving as base, a proton acceptor. Now we come to these next 2 equations, and I specifically chose HCO3- for a certain reason, because just like the water molecule, HCO3-, which is also known as hydrogen carbonate or bicarbonate, this is found in baking soda. It has this property. It is amphiprotic, and just like water, it is able to behave as either an acid or base. So when you look at these reactants, you'll notice that they are exactly the same, and yet the products are different. So in one of the reactions, water might be behaving as an acid, and then in the other reaction as a base. Let's go ahead and analyze this reaction. We can see that the hydrogen carbonate ion has been transformed into carbonic acid, H2CO3, which means it must have picked up an H+ ion, in this case, from the water. So based on the direction of the proton transfer, that makes water acting as a proton donor, so as an acid. And in our next example, the hydrogen carbonate or the bicarbonate has turned into the carbonate ion on the right, so it must have lost the H+ that was transferred to the water. So the bicarbonate is behaving as an acid, and the water as a proton acceptor behaves as a base. So the 4 correct answers to this question are right here on the screen. All right, moving on to our next practice problem. This particular problem involves concepts from units 6 and 7. We have to talk about a reaction being either endothermic or exothermic. That would be from thermodynamics in unit 6. And we're dealing with an equilibrium system. That would be unit 7. So here we have a chemical reaction between N2O4 on the left, and then we have 2 molecules of NO2 on the right. The chemical equation shown above represents the reversible reaction. You can see the double arrows there, in which N2O4 is converted into NO2, and the value of the equilibrium constant for this reaction, that's capital K, is equal to 0.005. Now we're not doing any calculations with the equilibrium constant, but just note that this particular value is at 25 degrees Celsius. That's important because something is about to change. It says if the temperature of the reaction vessel is increased from 25 degrees Celsius to 100 degrees Celsius, you have to make a prediction. Do you predict that the value of K, the equilibrium constant, will decrease, will increase, or remain the same, and justify your answer? So as I mentioned, thermodynamics is important, and energy, and the fact that this could either be an exothermic or an endothermic reaction. Some of you who are very familiar with this process and deciding if something is endothermic or exothermic might be focusing on the delta H right now. The delta H is positive 58 kilojoules per mole reaction. I'm going to ask you to ignore that delta H for just a moment, and I'm going to go ahead and just draw on the screen some structural formulas. Now, I'm not going to draw all of the complete bonding and non-bonding pairs. I'm just going to show the connectivity. So we have a molecule of N2O4, and on the right side of the equation, we have 2 molecules of NO2. And what I'd like to do is remember something that you may have learned already in AP chemistry, and that has to do with the energy associated with breaking and forming bonds. So as you can tell from these structural formulas, as you proceed from left to right in this particular reaction, clearly it involves we are breaking a bond. And what many chemistry students have learned in their classes is that breaking a bond is an endothermic process. So energy is absorbed in the breaking of a chemical bond. So that's your first clue if you did not have access to this delta H value. Your first clue looking at the structural formulas in that from left to right. Now sometimes in chemical reactions bonds are both broken and formed, but in this particular example, it's fairly certain that a bond is broken, and therefore this is an endothermic process. Of course, going back to this delta H, students who have studied the change in enthalpy will know that the delta H value for a chemical reaction or for a process, physical or chemical change, if it is positive, that's an endothermic process, and if it's negative, that's exothermic. So again, here we have another reminder, this is an endothermic process. I'm going to go ahead and add E for energy on the left side of the equation. So energy is absorbed. Now let's take a look at the second part of this question where it says if the temperature is increased from 25 to 100 degrees Celsius, do you predict that the value of K will decrease, increase, or remain the same? What you should know about equilibrium constants is that they are temperature dependent. So the correct answer to this question is that it's either going to increase or decrease, it will not remain the same. Now you're thinking, well, what would an increase in temperature do to the value of K? And it turns out that when you increase the temperature, that puts a stress on the equilibrium system, and the equilibrium position will respond to that stress by trying to affect a change that is related to the stress. In this case, adding more heat by raising the temperature. This reaction will shift in the endothermic direction, in this case from left to right. And as it experiences that shift, it will favor the products, and that will increase the value of K. So the correct answer to this question, the value of K should increase when the temperature is increased. The reaction is endothermic, and an increase in temperature shifts the reaction to favor more products relative to the reactants, resulting in an increase in the value of K. Now you might think, what does this have to do with acids and bases? It sounds like this is all about thermodynamics and equilibrium. Well, here we come to the next question. A chemist has 3 different samples of pure water. Each sample is at a different temperature as shown below. So we have 3 samples of pure water. One is at 10 degrees Celsius, one's at 25 degrees Celsius, and the other is at 40 degrees Celsius. Does each of these samples of pure water have the same pH value? If yes, explain why. And if no, explain why not. So depending on how you answer that question, yes or no, you might have the ability of ignoring the next part. The next part says if these samples do not have the same pH value, arrange them in order from lowest pH to highest pH. Now I've already kind of given you an outline and overview of this lesson, and you may recall that I talked about the dependence of Kw on temperature. So I'm going to tell you, especially based on that last problem we just did involving a change in the value of K, that the Kw for water as well as the pH is most definitely affected by temperature. So does each sample have the same pH value? No. If no, explain why not. Temperature will affect the magnitude of the Kw, which directly affects the value of pH. But how you arrange that from lowest pH to highest pH, you may not necessarily be able to do at this point. So I'm going to skip the answer to the arrangement for a little bit later in the lesson when we can talk about the specific effect of temperature on Kw. So we'll come back to this question in a moment. What I'm going to do now is to highlight some specific things that you need to know about topic 8.1. All right, so we have definition of pH and pOH. You can see, and these equations are also listed on the AP equations and constant sheet that you get on the AP exam, that the pH is the negative log of the hydronium concentration. concentration. Now, on the equation sheet, it's actually listed like this. It's the negative log of H+. So don't be confused when you see that, because remember, we said that H+ and hydronium are going to be things that we can see on the AP exam, so that's going to be something I'll mention there, interchangeable. Now, if you know your math and logs, you can actually rearrange the equation to solve for the concentration of H+. So the opposite, in this case, the inverse, would be 10 raised to a certain power. So in this particular case, because we have a negative log, that means that the concentration of H+, which is going to be in moles per liter, is equal to 10 raised to the minus whatever the pH value happens to be. That's a good relationship to be able to work with that on the AP exam. All right, so the term H+ and H3O+ can be used interchangeably. So if you look at these two reactions involving hydrochloric acid, the first reaction shows the transfer of a proton to a water molecule, and it forms hydronium, H3O+, and chloride. The second reaction does not show water as a reactant, but you still get H+ and Cl-. So as far as you're concerned, H+ and hydronium are used interchangeably. And with respect to, let's say, particle diagrams, here, for example, is a water molecule. H+ would just be a single white circle, and a hydronium ion in a particle diagram would look like a water molecule with an extra hydrogen attached to it. So do not be confused if on a particle diagram you see these little symbols. Here, for example, is a sample of HX, which contains H+ and X-. Now, the blue circles represent some negative ion that goes along with the hydrogen in a acid. But the diagram on the right would be equivalent in that we're not showing actual water molecules here, but in the particle diagram, if you see H3O+, you can think of it as the equivalent of H+. Right, well, I've already mentioned that water can behave as both an acid and a base. So when I say autoionization of water, what I'm talking about is a water molecule reacting with itself. That means that one of the water molecules is going to behave as an acid. So I'm going to go ahead and put a circle around this particular H+, and I'm just going to go ahead and transfer it over to this water molecule. So we have this water molecule behaving as a proton donor, and then this water molecule behaving as a proton acceptor. You would form the hydronium ion and the hydroxide ion. So the hydronium ion would be considered the conjugate acid of water, and the hydroxide ion is considered the conjugate base of water. Now, interestingly enough, you might wonder, does this particular reaction happen very much in water? Well, it does happen, and it's a very important process, but the value of the equilibrium constant, which in this case would be the concentration of hydronium times the concentration of hydroxide, is very, very small. Now, it's so small that we're going to go ahead and write this in scientific notation. So at room temperature, or 25 degrees Celsius, this particular value is, we call the kW, 1 times 10 to the negative 14. Now, when I show you a symbol in brackets, that means molarity, that's concentration, that's moles per liter. Sometimes you'll see it written like this, so moles per liter. Sometimes you'll see capital M, but that means the concentration of hydronium ion times the concentration of hydroxide ion, and that equals 10 to the negative 14. So in pure water, those two concentrations are the same. Earlier, I had mentioned the AP equations and constant sheet. So here I'm showing you a portion of that equation sheet right now. You can see that here is a reference to that particular equation. So not something you have to memorize. It's definitely going to be provided for you on the AP equation sheet, but it's going to be familiar with these. And then tomorrow's lesson, which talks about pH of strong acids and strong bases, you will definitely see these equations here. And on Friday, the lesson that has to do with weak acids and weak bases will focus on these equations. All right, so I'm now going to show you another particle diagram. We have a particle diagram on the left and a particle diagram on the right. The question says, which of these particle diagrams represents a sample of pure water? How can you tell? So you have to focus specifically on the H3O+ and the OH-. So it looks like I have 1, 2, 3 particles of H3O+, and it looks like I have 1, 2, 3, 4, 5 particles of OH-. So therefore, this particular solution is not pure water. It is a basic solution in which the concentration of hydroxide is greater than the concentration of hydronium. But on the right, if you count, you can see we have exactly 4 hydronium and 4 hydroxide. So therefore, this is classified as neutral because the concentration of H3O+ or hydronium is equal to the concentration of hydroxide. Now, many of you, if I were to ask, what is the pH of this particular solution? This is neutral pure water. Then you would say, well, it's a pH of 7. And the official answer is we don't know, because we don't know what the temperature is. And I'll come back to that. So only at 25 degrees Celsius is the pH of water 7. Some people think that pH of 7 is what defines neutral. In fact, what defines neutral is about the concentrations of each of these ions. So if the concentration of hydronium is equal to the concentration of hydroxide, that is what makes this a neutral solution. All right, so the relationship between pH and pOH in pure water is that they are the same. Because the concentrations of hydronium and hydroxide are the same, the pH is equal to the pOH. So at 25 degrees Celsius, the pKW, which is just the negative log of the kW, is equal to 14. That's where we get that number. And since they're equal, then 7 plus 7 is 14. Again, all these equations are given to you on the equation sheet. So now I want to talk about the effect of changes in temperature on the value of kW and the pH of pure water. You may remember that I had drawn an E on the left side of the equation for that reaction in which N2O4 was converted into NO2. And that was because it was an endothermic reaction. Well, it turns out that this one is also endothermic. That means that when you raise the temperature, you are going to shift the equilibrium in a certain direction, and when you lower the temperature, you will shift the equilibrium in the opposite direction. So the value of kW is temperature dependent, as all equilibrium constants are, and the pKW is going to be a number other than 14 when the temperature is something other than 25 degrees Celsius. All right, I'm now going to give you some guided practice. And as we do this, I'm going to switch my screen for just a moment so I can show you a calculator. So I'm going to go ahead and end the show. And what you should see is a calculator. And we have some problems involving pH and pOH and the concentration of hydronium and the concentration of hydroxide. So I'm going to go ahead and type in on my calculator the negative log of 1 times 10 to the negative 9. Now, I didn't necessarily need my calculator to do this because that was a really simple number, but just to show you the process, the negative log of the hydronium concentration gives us the pH. So in this case, if the concentration of hydronium is 10 to the minus something, then that something is what we call the pH. Now, if I want to figure out the hydroxide concentration, I could take the kW, which is 1 times 10 to the minus 14, and I could divide by the concentration of hydronium. In this case, 1 times 10 to the negative 9. And if I did that math, I would get 10 to the negative 5. 1 times 10 to the negative 5, which is the concentration in moles per liter of hydroxide. And of course, if I did the negative log of that value, I would get a pOH of 5. So even though I did use my calculator, this particular table is filled with a bunch of relatively easy kind of mental math problems. You will certainly have access to a calculator on the AP exam, but I wanted to go ahead and just show you that you could use your calculator to do some of these calculations. Tomorrow, in the lesson on topic 8.2, which is on the pH and pOH of strong acids and strong bases, you will certainly have an opportunity to do those same types of calculations. All right, so I'm now going to go back to the display here, and you should be able to see the rest of the problems in this table. Okay, so on the right side of the screen, you can see the relationships between concentration of hydronium and hydroxide and the pH and pOH definitions. So I'll give you a few moments to see if you can mentally or actually on your scratch paper fill in the remaining numbers in this problem. So I'm going to give you a moment to think about and work on these next 3 rows. All right, let's take a look at the second row. We have a pH of 4, so hopefully you can see that the concentration of hydronium ion would be 10 to the minus 4, and the pOH would be 14 minus the pH. That means that the pOH would be 10, and the concentration of the hydroxide ion would be 1 times 10 to the minus 10. In our next row of the table, we are starting not with the concentration of hydronium, but rather with the concentration of hydroxide. If we take the negative log and we get 12 on our calculator, remember, 12 is not the pH. 12 would be the pOH, and the pH would be 2, since 14 minus 12 is 2. So be careful when you're solving problems that you realize whether that's a pH or a pOH, and you can get that straight and not confuse those two quantities. In our final row of the table, if the pOH is 8, 14 minus 8 is 6, and the concentration of hydronium would be 10 to the minus 6, and the concentration of hydroxide would be 10 to the minus 8. All right, now as promised, we're going to talk more specifically about temperature and pH, and we'll get back to that problem I showed you earlier with the 3 flasks at different temperatures of pure water. So take a moment to process the information in this table. You'll notice that we have something called the pKw. Again, that's the negative log of the kW. So I ask you to look closely at these pKw values. Now what happens as you go from top to bottom in this table is the temperature is increasing. Look at what happens to the value of pKw as the temperature increases. And what happens to the value of kW as the temperature increases. So be careful that you have to realize that 10 to the minus 13 is a larger number than 10 to the minus 14. And 10 to the minus 14 is a larger number than 10 to the minus 15. So be careful that you don't confuse when something is increasing or decreasing. While the pKw's are getting smaller, the kW values are actually getting larger. So what I have done on my calculator is I have taken 10 to the minus 14.5, 10 to the minus 14.2, and then so forth and so on. So if you look down that far right column, you notice that the actual values of kW are getting larger. We've seen this before in other example problems where endothermic reactions, their K increases. So it says based on this information is the autoionization of water. An endothermic or an exothermic process justify your answer. So what I would hope you recognize once you realize how to do this math is that when a K value, when an equilibrium constant increases with increasing temperature, that results in a shift according to Le Châtelier's principle. So here's what I said. The autoionization of water is an endothermic process. As the temperature of water increases, we notice that the value of pKw decreases, but more importantly, the value of kW increases. So what does that mean? That an increase in temperature is causing a shift in this particular reaction in the endothermic direction, so from left to right, and it favors more products, and that increases the value of K. So how does this affect pH? Well, on the next slide, you can see that I'm showing you different temperatures, and we have the same pKw values I showed you on the previous slide. So now, on the previous slide, we talked about the kW. Let's talk about pH and pOH. 14.2, half of that is 7.1. So at 20 degrees Celsius, not 25, the pH of pure water is 7.1. The pOH is not 14 minus 7.1. It's actually 14.2 minus 7.1. And as you already know, in pure water, pH and pOH are the same. So as I continue to fill out this table, here is the message that I want to send to you. When water is hotter than 25 degrees Celsius, your pH goes down. This does not mean that water becomes acidic. It just means that the kW and of course the pH is going to change. So once you are no longer at 25 degrees Celsius, the pH of water is no longer going to be 7. So for pure water, at temperatures above 25 degrees Celsius, the pH of water is actually less than 7. So remember that for our follow-up to this question I showed you earlier with the 3 flasks. And at temperatures below 25 degrees Celsius, the pH of water is greater than 7. However, we are not changing the neutrality of water. Pure water is still neutral because pH equals pOH. So let's go ahead and return to this question. A chemist has 3 different samples of pure water. Does each sample have the same pH? We already said that answer was no, because the temperature changes, kW changes, and so does the pH. So how can we arrange these values from lowest to highest pH? Well, if you remember from what I showed you on the previous slide, hot water actually has a lower pH than room temperature water. So the correct answer to this question about how to arrange them is like this. The 40 degrees Celsius water would actually be the lowest pH, and the 10 degrees Celsius water would be the highest pH. A student heats a sample of pure water to a temperature of 50 degrees Celsius and records the pH at 6.6. What is the value of pOH at 50 degrees Celsius? Now, anyone who was not paying attention to all of these previous examples might say 14 minus 6.6, 7.4, but of course that's incorrect. In pure water, pH equals pOH, so the pOH would also be 6.6. All right, I'm going to show you one more practice problem, and then after this practice problem, I'm going to go to an AP practice problem that I will give you for homework. So this problem will be the last problem that we do together in this lesson, and then I will show you an AP problem on the screen. When I get to that final problem for homework, you can just take a screenshot or pause the video, and then in tomorrow's lesson, you'll be able to see the answer to that question. Let's go ahead and finish up with this particular practice problem. All right, a sample of pure water has a pH of 7.39. So what is the value of the pOH at this temperature? And the answer is 7.39. What is the value of the H3O plus in the sample? You have to do 10 raised to the minus something. In this case, 10 raised to the minus 7.39. If you do that on your calculator, you get 4.1 times 10 to the negative 8. That's the number of moles per liter for both hydronium and hydroxide. And if you multiply that number by itself, in other words, if you square it, that will give you the value of kW. In this case, it is not 10 to the negative 14. It happens to be 1.7 times 10 to the negative 15 if you do that math on your calculator. So is this hot water or cold water? Well, if we know that the reaction is endothermic from left to right, then this would represent cold water because the pH was actually higher than 7. All right, I'm going to move on to a summary and that final AP practice question. So in today's lesson, we talked about the definition of pH and pOH. We talked about the fact that H plus and H3O plus are used interchangeably. We talked about what it looks like in pure water and how the kW is affected by a change in temperature. So I'm now going to switch to your homework problem. This homework problem is going to take up 2 different slides. So if you are going to take a screenshot, it's going to be more than just this particular screen. And so this particular AP exam practice question will remain on the screen, or you can hit pause and you can write this down. So we have this particular question. Answer the following questions related to the chemistry of HI, hydrogen iodide. A solution of aqueous HI is added to a solution of methylamine, CH3 and H2. An acid-base reaction takes place. All of the water is removed by evaporation, producing crystals of the ionic compound methylammonium iodide. In the reaction described above, methylamine and the methylammonium ion represent a conjugate acid-base pair. Does the methylamine behave as an acid or a base in this reaction? Justify your answer. Write the chemical formula, including the correct charge for the methylammonium ion. Then, related to HI, we have a chemical equilibrium involving HI, and the reaction has an equilibrium constant of 790 at 298 Kelvin and 55 at 700 Kelvin. So based on the information shown above, is the forward reaction from left to right classified as an endothermic process or as an exothermic process? So again, if you're watching this video live, you can always pause the video. If you're watching it later on demand, these 2 questions will be what will be talked about in tomorrow's lesson. So this brings us to the end of this lesson on topic 8.1. I want to say thank you to everyone for watching. We hope that you will join us again for the entire series of AP chemistry questions. Again, be sure to complete that practice question and we'll review the answer in the next lesson. So again, thanks everyone for watching.
Good morning, everyone, and thank you for joining us on our second of multiple lessons on topics around AP chemistry. We appreciate you taking the time away from TikTok and Fortnite and joining us here for the next 45 minutes. I'm Mr. Sean Byrne. I teach at Lombard West High School outside of Chicago in Glenelg, Illinois. Go Hilltoppers! And I'm really excited to be here with you to share what will be the second in a long series of lessons. If you haven't had a chance to go back and look at yesterday's lesson about topic 8.1, now might be a great time to stop and go back and watch that lesson to prepare you for what's happening today. Before we get started, I do want to remind you of lots of resources that are going to be continually available for you over the next couple of days and weeks. Anytime you have a question about what's happening in your AP course, we encourage you to go to apcentral.collegeboard.org. When you get there, you will see that there is a link for all of the things that we are doing to support you during your times at home in reaction to the coronavirus precautions. Once you get to this screen, you'll be able to scroll through multiple different resources that are at your disposal. This is just one of many resources that are here to help you make sure that you're prepared for your AP exam in a couple of weeks. Just as a quick reminder that for all of us, our traditional face-to-face exams will not take place. All students will take a 45-minute online free response exam. Many students will take this at home, and some of you will take it at school with your teachers, depending on how your school is reacting to the coronavirus. Stay on there for a minute. Students will be given the choice of 2 different AP times, 2 different dates. One of them will be sooner. If you feel like you would like to take it right away while the content is still fresh, that's great. If you want some more time to practice, you'll be given that option as well. And again, your teacher will work that through with you, and so you should continue to communicate with your teacher about the testing dates. All of this information and lots more details will be released on April 3rd, which is a week from tomorrow. So until then, we're going to continue learning chemistry to the best of our ability, and when we have some more information about our exam in particular, everybody will share it with you, especially on apcentral.collegeboard.org. For our class specifically, chemistry, we know that units 1 through 7 will be on the exam, and units 8 and 9 will not be on the exam. You may notice that today's lesson and yesterday's and tomorrow cover topics that are important from unit 8. This is because we feel that these is still very important information for you to know about chemistry, because colleges has asked us to continue to work with you on these important topics. Eventually, many of you will go on to other science classes, maybe even more chemistry, and we know that this is important information for you to use when you get to those courses. There are multiple classes, multiple review sessions that are going to be happening every day for your pleasure. If you right here, we're at chemistry period 2. I myself will be tuning in for my good friend Kristen Brandt, and she'll be teaching us about some human geography later this afternoon. So let's get into our lesson overview. Today, as I said, we will be focusing in on topic 8.2, which is on the pH and pOH of strong acids and strong bases. This will build heavily on the material from yesterday, which was looking at the pH and the pOH of water in particular. So again, I would encourage you to stop when you have a minute and go back to watch that video. We'll be looking at many of the mathematical routines and how to solve mathematical problems on pH and pOH. Yesterday's topic alluded multiple times to Brown-Sedlowry acids and bases and conjugate acid bases and pairs, conjugate acid base pairs, excuse me. We'll do the same thing today, and we will spend a lot of time looking at models and representations of how molecules work when they are in an aqueous solution. Next, we're going to make sure that we are feeling very good about drawing reactions, or writing reactions, balancing those reactions so that they're consistent with a particular model. Again, our particle pictures will be very important today. Stoichiometry never leaves the conversation when we're talking about chemistry, and so we'll have some simple stoichiometry problems today, but we're again laying the foundation for what you will do tomorrow. So make sure that these mathematical routines are good habits for you starting today, so that you'll be able to take them out for a ride tomorrow when the math gets a little bit more challenging. I put together a number of different pictures for you, like I said, and then we can't talk about pH without talking about solutions and how the molarity of the solution is going to change and change our understanding of what's happening with the pH. So this is lots of mathematical routines that I think you can see we're going to be working with today. The overview, the plan that I have for today is we'll do a quick review of the problems that Mr. Faribault gave you yesterday and the topics that he covered in terms of pH, pOH, and KW. And then by the end of today's class, you should feel really comfortable finding the hydronium ion concentration, the pH, the hydroxide ion concentration, and the pOH of a strong acid and a strong base. We'll give you multiple opportunities to do it directly, and then we'll give you a couple of AP problems, or AP lab problems to be able to take your skills to the next level. So our warm-up every day is going to be in response to the problems that you saw yesterday. So the first problem that Mr. Faribault gave us asked us to consider what happens with hydrogen iodide. We have a solution of hydrogen iodide that gets added to a solution of methylamine, CH3 and H2. The problem tells us that this is an acid-base reaction, and that then all of the water is removed by evaporation to produce crystals of the ionic compound methylammonium iodide. Here again, we see the idea of a conjugate acid-base pair is coming up again for us to consider. So think about how methylamine and methylammonium behave as a conjugate acid-base pair based on what you remember from tomorrow. Our question for today, or to begin with, is does the methylamine behave as an acid or base in this reaction? And I think one of the keys here, one of the tricks, is to look at hydrogen iodide in an aqueous solution. And I hope that jumps out at you as one of our 7 strong acids, especially when it's in an aqueous environment. Hydrogen iodide can be called hydroiodic acid and is one of the 7 strong acids that we have listed up here. This is a great piece of information to put on a note card for yourself to review on a daily basis between now and your exam day. The more you're familiar with these, the more automatic these strong acids are for you. The easier problems are going to be for you to solve because you won't have to think as much about this. So that sort of hints at what the answer to this question is going to be, but let's dive even deeper. I'm going to isolate what are the important chemicals that are part of the problem that's given to us. I tell my students regularly that we have to start chemistry by writing some sort of a reaction. So based on the information that's given to us in this paragraph, we see that HI is reacting with CH3 and H2 to make methylammonium iodide. Now at this point, you may still not be able to write the formula for this, but I promise in a couple minutes this will jump off the page at you. So if we've identified that hydrogen iodide or hydroiodic acid is behaving as an acid, then we can assume that methylamine is behaving as a base in this reaction. However, we want to make sure that we're using good chemistry to answer this question. So saying that hydroiodic acid is an acid, so the other one must be a base, is probably not the strongest answer for us to provide here. And we want to go back to good chemical principles that say that methylamine behaves as a base because it accepts a proton. Bases by definition are proton acceptors, and that would be a really nice final answer here. For those of you that are having a hard time seeing how methylamine can be a proton acceptor, let's look at some pictures of what this, some different representations of what this would look like. So one way to talk about this reaction would be to draw some particle pictures. Hydrogen iodide might be represented something like this, with our hydrogen being the white sphere here and iodide being a purple one. Methylamine would look something like this, where we have a methyl group, C carbon, with 3 H's around the outside of it, bonded to an amine group. Now what I hope jumps out at you is the fact that this has a lone pair of electrons that is hanging off the right side of this. This is an area where methylamine can accept a proton because this lone pair is ripe for accepting that proton. Our next, the solution to the product of this would be something like iodide, a nice negatively charged particle having lost that hydrogen, and methylamine turning into methylammonium as it has a positive 1 charge. The proton that was here joins on to the amine group over here, and we have our carbon with 3 hydrogens around it, our nitrogen with 3 hydrogens around it as well. The third way we might represent this reaction would be to look at those structures. So you may feel comfortable writing HI. The iodide has lone pairs around the outside here, but if this is acting as an acid, this hydrogen is going to be able to jump out. We see a lone pair of nitrogen hanging over here. Again, this gives us our iodide ion on the right and our methylammonium in the middle. It's important for us to note that the hydrogen is bonded to the nitrogen here. It is not bonded to the carbon. Our carbon is stable with its 4 bonds around it. Adding a 5th one in there would be very destabilizing and not the expected way that the hydrogen would join itself over here. And so this structure over here is probably the best way for us to consider methylammonium. And that hints at the answer to the second part of this problem, right? The second part of the problem asks us to write the chemical formula, including the correct charge for the methylammonium ion. I hope that based on our earlier pictures, you can see that CH3 and H3 plus 1 is the best way for us to write the formula for methylammonium ion. Of course, there's some other ways that you might have gotten to this answer. If you're feeling comfortable with your functional groups and saying that methyl is here and ammonium instead of NH3 plus, similar to the NH4 ammonium polyatomic ion, that's great. But if looking at thinking about this in terms of particle pictures is a better way for you to do it, then you should go ahead and do that and feel comfortable drawing that on your pages as you're answering these questions. The second problem that we were asked to consider from yesterday, again, looks at hydrogen iodide, but it looks at the relationship between the temperature of this reaction and the equilibrium constant. We're asked to consider is the forward reaction as written an endothermic process or an exothermic process and to justify our answer. So the first thing that I noticed when I looked at this was that as the temperature increased, our equilibrium constant decreased. We see that the temperature goes from 298 to 700 and increased, but the equilibrium constant decreases from 790 to 55 because the equilibrium constant is written as products over reactants. This hints at the idea that when the temperature goes up, we have fewer products relative to reactants in our second experiment here. So I think a good response to this would say that the equilibrium constant K decreases when the temperature increases. We're stating what piece of information, what piece of evidence we're pulling out from this data. And this indicates that the amount of products in equilibrium is less at higher temperatures. Raising the temperature shifts the equilibrium to the left, meaning that we are using up some energy or towards the endothermic reaction. And this indicates that as written, the equation is exothermic. The energy can be considered some sort of product here. And when the temperature goes up, we're going to use up that product to shift it to the left. Okay, so let's jump into our lessons on pH and what you need to know for today. Like I said, we're going to start with a quick review of what we did yesterday and a review of pH, pOH, and KW. If you feel like you would like to stop at this point again and go back to watch our lesson from yesterday, this would be a great time to do this. This entire lesson will be recorded and you can come back to this at any time that you would like. We know that all of pH is built on the foundation of the autoionization of water. That all the principles that we're looking at over the course of the next couple of days come back to this reaction of water reacting with itself to make hydronium ions and hydroxide ions. We know that at 25 degrees Celsius, experimental results tell us that the KW, or the product of hydronium ions and hydroxide ions, is 1.0 times 10 to the minus 14. What we'll use today is 2 different variations of this equation that you would want to be comfortable with. While this information on the center of the screen is available to you on the AP Chemistry equations page, the rearrangement of both of these equations into the equations to the bottom is not given to you per se. And this is just algebra. We're dividing the OH to one side or the hydronium ions to the other side. If we are given an OH concentration and we want to find the hydronium, we would use equations like this. If we're given the hydronium and we're trying to find the OHs, we would use equations like this. I just used algebra to get here, and you will always have this equation at your disposal. So let's consider a question where we are given given a hydrochloric acid solution that's at 0.0025 molar, and we're asked to consider find the pH and the POH. Like we said before, we're going to start every equation for every problem by trying to write a reaction. So hydrochloric acid is reacting with water to make hydronium ions and chloride ions. If we are told that we have a 0.0025 molar concentration or solution of hydrochloric acid, we can assume that we have a 0.0025 molar concentration of hydronium ions. Now, I'm going to give you a second to think about why we are okay making that assumption. And I hope that many of you remember that hydrochloric acid is a strong acid. It's one of our 7 that we need to continue to come back to. So if hydrochloric acid is a strong acid, which it is, we know that it completely dissociates when it's put into water. This is why I can write an arrow here instead of an equilibrium symbol, and why I can assume that hydrochloric acid, the concentration of hydrochloric acid is the same as the concentration of the hydronium ions here. So the first step of this is solved for us pretty easily just by using our chemistry knowledge and no math at all. I promise you tomorrow that first step will get a little bit trickier. So making sure that we're comfortable with it today is probably a great idea. To get to our hydroxide ion concentration, we're going to use this equation from the previous slide. We're looking at Kw divided by the hydronium ion concentration, 1.0 times 10 to the minus 14 divided by 0.0025, and that solution is 4.0 times 10 to the minus 12. Now in a minute, I'm going to solve one of these problems live with you and show you how we would put this into our calculator. So if I'm going a little bit fast right now, be patient with me and I'll show you how this would look in my calculator. Next, we can get to the meat of the problem and answer the question as it's given to us, where we say the pH is equal to the negative log of the hydronium ion concentration. So pH is equal to the negative log of 0.0025, and that is 2.60. Similarly, our POH is equal to the negative log of OH, which is equal to, the same as negative log of 4.0 times 10 to the minus 12, and our solution there is 11.4. Now many of you may see a simpler or an easier way to get through any of the 4 problems, any of the 4 answers that are here. You may recognize that pH plus POH is going to consistently add up to 14, and that's great. You probably are very familiar with your log properties. You remember that your Kw, if we take the log of both sides, how that would look. You may be in pre-calculus or beyond, and that's great. If not, the method that I just showed you is going to work all the time, and so you should feel comfortable practicing this way of solving a problem like this. Now let's look at a second problem where instead of looking at an acid, we're looking at a strong base. And NaOH is a great example of a strong base. Our reaction looks something like this, where sodium hydroxide splits apart into sodium ions and hydroxides. And because sodium hydroxide is a strong base, we can say that our concentration of NaOH is equal to our concentration of hydroxide ions. And so for this problem, we're going to start on the right side of my table here at the bottom, the right side of my page, say that the OH concentration is equal to 0.0015 molar. Similar, slightly different from what we did earlier. Our concentration of hydroniums is 1.0 times 10 to the minus 14 divided by that hydroxide ion concentration. And so that's equal to 0.0015, giving us a hydronium ion concentration of 6.7 times 10 to the minus 12. We're almost there. We're going to look at our pH to give us our final answer. Our pH is equal to the negative log of our hydroniums, is equal to 11.8, and our POH is equal to 2.82. And a really good spot check for myself is to add these two up, say, do they equal 14? They do, and so I know that I'm on the right track. So let's do some practice together now. We're going to mix things up a little bit, and if you're watching from wherever you are and your name begins with A through F, I'm going to encourage you to look at that first problem. If your name begins with G through M, I'm going to encourage you to look at that second one with KOH. If your name begins with N through T, look at that third problem with HNO3. I'll give you a warning there that nitric acid is a strong acid, and so you can use the same methods that we've used in the past. Lastly, if your name begins with U through Z, why don't you analyze lithium hydroxide there for us and see what you can come up with. I'm going to give you approximately 30 seconds to get started on these problems. I'm going to switch over to my iPad so that I can solve it live for you. If you feel like you would like to pause the video and solve this entire thing out, I'm going to give you solutions to all 4 of these problems, which means that you have 4 practice problems that you can come back to later on today or over the next couple of weeks as you are going on and practicing for the exam. So go ahead and jump into one of these on a stretch piece of paper, in a notebook, on an iPad, wherever you are able to. I'm going to switch my technology for a minute and I'll be back to you in about 20 seconds. It gives you about 10 more seconds to continue your work, and then I'm going to begin with the problem that's shown on the screen. So being at the beginning of the alphabet, I know that we tend to get our problem solved first. So I'm going to jump to our last problem that I shared with you for the end of the alphabet and let you guys see this problem solved live. As I said, I'm going to show you a solution to all 4 of the problems back on our screen in a couple of minutes. But if we wanted to think about how this would be put into the calculator, how we would solve all the steps here, I thought it'd be useful to show how I would write this up. So we're looking at lithium hydroxide, and we're being asked to find the same 4 quantities that we've done before. So I'm going to start by writing an equation, and I'm going to recognize that if I have 8.75 times 10 to the minus 3rd molar concentration of LiOH, that gives me 8.75 times 10 to the minus 3rd molar concentration of hydroxides. Why? Because we said that this is a strong base. Great. So then our next step would be to say that our hydroxide ion concentration is equal to 8.75 times 10 to the minus 3rd molar. I'm going to try to be really careful with my units here and make sure that I include units on everywhere where it's appropriate. In this problem, I'm going to jump ahead to the POH just to show that we can do this in a different order. So the negative log of the hydroxide ion concentration. So our POH is equal to the negative log of 8.75 times 10 to the minus 3rd. So our POH is going to be equal to, and if you want to follow along with me on my calculator over here, I have the negative log of 8.75 exponent negative 3, and I get 2.60 as my answer. That's 2.06, excuse me, keep me honest, thank you. My hydronium ion concentration is going to be equal to Kw divided by my hydroxide ion concentration. So for this equation, I have 1.0 times 10 to the minus 14 divided by 8.75 times 10 to the minus 3rd, 1.0 e minus 14 divided by 8.75 e minus 3, and I have an answer that is, just double checking my work over here, H3O plus is equal to 1.14 times 10 to the minus 12. Are you still with me? pH at this point is equal to my negative log of my H3O plus. pH is equal to the negative log of 1.14 times 10 to the minus 12. So my pH is equal to the negative log of 1.14 e minus 12, and I get 1.19 times 10 to the 1, which is 11.9. And when I did this on a different calculator, I got another decimal point there, and I got 11.94. So go ahead and check that at home to make sure that I did that correctly. But my spot check is to see if these two numbers add up to 14, and because they do add up to 14, I know that I'm on the right track. So excuse my messy handwriting there, but I did want to show you kind of the thought process through solving each of these problems, as well as how this might look in a calculator, because I know that some of my students do have a hard time with the calculator aspect of this, and so we will. I just want to show that to you. Hold on for just a second, and I'm going to stop sharing this screen, and we'll go back to sharing this screen. Okay, so 4 different problems for you to look at here. As I said earlier, you can feel comfortable to go back to any of these 4 problems at any time, and the solutions should be here for the first problem, A through F. So if you're working along with us, check your work. If you were solving problem G through M, sorry, if your name begins with G through M, and you were doing our second problem, that is on KOH, here's your solutions. If your name begins with N through T, excuse me, here are your solutions. And lastly, I hope that these numbers match with what we had earlier, and I'm pretty sure that they do, so we're good. So you can feel free to take screenshots of these or bookmark this and come back to it as some really nice guided practice problems. Like I said, these are pretty straightforward in terms of the math and the chemistry. Tomorrow we will be kicking up a notch, but you want to feel really comfortable on these problems so that when we do get a little bit more challenging, we have the same skills kind of developed in our brains. A second problem that is coming right out of an AP-like problem where we're asked to analyze 3 different solutions. The first one is 100 milliliters of 0.1 molar HCl. The second one is 200 milliliters of a 0.5 molar NaOH solution, and the third beaker has just 300 milliliters of distilled water. And we'd like you to rank these solutions in order of increasing pH, and then consider which of them would have the greatest change in pH by the addition of 100 milliliters of distilled water. So I'm going to give you about 30 seconds just to start setting up the first problem to see what information jumps off the page at you, and are you able to rank these solutions. 5 more seconds just to write down a quick thought or an idea about how you would tackle this problem. Okay, great. If you need more time, feel free to pause and come back to us when you have a good solution you want to compare to our solution. So I would set up some sort of a table that looks like this, and I would want to make sure that I analyze each solution independently before I try to compare them. So for solution X, hydrochloric acid, we have hydrochloric acid as a strong base. Ding, ding, ding. We remember that from earlier. Is reacting with water to make our hydroniums and our chlorides. I'm sorry if the picture is cut off there. But underneath the picture, you should see chloride Cl-. That means that the pH is equal to the negative log of our 0.01 because hydrochloric acid is equal to because it's a strong acid, right? So HCl will completely dissociate. So the concentration of HCl is the same as the concentration of hydroniums. So our negative log of 0.1 is equal to 1. Similarly, our NaOH will split apart or dissociate like this. So our POH is our negative log of 0.5. If you put that into a calculator, you would see that that's equal to 0.3. Now there's a trick here that this problem is asking us to put the solutions in order of increasing pH, not POH. And so we need to take the added step here of saying that the pH is equal to 14 minus the POH, and that would give us 13.7. Lastly, our water is just distilled water, and because the problem told us that we're at 25 degrees Celsius, go back and read that carefully. We know from yesterday that our pH of a water solution is equal to 25 degrees Celsius. Now you may notice in this that I did not take the volumes of the solutions into account at all. That this was only I only looked at the concentrations, and that's because we know pH is only relied or only dependent on the concentrations of the solutions. It's not reliant on the volumes of the solutions. And so the fact that this is a larger volume has no impact on the pH. You may understand that this is going to have an impact on what happens in the second part of that problem, but for this step right here, we're just fine. So our final step is to make sure that we answer the question. The question asks us to write the solutions in the increasing order of pH. So we're going to start with the lowest, which is 1. Then we would go to solution Z, which is water at 7, and we'd end up with solution Y, which is our basic solution. Now, many of you may have looked at this and been able to say, oh, this is acid, it has a low pH. This is base, so it has a high pH, and water should be somewhere in the middle. And so you'd be able to rank it like this, and that's great. If that doesn't immediately jump off the page at you, this is a great way to make sure that you have some mathematical data to back up what your correct reasoning is at this point. The second problem asks us to consider which of the three solutions will have the greatest change in pH by the take all your liters of water, and then we would justify our answer. So take another 30 seconds to consider how you would even set this up, what kind of pictures you might draw, and I'll be back with you in 15 or 20 seconds. So for me, I would set up a problem or a table that looks something like this, where I want to analyze the original solution to the new solution. And by new solution, I mean the addition of another 100 milliliters of distilled water. So if my original solution was 100 milliliters, my new solution is 200 milliliters. And if my original concentration was 0.1 molar, I know that my new solution is 0.05 molar. How do I get that? Well, when the volume doubles, the concentration would become half, especially if I'm just adding water. Many of us can do that problem in our head, but if you can't do that in your head, I'm going to show you in just a second of how you can mathematically prove that relationship. Using the same equation we've used multiple times today, the pH of a 0.05 molar hydrochloric acid solution would be 1.3. For solution Y, we go from 200 milliliters. Oh, excuse me. The change in pH here, there we go, is going to be 0.3. We went from 1.0 to 1.3, and so our difference, our change here is 0.3. Solution Y started at 200 milliliters and is going to go to 300 milliliters. And so solving for the molarity here is probably much more challenging for many of us. And so we'll do a dilutions review here. Remember that the equation for a dilution is dependent on the fact that the number of moles of solute do not change. So we can say M1 times V1 is equal to M2 times V2. This equation is given to you on the equation page, and so it's not something you need to memorize, but it is a really handy one to use in multiple instances. If we are solving for M2, so the molarity of our new solution would be an M2. We can say M1 times V1 divided by V2. I will plug in my numbers here, and we get a final molarity of 0.33. Now many students will take the added step of converting the volumes here to liters, and typically we would look at volumes in liters, so we would have 0.2 and 0.3. But because the relationship between the volumes 2 to 3 or 0.2 to 0.3 stays the same, we can plug these numbers in to still get the same answer. So our new molarity here is 0.33 molar NaOH, and that's kind of the key to this problem. So our pH goes from 13.7 to 13.52 for a difference of 0.17. This pH happens to be going down, but the overall difference is 0.17. Water doesn't change, right? We add some more water to it, but the pH is not going to change. As we learned yesterday, the only way we're going to change the pH of distilled water is to change the temperature. So as long as we stay at 25 degrees Celsius, which the problem told us, we have no change in our pH. So a good solution to this would be to clearly identify that solution X will have the largest change in pH after 100 milliliters of water is added, because the concentration of the solution is changed the most. The larger change in concentration will cause a larger change in pH. This problem asks us to give a solution and to give an explanation. So I think both of these sentences are important for you to include on your final answer, so that the reader understands that you had more than just like a guess, that you really thought through what the answer was and you have good reasoning behind what your answer is. And that brings us to the end of our official lesson for today. As we went through all of our material today, we reviewed our pH, our pOH, and our kW from yesterday. I hope you're feeling much more confident in finding those 4 quantities for a strong base and for a strong acid. If not, you can watch this video multiple times because it is being recorded and will be available to you within the next couple minutes. Our exam practice problems for tomorrow, we have 2 of them for you. You want to take a screenshot of this, or you want to pause the video right here so that you can write down the important information. This one comes from the 2014 AP Chemistry exam. It looks very similar to, it is the same beginning prompt from what we looked at yesterday, but we're looking at part C2. Part C asks us to determine if this statement is true or false. We're looking at the pH of hydrochloric acid is the same as the pH of propanoic acid, and propanoic acid is identified up here as a pH of 2.79. So you probably are not yet able to determine the concentration of the propanoic acid, but given the fact that hydrochloric acid has a pH of 2.79, you should have enough information now to solve for the molar concentration of hydrochloric acid. So we would like you to calculate that before tomorrow's lesson, and then what Mr. Fairbaugh will do was help you to solve that and preview what we would do for propanoic acid. And by the end of class tomorrow, you would be able to solve all of this problem. Second problem for you is to consider 4 different acids, 1, 2, 3, and 4. This may be cut off, but it says pH of acid 4 up here. And each of these acids was tested at 5 different concentrations. These are increasing concentrations, and the pH of each of them was measured. The experimenter knows that these 4 acids are chloric, lactic, and propanoic acid, but we don't know which one is which. But you should have enough information to be able to determine which of the 4 acids listed in the table is hydrochloric acid. So think about the knowledge that you have so far, and you will be able to answer this question. Again, Mr. Fairbaugh will answer this question for you at the beginning of class tomorrow. So thank you so much for sticking with us and for all your efforts on today's problems. As you're working through the next couple days and weeks, I just want to do a quick reminder again for you to go back to apcentral.collegeboard.org with any questions that you have. I know that information is changing quickly every day, and we will continue to update this page as often as information is available. And so just keep going back to that as often as you can. Another important piece of information is that we know that not all students have consistent access to internet or a device at home, and our plan is to have every student take their AP exams on through the internet on a device. And we really want to make sure that every student has the ability to show their best work. So if you need a tool, or you need help with connectivity, or you know somebody who does not have either of these 2 things consistently, please go to cb.org/tech and fill out the form to give us some information about how we can help you. It's really important for us that you show us your best work, and that will allow us to give you the support that you need. So thanks again for watching. I had a great time sharing this information with you. I encourage you to watch this again and to come back and see us again tomorrow. So have a great day.
Hello everyone, and welcome to this AP Chemistry virtual lesson. If you are joining us for the first time today, that's great. We're glad you're here. Thank you for watching. If you have already watched the 2 previous lessons that were presented this week, super, welcome back. And we're happy that you have been a consistent viewer. I would like to remind everyone that this is day 3 in our series of lessons on AP Chemistry. These virtual lessons will be presented daily, Monday through Friday. We began on Wednesday, March 25th, and this series of lessons will run through Friday, May 1st. My name is Michael Fairbaugh, and I teach AP Chemistry at Albemarle High School, Go Patriots, in Charlottesville, Virginia. Good morning to you. It's 10 o'clock in the morning where I am, and I want to say that no matter where you are in the world or what time it is for you right now, each of these virtual lessons in AP Chemistry will be recorded and available for students to watch on this YouTube channel at any time. As I mentioned on Wednesday, this is a virtual lesson, which means This is a different experience from what I would normally do in my own classroom. In my class, I would be able to walk around the room and check on student work. Students would be able to ask me questions during the lesson. During these virtual lessons, I will make every effort to present the information clearly. I will give you examples and diagrams and practice problems that are designed to help you better understand the content and skills in the AP Chemistry curriculum. Today's lesson will cover topic 8.3, which is on weak acids and base equilibrium. During today's lesson, if you are in the middle of solving a problem or thinking about what the correct answer is, and your teacher, start explaining the answer to the problem before you are ready, please feel free to pause the video. Give yourself time if you need to answer the question that appears on the screen, and then when you're ready, you can click play and see if your answer is correct. I mentioned this on Wednesday, but I'd like to say it again for any new people joining us for the first time. For more information about AP exams, you can visit the following website, apcentral.collegeboard.org, and at the top of the page, you can click on the link that will give you more information about how the College Board is supporting schools that may be closed right now. You may have already heard that in AP Chemistry, the exam this year will only cover the material in units 1 through 7 from the course and exam description. That being said, people watching this lesson today might be asking the following question: if only content from units 1 through 7 will be tested on the AP exam this year, why are we learning about a topic from unit 8? Well, today, the topic that we are covering, 8.3, acid-base equilibrium, is one that colleges have asked all AP students to study, even if it will not be tested on the exam in 2020. Colleges are supporting AP students this year by allowing a more flexible approach to the exam, where it will focus on a lesser amount of content than in other years. To make this relevant to your upcoming AP exam, I will include AP exam practice questions in today's lesson, and there are lots of connections between topic 8.3 and topics from earlier units, such as Unit 3, Intermolecular Forces, Unit 4, Chemical Reactions, and Unit 7, Equilibrium. Those units are important and will be included on the AP exam. Eventually, the full schedule of review topics for the remainder of this course will be made available to you, so that you, the student, can choose which topics you want to prioritize or review, and thus which virtual lessons you'll want to watch. Well, I'm ready if you are. If you happen to have a pencil or a pen, a scratch paper, and a calculator, great. If you need to pause the video right now so you can go grab those items, feel free to do that. Now, let's get started. So in this lesson, you will learn about the following topics and skills: 8.3, weak acid and base equilibria, and the skill or the science practice, explain the relationship between variables within an equation when one variable changes. Today we'll touch upon topics from Unit 3, such as solutions and mixtures, especially molarity. We'll do calculations along with the paying attention to significant figures in today's lesson. From Unit 4, which is on chemical reactions, we'll talk about net ionic equations, we'll talk about stoichiometry, mole relationships, we'll talk about titration, and of course acid-base reactions. And because it's weak acids and weak bases, a lot of topics from the Unit 7 equilibrium, the calculations of the equilibrium constant, the magnitude of that constant, and Le Châtelier's principle will definitely be addressed. So today we'll talk about the difference between a weak acid and a strong acid. We'll talk about the Ka expression, the acid dissociation constant for a weak acid, the relationship between the magnitude of the Ka or the pKa and the strength of the acid. And of course we'll talk about bases as well, so weak bases and the Kb expression and percent ionization. All right, now our warm-up today is going to be the problem that Mr. Byrne presented in yesterday's lesson. So this was from 2014, and we have propanoic acid. Now propanoic acid, there is the formula. You might be wondering whether propanoic acid is a strong acid or a weak acid. Well, something that you should know from the AP chemistry curriculum are that these 6 formulas represent the strong acids in chemistry: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric acid, and sulfuric acid. Since clearly propanoic acid is not on that list of 6 strong acids, we know it is a weak acid. In this particular problem, it says if the pH of a hydrochloric acid solution, which again we know that HCl is a strong acid, has the same pH as that of a propanoic acid solution, then the statement says that the molar concentration or the molarity of the hydrochloric acid solution must be less than that of the propanoic acid. Now, for this particular problem, we can pick any pH we want. I'm going to pick 2.79 because it's right there in the problem. As far as the concentration of propanoic acid, that is also stated in the problem as 0.2 moles per liter. But we don't know the concentration of the HCl. Now, you might wonder, could the concentration of hydrochloric acid also be 0.2 moles per liter? Well, not likely. If you remember the lesson from yesterday, the pH would have to do with the negative log of the hydronium concentration. For a strong acid, that is the concentration of hydronium because it's 100% dissociated in water. So take a moment on your calculator and do the negative log of 0.2. If you do the negative log of 0.2, you would get a pH of around 0.70. So clearly, a 0.2 molar solution of HCl would not have a pH of 2.79. All right, how would we take a pH of 2.79 and turn that into a concentration? Well, if this is our formula for pH, but we already know the pH and we're trying to find the concentration of the hydronium ion, which essentially is the concentration of the HCl, then we have to do the opposite of that log base 10. So 10 raised to the minus 2.79. So do that right now on your calculator. Take 10 raised to the minus 2.79 and see what you get, because your answer will be the concentration of HCl. All right, well, if you have done that math on your calculator, then you should get a concentration of 0.0016. Now let's compare those two concentrations. The concentration of the HCl is much less than the concentration of the propanoic acid. Well, that looks like that statement is true. HCl is a strong acid that ionizes completely. So therefore, fewer moles of HCl would be needed to produce the same hydronium concentration as the propanoic acid solution, because propanoic acid, being a weak acid, only partially ionizes. So we need fewer moles of HCl to achieve that same concentration. All right, there was another question that Mr. Byrne talked about yesterday, and this relates to pH. We have 4 acids, 1, 2, 3, and 4. Remember that the strong acids are listed there at the top of the screen, and they say in this question, which of these 4 acids is hydrochloric acid? So I'm going to go ahead and take the negative log of this particular concentration, and I can do this on my calculator, or I could actually do this in my head. It turns out that 0.01 is 10 to the negative 2 power. And so if you take the negative log of 10 to the minus 2, then you would get a pH of 2. So I think that this is our strong candidate for being hydrochloric acid. Let's continue. Take the negative log of 0.1 on your calculator, or you could do this in your head, because 0.1 is 10 to the minus 1, you get a pH of 1. And you already know from math class that the log of 1 is 0. So correct answer, which of the 4 acids is hydrochloric acid? It looks like it's going to be acid 2, the second one in the column there. Now you might have had another way to figure this out, which is just simply look at these 4 acids. If anyone is going to be hydrochloric acid, the strongest acid should have the lowest pH. So if one of them is hydrochloric acid, it would be the one that consistently has the lowest pH of all of the concentrations that were checked. All right, let's move on to what you need to know about topic 8.3. So I mentioned we're going to talk about weak acids today. The difference between a weak acid and a strong acid, as I've already mentioned, is that a weak acid only partially ionizes, whereas a strong acid is completely ionized in solution. So in general, the majority of the molecules have not broken up into H+. So let's go ahead and write a weak acid as HA. It would react with water. It would transfer the H+ to the water, and it would produce hydronium. And then after that transfer occurred, you'd be left with A-. Whatever A is, it's simply the negative ion. Like for example, A could be fluoride, or it could be nitrite, or some other negative ion. So on the left, we have 1, 2, 3, 4, 5, 6, 7 molecules of HA that have not lost the proton. And on the right, you can see that every single molecule of HA has already been split up. So the molecules that are shown in the ions on the right, that would be a strong acid, which is 100% ionized. Whereas on the left, this would be a weak acid because it is only partially ionized in solution. Well, if it's only partially ionized in solution, then we're going to talk about the equilibrium constant. Again, I mentioned unit 7. So we're going to be talking about the equilibrium constant for this reaction. So here, as I mentioned, the HA transfers a proton to the water molecule, and you get the hydronium ion. And then we're going to call A- would simply be the negative portion of the molecule, the -1 charge. So that particular expression, the Ka expression, has to do with the equilibrium constant for this reaction. Now, normally, if we're talking about concentration, we put that in brackets. That would be the concentration of the products divided by the concentration of the reactants. That's how we typically set up an equilibrium expression. Now, there are no coefficients to worry about in this expression expression, so we're not raising things to the second or the third power. But you might notice that there are 4 chemicals. One of them, water, is a pure liquid. Pure liquids and pure solids cannot be expressed in this equilibrium constant expression because they don't have a concentration. Pure liquids and pure solids are excluded from the equilibrium expression. So therefore, we're going to have the concentration of hydronium times the concentration of this conjugate base, the A minus, divided by the concentration of HA, and that's it. The water is not included. Is there an equation sheet that you guys will have available on the AP exam? Absolutely. I'm showing you a portion of this equations and constant sheet, and if you look closely, there are a number of different equilibrium expressions, but one of them I just circled, that's the Ka expression. Whether it's H plus or H3O plus hydronium, that means the same thing. So you have your products over reactants, and again, notice that water is excluded from that expression. All right, I want to give you 2 examples of a weak acid. We have acetic acid, which is also known as vinegar, and then we have hydrofluoric acid, which has the formula HF. These are not on the list of strong acids. They are both classified as weak acids. Which of these 2 weak acids is the stronger acid, and how can you tell? Now, if they're going to be strong acids, they'd be 100% associated. We know that neither of these is a strong acid. They're both weak. These are both weak acids, but the question is asking which of the 2 is stronger. The answer is you actually can't tell from what I've given you so far. You have to be given a little more information about things like pH or percent ionization, or in this case, the Ka. Let me go ahead and put the Ka values up on the screen. All right, take a moment to look at those 2 Ka values. They are both less than 1. Very consistent with the fact this is a weak acid for each one, but compare the magnitude of these 2 Ka values and what you notice. Well, hopefully you notice that one of them has a larger Ka value than the other. So that means that the larger the Ka value is, the stronger the acid is. The larger the magnitude of Ka, the stronger the acid. There's something else on this screen. It says the smaller the value of the pKa. Now pKa would equal the negative log of the Ka value. And again, the pKa, that formula is also on the equation sheet that I showed you earlier. Okay, so again, the idea that we have something called the pKa, which is the negative log of the Ka. All right, so what it says is the smaller the value of the pKa, the stronger the acid. Well, I'm going to ask you to take the negative log of this Ka. I'm going to modify it slightly. I'm just going to go ahead and scratch through this for now. Can you do this without a calculator? Absolutely. Just focus on the exponent. The negative log of 10 to the negative 5 would be 5, and the negative log of 10 to the negative 4 just be 4. That means, as I said earlier, the smaller the value of the pKa, the stronger the acid. We already know that HF was the stronger acid because it had a larger Ka. You can go ahead and pick up your calculator now and do the math. Go ahead and type in the negative log of 1.8 times 10 to the negative 5. If you do this, you're going to get around 4 point something. Okay. What I did on my calculator is I got the pKa for acetic acid was around 4.74. If you take the negative log of the other Ka value, which would be 6.8 times 10 to the negative 4, put that in your calculator, the negative log of that number should be around 3 point something. When I did it on my calculator, I got around 3.17. So consistent with the information. If you compare the pKa values, the one that has a smaller pKa was the stronger acid. Now again, for those of you that might be thinking, this is topic 8, that's excluded on the AP exam. If you go back to unit 7, which is definitely covered on the AP exam, one of the topics in unit 7 on equilibrium is to talk about the magnitude of the equilibrium constant. So AP chemistry students should be able to compare the K value, the equilibrium constant for 2 different reactions and make a conclusion based on what information tells us about the strength of the reaction from left to right. So again, that's information that's important to know for equilibrium. All right, let's talk about bases. You can have a weak base. Now I'm showing you a molecule on the screen here. I'm just going to call it B for base. This might be ammonia, or it might be methylamine, or other weak bases. It would act as a proton acceptor. So one of the H plus ions from a water molecule would get transferred to the base, and you would form for your products HB plus. That would be the conjugate acid of that base, and the hydroxide ion. Again, because it's a weak base, it's not completely ionized in solution. It's only partially ionized. So therefore, we have a K expression. Remember that the water would not be included in this expression because it is a pure liquid and doesn't have a concentration. You have the concentration of the conjugate acid times the concentration of the hydroxide divided by the concentration of the base. Do they give you this equation on the AP equations and constant sheet? Absolutely. It's right there underneath the Ka. There's the Kb. So it's nice to know you have access to these equations, and it's also nice to know that you understand the meaning and where they come from. All right, next thing I would like to talk to you about is percent ionization. So look at the particle diagram that we have here on the screen. I'm going to go ahead and circle. How many acids do we have? 1, 2, 3, 4, 5, 6, 7. Technically, we have 8 acid molecules, but only one of them has dissociated, split up, ionized, and formed a hydronium ion. So what we have is a weak acid that has been ionized, but only a little bit. And you can do this either on your calculator, or you might know that the fraction 1/8 is 0.125. So therefore, this is roughly about 13% ionized. So how do you define the percent ionization with a formula? Well, we define it in this way. This was our Ka expression. I'm just adding a little subscript here, original, to remind you that this is the concentration of HA that would be given in the problem, or possibly listed on the bottle of chemical if you're looking at this in the lab. So the ratio of the concentration of the hydronium ion divided by the original concentration of the acid times 100, that is your percent ionization. So I just did it. In the previous screen, I said it was around 13%. You would get information from the problem where you could have molarity or pH. You can figure this out. Now there's also the equivalent ratio for a base. It's not going to be hydronium, but rather hydroxide. The concentration of hydroxide divided by the original concentration of the base times 100. The percent ionization of a weak acid or a weak base can be calculated based on the given information. So they might tell you the Ka or the pKa. They might give you the initial concentration of the acid. So for example, the concentration of whatever that acid happens to be, and then you could calculate that ratio. You could figure out the percent ionization for either a weak acid or a weak base. All right, we're now going to move on to some guided practice. I had mentioned that net ionic equations were covered in topic 4.2. That would be unit 4 on chemical reactions. 3 different acid-base reactions are shown. For each of these reactions, I'd like you to write the net ionic equation. This would be a good time if you need to pause the video. Then you could write down these reactions. You could think about how to represent each of these substances as either a molecule or as ions if they are extensively ionized in solution. And then you would cross off what we call in chemistry the spectator ions on both sides. So any formulas for ions or molecules that appear unchanged in this reaction will get crossed off. All right, so I have 3 reactions. These are all acid-base reactions. Here we have an acid. This is propanoic acid. Here we have a base, potassium hydroxide. Here we have an acid. That's nitric acid. Here we have a base, calcium hydroxide. Here we have an acid, hydrobromic acid, and then this would be the weak base. This is called dimethylamine. In each of these reactions, a proton is transferred from the acid to the base. In our first example, the proton will get transferred to the hydroxide ion to make water. In our next example, the proton will get transferred to the hydroxide ion again, but because we have 2 H pluses and 2 OH minuses, we're going to make 2 water molecules. In our third example, there is no water on the right side of the equation. That's because the base is this molecule. This is like the equivalent of what I showed you earlier. This is like the Hb plus. So this portion, which I guess you would call the dimethylammonium ion, that would be the conjugate acid of the base. All right, so I'll give you a moment to write down these reactions and to figure out the net ionic equation. I'll also mention that because they are acid-base reactions, everything is soluble. There are no precipitates to worry about. Students should know, if we were talking about precipitation reactions, which again we are not talking about that today, that's from topic 4.7, that if you contain a sodium ion or a potassium ion or ammonium or nitrate, you will definitely dissolve in water. But again, no precipitates here. Your job is to decide, should I split this up into ions or not? All right, well, if you have copied down these 3 equations, we're going to take them one at a time. I'm going to start with the first one on the next slide. The strong acids, HCl, HBr, HI, HNO3, HClO4, H2SO4. Propanoic acid is clearly not a strong acid, so it's only partially ionized. From yesterday's lesson, 8.2, we talked about strong acids and strong bases. If you have a soluble compound that contains hydroxide, that is a strong base. That completely, I guess I would say, dissociates, splits up into K plus and OH minus. On the right side of the equation, even though I have written it as one formula, it actually contains a cation and an anion. Well, the cation is the K plus, which came from the potassium hydroxide. The anion is the propanoate, that is the conjugate base of the propanoic acid. Everything is soluble. So should we split up a weak acid if it is only partially ionized, or should we leave it together as one formula? Well, hopefully you answered. We should leave it together. Again, it's a weak acid. The majority of those molecules have not been ionized. Of course, for a strong base, it's very soluble. It's an ionic compound. It definitely dissociates into cations and anions. We're not going to split up water. Water is a covalent molecule that is not going to be broken up into ions. And then we have this soluble ionic compound that contains both potassium ions and this propanoate, the conjugate base of propanoic acid. Remember, let's cross off any spectator ions that appear on both sides. And once we do that, we have our net ionic equation. Right. Our next example was the nitric acid and the calcium hydroxide. You know that nitric acid is on your list of 6 strong acids. Let's go ahead and split that up into separate ions. So we'll have H plus and NO3 minus. Calcium hydroxide is a soluble ionic compound. We should split that up. That's a strong base. We're not going to split up the water. And the calcium nitrate is a soluble ionic compound. All nitrate compounds are soluble. That contains calcium ions and nitrate ions. So let's split up the nitric acid. And because of the coefficient of 2, I have 2 H pluses and 2 NO3 minuses. Let's split up the calcium hydroxide. So we have 1 calcium ion and 2 hydroxide ions. We're not going to split up the water. And then we have the calcium and the 2 nitrates. We'll split that up as well. We'll cross off our spectator ions, which means I see nitrate on both sides. Let's get rid of that. I see calcium on both sides. Get rid of that. And then what we're left with is H plus and OH minus and water. Of course, each coefficient is 2, so we can go ahead and just reduce that to a 1-to-1-to-1 ratio. All right, one more example of a net ionic equation involving acids and bases. This time we have a weak base and a strong acid. So HBr is definitely on your list of 6 strong acids. We're going to split that up into H plus and Br minus. Remember that the proton was transferred from the acid to the base. So we're going to form the CH3 parentheses 2 NH2 plus, or the dimethyl ammonium cation, the conjugate acid. And of course, bromide comes along for the ride as well. We are not going to split up a weak base because it is only partially ionized. We're going to definitely split up the H plus and the Br minus because it is a strong acid and fully ionized. And this is a soluble ionic compound with the conjugate acid being a cation and the Br minus, the conjugate base of hydrobromic acid. It's on both sides. We're going to cross that off as a spectator ion, and we have our net ionic equation. Now, something else we can talk about is how do we calculate the value of Ka? Because it's nice when they give it to you in the problem, but if we had to calculate the value of Ka, how would we do that? Calculate the value of Ka for acetic acid. It is a weak acid, so we're talking about this. Ka is equal to H plus, or you could write hydronium times the concentration of A minus, which in this case is the acetate ion right there, and then divided by the concentration, the original concentration of the acid, which would be this HA. So we know the number on the bottom. We know that HA is 0.1. Now, what are we going to do with a pH of 2.87? Can we turn that pH somehow into the concentration of hydronium? Yes, we can definitely turn a pH into the concentration of hydronium. So we're going to go ahead and set up what I would call a RICE table. So the word RICE appears on the screen. That's an acronym for R, reaction. And then the next row of the table would be I, that stands for the initial concentration. And then we have C, which is the change, how things have increased or decreased. And then E is what you have at the end, or rather at equilibrium. Now, of these 4 chemicals in this reaction, remember that pure water is not going to be included in the Ka expression, so we can ignore any information about that. So what are we going to do with a pH of 2.87 so we can figure out what this number is right here? Well, if pH is equal to the negative log of the hydronium concentration, then the hydronium concentration is equal to 10 raised to the minus whatever the pH happens to be. So on your calculator, you can go ahead and punch in 10 raised to the minus 2.87. Okay, see what you get. 10 raised to the minus 2.87. You should get a pretty small number. It should be 0.00 something. And if you've done that math on your calculator, you get 0.0013. And I talked about stoichiometry at the top of this lesson. That would be one of those relevant topics from Unit 4 on chemical reactions. Hopefully you can realize there's a 1-to-1 mole ratio between hydronium and the acetate ion, or the A minus ion. So I don't need to calculate the concentration of acetate. I know it's the same because of the stoichiometry and the 1-to-1 mole ratio. Now you might wonder, do we put this 0.10? Does that go here? Well, actually that's the initial concentration. So let's go ahead and put that right there. And initially let's pretend that this molecule has not ionized at all. So the concentration of hydronium and acetate is 0. You might say, but in pure water, isn't that 10 to the negative 7? Well, yes, it is. But we're going to focus on just the hydronium ions that are coming from this particular reaction. And so I'm going to go ahead and say it's very small, and so therefore 0. Now, what has happened in terms of the change? The change has to do with the concentration that has either gone up or down. So the acetic acid has gone down by a little bit, and the hydronium ion has gone up by a little bit. So we now have numbers on the right side of this table. There is no such thing as a law of conservation of mass. So we're not going to say that the acetic acid has gone down by 0.0026. No, we don't do that. We get the change based on the mole ratios. So with a 1-to-1 mole ratio, the change in acetic acid is exactly the same as the change in hydronium. It's just simply a decrease as opposed to an increase. Now, on your calculator, go ahead and do this math. What is 0.1 minus 0.0013? I'm assuming that if you do this math on your calculator, you get 0.09 something. So when I did this on my calculator, I got 0.0987. There is a rule which is related to significant figures. It has to do with what you do when you add or subtract numbers in chemistry. Now, when you subtract 2 numbers and there are different amounts of decimal places, you always round off your answer to the one that has the least number of decimal places. In this case, 2 decimal places should appear in our answer. Well, how does 0.0987 round off to 2 decimal places? We can't just say 0.09 or 0.099. It has to just be 2 decimal places, and that would actually round to 0.1. It almost looks like the concentration of acetic acid did not change at all. Well, it did change, but by a very small amount. Remember that. That's going to come up in the next problem. The fact that the change for a weak acid in terms of the initial concentration and the final concentration is so small, that'll be something to pay attention to. Okay, let's go ahead and plug in these numbers in the final row of our little RICE table. Let's plug them into the Ka expression. So 0.0013 times 0.0013 divided by 0.1. If you do that in your calculator, you're going to get the Ka for acetic acid, which is about 1.7 times 10 to the minus 5. Something else we have to calculate is the percent ionization, and that is going to be the concentration of hydronium divided by the original concentration of the acid, and then times 100. So if we do this math, 0.0013 divided by 0.1 multiplied by 100, we get 1.3%. So let that sink in for a moment. About 98.7% of the molecules of acetic acid have not dissociated or ionized at all. Definitely a weak acid. Okay, here's another problem that relates to a weak acid, but this time we're not calculating the Ka. They actually gave us the Ka, and this time instead of telling us what the pH is, we have to calculate the pH along with the percent ionization. Okay, how do we figure out the pH if it's unknown? We're going to go ahead and start with our RICE table. Again, we're going to write down, I've got it in the upper left corner of that slide. This is what we know. This time I can plug in information, but I cannot ignore the water. I cannot write this. I don't know what this is because it's not going to come from the pH since I don't know the pH. Let's fill in what we do know. Initial concentration of this acid. And again, this is called hypochlorous acid. It's a weak acid. It's not on your list of strong acids. I don't know what the change is. I'm going to go ahead and call the change in hypochlorous acid X. So the hypochlorous acid concentration has gone down by X, and the hydronium and the hypochlorite ion have gone up by a certain amount. So I don't know what these numbers are, but I do know the Ka. So that's helpful. I'm going to go ahead and solve for X. We know that the Ka is 3 times 10 to the negative 8. We just don't know anything else in this expression. We have to solve for X. We are not going to use the quadratic equation. That's not something you'll see on the AP chemistry exam. And how do we get around this? Remember how I said that the change in the concentration of the acid was very, very small? Since the value of X is much smaller than 0.1, we can go ahead and simplify this expression by changing 0.1 minus X on the bottom to just 0.1. Well, that cleans up our math. Now we have X squared equals 3 times 10 to the minus 9. When you multiply both sides by 0.1, we'll take the square root, and then we end up with our answer for X. And since our answer for X is the concentration of hydronium, all we have to do now is take a negative log of that number. And if you do that, you get around 4 point something. So on your calculator, the negative log of 5.5 times 10 to the minus 5 is around 4.26. All right, we have to figure out the percent ionization. So could we take this number, divide it by the original concentration of acid, and then multiply by 100? All right, let's do that. And we get, wow, look at that. Look how small that percent ionization is. Over 99% of those molecules of HOCl, the weak acid, have not ionized. Okay, so definitely a weak acid. Now, what you see on this slide is a summary of the 2 guided practice problems that we just did. Examine the data in the table below. Can you tell which acid is the stronger acid? Has a larger Ka, has a lower pH, has a higher percent ionization? Definitely, the acetic acid is the stronger of the two acids in this comparison. All right, now I'm going to just briefly, I'm going to go kind of fast through this next slide series. I'm going to talk about bases. Okay, this happens to be called trimethylamine. Water donates a proton to the trimethylamine right there, and it produces the trimethylammonium ion. That's the conjugate acid. This is completely analogous to weak acids. There's a little bit of a catch though, in that when you figure out the concentration of this chemical here and you take the negative log, don't forget that the negative log of the concentration of hydroxide will not give you the pH. It will give you the pOH. So you'll have to do 14 minus the pOH to figure out what the pH is. So watch out for that. Otherwise, it's a very, very similar process. And so because of the similarity, I'm going to go pretty fast. Feel free if you have to pause the video to absorb all this information. You're welcome to do that. So 0.1 is the initial concentration of the weak base. The other ones are 0 for now, and we have minus x and plus x like we did before. We're going to go ahead and plug this into the Kb expression so we can solve for x. We're going to make that simplifying assumption we did before, and that x is so small I can ignore that 0.1 minus x on the bottom and just call it 0.1. Then we do the math, and when we solve for x in this case, and we take the negative log of 0.0025, again, this will not give us the pH. It gives us the pOH. So don't get to do all this great work on the AP chemistry exam and then realize, oh, the pH is not 2.6. It's actually 11.4. Okay, this is a base. Therefore, you should expect the pH to be higher than 7, not lower than 7. Now, for percent ionization, we can go ahead and take the concentration of hydroxide, divide by the original concentration of this weak base, and then times 100. And if we do that math, we see that the weak base is about roughly 2.5% ionized. All right, my next problem has to do with a solution of a weak acid, and we're going to add some water. We have 100 milliliters of a 0.1 molar solution of this weak acid, and we're going to add some water. So now we have 1 liter. Have we changed the concentration? Absolutely. We have changed the concentration by a factor of 10. You remember, Mr. Byrne yesterday talked about this equation, M1V1 equals M2V2. The volume of this solution has gone up by a factor of 10. Therefore, the concentration has gone down by a factor of 10. So what happens to the hydronium concentration in this flask on the right that has been diluted? What happens to the pH? And what happens to the percent ionization? I'm going to go again pretty quickly through these calculations, so feel free if I go too fast to pause. Here we have the data we already calculated for the 0.1 molar solution of acetic acid. I'm now going to calculate the concentration of hydronium for the 0.01 molar solution. And when I do this math, I get that the concentration of hydronium is less than what it was before. I think that makes sense to us. You added water, the concentration went down. What do you think is going to happen to the pH? Well, if you know anything about pH, you realize that the higher the concentration of hydronium, the lower the pH. So therefore, if you have a smaller concentration of hydronium, you have a higher pH. I think that makes sense to us. But you're going to be a little bit surprised by what happens in our next calculation. What happens to the percent ionization? If you take this number right here and divide by this number right here, you end up with a percent ionization that's actually greater than 1.3%. Now that seems a little strange to us. What happened to the percent ionization? It actually went up. All we did was we added water. Did we make this a stronger acid? No. In fact, we just did something that has to do with, this is from Unit 7, the Châtelier's principle. Okay, so the Châtelier's principle has to do with a shift in equilibrium. So we added water, and that caused the concentration of all three of these aqueous species. Again, we don't count the water as an aqueous species. It caused them to go down. Well, that naturally makes sense. We added water. But because the system was now put under a stress, the equilibrium position was trying to respond to that stress. And so it shifted toward the side of the equation that had a greater number of moles of aqueous particles to effectively counteract that stress. So as a result, the percent ionization actually went up for this more dilute weak acid. There is another way to explain this, and it's a mathematical way to explain this. This is a conceptual way of thinking about the Châtelier's principle. Take a look at the Q, and the Q is going to be where we are right now. By diluting it, we have caused the concentration of all three of these species to go down by, in this case, a factor of 10. That means that our value of Q, which is the reaction quotient, is actually less. And when Q is less than K, and this comes from Unit 7, when Q is less than K, it will cause a shift in the equilibrium toward the product side. All right, well, that was a little review of equilibrium. I do have one last problem to show you. Again, I'll go kind of quick, and then we'll get to our AP problem for homework. Here we have a titration experiment. This is from the 2016 AP Chemistry exam. And in this titration experiment, we have a before and an after picture of what the burette looked like. Let's talk about significant figures here. How do you read this burette? Every line on that burette is worth 0.1. So if I were to look at that burette and say, oh, it's approximately around 5.6, that would not be good enough. I'm going to have to record this to 2 decimal places, and I estimate that final digit is about halfway between 5.6 and 5.7. Over here, if I were to say that this burette is around 37.3, that's not good enough. I have to record that to 2 decimal places. The final digit, I think that meniscus is on the line. I'm going to go ahead and say that would be 0. So to record a burette that is marked off in 0.1 increments, you have to go to the 10th place. Let me go ahead and show you the answers. That was the answer to part A. Again, feel free to pause the video if you need more time to process. I'm going to quickly show you the answer to part B. Okay, because we're kind of running over our time here. I'm looking at the clock and realizing we need to wind this up. So I'm going to go ahead and show you my answer to part B. I apologize for kind of rushing through this, but again, feel free to watch this and pause and you can kind of absorb this information. So there is the answer to part B. And then moving on to part C of this question. All right, so as I wrap up, we talked about a weak acid, we talked about a weak base, we talked about Ka and percent ionization. I now come to your homework for next time. And again, you can take a screenshot or you can pause the video. So Mr. Byrne will explain this question from the 2018 AP Chemistry exam with you on Monday. And this is part A of the question, and this is part B of the question. So that will be what Mr. Byrne will talk with you on Monday about. All right, as I wrap up today, I want to remind you that in the video description, you can see a link down below, tinyurl.com/helpfulchem resources. So check it out. Lots of good things for online learning and simulations and lots of good chemistry information. Thank you all so very much for watching. I hope that this lesson was helpful and you enjoyed it. And we look forward to seeing you guys back on Monday for more AP Chemistry lessons. As a final note, if you are having any technology issues or you are aware of someone who does, please have that person or yourself go to cb.org/tech and you can fill out a survey about your needs for mobile tools or connectivity. Again, this is Michael Faribault. Look forward to seeing Mr. Burns' lesson on Monday. Thanks for watching.
Good morning, everybody, and welcome back to AP Chemistry and our fourth live lesson on AP Chemistry. This is our second week. We're really happy to have you back. This is the start of spring break for my students at Glenbard West, and some of you may be coming back from Glenbard West. I'm Mr. Byrne. I teach at Glenbard West High School in Glen Ellen, Illinois. Today's Monday, March 30th. If you are just joining us for the first time this morning, remember that there are 3 great lessons that Mr. Faribault and I did for you last week. If you want to start there and jump back and see how we started the process, that would be great. If you want to watch this one and then go back and watch those another time, remember that everything is recorded for you, and you can watch any of this on your own time in your own place. I hope you're safe, and looking forward to a great day today. Special shout out to any of my Hilltoppers who are watching us even on their spring break. Before we get started with our lesson, I do want to make sure that I remind you of some great resources that we have prepared for you to be ready for all the information that's coming out in the next couple of days. apcentral.collegeboard.org is always a great place for you to go to get the most up-to-date information about how AP exams will be changing this year and how we're supporting you in your school if you are closed due to the coronavirus. If you click on that link that was indicated before, you'll see something that looks like this that has an update for everything that's happening at each school. The big highlights of this are to remember that students will not be taking any face-to-face exams. All students will take a 45-minute free response exam on their own device. Many of us will take those tests at home. Some may be back at school by that time, and we have no way of telling that. So we're going to make sure that we've accommodated all students. There will be 2 different testing dates for each test, and more information will be released by this Friday, April 3rd. So keep checking back to apcentral.collegeboard.org, and you'll get the most up-to-date information. As you may have heard, for AP Chemistry, we do know that our AP exam will only cover units 1 through 7. The units 8 and 9, while they are very important, will not be directly tested on the exam this year. So what we have done is we started with a couple of units last week, or a couple of lessons last week, units 8 and 9, and now this week we're going to revert back and start from the beginning, lessons 1 through 7. We're going to sprinkle in the rest of the lessons that were not covered last week from units 8 and 9. And that's for two reasons. A, chemistry builds on one another, and there's some really great exciting topics that we want to make sure that you have an experience of and can relate back to units 1 through 7. Secondly, colleges have asked us to make sure that we cover this material because we know that many of you are going to be moving on to other chemistry or other science classes. We want to make sure that you have an experience of these topics before you move on to those classes so that you're very well prepared for that. So what we have done is started to release more and more of the schedule. If you look on the AP or the YouTube channel right now, you're going to see more of a plan for this week. And as we have more plans, we will continue to release them to you. But suffice it to say that this week and next we'll be beginning to dive into units 1 through 7 as we're moving forward. Okay. The same is true for all of the AP exams. I noticed as I noodled around through some of the other courses on YouTube that more and more information about what the upcoming lessons will cover is being released. The schedule will stay the same, so you can check into different periods of the day if that works for you, or you can just on demand each of the lessons for different courses. Again, on that YouTube channel, it's a great place to look. Okay. So we're going to jump into the lesson here in just a minute. This would be a great time for 2 reminders for you. Remember that at any point, if I'm going too quickly or you want to re-listen to anything that I'm explaining, feel free to stop this video and go back and rewatch it, or stop it and maybe solve a problem on your own. Give it a try on your own before you see what our solution is. And that's my second reminder: is you might need a pen or a pencil and maybe a calculator right on your desk in front of you or table in front of you to make sure that you can solve the problems as I'm solving them. Keep me honest and see if there's any mistakes that I made. I promise you, there's a bunch of us that have gone over these today, so we're pretty sure these are good. But I always love it when a student can challenge my work and see that there's a new or different way for it. Okay, so we're going to follow a very similar lesson overview as we did last week. We'll start with a warm-up, and every day our warm-up will always be a review of the quote-unquote homework problems from the previous day. So Mr. Fairbaugh gave us 2 or 3 great problems, AP problems to consider on Friday, so we'll start with that. And then we're going to go into lessons 1.1 through 1.4 for students at Northwest. These are things that we studied way back in August or September, so it's a great way to review some really fundamental foundational information, but make sure that we can adapt it and integrate it into some more modern questions. I'm going to do things a little bit differently today, and then I'm going to go over what you need to know and then give you guided practice right away on each of these lessons. So we'll split up each of the 4 things here, talk about it for a minute, and then do a sample problem. Go through that process 4 different times, and then at the end we'll give you some AP exam practice that I'm going to be actually with you tomorrow to go through and show our solutions. So these exam practice problems will be your homework getting ready for tomorrow. So let's jump into our review of homework from yesterday with our warm-up. The first thing that Mr. Fairbaugh asked us to do was to look at the 2018 AP released exam, question number 5, about the ionization of HF or hydrofluoric acid. Now, I hope based on what we talked about both on Thursday and Friday last week, that hydrofluoric acid is the first question in your brain. Is that one of our strong acids? And we gave you a list of strong acids. If you go back and check on them, hydrofluoric acid was not present on either of them. So that tells us that hydrofluoric acid is in fact not a strong acid, which makes it a weak acid. My face might be covering up a couple words over here, but they're not important. 0.00350 molar HF solution has a percent ionization of 13%. So that's another piece of information that tells us that hydrofluoric acid is a weak acid. It does not ionize at a large percentage. And so we are so you want to stick with this being a weak acid. So the question asks us to consider these 2 different particle pictures, one of which, this figure on the left, has a lot of HFs and 1 hydronium ion and 1 fluoride ion by itself over here, and the one on the right has a lot of fluoride ions and a lot of hydronium ions. And the problem does a nice job of saying that the representation on the left, figure 1, is more accurate, but our job is to explain why this one is more accurate. So I'm going to do a comparative analysis here, and I'm going to start with figure 2 and break down what's happening here. When I look at this picture, I see that there are 0 HFs. If I were to count and look for molecules, there are none of them here, but there are 8 each of hydroniums and fluorides. That tells me that this is 100% ionized, and if it is 100% ionized, that makes it a strong acid. So if I've identified hydrofluoric acid as not one of my strong acids, this is a pretty inaccurate representation of what would happen for hydrofluoric acid. It's an accurate representation of what might happen for another acid, just not for hydrofluoric acid. So let's make a similar analysis of what's happening in figure 1. I count 7 HFs, I count 1 each of a hydronium and a fluoride, and that tells me that about 13% or 1 in 8 of the molecules is ionized. And this is both representative of a weak acid and is reinforced by the information that's given to me in the problem. And so therefore, this tells me that the picture on the left, figure 1, is the more accurate representation of hydrofluoric acid. The scoring guidelines tell us that we can do one of 2 things. We can either recognize, as we did, hydrofluoric acid as a weak acid is only personally ionized. This fact is consistent with the figure. We even got some numerical values here, 1 and 8, 13% of HF molecules are ionized to form 1 each of hydronium and fluoride. We also could have said that, talked about what was inaccurate about figure 2 in saying that figure 2 cannot represent HF because it was 100% ionized. For me, I prefer this first explanation because it's explaining a lot of the chemistry that's going on here, but either one of them would bring you the point toward this particular question. Great. Let's look at the second part of this question where we use the percent ionization data to calculate the Ka for HF. So the same situation, but we're going to now use this to calculate our Ka. And I would say that there's 3 steps that we want to follow in order to get there. First, we're going to use this percent ionization to determine our hydronium ion concentration. We'll set up an ice table to determine our hydrofluoric acid and fluoride concentrations, and then we'll calculate Ka from it. Let's get to it. The first thing we're going to do is we're going to use an equation that Mr. Fairbaugh talked to us about on Friday. The percent ionization of hydronium ions is going to be the concentration of hydronium ions over the concentration of the entire solution. And because in this case, we know that this percent ionization is equal to 13% here. We've converted 13% into its decimal point by dividing by 10. So 13% is equal in this case to 0.13. And by the magic of algebra here, we would multiply both sides by 0.0350, and we would determine that our hydronium ion concentration is 0.00455. There's our first step. Our second step, as I said, is to set up an ice table to determine what our hydrofluoric acid concentration and fluoride ion concentration is. Our ice table will look similar to what we did yesterday. I guess on Friday we could call this a rice table. That was something that I learned from Mr. Fairbaugh. I've never added the R up here to talk about what our reaction is, but I like it. We're not going to worry about our water here. Water is in a liquid form, and so will not be a part of our equilibrium expression. So you're going to notice that through this process, I'm going to leave that blank. We can fill in our initial concentrations based on information from the problem. This concentration of HF 0.0350 molar is the initial concentration of HF, and we have no fluorides present in the solution to begin with. We're going to say this is about 0 hydronium ions because we know that water will auto-ionize, and so there's a very, very small quantity of hydronium ions in the beaker before we add HF. However, it's such a small amount that it can be assumed to be 0 at this point. Next, we're going to say, based on what we had in number 1, or in our first step up here, our hydronium ion concentration at equilibrium is 0.00455. That would fill in right down over here in our ice table. So we're filling this out a little bit backwards. To get from 0 to 0.00455, we had to add 0.00455. We know that if we added 0.00455 molar hydronium ions, we had to do the same thing to the fluoride ions. These together in a 1-to-1 ratio. So whatever happened to hydroniums had to happen to fluorides as well. Lastly, we know if we added 0.00455 on the right-hand side of the equation, we used up that same amount of hydrofluoric acid. And so 0.0350 minus 0.00455 gives us 0.03045 molar. Remember that change, that middle row on our ice table, is all about stoichiometry. It's all about reading what our coefficients are on each of our species we're looking at here. These are all in a 1-to-1 ratio. We're going to add on the reactant side, and then we would subtract. So we're going to add on the product side. There we go. And we're going to subtract on the reactant side. So our next step, now that we have our equilibrium concentrations of everything, is to calculate our Ka. So our Ka is equal to the concentration of the products over reactants. That's consistently always how we would calculate any kind of equilibrium expression. Ka just means that it's equal equilibrium expression for an acid. We plug in our numbers from our ice table, 0.00455 squared, 0.00304, rounded from our concentration, and that gives us a Ka value of 6.81 times 10 to the minus 4. I'm being purposeful in cutting and pasting some of the scoring guidelines from the way that this question would have been scored at the AP reading, just so you can see what an AP grader would be using as their example of a good answer. Next, our last part of this problem was to consider how the solution would change if we add 50 milliliters of distilled water to our original equation, our original beaker. Specifically, we're asked will the percent ionization increase, decrease, or remain the same, and justify your answer with an explanation or calculation. I'm going to do a little bit of both for our justification of our answer. I think that we have 4 steps to this problem. We're going to want to determine our new concentration of HF. We want to use a Ka from part B and a new ice table in order to determine our hydronium ion concentration. Then we'll calculate our new percent ionization, and then we have to make sure we go back to answer the question. Right? The question asks us whether it increases, decreases, or remains the same. So for us to just say, what if we stopped right here, we would not have answered the question, and that's not a good way for us to answer what's here. Okay. So the first step is to determine our new initial concentration of hydrochloric acid. When we add 50 milliliters to 50 milliliters, we're cutting the concentration in half because we doubled the volume. You might want to review dilution problems, or I gave you a quick tutorial on that during our lesson on Thursday of last week. So if that's a mathematical process that you need to review on, go ahead and double check that towards the end of our second lesson on Thursday, which was on Thursday. Okay. So our new initial concentration of hydrochloric acid is 0.0175. So we plug that into a new ice table here, 0.0175. Now this is going to be a different kind of ice table because we don't know our equilibrium concentration. So here we're going to add x, our unknown, to the right hand side to give us 0 plus x just gives us an x. And on the left hand side, our reactant side, we're subtracting x. So here's again following that pattern, everything is in a 1-to-1-to-1 ratio. So x is going to be consistent, but we add it to the product side and we subtract it from the reactant side. We can now plug this into our Ka expression. I need a little more room there, so excuse the jumping around. Same Ka expression as before. It's constant. We haven't changed our temperature, so we would not expect our equilibrium expression value, our Ka value to change unless the temperature is changed. So we can use our answer from part B above to solve the problem here. So we can say that 6.81 times 10 to the minus 4th is equal to x squared divided by 0.0175 minus x. Take a second to look at our equilibrium, our ice table here, and our equilibrium row to see how all of that fits in down here. It's a little bit different than the way we did it in the first problem. And then we're going to make our assumption here that 0.0175 minus x is equal to 0.0175, or it's very close to 0.0175. And that's because we know that x is going to be a small value. And when we subtract a small value from this relatively larger number, we're going to not significantly change our answer. Now, many of you that are in high-level math classes understand that there are ways to solve this problem using either the quadratic formula, you can use a graphic method. There are multiple ways for you to solve this problem without making the assumption. However, you will never be asked to do that on an AP test. So this process of assuming that our 0.0175 minus x is equal to 0.0175 is something that you should become comfortable with and that you should practice doing on problems for AP chemistry. So then our final step here is to solve for x through the powers of algebra. Here we would get that x is equal to 0.00345. That'd be a great place for you to just double check the math in your calculator and make sure that you are feeling comfortable with how we got that answer. Halfway through this problem, I hope you're still with me. We're going to calculate our new percent ionization here. We use that same equation that Mr. Hasselbalch shared with us on Friday. Our concentration of hydronium ions over our concentration of acid to begin with times 100, and now we have a percent ionization of 20%. Now remember what I said, we don't want to just stop here because this doesn't give us an accurate representation. It doesn't answer the question that has been asked of us, right? So the question asked us, will the solution increase, decrease, or remain the same in terms of its percent ionization? And so what I would suggest we do is we put some bullet points in, identifying that we know that the original percent ionization was 13%, our new percent ionization is 20%, and so therefore our conclusion is that the percent ionization increases when 50 milliliters of distilled water is added to the original. I think if you were to do all of that with the math that was above, that would be a great way for you to solve this problem. Now, a second way you might want to do it, and the scoring guidelines certainly represent that this is a completely okay way to answer it, would be to use the Q and K comparison method, where we say that all of the solutions were initial concentrations were cut in half. This again is a process that Mr. Hasselbalch talked to us about on Friday. In the interest of time, I'm going to just leave this up here for a minute. When we get into solutions and equilibrium concentrations later on in this process, we'll talk a lot more about K. So I'm not going to go through a very thorough explanation of this. But if you solved it this way, you're doing great, and you would come to the same conclusion that because the equilibrium position shifts towards the products, it increases the percent ionization. All right. So take a breath, get a drink of water, get up and stretch a little bit, and we're going to go through our topics for today. We have 4 of them, so we're going to zoom through them a little bit more quickly than we have in the past. Follow along with me. Feel free to stop at any point if I'm going too quickly. I'm happy to make sure that we want you to understand what's happening here, so that moving forward you're not feeling overwhelmed. Okay. So the first lesson the first topic we're looking at here is topic 1.1, way back in the beginning, just summarizing moles and molar mass and being able to calculate quantities of the substance and its relative number of particles. Now the topic and the test designers are asking us to use dimensional analysis and the mole concept. So these are 2 things that I'm going to represent. Regardless of maybe your teachers are teaching some other ways to do it, we want to make sure that we're getting comfortable with dimensional analysis as a mathematical routine that we use regularly in solving problems. So just a quick couple of notes on moles and molar mass. We should know that scientists cannot count particles directly. If I send you into the lab, I often joke with my students and say, okay, go count me out 15 water molecules in a speaker or something like that. That's impossible to do. In part because molecules are so small and because they're moving so quickly that trying to count them directly is impossible to do. So we find connections so that we can count them by mass. You probably heard your teacher use that phrase, counting by mass, where we mass the amount of a substance and that will give us a representation of how many particles we have. We know also that representation is Avogadro's number. 6.022 times 10 to the 23rd tells us the number of particles in 1 mole of a substance. So that could be molecules, that could be atoms. If I said I need a mole of cotton balls, you would know that that means to go get 6.022 times 10 to the 23rd. That's a lot of cotton balls, so please don't go out and do that right now. But that number always means Avogadro's number, 1 mole always means this 6.022 times 10 to the 23rd. Lastly, part of this topic is understanding that the mass of an individual molecule is sometimes expressed in these units called atomic mass units. And in reviewing AP some of these exams, the AMUs came up a number of times, and enough times that I felt it was important for us to talk about it here for a second. So if we were to look at just the element oxygen, we would say that one atom, or the typical atom of oxygen, has a mass of 16 AMUs. But we also know that 1 mole of atoms has a mass of 16 grams. And both of those numbers come off of the periodic table, come off of the symbol on the periodic table for oxygen. So we know that oxygen is O, it has the protons on it. This atomic mass right here is the number that we would associate both with 16 AMUs for 1 atom and 16 grams for 1 mole of atoms. And that confuses some of my students, so I thought it was worth pointing out. So looking at a specific question that could deal with some of this information, obviously this is going to come up time and time again on almost every chemistry question. But here's a pretty complex equation. And I'm giving this to you because I want you to feel confident to be able to pull out, even if there are multiple things that are overwhelming you, pull out just a couple of pieces of information. What's the most important information for us to answer this question? A student is given a solution of sodium carbonate. They're going to determine the concentration by mixing it with calcium nitrate. Balance equation is something like this. We're going to dry out the precipitate of calcium carbonate, and they've recorded in this data table right here. So the question is, determine the moles of sodium carbonate in the original solution. So there's a lot going on here, and I understand that your eyes sort of hurt when this jumps out on the screen at you. What I'd like us to get good at is understanding, all right, I see number of moles here. This is something that I can do. I just need to use all of my scientific reasoning in order to solve that problem. So I'm going to start with the one piece of information that is probably needs to jump out at you from this data table. We should feel comfortable converting from grams to moles is a process that we know well. And oh, hey, they gave us a hint. Molar mass of calcium carbonate is 100.1 grams per mole. That would be a great thing for you to review right now Also, if you wanted to stop and just confirm for yourself that the molar mass of calcium carbonate by adding up 1 calcium, 1 carbon, and 3 oxygens is 100.1 grams per mole, stop and do that right now just to confirm that they gave us the right number. It is, in fact, the correct molar mass for calcium carbonate, but make sure that you're comfortable with how scientists would found that. So I'm going to start with our 0.93 grams of calcium carbonate, and I'm going to multiply by that molar mass. So I'm going to put grams on the bottom here and moles on the top so that my grams will cancel out one another. I use the gift tag analogy when I'm talking to my students. If I was giving somebody a present, I would write that it's to Mr. Byrne, or to Bombardat from Mr. Byrne. The same thing is going to be true with my dimensional analysis here. Whatever units I'm going to, whatever I want my answer goes on the top, whatever unit I have where I'm from goes on the bottom. And so 0.93 grams of calcium carbonate times 1 over 100.1. Put that in my calculator. That would really be like a division problem, and I get 9.3 times 10 to the minus third moles of calcium carbonate. Now, I haven't finished and really answered the question yet, right? I need to know the number of moles of sodium carbonate. But my equation tells me that these are together in a 1-to-1 ratio, right? This is one where the fact that they're different species does not matter. I'm not looking at my equilibrium constant, just looking at stoichiometry here. It never ends. So they're in a 1-to-1 ratio. So my final answer for this can be 9.3 times 10 to the minus third moles of sodium carbonate. And we can extend this a little bit. I'm going to rush through this quickly because we're running short on time and we're just on our first target here. But you could also analyze that sample further by asking the question, how many particles of sodium carbonate are there? How many carbon atoms are there? And how many sodium atoms are there? So I encourage you to pause here and see if you can solve one or all of these problems before I give you your answers. Okay, I hope you're back. I hope you paused for a second there. The number of particles for sodium carbonate is going to be our moles times Avogadro's number. So we have a really large number of particles. Even though we have a fraction of a mole, we still have a really large number of particles here, right? If I wanted to extend that to say how many carbon atoms there are, I'm going to say that there's 1 carbon atom for every Na2CO3. So there's no coefficient right here, which means that there's no subscript here. So it means that it's a 1, right? So there's 1 atom of carbon in every molecule of sodium carbonate. So our number ends up being the same, but here's a really good practice of using dimensional analysis and what element we're coming from, where are we going to. And lastly, if I wanted to know my sodium particles, I'm going to let I know that there are 2 atoms of sodium. That's this 2 over here indicates there's 2 atoms of sodium for every molecule or particle of sodium carbonate. And so my number of atoms of sodium, this should say atoms of sodium right here. We have 1.12 times 10 to the 22nd atoms of sodium right over there. Okay, lesson or topic 1.2 talks about mass spectroscopy of elements and trying to explain the quantitative relationship between the mass spectrum of an element and the masses of the element's isotopes. And so one of the things that we need to really zone in here is that we're going to be looking at some graphs that incorporate isotopes of different atoms and different atoms of an element. And we want to make sure that we can connect the information that's given to us into a graph and what that tells us about the overall information in it. So we know that a single element, we are only going to be looking at single elements in AP chemistry. And you get into further courses in chemistry, you may look at molecules or other more complex substances. We're only going to be looking at a single element here in chemistry to try to figure out the relative abundance of isotopes. So how often do each of the isotopes appear in nature? So let's just do a quick review of what this information for an element just like boron is. And oxygen earlier we had 16 down here, so it seemed like it was pretty easy to understand what the most common elements look like there, or what the most common isotope of oxygen look like. But here, there's no one atom or no one isotope of boron that has a mass of 10.81. In fact, there are the two most common isotopes of boron look like this. The first one has 5 protons and 5 neutrons, and we would call that boron 10. The second most common, or the other most common isotope. You see what happened here? We added on another neutron here. It still has 5 protons. It has to have 5 protons. It's boron, and then it has 6 neutrons in it. So we call this boron 11. Now, even looking at these two, you might think, oh, well, if we have 2 isotopes, we just find the average between them. But that doesn't give us the whole answer, because what we know is that the relative abundance of these 2 isotopes is not equal to one another. What that means is, in nature, we don't have the same amount of boron 10 as we have of boron 11. We have different amounts. And so what a scientist can do is they can analyze boron, a random sample of boron from around in nature, using a mass spectroscopy. And then we get a graph that looks something like this. And what this tells us is the relative abundance of each of the isotopes for boron. And boron 10 is only found 20% of every sample in nature, and boron 11 is found 80% of the time in a sample of nature. So if we wanted to calculate what the average of all of these are, we would have to do something called a weighted average. And the math is going to look something like this. And I apologize, it's way down in the bottom of the screen, but I wanted you to have it all in one place. So what I'm doing here is I'm taking the mass of the first isotope of boron 10 and multiplying it by the percentage 20% in its decimal form is 0.2, right? And I add that to the mass of the other isotope multiplied by its percentage 80% in its decimal form to get 10.81. Now, as you can imagine, there are some other isotopes of boron that are out there. The masses of these change slightly, but for our purposes, this is a really good method for us to get to certainly be able to identify that this sample is boron. And if this is something that you think is really cool and you wanted to study more, then you would take further chemistry classes when you get into college. What I'm going to encourage you to do now is to use this problem as a guided practice where you look at this relative abundance graph and we're trying to identify what is element Z. Can we use the information here in order to get to element Z? And as you're doing that, I am going to jump on my iPad and show you how I might solve this problem. So we have the same problem here on the screen. And what's cool about this one is that we really have to do some estimation of what our percentages are here. Okay. And so if I'm looking at that, I'm going to estimate that as about 52%. Okay. I'm going to look at this one. And for me, that one comes out to almost exactly 10%. See how this one's up? So there we go. So these each look like they're about 18% for me. And they look about the same. And these are 2%. I'm going to double check my work by adding these up and say, did I actually get to 100% of the sample that's here? We should get to something that's close to 100%. And I think that if I add this up, 52 plus 10 plus 18, 18, and 20, that does give us 100%. Okay. And so then I just follow the same process that I showed you before. 90 times 0.52, I've converted 52 into its decimal form, plus 91 times 10%, plus 92 times 18%, plus 94 times 0.18 or 18%, and plus 96 times 0.02. Now be careful, remember 2% is equal to 0.02, not 0.2. 0.2 is 20%. All right. So now let's show how we would do this in a calculator. Plus 91 times 0.1, plus 92 times 0.8, times 0.8, plus 96.2, and we get 91.3 as our atomic mass. Okay. Some bad handwriting there. Excuse me. 91.3. Okay. So let's jump back into our periodic table and see. Remember that number if you can. 91.3. We're going to stop sharing, and I'm going to share this screen back with you again. All right. And now we're back at our periodic table. And do you remember what that number is? We were trying to 91.3. So if we look through all the atomic masses here, we're going to look for the one that is closest to 91.3, and I think we're going to end up right there with zirconium. And it turns out that is an accurate representation of what the mass spectrum would look like for zirconium. Okay. We're going to give you some more problems like that to practice in our homework tonight too. So stay with me. I'm going to zoom through. I'm looking at our time here. I want to be respectful of how much time you have and give you a chance to get to some of the classes. So I'll zoom through a couple of ideas that are here. Again, remember that you can stop and review any of this at any time that you want. Topic 1.3 asks us to look at the composition of a pure substance in terms of its elements. We can really look at this in terms of both an individual molecule or a formula unit, which is typically for an ion compound, could be for some other things as well. And what we're looking at is reminding ourselves of the law of definite proportions. The law of definite proportions tells us that the ratio of mass of the elements of any pure substance is always the same. So if I have water, the ratio of the mass of hydrogen and oxygen is always the same, regardless of whether I have 100 grams or 200 grams or 300 grams, right? That I can, if I somehow took 3 different samples and I separated them out, I would always have the same ratio of the masses to one another. We're going to use that idea in a couple different ways. The empirical formula then is the lowest whole number ratio. So it's just the ratio of the masses of one another. It doesn't tell us exactly how they're all put together. It doesn't tell us a picture of the molecules of the particles, but it does at least tell us the ratios of the elements put together. Okay? So we would get a problem. We could solve a problem that looks something like this. A sample of a compound contains only sulfur and fluorine. So what's what's the empirical formula for the compound? And what I want to do is I want to look at how the moles are related to one another. So I'm going to convert each of these into their moles and say that the ratio of moles of fluorine to moles of sulfur is 6:1. Now I flip the order of these in our fraction over here just because I tend to like the larger number first, but as long as you were consistent with the way that you showed your answer and you showed what ratio you were explaining, 6:1 or 1:6 would be fine, depending on what the question asks. If we were asking for an empirical formula, though, we want to be pretty clear that SF6 sulfur hexafluoride is the best answer here. And that's because we want to list our non-metal first and then our metal second. So our non-metal, which is sulfur, is in a 1:6 ratio with fluorine. Our last topic for today is section 1.4, where we look at mixtures that contain a molecule or formal units. A mixture is a combination of several molecules all put together. And so we want to make sure that we are identifying how mixtures are all put together. And we're going to do a similar kind of elemental analysis of what's happening there. So we have a sample of carbonate rock and a mixture of calcium, which we know is a mixture of calcium and magnesium. That rock is analyzed in the lab, and the results are recorded in the table below. So this is another one of those examples where we're given a lot of information, and we need to identify just the most important information for us to be able to answer the question that's here. And as it turns out, the only information we need to analyze how much calcium to magnesium is here is just the 4 columns that I've highlighted. We want to know how much magnesium is there compared to our sample of calcium. So our magnesium has 0.1 moles, our calcium has 0.9 moles, and as I compare those two to one another, our question asks us what's the mole ratio of calcium to magnesium is 0.9 to 0.1 or 9 to 1. Here I'm going to be really clear on what my how I'm representing my ratio, and this is calcium to magnesium 9 to 1 there. Okay. So in today's lesson, we spent a lot of time looking at particle pictures. So these are some topics from earlier on in the year, that you should be familiar with. 4.3, where we're looking at chemical reactions and particle pictures. This is something that we are never going to get away from, right? And stoichiometry, where we're explaining the changes in the amounts from one to the other. Anytime we have an ice table with that change row right there in the middle, that's going to give us a good representation of what's happening in our stoichiometry. Okay. So what do we do today? I hope that you got a much better understanding of those homework problems from Friday. You have some understanding of the first 4 topics in our course, and we'll continue on with 4 more tomorrow. Feel free to go back and review anything that we've already gone through over these first 4 days. And now's the time to take some screenshots so that you can get some practice problems in ready for tomorrow. We're going to look at section or topic 1.2 with mass spectroscopy. Here, I'm giving you what the 2 isotopes are, and I'm asking you to calculate the percent abundance of each. So we're working backwards rather than having a graph in front of us. We have the isotopes, but we want to know the percent abundance. And so I'm going to encourage you either to think about this like a graph, or to mathematically prove how each of these things will work out to give us an average atomic mass in the naturally occurring neon of 20.18 MUs. Okay. The second thing I'm going to ask you to look at is a problem that has carbon, hydrogen, and nitrogen. It is burned in the presence of lots of oxygen to produce carbon dioxide, water, and nitrous oxide. So I'm going to ask you to determine the empirical formula. Remember that empirical formula is the lowest compound, or the lowest lowest ratio of elements to one another. And finally, from the 2018, we've used that a lot, is to look at I want you to draw a particle picture of what's happening here. And this particle picture is, we have a particle picture that's complete on the right-hand side, that these are the products. I'll get my cursor out of the way here, go ahead and take a screenshot. And what we want you to do is to show us that you understand what is an accurate representation of what the reactants would look like first in order to yield these products over here. So we've come to the end of our time here. Thanks so much for joining with us. I know that we sped through some of those slides there at the beginning. Feel free to jump back into apcentral.collegeboard.org anytime that you need to get more updated information. I think that's going to be changing almost daily this week, so continue looking on there. We've put a whole lot more links to helpful chemistry resources down below this video and in this tiny URL right here. So we encourage you to go to those when you have a free minute, or when you want to get some extra resources. And finally, make sure that you're reaching out to any friends, classmates, relatives that may not have access to the internet or a device consistently. We are working with students to try to make sure that everybody's able to show us their best work, and it will take us some time, but please encourage them to go to the cb.org/tech link to tell us how we can support them so that they're able to give us their best work. Thanks again for all your hard work today. We look forward to seeing you tomorrow and for the rest of our lessons. Have a great day. Good morning, AP Chemistry students. Thank you so much for joining us yet again on an awesome day of chemistry instruction. My name is Sean Byrne. I'm coming to you from outside Chicago. I am a teacher at Glenmore West High School, which is in Glen Ellen. Go Hilltoppers. I know that a lot of us are watching from Glen Ellen. Today is Tuesday, March 31st, 2020, and we have some really great lessons in store for you today. Before we get started, we're going to start just quick reminders, like we do most days, of where you should be going for all of your most up-to-date information about AP tests and all things College Board, apcentral.collegeboard.org. Click on the link there for some specifics on how we're supporting you in your school or coronavirus precautions. You'll see a website that looks something like this. And I'll just highlight a couple of really quick reminders in case this is your first video. Remember that our face-to-face exams will not take place this year. Everybody is taking a 45-minute free response exam on their own device. We'll have 2 different dates for that to happen, and lots more information will all be released to myself, Mr. Fairbaugh, and the public on April 3rd. So we're all holding on to this April 3rd date, and encourage you to keep checking back to apcentral.collegeboard.org for the most up-to-date information. We know that our exam is going to focus on units 1 through 7, and units 8 and 9 will not be directly tested on this year's AP exam. However, that is still important information for those of you that will be moving on to other chemistry or other science classes. So Mr. Fairbaugh and I are going to do a good job of sprinkling that content in throughout the rest of our time together. I did notice this morning that more and more of our topics have been populated into our YouTube playlist. So if you want to see what the upcoming topics are going to be, and notice that while we started at unit 8, we bounced back through unit 1 and 2 moving forward, and this is continuing to be added. More information to be continued to add on the YouTube channel every day. So keep checking back there. All of these are still recorded, and we've noticed that a lot of you are going back to rewatch the best of videos from last week. So continue to do that. That's a great resource for you that are going to be here for the rest of this year, at least as we prepare for our AP exam in the next couple months. Our lesson overview for today, we've got a lot of content to cover, so I'm going to get right to it. We're going to do a quick review of our homework problems from yesterday, not from Friday, from yesterday, and then we will be looking at 4 topics from unit 1 of AP Chemistry. And I'll give you some AP practice to look at for homework tonight that Mr. Fairbaugh will review with you tomorrow. Just a quick reminder of 2 things. Anytime that you need to stop this video, work out a problem on your own, have a piece of paper right next to you or a notebook or something where you can collect all of your materials. Feel free to stop, rewind, take a minute to get your calculator out, and see if you agree with the work that we're doing. The special note about today's lesson is that you're going to notice that I have grabbed a couple of images from a site that's OpenStax. This is an open source, freely available chemistry book that's available to any of you. If you have your chemistry book at home, if you left school, your last day, and you brought your chemistry book at home, then you should be relying on that, because that's the book that you've been using all year and that your teacher is presumably going to be teaching you lessons from. If you don't have a chemistry book at home, there's lots of open source chemistry books online if you do a search for it. This is a very good one that I've had experience using, which is why I'm using it here. But this is not endorsed per se by the College Board or by AP or anything like that. There are multiple sources out there that are really good. So I just wanted to make sure that I was getting credit to a great source. You'll see a couple of sites where I've used it today. You can look for this one or others online where you need to. All right. So let's get to a review of our homework problem from yesterday, which is our warm up for today. We looked back at some mass spectroscopy of a specific element of neon here, and in this case, it's a little bit of a switch of what we talked about yesterday. Instead of looking at a graph, graph, we're told that the average atomic mass for neon starts at 20.18 AMU. And so we're also told there are two common isotopes of neon that are in the table over here. And so this is a good example of how the mass is maybe slightly different from the mass numbers that we were working with yesterday. But the problem is asking us to calculate the percent abundance of each of the isotopes that's here. And so what we're going to do is we're going to let X equal the percentage of neon 20, and we'll let Y equal the percentage of neon 22. And so our equation will look something like this, where 20.81, our average atomic mass, is equal to 19.99 times the average, times the percentage of neon 20, plus 21.99 times the average of, the percentage of neon 22. We also know that X plus Y has to equal 100%. Okay, we're told that there are only two common isotopes that we're looking at here. One of the sources of error, if we were looking at this problem with a more complicated atom, might be that there are 3 or 4 or 5 common isotopes, and we certainly could do one of those problems if we had more time, but we're going to keep it simple here with just 2 isotopes that have to add up to 100%. And so one trick that we use is the fact that we can rearrange this equation to say that Y is equal to 1 minus X and plug that in over here for our value for Y. So now we go from having 2 variables in the equation, which is pretty difficult to solve, to only having 1 variable in the equation. We have our X value. We can distribute our 21.99 here. We'll isolate our X, and we'll come up with X being equal to 0.91. Then we bring this X back over here, plug it into our Y to say that Y is equal to 0.09. 0.09 plus 0.91 is going to be equal to 1.0. And then we can go back and we can convert both of these into percentages again to say that our percent of neon 20, X, this is why it was really important to define what our variables were at the beginning. X is equal to a percent of neon 20, so that would be 91%, and Y is equal to our percent of neon 22, which would be 9% down here. And so there's our final answer for that kind of problem. Okay, so this is 2 different ways. If you go back and review our lesson from yesterday, we were given our percentages and asked to find the average atomic mass. Here we're given the average atomic mass and asked to find the percentages. So if you put those 2 problems together as practice problems for yourself, you should be able to solve both kinds of problems. If you were paying attention yesterday, you may have noticed that I left a key piece of information out of our second practice problem, and I apologize for that. Thanks to Mr. Fairwell for pointing that out for me halfway through the day yesterday. We needed to know, in order to solve this problem correctly, we needed to know that the entire sample of the problem of the compound was 31 grams. So if you got stuck in this one because you didn't have that information, I apologize. Now's a great time for you to pause and see if that key piece of information helps you to be able to solve the rest of this problem. If you're still with me, I'll go through the problem here and show you how I would solve it given that key piece of 31 grams. Without that, we can still start the problem by looking at how much carbon dioxide is produced as a result of this burning in oxygen. When we burn that, we have 44 grams of carbon dioxide that are produced, and so that tells us that we have 1 mole of carbon that was originally in the compound. The only place that the only source of carbon was our original compound, right? So all of the carbon that's in carbon dioxide had to come from here. So if we have 1 mole of carbon in the carbon dioxide, that means we have 1 mole of carbon in our original compound. And similarly, we can take the amount of water that we produced, convert that to moles, and then say that there were 2 moles of hydrogen. You see where that came from down over here, 2H2, 2 moles of hydrogen for every 1 mole of water, and that gives us 5 moles of hydrogen. So how are we going to figure out how much nitrogen is in our original compound? Well, this is where we can just do a little bit of quick math. We're going to say our original sample was 31 grams. We had 1 mole of carbon, which would have a mass of 12 grams. We have 5 moles of hydrogen because each of them is 1 gram per mole. We could say that we had 5 grams of hydrogen. When we subtract both of these out, that leaves 14 grams of nitrogen, right? So this is the key piece of information that we were missing yesterday, and this gives us how many grams of nitrogen were originally. If it was only elements of carbon, hydrogen, nitrogen, we know how much the original sample was. We take out the carbon and the hydrogen, so whatever's left is nitrogen. Okay, so we go through a similar process. We have 14 grams of nitrogen times 1 mole of nitrogen. This is the molar mass, gives us 1 mole of nitrogen. And so our empirical formula, this is remember the lowest ratio of elements to one another is CH5. Okay, 1 mole of carbon to 5 moles of nitrogen to 5 moles of hydrogen and 1 mole of nitrogen. So in order to get to the molecular formula, we would have to do some other kind of experiment. We'd have to have some more information, and that's what would fit into this problem as written in this topic as we discussed it yesterday. Okay? The last problem is from the 2018 chemistry free response question. Exactly. We're given a particle picture, and you were asked to draw your own version of a particle picture that describes what the reactant mixture would have looked like. In the box on the left, show the reactant mixture of NO and O2. So one key piece of information when you're solving this problem is either to look at this or to go back to your original equation. Right? So the only things that should appear in your reactant mixture are NO and O2. The second key piece of information is to remember that the conservation of particles, the concentration of mass, is that all of these particles that are represented here must be represented over here. They can be rearranged and act chemical reaction. Of course, rearranges the particles, but however many particles we ended up with have to have the same number to begin with. So for me, what I did is just organize how many of each atom we have. And I just made 2 columns of them here. I have 1, 2, 3, 4, 5, 6, 7, 8. So 8 nitrogen atoms over here. And I counted up the number of oxygen atoms and listed them all right in here. Okay, and then I went back to my original equation. So here's conservation of matter, right? So however many particles were here, I had to have from the reactant. They came from somewhere. They had to come from over here. The second part of it is that the only arrangement of the atoms is either in NOs or O2s, because oxygen could be in either of these places, but every nitrogen must be connected to an oxygen. I just kind of zip them all together like this to say that every nitrogen, all of these NOs are over here, and then the oxygens are up here in the gaseous form as the diatomic molecules that they are. And so the scoring guidelines tell us that there's 2 points for this: one for having the same number of particles on either side, and the second part for having them arranged in the proper way as we have it right here, all either in NO or in O2. Okay, so this would be a great one to take a screenshot in. Depending on how I draw this picture, I probably would mix them up. I wouldn't put them in these nice little stacks like this. If you see the scoring guidelines on AP Central, you'll see that they're mixed up a little bit, but you would see something similar to this, at least in terms of the quantity and the arrangement of the particles. All right, so similar to what we did yesterday, we're going to mix together the what you need to know and the guided practice. We have a lot of content to get through today, so I'm going to be speeding through a number of different complex topics. So I'm going to just encourage you to use that pause button anytime you need to in order to reread or re-listen to some of my explanations, look back at the pictures that we provided for you, and listen to as many times as you need before you get to the guided practice. We're looking at these 4 topics, the last 4 in Unit 1 about atomic structure and electron configurations. We'll look at photon electron spectroscopy, so this is a little bit different than what we looked at yesterday. Similar, but here we're going to be focusing on electrons. Seriously, one of my favorite topics in all of AP Chemistry's periodic trends, and I could spend all day talking about that today if you wanted to, but I promise not to. And valence electrons and ionic compounds, which are related through all of this. What you're going to notice as a theme through all 4 of these is the way that electrons are behaving in all of these topics, or how electrons are behaving in atoms in general, and how that has an effect on how compounds and atoms will behave when they're interacting with one another. So try to keep that idea in the back of your brain. We're looking at electron configurations in this first topic, and we're going to use this idea of the Aufbau principle and we'll introduce Hund's rule as well in order to be able to draw and explain what's happening in electron configurations. It's important for us to remember that this is just a model, right, of what is happening inside of an atom, and that atoms are far too small and our particles are moving too, the subatomic particles are moving way too fast to have a specific snapshot of what's happening here. But all of these models that we're looking at help us to understand more organization of the atoms, or more organization of how the electrons will behave. And so any of the pictures that are up here, we know are just models of how atoms interact with one another. So important information for us to know, starting way at the beginning here, that we know that atoms have negatively charged electrons on the outside and a positively charged nucleus. You go back and study your scientists who contributed to this understanding and some of the really amazing experiments that they had through much of history. One of the important things that's highlighted in this topic is Coulomb's law, which is a shout out to our physics friends that are listening as well. We're going to calculate the force between 2 charged particles, and that force is proportional to the product of the 2 charges, the 2 charged particles, and inversely proportional to the square of the radius between them. So this is a good example of an inverse square relationship, where the further away something is, the more drastically this force is going to disperse or would lessen. There are multiple examples of this all over nature, and so it's cool for us to be able to talk about this here because forces is something that's so integral to what happens in physics as a connection to other forces that you'll see. We're going to keep our relationships pretty qualitative in our discussions today and in a lot of the problems that I've looked at, but just being familiar with this idea that the force will decrease as particles get further away from each other is something that is pretty intuitive to most of us, I think, but keep that in the forefront of your brain as you're working through today's class. In atoms and even in ions, electrons are organized and or thought of as being in shells and in subshells, and this is just a model, but it's a very useful model for us as we're looking through our lesson today. Electron configurations will describe this model. We'll put this model in order such that we can see core electrons. What we call core electrons are the ones on the inside, and then valence electrons, which is a phrase I hope that you're familiar with, are the outer electrons are the ones that are there outside of our atoms. And so we look at a picture like this that's going to help us organize our electron configurations. And what we're going to see here are subshells that are listed. We have S's, we have P's, we have D's, we have F's. Each of these lines here represents a subshell that is capable of holding electrons. And when we're given a problem like argon, which has 18 electrons in it, what we're going to use is a principle called the Aufbau principle. I've read multiple times that Aufbau in German means to build up. I've even talked to the German teacher at school, and she confirms that that's one translation of that word. And so what we're going to see is that electrons are added to the lowest subshells first. So that's what's so great about a picture like this or a diagram like this. You're not going to be asked to recreate this as such, but it's a great picture to have in your brain as you are adding in electrons. So as we're trying to go from an example of argon has 18 electrons, what does its electron configuration look like? You may want to think about how you would fill up this chart from the bottom to the top in order to get to the electron configuration. And so as I add electrons, each of these arrows would represent one electron. So that we start at the bottom. We know that we typically put the arrows in opposite directions to indicate their spin. So one up and one down for the 1s. There's 2 electrons there. 2 more in 2s, so we're 4 electrons. So I'm building up and I'm kind of counting to get to this 18 electrons in argon. There's 6 more that can be in the 2p orbital. Now we're at 12, 13, 14, 15, 16, 17, 18 electrons there. So 18 total electrons that are now accounted for. Now we've organized them in this diagram to help us to get to our electron configuration. And so from here, we should be able to write an electron configuration as 1s2, 2s2, 2p6, 3s2, and 3p6. So what I'm listing is the principal energy level. We know that the principal energy level number 1 has 1 sublevels, 2 has 2 sublevels, 3 actually has a third one possible, but we don't have enough electrons to get there yet. We'll see one in just a minute. And 4 has 4, 5, 6, 4, the fourth principal energy level has 4 orbitals right here. So this is obviously a very complicated process. The way that electrons behave in a atom is super complicated. What this picture is doing is helping us to understand how we use the Aufbau principle to build up the electrons and get to a electron configuration that looks like this. A second way that we could represent an electron configuration is using something we call the noble gas configuration, and that's where we look at the bracketed electron configuration here as the noble gas that appears directly before argon. We typically probably wouldn't do this for a noble gas itself, but if I look at the bracketed electron configuration here, I could replace that with neon and then add on whatever electrons are after that that noble gas. So these two different electron configurations, this one and this one, both mean the same thing. They're both an accurate representation of the electron configuration for argons. Okay, take a second. You could stop here and look at vanadium. Vanadium is another element that has 23 electrons in it. If you wanted to try to use the Aufbau principle and to fill up our electrons from the bottom to the top to build up electrons, you could do that in a picture like this. Either do it in your brain or just sketch something out on your piece of paper. And those of you that were paying really close attention in our last problem notice that we were using a second rule that guides our electron configuration creation, and that's called Hund's rule. And that tells us that each sublevel should have 1 electron before any are doubled up. That's each sublevel within a principal energy level. So that's going to be looking at our anytime we have 3 in a row right here, 3 in a row, or 4 right up here. Okay, so you may have noticed that for 1s we have 2 electrons there, for 2s there's 2 electrons there. Okay, but for 2p when I was filling these up, I put 1, spread them out. Right, I put 3 pointed in the up direction before I filled in a 4th that was going down, and that's an example of Hund's rule. We would not necessarily notice that for something like vanadium because 2p sublevel is completely filled up, the subshell is filled up. The same thing would be true for 3s, 3p. We're going to see that we put 1 in each of those before we double any of them up. 4s, we'll talk about that in just a minute, has 2 electrons, but then our 3ds will get spread out. And so what we can talk about is that each of the electrons over here are in what we call are in pairs, right? That these are all pairs of electrons, whereas these 3 electrons over here are unshared pairs of electrons. The second thing to notice about this diagram in particular is the fact that as we're filling up, we go from 1s to 2s to 2p, 3s, 3p, but then we jump to 4s before 3d, and then 4p, and then 5s. And so for a lot of reasons that are much more complex for us to get into today, the order in which our subshells get filled up is not necessarily just in numerical order. That the process is much more complicated than that. I'm going to jump back to this just so you can see them without the arrows in there. There's a couple of different versions of the way that you could fill this up, whether you could write this in order to remember the order of this. One of them that I really enjoy, sorry, I'm going to fill these in super for you, okay, would be to look at or notice how this plays itself out in the periodic table and understanding that our s orbitals are filled up over here, our p orbitals, our d orbitals, and then our f orbitals, especially if we remember that fills in right over here. And so if I was looking at something like chlorine to write its electron configuration, excuse me, I would start from hydrogen and I could just read from left to right and continue to fill in until I realized that the final part of chlorine is 3p5. But leading after that, I have a 3s2, a 2p6, a 2s2, and a 1s2. But when I look at here's vanadium, we just looked at, I could do a similar thing for any of my elements in transition metals. I would read across 3p6, 4s2, 3d. So these 4 are all the d block, we would call the d block, and they're depressed ones. So that the third is filled in right here, it's down 1 row. It's in the 4th row of the periodic table, but the 3ds are filled in here, and that's consistent going down here. And then these guys that filled in right here are depressed twice. So 6s, 4s, right? So we just spread it too. So this is a handy picture, and it's a really nice kind of way that we can use the periodic table as a little bit of a cheat sheet to help us understand how the electrons are filled in. This is one of those we probably want to do a significant number of practice problems, and because we're running quick on time here, I'm going to move us forward towards our next topic. But go ahead and take a look at a lot of the examples that are available either in your textbook or through your teacher to be able to continue on with electron configuration. Okay, photoelectron spectroscopy is another way that we can analyze what's happening inside of an atom, and this is, or we're going to have a very specific type of graph. We're looking at a model of how electrons again are organized within an atom, and we're trying to understand the relationship between the spectrum of atoms and its electron configuration, which we'll see in a minute, and the interaction between the electrons and the nucleus. So as we're looking at each of these, we should definitely make sure we answer the question and see both of these things. Photoelectron spectroscopy is a specific graph that is going to have lots of peaks on it, and what we want to remember is that the position of the peak, and I'll give you an example of one of these here. Let's use one. Okay, the position of the peak, we see this small little peak right here. Okay, the position of the peak is related to the energy required to remove an electron from that subshell. Okay, and so what we see is sort of a backwards scale first of all on our x-axis, right? So this is relatively close to 0 if the higher numbers are over here. What I sometimes like to think about is if this electron is further, if the nucleus were over here, let's say, and the electron is further away, it's probably easier to grab that electron and pull it away. So putting it over here helps us to understand that it's further away from the electron, which means less energy. Right? And then the height of the peak is proportional to the number of electrons in that subshell. So what we're going to notice here is that this is right along our first line, which could indicate since it's a relative number of electrons, here it's going to indicate that there's probably 1 electron that has this amount of energy. Let's call that 1.5 or 1.75 megajoules per mole in order to pull the electrons off of that subshell. Since there's just 1 electron that is indicated here, we can assume that this is the photoelectron spectrum for hydrogen. And these are much easier to read, I think, once we start comparing them to other elements. So let's put up helium next to it. And there's 2 things that we notice. We notice that the peak went up to the second line, so we went to a second electron here, right? If this is 1 electron, then this one is 2 electrons. And the second thing that we notice is that the peak moved a little bit further away from 0. There's more energy that it takes to pull these electrons away. And we know that helium in this nucleus has 2 protons, whereas hydrogen only has one. So it makes sense that it would take more energy to pull electrons away from a helium nucleus than it would from a hydrogen nucleus. So two things I'm noticing here: the peak went up and the peak moved to the left slightly, meaning there's more energy, or it's more difficult to pull electrons away. Let's keep going, and we'll compare helium to lithium. We notice that this peak of 2 electrons jumped even closer to, moved further to the left, meaning that it takes more energy. Once we added a third proton in here into lithium, it's going to be even harder to pull these electrons away. But now we have a third electron out here. This was going to be easier to pull away, in part because these two electrons are probably shielding it, and it's on a higher energy level, which corresponds to what we're looking at in topic 1.5. We have this one electron that's right here versus the 2 electrons right here, so this is going to be a little bit easier to grab. Lastly, let's compare that to beryllium. The same patterns are coming over and over again. We see that the peak slid slightly over to the left, and this one doubled. It's probably moved over a little bit to the left, but not too much here. We've got 4 electrons that we're showing here, and that's a key piece of information that helps us to see that this is beryllium, right? So now why don't you give this one a try? Obviously, this is much more complicated. You notice that the numbers have shifted down here at the bottom. However, we still have the larger amount of energy is over here on the left, the smaller amount of energy is over here. If this is the complete spectrum that's given to you, can you tell me the electron configuration and then ultimately what the identity of this element is? Pause for a second and see if you can do that. My solution to this would be to start from my left and indicate which part of the electron configuration I can correspond with each of these peaks. So here I see 1s2, 2s2, and 2p6. I counted this out: 1, 2, 3, 4, 5, 6, all the way up here. Another 2 is right there. We're in the third principal energy level, and we're left with 3p3. I put all that together. That tells me that this is the electron configuration for phosphorus. And if I were to add up all my electrons here, 2 plus 2, I've got 15 electrons, and that would be consistent with what's happening with phosphorus as well. Okay, there's lots of examples of these again on AP Central. This has appeared in a couple of different parts of the AP test, so I would encourage you to keep looking for more examples like this. But writing your electron configuration across the top of the page, I think, is a really effective way for you to analyze this type of a picture. Now, my favorite part of the lesson, looking at periodic trends, and what we're asked to do is to consider 4 different trends on the periodic table, 4 different properties of atoms that will change in a consistent way based on some behavior and some, I guess I should say, based on the organization of the atoms, and then their behavior the atoms will follow along with that. I always like to look at atomic and ionic radius first, because I think so many of the other trends will come from a clear understanding of what the size or the radius of an atom is. And so once we have an understanding of that, I think the other 3 fit in really nice. So I'm going to start with atomic radius. Okay. Oh, this idea, that periodicity, right? That there are repetitive patterns on the periodic table, and that when we look at a column within the periodic table, we're going to be able to make some really nice predictions about if we know where something is, we can predict how it's going to behave based on how the other atoms in that column will behave as well. So let's look at the radii. Okay, and atomic radius is just a measurement, generally in picometers, of the radius. So from the center of an atom to its furthest electron, and that's a way oversimplified example or model of what happens to an atom. We know that atoms are not actually spheres, but if we imagine them as a pool ball or a pool cube, we would see that if it has a larger radius, this is a larger sphere versus a smaller radius, it would be a smaller sphere. Okay, I'm not saying that I think that atoms are spherical, but for this example and looking at radii, that's a really good model just for us to use in this case. So we see as we read across the periodic table here, from lithium all the way over to fluorine, we see that the radius is getting smaller. Okay, from 145 to 50. We also know that as we go across, I'm labeling this as nuclear charge. Think about what these numbers could also represent as I go from left to right on the periodic table. What identity for lithium is a 3, beryllium is a 4, boron is a 5. If you said number of protons, then you're right. The nuclear charge, the charged particle in the nucleus, is the proton. And we know that there are more protons as we go across the periodic table. 9 protons over here. And so what that means is, even though I'm adding electrons as well, the size of the atom will decrease. I'm adding electrons to a second principal energy level. If these models look familiar, these Bohr models, they don't tell us exactly what an atom looks like, but they're a useful model in this example or for this explanation. I'm adding electrons to the second energy level. As I continue to add an electron, I go from 1 to 2 to 3 to 4 to 5, 6 to 7 on that last ring. I'm also adding a proton to the nucleus, because the effective nuclear charge, the pull that the nucleus has on those electrons increases. It's able to pull the whole radius in. And so as I look across a row on the periodic table, I would expect the radius to decrease because the effective nuclear charge, or the number of protons, is increasing, and they're pulling on electrons in the same energy level. Let's continue looking at fluorine here and look at what would happen if we go down the column that fluorine is in. Look at all the halogens. We notice that the nuclear charge is increasing again, right, from 9 to 7. These are some really big jumps as I go down the number of protons. And so I might expect that the radius is going to go down as well. That when I have 53 protons, that I would have a much smaller atom as well. But what I notice as I go down a column on the periodic table, that the atomic radius actually increases. And it increases because we're adding energy levels around the outside. Again, this Bohr model is a very limited model, but in this case, it works well because we're adding rings on the outside of the atom. Because this iodine here has more rings on the outside, we would say that this is a larger atom, has a much bigger radius. Okay, so if the nuclear charge increases as we go down the periodic table, but the number of energy levels for the electrons increases as well, and so that's an important piece of information that's going to give us a larger radius at the bottom of the periodic table. Here's a nice picture that kind of shows the entire periodic table, and it's pretty clear over here. Our first group, that from hydrogen all the way down to francium. Francium would typically be considered one of the largest atoms on the periodic table. Okay, we're typically going to have the smallest atoms over here. Hydrogen might be an exception just because it's only 1 proton and 1 electron, but these certainly, as we go across all of the other rows, we have smaller atomic radii. All right. We look at ionic radius. So how does the radius of an atom change when we turn it into an ion? It's going to be a different story for cations and for anions. So for aluminum, this is typical for all cations. Cations are generally smaller than the atoms they came from. Why is that? Well, they lost electrons, and if we're clear, which electrons did they lose? They lost their valence electrons. So aluminum is maybe an extreme case because it lost 3 electrons, 3 valence electrons from its outer energy levels. The energy levels now just effectively disappear. But the number of protons on the inside of the nucleus stays the same. And because it has all those protons pulling in on the fewer electrons that are there, what we can say is the effective nuclear charge is even greater. They're pulling those electrons in, and so the radius is pretty significantly smaller for a cation. For an anion, the explanation is just the opposite. We're adding electrons. We're adding electrons to an energy level that is admittedly probably already there. But the ratio of protons in the nucleus to electrons on the outside is now flipped towards more electrons on the outside. We have the same number of protons pulling on more electrons. They're not able to pull as effectively, and so the radius is going to get larger. And that would be consistent for most anions. Anions are generally larger. Negatively charged particles are larger than the ion they came from. Cations are generally smaller. So if you were to look at these 5 sets of elements, these 5 sets of atoms, to see which one of them would have the same, which one of them has the same atomic radius, we would probably want to zero in on this group right here as being the closest to the same. We know that these are going to get much bigger as they go down. These are going to get much bigger as they go down. These go bigger and across. So even though they're going across, they're still going to be much bigger than one another. Okay, and these have even though they're similar to what's happening here because these are closer to one another and we haven't jumped up the principal energy level here, we're going to say that this group, the group in black, has the most same atomic radius as everything else. I'm going to zoom through a couple of other terms, looking just being aware of what our time is right here. When we define ionization energy, we're saying ionization energy is the energy needed to remove an electron. So we're making something into positively charged cation. Okay, and for me again, I think this is strongly associated with atomic radius. If I understand atomic radius, this seems to make a lot of sense to me. If I have an atom with a small radius, or all of the atoms with small radii, it's really difficult to remove that electron. Right? It's being held onto more tightly by the protons that are there. So our ionization energy is higher, and the opposite would be true for atoms with a larger radius. It's easier to remove electrons because meaning that the ionization energy is lower. It's easier to remove an electron that's further away from the nucleus, so the ionization energy is lower. We look at a graph or a version of the periodic table with ionization energies on it, and we see that all of these over the right-hand side of the periodic table, which are our largest atoms have, sorry, our smallest atoms have the largest ionization energy. So it's very difficult to pull an electron away from these small atoms. Electronegativity is defined as the ability of an atom to attract shared electrons. We see here that typically in electronegativity charts, we leave off the noble gases because they typically do not make a lot of covalent bonds. And so there's not a lot of shared electrons that they are going to be pulling electrons towards. I like to tell my students, E.T. Phone Home, that's probably a movie that dates me a little bit, but F, O, and N are three most electronegative elements. We've got chlorine right here. If we remember that these 3 or 4 elements over here are the most electronegative elements, that fluorine is typically considered the highest electronegativity value at 4. Then everything else kind of decreases as we move further away from fluorine. And when we get into polarity of molecules, this is going to be a really important topic for us to remember. So we'll review this again when we get to that. Electron affinity is just the opposite. It's the energy change when an atom becomes negatively charged. And so we see we have both positive and negative values here because they have its energy is released here when we have electrons. Because fluorine is going to gain an electron very easily. It has a very easy place in its outer electron shell to add that last electron to make it eighth in a complete stable energy shell. And so this releases a ton of energy over here, whereas we have to force an electron to gain, or force strontium to gain it. We have to put energy in here. This is a calculated value. This is a theoretical idea. Okay. So real quick, I'm going to zoom through these where we look at, if we consider the 5 elements that are circled here, which one do you think has the highest electronegativity value? We're going to look for the one that's closest to fluorine. So that's this one up here. Which one has the largest atomic radius? And that would be cesium down here in the bottom corner. Which one has the lowest first ionization energy? Well, we're going to look for the largest atomic radius because it's easiest to pull that electron away from something that's bigger. So that's going to be cesium as well. And so you see, typically with problems like this, we're going to have the 2 opposite sides of the periodic table with the answers to questions we look at. Here's a great summary of all 4 of the trends from this topic, all put together on one screen. So this is a great one to take a screenshot of, maybe make a note of. Just remember that anytime you're asked to give an explanation of one of these elements or one of these trends, you want to talk about the chemistry, not talk about its location on the periodic table. So saying something like helium has the highest ionization energy because it's the top right of the periodic table would not be an acceptable explanation. But talking about its size, talking about its effective Beer charge, its relationship to protons and electrons would be the best way for you to do that. Lastly, we're going to look really quickly at valence electrons and ionic compounds and understand that it's really important to understand how many electrons are on the outside of the atom because that's going to help us to in our conversation of what's happening with chemical bonds. Right? It's all in service to a good explanation of chemical bonds. And so we know that elements of the same column tend to form similar compounds, and that is because they have similar charges associated with them. Okay? So I think we all probably have a version of a periodic table that has the number of valence electrons for each column in here. But if you don't have one of those already, here's just a really quick example of how the number of valence electrons they go from left to right increases. 1, 2, 3, 4, 5, 6, 7, 8. Come down here because I think you have a picture up on the top right of your screen. Didn't want that one to get covered up. And the number of valence electrons varies in here, and it's a little more complicated. And we'll leave for another conversation on another day. And then if we're looking at what the charges are that each of the columns in the periodic table make, we have a nice color-coded version here. And my students have one of these in their notebooks already, where we know that metals on the left-hand side of the periodic table make positively charged atoms because they lose electrons at a predictable rate 1, 2, and 3. And atoms on the right-hand side of the periodic table gain electrons at a predictable rate. These guys gain 1, 2, and 3. And the noble gases over here don't typically add or remove an electron, nor do anything in carbon's column. Okay, so I would imagine that this is a review for many of the people listening to this, but just making sure that you have this in your brain when we're solving some problems like this. And so magnesium combined with fluorine, which other elements would you expect to combine with atoms of fluorine in the same ratio? And here we would go back. I'm going to go back just real quick, and I would want to say, notice that magnesium is here. So I'm going to look for any of the elements that are in the same row. So any of the alkaline earth metals would be great. The second problem that you might want to look at is based on this information. We're going to look at hydrogen, lithium, sodium, potassium. These are some oxides or some compounds that each of these elements make with oxygen. What would we expect rubidium to do? Noticing that as we go down this column of the periodic table, we're increasing the number of oxides that it makes. So we would expect rubidium to do the same thing, to behave most like potassium here, not like hydrogen because it's below, because rubidium follows in right below here on the periodic table. Okay, so that was a lot of information in a really short amount of time, and I'm already over our allotted 45 minutes, or expected 45 minutes. So I apologize for that. I hope that you're still with us. I know that there's a lot that we shared with you today, but please go back and review, take some notes, take some screenshots so that you're feeling more confident in what we have there. I've got 2 exam practice problems for you to look at. Mr. Faribault will go over these with you tomorrow. This is from the 2015 free response question. We jump ahead to letter E. And I don't even remember which problem this is, but not important for you right now. You should be able to give me an electron configuration and then consider what sublevel the electrons would be removed from. And then the 2018, we've used that one a lot. There's lots of great information on that test question number 3, where the ground state electron configuration for an ion. So notice this is an ion. And then when we look at the radius use principles of atomic structure, okay, so here's that phrase. We're not going to talk about where it is on the periodic table. We're going to talk about its atomic structure as evidence of why this behaves like this, why iron behaves like that. Okay, just a quick reminder. I keep going back to apcentral.collegeboard.org to get up-to-date information. We've got lots of extra resources at the bottom of the screen for you, and at that tiny URL. If you or anybody you know is still having trouble with the internet or getting a device on a consistent basis, we want to see your best work. So please either reach out to us directly or send your friends to this site so that they can get the resources that they need. Thanks so much for sticking with us today. I know we threw a lot at you, but it's always great to be with you, and we look forward to seeing you again in the next couple days. Have a great day.
Buenos días, estudiantes. Hoy es miércoles 1 de abril y bienvenidos a esta lección de AP Español, Lengua y Cultura. De nuevo, yo me llamo Miguel Faribault y seré el profesor de esta lección hoy. Y bienvenidos a algunos participantes nuevos que tal vez estén aquí por la primera vez. Okay, in case you haven't checked your calendar, today is April 1st, and many of you watching now probably know what that means. That introduction was nothing more than a silly April Fool's joke. Hello, everyone, and welcome to this AP Chemistry virtual lesson. My name is Michael Faribault, and I really do teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. This is day 6 of our series of lessons on AP Chemistry. These virtual lessons we present daily, Monday through Friday. We began on Wednesday, March 25th, and this series of lessons will run through Friday, May 1st. Today and tomorrow will be a review of the chemistry in Unit 2. That would be molecular and ionic compound structure and properties. I would like to remind you, as always, that you should feel free to pause this video if you feel that I'm going too fast, or if you perhaps I'm not even speaking English, or if you need more time to think about a question that I've asked you. Again, for more information on the AP exams, you can visit the following website. That's apcentral.collegeboard.org, and you can get updates of the AP exams. All right, well, if you have a pen or pen and save to 3D10, but you don't have to necessarily write the entire configuration full like that. You could also abbreviate it with the noble gas, argon, and then write 4s2 3D10. So either of those would be acceptable. And the language of the AP question, unless they say specifically write the complete configuration, and they make any comment about not using the noble gas abbreviation, either of these would be acceptable. All right, well, the next part of the question had to do with which sublevel are you going to remove electrons from when zinc becomes oxidized. So zinc normally loses 2 electrons. So here is the rule. When removing electrons from a neutral atom to form a positive ion, the electrons in the orbitals that have the highest energy level are removed first. So if you have a choice between 3d and 4s, which electrons should be removed first? And the answer is 4s. You should definitely remove the electrons from the 4s sublevel. So therefore, in this case, if you have a choice between 3d and 4s, you go with the highest energy level. So this is the scoring guidelines, the official answer. All right, let's move on to the next part of the question. This question has to do with iron. We have to compare iron 2+ and 3+, and we need to also talk about electron configuration. Oh, okay, that's what happened. I was trying to figure out exactly why. Sorry about that. I was trying to figure out why my camera went off. I think it's back. All right, let me just continue here. I just didn't seem like it. Okay, so here we are talking about the ground state electron configuration of the iron 2+ ion. Now, the ground state electron configuration of iron is going to be 1s2, 2s2, like we did before, all the way up through 3d6. But you have to be careful that you read this question carefully. Okay, in this case, we're not looking at the electron configuration of iron, the atom. We're looking at the electron configuration of the ion, the +2 ion. So you have to be careful that you realize that we are answering the correct question. This is not going all the way through to this particular configuration. We're stopping by removing the 4s. So the configuration of the iron 2+ ion would be without that 4s. All right, and then our next part of the question, so we answered the first part, which is the electron configuration of iron 2+. The next part of the question says that the radii of the ions, iron 2+ and 3+, are given, and we have to explain why is iron 2+ larger than iron 3+. Now, before I talk about this particular question, let me just remind you of something that Mr. Byrne talked about yesterday. So this would be, for example, in a period on the periodic table, the atomic radius is getting smaller within a period from left to right. And we normally describe this because of increasing nuclear charge. So the problem with that particular trend is it doesn't apply in this particular case. We're not comparing sodium with magnesium. We're not comparing fluorine with neon. We're comparing iron with iron. So in fact, because each of them has the same number of electrons, because each of them has the same number of protons, and they have a different number of electrons, they have the same nuclear charge. So if we're going to compare the radii of iron 2+ and iron 3+, we cannot say that iron 3+ has more protons or greater nuclear charge. All right, well, before we answer this question, let me remind you of an example from another part of the periodic table. So why is fluorine -1 larger in size than fluorine atom? And the answer is because fluorine, the -1 ion, the fluoride ion, has one more electron. So it's not about protons, it's about more electrons. So why is it larger? It's because of electron-electron repulsions. So therefore, that is what we're going for in this question. Each ion, iron 2+ and iron 3+, have the same number of protons, but with one more electron. That's going to cause the iron 2+ to be larger, and you should mention electron-electron repulsions. So any student's answer that talks about greater nuclear charge is not going to receive credit for this question. All right, then the last part has to do with Coulomb's law. Let's go ahead and talk about what Coulomb's law represents. Coulomb's law has to do with an attractive force between charged particles. And so we have on the top the magnitude of the charges, and on the bottom the distance between the particles. So we are talking about a situation with Coulomb's law where it's either because of a greater charge magnitude that could increase the strength of the attractive force, or because of a smaller distance between the particles. So we actually have both situations in this case. We're talking about a water molecule, and the polar water molecule is attracted to either an iron 2+ ion or an iron 3+ ion. So we actually can talk about both charge and distance and get the correct answer to this question. You only had to mention one of them to get the point on this particular question. So you could have talked about the greater charge magnitude of the iron, the +3, or you could have talked about the smaller ionic radius, which brings the ion closer to the water molecule. So either of those would be acceptable. So before we get started, I'll just go ahead and show you the scoring guidelines for this particular question from the 2018 AP Chemistry exam. So there was the official answer part A, either the long form or the noble gas abbreviated form of the electron configuration. In part B, talking about greater electron-electron repulsion for the Fe2+, leading to a larger radius, and then either mentioning the higher magnitude of charge or the smaller size. Note, you did not actually have to explicitly state Coulomb's law in order to earn points for that question. All right, so now let's move into our lesson. So what you need to know today has to do with electronegativity, and that is a periodic trend along with things like ionization energy and atomic and ionic radii. So what do we know on the periodic table with respect to electronegativity? Well, we know that since atomic radius decreases from left to right, electronegativity values generally increase from left to right across the period, and they generally decrease from top to bottom down a group. Here are some electronegativity values of selected elements on the periodic table. You can see that that general trend holds true, increasing left to right and generally decreasing or perhaps remaining about the same as you go down. So how do we tell whether a bond is polar or non-polar? We have symbols X and Y represent two different elements. So here we have two different elements. I'm going to go ahead and classify this bond as polar. I don't have to know what the electronegativity values are to decide that this is a polar bond. I have two atoms and they're different, so they have a different electronegativity, which means a different pull on the electrons that are being shared. So therefore, if I have two atoms and they are the same, that is a non-polar bond. Now the AP exam is going to ask you sometimes to compare the polarity of the bonds, and we'll talk about that as well. All right, the symbols X and Y represent two different elements. Which of these polar bonds has been labeled correctly? We have a partial positive charge. There's a little lowercase delta plus, and we have a partial negative charge. Now at this point, without knowing what the identity of the atoms are, it's kind of hard to say which of these bonds has been labeled correctly. So let's go ahead and give you some examples here. Suppose that we have, let's say, phosphorus, and it's bonded to chlorine. Now phosphorus and chlorine are in the same period, and since chlorine is further to the right in the periodic table, that would mean that chlorine is in fact more electronegative than phosphorus, and that would be a partial negative charge on chlorine. Suppose, for example, we had a oxygen bonded to a carbon. Well, on the periodic table, since oxygen is further to the right, that's more electronegative. This would also be correct. So you have to know on the periodic table in general what the trends are for electronegativity to decide which atom has a partial negative charge. Okay, so as I said, in a polar covalent bond, the atom that has the greater electronegativity value will have a partial negative charge, and you don't have to know those values per se, just know the general trend. Right, in a polar covalent bond, the greater the difference in electronegativity, the more polar the bond is. So for example, if I gave you, let's say, boron bonded to nitrogen, and let's say boron bonded to fluorine, you could decide that of the two bonds, the boron-fluorine bond would be more polar because of a greater difference in electronegativity. Not because you had those numbers in front of you, but simply because they were farther apart from each other on the periodic table, there'd be a greater difference. So the BF, the boron-fluorine bond, would be more polar. Now, this next slide has to do with a general thing that most students learn with respect to bonding, that for a typical binary compound that contains two elements, the metal and the non-metal, when they bond together, they tend to form an ionic bond, and that when two non-metals bond together, they form a covalent bond. Now, of course, there is a continuum between covalent and ionic bonding. If you look hard at a variety of examples of compounds in the world of chemistry, you can find some metal-non-metal combinations that actually have some covalent character, and you can find some extremely polar covalent bonds that sort of border on being partially ionic. So this is a very simple general rule that can solve some of your problems to decide what kind of bonding is it. But another way to characterize the type of bonding would be to examine the properties. So I'll just give you some examples of properties. Suppose we have a solid that is a good conductor of electricity. Well, what kind of bonding should that solid have? Typically that would be a metal. So metallic bonding is characterized by solids that are excellent conductors of electricity, so things like copper and aluminum and zinc. If a solid does not conduct electricity as a solid, but can become a conductor when either melted into a liquid or dissolved into water, that's a good characteristic of ionic bonding. So things like sodium bromide or potassium chloride or aluminum nitrate, those would be compounds that while they don't conduct electricity, when dissolved in water or melted, they do become conductors. Other properties that might give you a clue about the type of bonding: if a solid does not conduct electricity in any phase, solid, liquid, or aqueous, and has a relatively low melting point, so something like water, that would be molecular or covalent molecular. And a solid that has all those properties about not conducting electricity but actually has a very, very high melting point, that would suggest covalent network. Now, we are right now in topic 2.1, 2.2, 2.3, 2.4, that's in unit 2. I will tell you that on Friday, we will be talking more in topic 3 about properties of solids and intermolecular forces. So you'll see more discussion of these types of things. I'll move on to metallic bonding, which I mentioned. You should know that at the particle level, a metal consists of a crystal lattice of positive particles, and in that positive particle is the nucleus of the atom and the core electrons. Now, the valence electrons are free to move throughout the lattice. So chemists and teachers and textbooks often refer to this model as a SEA, of delocalized valence electrons. And so that mobility of the valence electrons is why metals are such good conductors of electricity. All right, I mentioned earlier we're going to be talking about this diagram of potential potential energy versus internuclear distance. So potential energy is on the y-axis and internuclear distance is on the x-axis. So in this region of the diagram, the potential energy is high, which means that would be a less stable arrangement of the atoms. And then down here at the bottom of the diagram, the potential energy is low. That would be a more stable arrangement of the atoms. So internuclear distance just literally means the distance between the nuclei of the two atoms. Now suppose we have these two atoms. As you can see, they are relatively far apart from each other. So the potential energy is essentially zero because there are no attractions between the protons and the electrons, and there's no repulsions either. So these two atoms are not forming a bond. What will happen if we bring them closer together is that the protons of one atom start to become attracted to the electron cloud of the neighboring atom. And so as that becomes a more stable arrangement, there is attraction between the atoms, potential energy is less than zero. Now it keeps moving down along the y-axis until we reach this local minimum. At this point, this is the most stable arrangement for the atoms. There is a balance between attractions and repulsions, and we have a stable bond. So that means that potential energy is at a minimum. This is the most stable arrangement. Along the y-axis, this would be the energy required to break this bond, and along the x-axis, this would be the length of the bond itself. And we'll talk more about this diagram as we take a look at examples of bonds. What happens if we go even closer for these two atoms? With it now, there's too much repulsion between the nuclei, and this is an unstable arrangement. So as you can see, potential energy is now greater than zero when the atoms are too close together. So a chemical bond is essentially a balance between attraction and repulsions in terms of potential energy. All right, next thing I want to talk about is trends in bond length and bond energy. How are these two properties of a bond related? So we have four bonds: HF, so hydrogen and fluorine; HCl, hydrogen and chlorine; and then HBr, hydrogen and bromine; and finally hydrogen and iodine. Which of these bonds is the shortest, and which of these bonds is the longest? Let's review the periodic trend for atomic radius. Well, we know that from left to right across a period, atomic radius tends to decrease because of increasing nuclear charge within that energy level. But when you're going down a column on the periodic table, you are changing to the next occupied energy level, which is going to be farther and farther away from the nucleus, so atomic radius increases. Therefore, fluorine, chlorine, bromine, and iodine, they're all getting larger. So we're going to draw the size of fluorine, and then the size of chlorine, I'm going to draw this a little bit larger, and then the size of bromine a little bit larger than that, and then the size of iodine. Now, I still have my little hydrogen bonded to it. Hopefully you can see that based on your knowledge of periodic trends in atomic radius, that the Hi bond would be the longest bond, and that the HF bond would be the shortest bond, just based on the fact that fluorine is smaller than iodine. Well, how much energy do you think is required to break these bonds? We're talking about bond length right now. Let's talk about bond energy. Which of these bonds do you think would be the easiest to break, therefore the smallest bond energy? And which bond do you think is the most difficult to break, the largest bond energy? Well, hopefully you can reason through this and think that the longer the bond is, the farther the atoms are apart, the easier it is to break. So Hi would have a low value for bond energy relative to HF, which has a high bond energy. Let me go ahead and show you the data. So take a moment to process that data, and you can see how bond length and bond energy are inversely related. All right, let's talk about, so we look at single bonds, let's talk about double and triple bonds. There's something called the bond order, which essentially means how many bonds you have between the atoms here. So we have a bond order of 1 for a single bond, a bond order of 2 for a double bond, and 3 for a triple bond. Which of these bonds, in your opinion, should be the shortest and which is the longest? Well, hopefully you can kind of reason through this for a given pair of atoms of a certain element. So we're not comparing a double bond of carbon with a single bond of chlorine or something like that, but for a given element, as the bond order increases, bond length should decrease and bond energy should increase. So you should be, hopefully, should make sense to you that the triple bond is not only the shortest bond length and the single bond is the longest bond length, but in terms of energy, the triple bond should be the one that's most difficult to break. So it's easiest to break that single bond and more difficult to break the triple bond between carbon. Let me go ahead and show you the data and you can process that. So here we're looking at bond length for carbon, single, double, triple, getting shorter, and bond energy increasing. All right, I want to talk about Coulomb's law again with respect to the attraction, but this time not between an ion and a water molecule, but between ions themselves, between cations and anions in the crystal lattice of an ionic compound. So as we can see in terms of the numerator, which is about charge, and the denominator, which is about the distance between the ions, the greater the charge on the ions, the stronger the attractive force between those ions. And the smaller the ionic radius, the closer we can bring those ions together, the stronger the attractive force will be. And we'll see examples of Coulomb's law in just a moment. Another thing I want to mention, excuse me, about particle diagrams is that we represent particle diagrams for ionic compounds very differently than we do for molecules. With a molecule, you might show an individual oxygen, bonded to a hydrogen like a water molecule, but with respect to ionic solids, the crystal lattice has this big matrix, this big network of oppositely charged ions. And as we'll see on Friday talking about properties and intermolecular forces, this gives ionic solids unique properties such as hardness, high melting point, they're very brittle. All right, I want to also mention some particle diagrams for alloys. So we have an interstitial alloy as opposed to a substitutional alloy. What's the difference? Here we're looking at a particle diagram of an interstitial alloy. This is formed between two elements in which there is a significant difference in size between the elements. The atomic radius of one element is much smaller than the other. So the smaller atoms can fill in the interstitial spaces between the larger atoms. Now for a substitutional alloy, because the atomic radius of the elements are roughly the same size, one element simply substitutes for another within the matrix. All right, on to the guided practice portion of today's lesson. We had talked earlier about electronegativity. So now I'm going to give you a chance to put a partial positive and a partial negative charge on the atoms in these three bonds. So here we have carbon bonded to nitrogen. Take a look at your periodic table, and once you find the elements, can you tell me which element is more electronegative based on the position of the periodic table, and that will help you decide who gets a partial negative charge. So if you're looking on your periodic table along with me, you will notice that nitrogen is further to the right, and if nitrogen is more electronegative, it's going to have a partial negative charge. Moving on to our next example of a bond, these are two elements that are located in the same group. So fluorine and bromine are in the same column, they're both halogens. So which element is more electronegative? Well, hopefully you can see that based on the trend we've been talking about with electronegativity, fluorine is more electronegative than bromine and therefore gets the partial negative charge in that bond. Now we have silicon and oxygen next. They are not in the same period or in the same group, but can we still use our understanding of periodic trends and electronegativity to decide which element is more electronegative? So here we see that oxygen is further to the right in the top right corner. So oxygen is more electronegative than silicon and therefore we get the partial negative charge. I want to remind you that the periodic table does give you these trends without the electronegativity numbers given to you. The AP exam would not ask you to compare something like nitrogen, for example, and bromine. So had you been given these two elements, you'd have to be given the electronegativity values because it's difficult to decide based on the trends whether because bromine is further to the left, but it's also further down the periodic table. So that would not be a fair comparison without electronegativity values. All right, now we're going to be given three bonds and we have to arrange them in order from least polar to most polar. These are all containing fluorine and then either nitrogen, phosphorus, or oxygen. You might be asking, would we be given a table of electronegativity values to answer this question? Well, if you were, then certainly you could do the math. But suppose you were not given the actual values. Could you still make this comparison? Let's take a look at these elements. Which element do you think is the least polar? So considering we have fluorine, oxygen, nitrogen, and phosphorus, I would say that the least polar bond has the smallest difference in electronegativity, and so I would go with the ones that are closest to each other on the periodic table. So in this case, the oxygen-fluorine bond should be the least polar. And then as we get farther apart, since phosphorus is not only to the left but also down one column, phosphorus and fluorine should have the greatest difference in electronegativity, and that puts the nitrogen-fluorine bond in the middle. So you could definitely rank the polarity of these bonds even without electronegativity values just based on trends. All right, as I mentioned earlier, we're going to revisit that diagram of potential energy versus internuclear distance. And we have two bonds, the bond between chlorine atoms and the bond between bromine atoms. We are told that the bond length is 200 picometers and the bond energy is 243 kilojoules per mole for the chlorine-chlorine bond. Now, take a moment to make a prediction about the bromine-bromine bond in terms of bond length and bond energy. So in other words, based on your knowledge of periodic trends, do you think that the bromine-bromine bond would be longer or shorter than 200 picometers? And would the energy required to break the bond be higher or lower than 243 kilojoules per mole? Now, here I have a diagram. This is for the chlorine-chlorine bond, and we can see that this represents the minimum energy, and that would correspond to around 243 kilojoules per mole. We also see along the x-axis, this would be the distance between the nuclei. That's going to be around 200 picometers. So I'm going to go ahead and draw another curve, and this time I'm going to go ahead and make the value a little bit higher, like that. We definitely have data. We also have our periodic trend. We know that bromine is larger in size than chlorine. So did I do a good job of giving a smaller bond energy? I think that bromine-bromine bond is probably easier to break, but what I did not pay attention to is the x-axis. Let me try this again. What if I drew a curve like this? Well, now I did a good job of looking at the x-axis and making that a longer bond, but I also did not pay attention to the y-axis. This has the same bond energy. So I think what's going on here with respect to the bromine comparison is that it should be a longer bond because bromine is larger than chlorine, and it should be easier to break. So this is the curve that you should have drawn. And if the AP exam asks you a question like this, it's possible they might make this worth 2 points. It might be worth 1 point for shifting the bond length to the right, so it's a longer bond, and you might get a point for showing that the bond energy, that is the depth of that valley or that well in the curve, is smaller as well. All right, I would now like to show you the data. So the bond length is around 228 picometers for bromine, which again is longer, and the bond energy is about 193 kilojoules per mole, so less energy to break the bond. All right, next thing I want to talk about is something called lattice energy. Now we did see on the screen earlier that you could draw a diagram for a ionic compound that would look something like this. That's in the solid state, but in the gaseous state, they would be completely separated from each other. So the lattice energy is the energy required to break apart or separate the ions in the solid crystal lattice into individual gaseous ions. We are given some data. We're given data for sodium fluoride. It's 930 kilojoules per mole. That's the lattice energy. And I want you to use Coulomb's law to make a prediction about the lattice energy of magnesium oxide and potassium chloride. So do you predict that magnesium oxide's lattice energy will be higher or lower than 930? And will potassium chloride's lattice energy be higher or lower than 930? I'm going to explain each of these on the next few slides. This would be a good moment to pause the video if you want to think about this and make a prediction, and then you can press play to see if your predictions were correct. All right, let's take a look at charge magnitude and distance between the ions. Remember, the greater the charge on the ions, the stronger the attractive force, and therefore the higher the lattice energy. And the smaller the ionic radius, or the distance between the ions, the stronger the attractive force as well. And we are comparing sodium fluoride and magnesium oxide. Let's think about charge and distance. Go to our periodic table and find these 4 elements. Now, sodium and magnesium are in the same period, and oxygen and fluorine are in the same period. In terms of size, sodium is a little bit larger than magnesium, and oxygen is a little bit larger than fluorine. So therefore, sodium fluoride and magnesium oxide is not a significant difference in terms of size. But as you probably know, with respect to the charge on the ions, we're talking about +1 for sodium, +2 for magnesium, -2 for oxygen, -1 for fluorine. So therefore, if I'm comparing sodium fluoride, which is +1 -1, with magnesium oxide, which is +2 -2, a higher charge magnitude is what's going on here. So in terms of our prediction, since the magnitude of the charge on the ions for magnesium oxide is greater than that of sodium fluoride, the lattice energy of magnesium oxide should be greater. So that's our prediction, greater than 930. Now on to potassium chloride. Well, if you look on the periodic table, sodium and potassium are in the same group, the alkali metals, and fluorine and chlorine are in the same group, the halogens. So we're not talking about a difference in charge. They're both +1 and -1. But as you know, as you go down a column, atomic radius increases because of the increasing energy level of those occupied valence shells. So the potassium and the chloride ions will be located farther away from each other in the crystal lattice. This is not about charge, it's about distance. And since the ionic radii of the ions in potassium chloride are larger than that of sodium fluoride, the distance between the ions is greater, and the lattice energy of potassium chloride should be less than that of sodium fluoride. Now, we've made our predictions. Let's see if our predictions are correct. Lattice energy for magnesium oxide is around 3,800, and for potassium chloride around 720. So yes, our predictions were true. All right, let's talk about metallic and ionic bonding for a moment. Hopefully you can recognize that in this table, copper is a metal, and copper chloride, CuCl2, is an ionic compound. A student checked the conductivity of 2 different solids, and the results are listed in the table above. Explain why the student got these results in terms of principles of chemical bonding. Now, I added the next sentence because I know in my classroom, sometimes my students will give the following answer. Copper is a conductor of electricity. Why? Because it's a metal. Well, that's not really an explanation of the specific particles and how the behavior of these particles is related to the conductivity of the solid. So you have to go beyond saying it's a metal and that's why it's a good conductor. It's kind of like saying, why is potassium larger in size than sodium? Your answer cannot be because it's located further down on the periodic table. You have to be more specific and talk about what's going on in terms of energy levels and particles and such. All right, so we know that copper is a conductor of electricity and copper chloride is not in solid form. So what I said for copper is the following. You may remember seeing that picture of the CSEA of mobile valence electrons. Copper is a metal and can conduct electricity because the valence electrons are delocalized and able to move freely throughout the crystal lattice. So the C of mobile electrons is why copper, or any metal, is a good conductor. Now for copper chloride, something is not able to move around. It's not exactly the electrons that are locked in place, but rather the ions, the charges that are the copper ions and the chloride ions. So copper being an ionic compound, in the solid form, the ions in the crystal lattice are unable to move freely within the solid. Again, be specific and talk about what particles are moving or not able to move. Now, if copper chloride is not a conductor of electricity in the solid form, what are 2 different changes that could be made to the sample of copper chloride that would enable it to become a conductor of electricity? And so the 2 things that we could do would be either heat up this copper chloride solid until it melts, so in the molten form, then the ions are able to flow and move and conduct electricity, or we could take a sample of solid copper chloride and dissolve it into distilled water. And in aqueous solution, now the ions are broken up from that matrix and they're able to flow and move, and a solution of salt water, copper chloride dissolved in water, aqueous, could conduct electricity. All right, next thing I want to mention, I talked about substitutional and interstitial alloys before. Here is some data for copper and zinc. Should we identify brass as an interstitial or a substitutional alloy? Justify your answer. Well, since all we really have here is the atomic radius, that should feature prominently in our answer. A substitutional alloy is one in which the atoms of the minor element replace host atoms in the crystal lattice. So substitutional alloys form between metals whose atomic radii are similar in size. So brass is a substitutional alloy because the atomic radii of copper and zinc are similar. Here we have iron and carbon, which are combined to make steel. Should we classify this as substitutional or interstitial? We'll take a look at those atomic radii. They are very different. So an interstitial alloy is formed between atoms of different radii, where the smaller atoms fill in the interstitial spaces between the larger atoms. So steel is a good example of an interstitial alloy because the atomic radii of iron and carbon are quite different. All right, I will now do a quick debrief and summary for this lesson on bonding, and we will then take a look at our homework, which is the AP practice problem for tomorrow. So we looked at types of chemical bonds. We talked about the attractive force within the molecule, so intramolecular. Talked about potential energy. Looked at the structure of ionic and metallic substances, including alloys. We learned about how to tell if a bond is ionic or covalent, how to tell if a covalent bond is polar or nonpolar, how to compare 2 polar covalent bonds and decide which one is more polar than the other. Again, we talked about metallic and ionic bonding. We looked at graphs of potential energy versus internuclear distance. We talked about the relationship between bond length and bond energy. We talked about Coulomb's law as it relates to the attractive force between ions in an ionic compound, and then I did mention the definition of interstitial and substitutional alloys and gave you some examples. So now here is your AP exam practice homework for next time. Number 1, answer the following questions about nitrogen and oxygen. In part A, all you're doing is writing the Lewis electron dot structure for the diatomic molecules N2 and O2. Now we didn't talk about Lewis electron dot structures today, but we will be talking about them tomorrow, and I think these molecules are fairly straightforward for you all to do. In part B of this question, you are given a potential energy as a function of internuclear distance diagram, and these are for the diatomic molecules N2 and O2. So based on the data in the graph and the Lewis structures that you drew in part A, which occur 1 or 2 is the better representation of the N2, the nitrogen molecule? Justify your answer in terms of the principles of chemical bonding and bond energy. There's also a part 2 for the practice for homework. Answer the following questions related to magnesium and strontium. Part A, write the complete ground state electron configuration for the ions Mg2+ and Sr2+. Part B, do you predict that the ionic radius of Sr2+ is larger or smaller in size than the ionic radius of magnesium 2+? Justify your answer in terms of atomic structure and the electron configuration of each ion. And then finally, part C, the lattice energy of magnesium chloride MgCl2 is 2300 kilojoules per mole. Make a prediction about strontium chloride. Do you predict that the lattice energy of SrCl2 should be less than or greater than 2300 kilojoules per mole? Justify your answer in terms of Coulomb's law. All right, as this virtual lesson comes to a close, I want to remind you about there should be a link in the video description where you can see a variety of helpful chemistry resources that relate to online learning of chemistry. Again, this has been Michael Faribault from Albemarle High School. I want to say thanks for watching this lesson. Remind you to go to cb.org/tech if you or anyone you know has some needs for mobile tools or connectivity for the online AP chemistry exam. All right, that's the end of this lesson. Tomorrow we'll talk more about Unit 2. Thanks for watching. Hello everyone, and welcome back to another AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School. Go Patriots! And I'm in Charlottesville, Virginia. Thank you for this particular lesson and coming back, and we're going to be continuing our exploration of Unit 2, which is molecular and ionic compound structure and properties. So we'll talk more about bonding today. I want to remind you that you can go to apcentral.collegeboard.org to get more information about how the College Board is supporting schools that may be closed right now. And again, any updates that you're looking for about the AP exam can be found at that website. All right, because we're talking about bonding and valence electrons, make sure you have scratch paper, something to write with, and definitely a periodic table. Feel free to pause the video at any time if you need to either take a break or finish a problem or get some more resources to help you understand what's going on. Let me give you a lesson overview. We'll be talking today about Unit 2 and focusing on topics 2.5, Lewis diagrams, so Lewis electron dot diagrams, 2.6, resonance and formal charge, and 2.7, valence shell electron pair repulsion theory and bond hybridization. The science practices that go along with these topics include represent chemical substances or phenomena with appropriate diagrams or models, and support a claim with evidence from representations or models at the particulate level. So today we'll talk about the Lewis electron dot diagrams, how to draw them, talk about resonance structures and formal charge, talk about valence shell electron pair repulsion theory and molecular geometry, bond angles, hybridization of valence orbitals, and a little bit about sigma and pi bonds. For our warm-up problem today, this would be the free response question that I had presented in yesterday's lesson. So part 1 was answer the following questions about nitrogen and oxygen. Part A, write the Lewis electron dot structure for the diatomic molecules nitrogen N2 and oxygen O2. Now we did not look at that yesterday in terms of a skill for how to write Lewis electron dot structure. So on your periodic table, most of you should know that the valence electrons can be found for a given element by looking at the groups. Ignoring the transition metals between scandium and zinc, the number of valence electrons goes from 1 to 8. So since we have nitrogen, which has 5 valence electrons, and it's a diatomic molecule, that would be 10 electrons. The valence electrons for N2, and then for oxygen would be 6 times 2, which is 12. So these are the electrons we have to work with. Let's start drawing the Lewis electron dot structure for nitrogen first. So initially we'll just connect the atoms with a bond. Now right there, that is 2 electrons. Okay, so that would be a bonding pair of electrons. I can also add a lone pair of electrons or a non-bonding pair of electrons. And I have to remember what my count is. So I have to go to 10. So we'll continue. That would be 4 right now. So 6, 8, 10. And then that's it. I have no more electrons I can add. You may remember learning about something called the octet rule. So if I draw a big circle around this nitrogen atom, inside that circle are 6 valence electrons. If I make a double bond, well, that would now change to 8. But on the other side, this nitrogen still only has access to 6 electrons. So we're going to go ahead and make a triple bond. So that now is the Lewis electron dot structure for nitrogen. Moving on to the Lewis electron structure for oxygen, we now have 12 electrons to work with. 2, 4, 6, 8, 10, 12. And that's it. We have no more electrons. We'll go ahead and move a pair of electrons from the oxygen on the left and make a double bond. Now that you know we have a triple bond for nitrogen and a double bond for oxygen, this will help us answer part B of this question. The potential energy as a function of internuclear distance for the diatomic molecules N2 and O2 is shown in the graph above. Based on the data in the graph and the Lewis structures that you drew in part A, which occur 1 or 2 is the better representation of the N2 molecule. Justify your answer in terms of the principles of chemical bonding and bond energy. So as you can see on the diagram, curve 1 has what I might call a deeper valley in terms of that local minimum in potential energy than curve 2. So the deeper valley, or the lower the potential energy minimum is, that represents a more stable arrangement of atoms. It also represents a higher bond energy. And I think we did talk about in yesterday's lesson that a triple bond is going to be stronger than a double bond. So therefore, since we have a higher bond order in nitrogen, and that's going to have a greater amount of energy required to break the bond, curve 1 is a better representation of the N2 because it represents the diagram with a higher bond energy. All right, we had another problem from yesterday for homework, and this had to do with magnesium and strontium. Part A, write the complete ground state electron configuration for the ions magnesium 2+ and strontium 2+. So again, on your periodic table, you can find magnesium, and if you were to write the electron configuration of magnesium, it might look something like this. So 1s2, that takes care of helium. 2s2, now we're up to beryllium. 2p6, that gets us to neon, and then finally 3s2. Now that would be the electron configuration of magnesium, the atom. But since we are talking about magnesium with a 2+ charge, then you would not include the 3s. So your electron configuration would look something like this. For magnesium, 1s2, 2s2, 2p6, and then you would stop right there. That's exactly how many electrons the magnesium 2+ ion has. Now for strontium, we have a lot more electrons. So if I write the entire electron configuration all the way through 5s2, that would be for strontium, the atom. If we take away these electrons, so the 5s having lost 2, then you would stop at 4p6, essentially having the same electron configuration as the noble gas krypton. And you certainly could abbreviate. You could replace all of this portion of the electron configuration up through 3p6 with the argon as a noble gas abbreviation. Okay, part B. Do you predict that the ionic radius of strontium is larger or smaller in size than the ionic radius of magnesium? Well, hopefully you can realize that the strontium should be larger, and there's a variety of reasons you can figure that out, but here are some examples of wrong answers or incorrect answers that a student might say. They know that strontium is larger. Justify your answer in terms of atomic structure and the electron configuration of each ion. So if your answer says, oh, well, strontium 2+ is larger because it has more electrons, that's not good enough. That's not specific enough. That's just way too general. So try again. You might say, oh, it's because it has more energy levels or it has more shells. Again, you're starting to talk about electron configuration, but that's still not specific enough. Simply saying that it has more energy levels, it's not specific enough. So let's say if you said something about it has more occupied energy levels. Well, now you're getting closer. I still would like you in your answer to talk about the energy level, the difference between level 2 and level 4. So I'm going to go ahead and give you my official answer. Certainly, this is just, me encouraging you all to write good answers to free response questions, and hopefully no one out there would be satisfied with an answer such as, well, strontium is located further down the column on the periodic table. So because strontium is below magnesium, and size increases as you go down. You cannot justify with a trend. You cannot just simply say size increases as you go down the periodic table. That's not giving us an understanding of the atomic structure and the reason why. So the strontium 2 plus ion is larger in size than the magnesium 2 plus ion. Why? Because it has additional occupied energy levels. And I go on to say that the valence electrons in the fourth energy level should be farther away from the nucleus than the valence electrons in the second energy level. So that answer is clear, representing an understanding of atomic principle. So be careful when you write your answers. More electrons or more energy levels would not be a sufficient answer to this question. All right, we have part C. We're talking about comparing the lattice energy of magnesium chloride with the lattice energy of strontium chloride. Now, Coulomb's law has to do with both charge and distance. It looks like, based on the information from the periodic table, that both magnesium and strontium should have the same charge. And obviously, chloride has the same charge. So your answer should be in terms of distance. It's not going to have to do with charge, but rather distance. So here's what I said. Coulomb's law states that the force of attraction between cation and anion is inversely proportional to the square of the distance between them. I'm just kind of stating Coulomb's law in words. Now, since the distance between magnesium and chlorine, because magnesium is a smaller ion, you already addressed that in part B, that's a shorter distance between the ions, the attractive forces in magnesium chloride should be stronger. Now, be careful that you don't omit this last sentence, okay? You have to read the question carefully. So some students do a great job of explaining why, and then they forget to actually answer the question. They were looking for less than or greater than. So make sure that when you're reading the question, you address the question that is being asked. If a student forgot to actually say that the lattice energy of strontium chloride should be less than, we can't give them credit for what is probably in their head, but they just didn't actually put it on paper. All we have to go with as readers is what the words are on the page. So make sure you are reading the question carefully and answering the question that was asked. Okay, let's get to our lesson for today, starting with Lewis electron dot diagrams. I'll remind you of your valence electrons once again. I'm sure you already know all of this, but I'm just going to go ahead and present this. And we're going to start with some simple molecules. Now, carbon has 4 valence electrons, and each hydrogen has 1. So we have a total of 8 valence electrons for methane, CH4. Let's go ahead and connect all the hydrogens with the carbon. Remember that we have bonding electrons as well as non-bonding electrons. So here, this would represent a bonding pair of electrons. Well, since we have 4 dashes, 4 times 2 is 8, we're done. That's the molecule. There's nothing else to write. The octet rule talks about the idea that atoms tend to gain, lose, or in this case, talking about covalent bonding, share electrons. So each atom has a full valence shell. Usually that's 8, but for something like hydrogen, that would be 2. So hydrogen only needs 1 single bond to satisfy a full valence shell. All right, this is nitrogen bonded to 3 hydrogens. This is the ammonia molecule. Since 5 plus 3 is 8, I haven't finished the structure yet, but I've just simply shown the connectivity between the atoms. That would represent 6 valence electrons because I have 3 bonds. So now we have a non-bonding pair of electrons, which satisfies the octet rule for nitrogen. So you can add both bonding and non-bonding pairs of electrons, and I would recommend you start out with single bonds, and eventually we'll talk about double bonds and triple bonds. Okay, this is water. 6 plus 2 is 8. You might say, I thought the water molecule has a bend to geometry. We will talk about molecular geometry today, but right now in these Lewis electron dot diagrams, I am not worried at all about making these structures to match the bond angles or to make them look like the molecule in 3 dimensions. So this is a fine Lewis structure for the water molecule, and the octet rule has been satisfied for oxygen. All right, here we have CH2Cl2. Okay, so the dichloromethane. So carbon is 4, each hydrogen is 1, and we have 2 of them. Each chlorine is 7, and we have 2 of them. So a grand total of 20 valence electrons. So we'll go ahead and fill in the connectivity between the atoms, and carbon tends to form 4 bonds normally. So now we still have 20 minus 8. We still have 12 valence electrons we have to put somewhere. Hydrogen does not need lone pairs of electrons. It's already satisfied with a full shell. But we'll go ahead and finish off the molecule with 6 lone pairs of electrons, and now every atom has a complete valence shell. Sometimes you can have to draw the Lewis electron dot diagram for a molecule. Other times it's for a polyatomic ion like ammonium. So while nitrogen has 5 valence electrons, and each hydrogen has 1 valence electron, 5 plus 4 is 9. But remember, the plus charge means that we lost an electron for this total, so it's actually 8 valence electrons. We typically, in Lewis electron dot diagrams, like to show an overall charge by wrapping brackets around the structure and then putting the charge, the overall charge, on the outside. Nothing else to add. 8 valence electrons, full shell. This is the hydroxide ion, which would be in this case 6 for hydrogen, for oxygen, 1 for hydrogen. And then because when you have a negative charge, that means you have gained an electron. We actually have 8 total. I'll go ahead and add my last 3 sets of lone pairs of electrons around the oxygen to complete the octet. All right, I mentioned we can talk about single and double and triple bonds. Let's take a look at that in these examples here. So carbon has 4. We have 2 carbons. That's 8 electrons for the 2 carbons, plus 6 for the hydrogens. That brings a grand total of 14 valence electrons for C2H6. Now for C2H4, we have 2 fewer hydrogens. That would be only 12 valence electrons. And for C2H2, again, taking away 2 hydrogens, now we have only 10 valence electrons. Let's start with a skeleton structure that connects the carbons and hydrogens, and carbon tends to form 4 bonds. Let's put carbon in the middle, and so now we have 2, 4, 6, 8, 10, 12, 14 electrons in bonding pairs. Nothing else to add. That molecule is done. But for C2H4, after I've made the connectivity between the carbons and hydrogens, and I've chosen to give each carbon 2 connections to hydrogens, 2, 4, 6, 8, 10, I still have 1 more pair of electrons, but I'm not able to satisfy the octet for each carbon with only a lone pair of electrons on 1 carbon. It's not going to work. So I have to take that pair of electrons and put it in a place where both carbons can have access to that pair of electrons at the same time, and we make a double bond. In a similar way, we're going to make a multiple bond between the carbons with C2H2. So I now have 6 electrons I've used up so far in drawing these 3 bonds, 8, 10, and now I'm done. I have no more electrons I can add. This carbon only has access to 4 electrons. So I'm going to have to find a way to move the electrons. This would not be satisfactory because each carbon only has access to 6 valence electrons. I'm going to have to put the electrons in a place where both carbons can have access to a full set. So I'm getting closer, but this would be my final answer for that structure. So sometimes you have to make multiple bonds. Now don't go crazy with these multiple bonds. So for example, if you had something like, let's say, carbon tetrafluoride. Okay, so carbon tetrafluoride is carbon with 4 fluorines. Don't start getting crazy with all of your double bonds. Only make double bonds if you absolutely need to do that. So try to satisfy the octet rule first, and then possibly make multiple bonds if you start to run out of electrons. All right, this next molecule we're going to take a look at, this is called phosgene. This is CCl2O. It has a total of 4 for carbon, 7 for chlorine, and we have 2 of them. That's 14, and 6 for oxygen. So a grand total of 24 valence electrons. I'm going to go ahead and just make a skeleton structure. And in the skeleton structure, I'm going to go ahead and put the carbon in the middle, and I'm going to finish off the molecule with lone pairs of electrons. At some point, I'm going to get to 24, and I think I have finally arrived at 24. So I have 24 electrons. However, the carbon does not have a full octet. Now this is a little bit of a dilemma because I could make a double bond between the carbon and the oxygen, or I could make a double bond between the carbon and the chlorine. And for some of y'all that might be thinking, why did I put the carbon in the middle? You might be thinking, maybe I'll put the chlorine in the middle. And you realize that now when you go down that road, every one of those Lewis structures, except for the structure here that doesn't have a full octet, so that one, but every other structure that's on the screen here actually has a full octet for all the atoms. So you might wonder, how do we decide how to draw these Lewis electron dot structures? And could there be more than one possible structure that would be considered correct? Well, there's several answers to that question. Let's address one of the possible answers, and that is sometimes the AP exam helps you out. So they might give you a skeleton structure. Here's an example from 2018. Complete the Lewis electron dot diagram for the HNO2 molecule, include any lone pairs of electrons. Now, all you have to do is finish the skeleton. Or from 2017, in the box below, complete the Lewis electron dot diagram for the S2Cl2 molecule by drawing in all the electron pairs. So they've taken some of the work out for you. Here's another example from 2015, where they have given you a structure on the left, and they ask you to complete the Lewis electron dot diagram for the structure on the right by drawing in all of the electron pairs. But in terms of, is there more than one possible Lewis electron dot structure? And the answer is yes. Sometimes there is. This has to do with a topic called resonance structures. So if there is more than one equivalent Lewis structure, let's talk about that. This is called ozone, O3, which is going to be 3 times 6 for oxygen, so we have 18 valence electrons. I'll start with a simple skeleton. I will then continue to add lone pairs pairs of electrons. So right now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, and that's it. I have no more electrons I can add. So could I make a double bond on the left? Yes. Could I have made a double bond on the right? Yes. In fact, each of these is considered a equivalent resonance structure. Now, I'm going to caution you that you might be confused a little bit by this arrow right here. This is just a convention that we use in chemistry to indicate resonance structures, but this is not an equilibrium. So we are not saying that the ozone molecule rapidly vibrates back and forth between these two structures. Essentially, what it comes down to is this. You have two structures. Which of these resonance structures accurately describes the bonding situation in ozone? Technically, neither one of these structures is correct, but it's the best we can do. So we can't actually do this. Do not do this on the AP chemistry exam. Okay, you have to show a valid Lewis electron dot diagram. Do not show half a bond or something that indicates that you haven't quite completed your Lewis electron dot structure. So the structures at the top of the screen here represent the best we can do with our Lewis structures. Technically, the true structure of the molecule is an average of these two structures. What I'm showing you here is a table that has to do with bond length. Now, the OO bonds, the oxygen-oxygen bonds in ozone, have the exact same length. We do not have a short bond and a long bond. And because they are the same length, in this case 128 picometers, take a look at a single bond and a double bond. You would not be surprised to discover that a double bond is shorter than a single bond. But in fact, the OO bond in ozone is somewhere in between in terms of length, a single and a double. So it is shorter than a single bond, but it is longer than a double bond. So we can describe the bond order of the bonding in ozone as 1.5 bonds as the average of these two structures. But again, on the AP exam, do not draw half a bond. Here's another example of a polyatomic ion as opposed to a molecule that exhibits resonance. Now, if we do the math, for carbon, that would be 4 valence electrons, and then for oxygen, that would be 6. We have 3 of them, so 6 times 3 is 18. Plus, we get to add 2 more electrons for the negative charge on the carbonate ion. That brings our grand total to 24 valence electrons. I'm going to go ahead and draw a skeleton structure, including the overall charge. I'm going to finish all of the lone pairs. And once I get to 24, I have to stop. Well, now, to complete this Lewis electron dot structure so I can have a full octet for the carbon, I have to make a double bond somewhere. I can make a double bond here, or here, or here. So in fact, we have 3 equivalent resonance structures for the carbonate ion. The actual bonding in the carbonate ion is in fact all 3 bonds are the same length. And as you can see here, that bond length in carbonate is somewhere in between a single and a double bond. So based on these 3 resonance structures, we could describe the bond order of carbon, oxygen in carbonate as about 1 1/3 is the average of these 3 structures. Okay, well, I mentioned that we have more than one way to write a Lewis structure, but now I'm going to talk about which one is preferred. And this brings up a concept known as formal charge. So here's how we define formal charge. Start with the number of valence electrons that the atom normally has. You get that off the periodic table. Take a look at the atom specifically in a particular Lewis structure and count the number of non-bonding electrons that are on that particular atom. So you would subtract that number and then count how many bonds are directly attached to that atom. So in the case of a single bond, that would be 1. In the case of a double bond, it would be 2, and a triple is 3. So I'm going to go ahead and highlight the chlorine in this Lewis structure on the left. Chlorine normally has 7 valence electrons. Right now, there are 6 non-bonding electrons on that atom, and there's 1 bond. So chlorine, by this math, has a formal charge of 0. We'll continue analyzing the formal charge of the atoms to make a decision about which structure we think is more preferred. So I'm going to move on to the oxygen now. Oxygen has 6 valence electrons. There are 4 dots or bonding electrons on that oxygen, and there are 2 bonds. Oxygen also has a formal charge of 0. Let's take a look at the carbon. Carbon has 4 valence electrons. There are no dots. There are no non-bonding electrons, but it has 4 bonds. So in that particular molecule on the left, each atom had a formal charge of 0. Let's move on to the molecule on the right, and we'll look at this chlorine. So that's 7 valence electrons, 4 non-bonding, 2 bonds. So that chlorine has a formal charge of +1. Now move on to the oxygen in the same molecule. 6 for oxygen valence electrons, 6 non-bonding electrons plus 1 bond. That would mean a formal charge of -1. So when you analyze these 2 Lewis electron dot structures, now that you know that formal charge can be used to analyze the structure, let me give you some guidelines. First of all, remember that formal charge is a bookkeeping system that will help us analyze Lewis structures. It's useful when comparing 2 different Lewis structures, each of which obeys the octet rule. So if I have a choice between the structure on the left and the structure on the right, if I have to decide which one is more preferred, I'm going to go with the structure on the left, trying to get formal charges of 0 and still obeying the octet rule. That's what I'm focusing on right now. So if I show you this screen, and it's certainly a good time to perhaps pause or take a screenshot, you can then remind yourself of the formal charge and how you would go through each of these molecules and analyze them and decide that yes, the structure in the top left corner would be the best, but all these other structures that you might draw, what makes them less preferred is that they have formal charges other than 0. In general, the higher the magnitude of the formal charge, the less likely it contributes to the overall structure of the molecule. All right, here's some other guidelines. I said it was a bookkeeping system, so it's not a real charge. If you have a molecule in which each atom obeys the octet rule, the most preferred structure is the one in which each atom has a formal charge of 0. Of course, if you have a polyatomic ion, like for example, I had given you hydroxide before, so hydroxide has a formal charge, has an overall charge of -1. So it has a hydrogen, which has a formal charge of 0, because that would be 1 - 1, and the oxygen has a formal charge of -1, that would be 6 - 7. So if you have a polyatomic ion, the sum of all the formal charges in the Lewis structure will equal the overall charge on the ion itself. Now, sometimes it's not possible for each atom to have a formal charge of 0. If you have to choose between 2 different structures, and one of them, let's say, has a negative charge on a particular atom, and then the other structure has a negative charge on a different atom, you should go with trying to put the negative formal charge, if there is one, on the atom with the highest electronegativity value. Now, I mentioned this because this will definitely come up in your homework problem. So remember the advice about putting the negative formal charge on the atom with the higher electronegativity value. That will show up later in your homework. All right, next thing I want to talk about is exceptions to the octet rule. Here we have boron, which has 3 valence electrons, and of course each fluorine having 7. 3 times 7 is 21, so we have a grand total of 24 valence electrons. If I draw a skeleton structure for boron and I fill in all of the lone pairs of electrons around the fluorine, I now get to 24. You might be thinking, like you saw with the example of carbonate, we should go ahead and make a double bond between the boron and one of the fluorines, and that there are 3 possible resonance structures. Well, let me go ahead and bring up formal charge one more time. Focus on this fluorine for just a moment. We have 7 valence electrons for fluorine. There are currently 4 dots, so 4 non-bonding electrons and 2 bonds. That will give you the following formal charge. So think about that. Let's go ahead and do boron. So we have a +1 on the fluorine. Boron would be 3 valence electrons. It currently has no dots around it, so no non-bonding electrons, and 4 bonds, so -1. As you consider electronegativity, fluorine is the most electronegative atom on the entire periodic table. So does this structure, in your opinion, if fluorine is electronegative and pulls electron density toward itself, does this structure represent a probable or a likely Lewis structure? And the answer is no. So the dominant Lewis structure is actually the one that does not obey the octet rule, because these structures, because of their unfavorable formal charges, are less important and do not contribute significantly to the bonding picture. So it's okay for this particular example, boron, for it to be less than an octet. You might be thinking, what about more than an octet? Absolutely. So here we have phosphorus pentafluoride and sulfur hexafluoride. So for phosphorus, that would be 5. For fluorine, that would be 7, but we have 5 of them. So 5 times 7 is 35, plus 5 is 40. Sulfur, we have 6 for sulfur, and we have 6 times 7 for fluorine. That would be 42 plus 6 or 48. So how would you draw the Lewis electron dot structure for an atom where it actually has more than an octet? Well, as we talk more about valence shell electron pair repulsion theory, we'll definitely see examples of molecules like these, but be aware that there are some atoms that are what are called hypervalent. So on the periodic table, focusing on phosphorus, sulfur, chlorine, those are in period 3, and elements in periods 3, 4, and 5 can be a central atom in a molecule that is hypervalent. So because the central atom has a larger size, it can accommodate extra electron pairs. So look above phosphorus. Okay, we have nitrogen. So does nitrogen pentafluoride exist? Or above sulfur we have oxygen. Does oxygen hexafluoride exist? And the answer is no. And the the reason why is because those atoms are too small to accommodate the extra electron pairs. So now that you know that some atoms can break the octet rule, I want to talk about how this plays a role in your decisions with respect to drawing Lewis electron dot structures. Okay, so we have an example of a polyatomic ion here. Sulfur is 6 and oxygen is 6. We have 6 plus 24, that would be 30, but we also get to add 2 more electrons to the negative charge, so this would be 32. I'll go ahead and set up a skeleton structure and fill in the dots and stop when I get to 32. If you do formal charge for all of these oxygens, it would be 6 minus 7, so negative 1. And if you do formal charge for sulfur, it would be 6 minus 4, so positive 2. Well, we just were told that elements in periods 3, 4, and 5 can expand their octet, so sulfur could expand the octet. So now we have 6 bonds to sulfur, formal charge of 0. So for these alternate structures, it might seem that now you're on a new mission to draw structures with all kinds of expanded octets, and your goal is to now minimize formal charge wherever possible. Let me give you some helpful advice on this. If you can draw a Lewis electron dot structure in which each atom obeys the octet rule, then do that. The AP exam will never ask students to decide on their own when drawing a Lewis structure whether they should obey the octet rule or expand the octet in order to get better formal charges. So now sometimes you have to expand the octet because obviously 5 fluorine atoms have to fit somewhere around the central atom. But take a look at sulfur dioxide for a moment as an example. So sulfur dioxide is SO2. That's going to be 18 valence electrons to work with. You might draw a structure like this. That's a perfectly valid Lewis electron dot structure. 18 electrons, every atom has a full octet. You might recognize that because you could have drawn the double bond on the other side, these are 2 equivalent Lewis electron dot structures. These are resonance structures, and it turns out that the bond in sulfur dioxide is actually the same. You might also think formal charge. What about this sulfur in the middle? This would be 6 minus 5, that's positive 1. This would be 6 minus 7, negative 1. So maybe I should draw a structure like this. So my advice to you is don't worry on the AP exam about always trying to get better formal charges. If you can draw a Lewis structure in which each atom obeys the octet rule, then do that. Unless the question specifically asks you to minimize formal charges, then that's an option. But do not feel like you have to decide between should I obey the octet rule or not. Octet rule always works. Here's another example. This is called chlorate, ClO3-. There are a total of 26 valence electrons in the chlorate ion. The structure on the top is perfectly fine. Yes, you could do a better job of minimizing formal charges by drawing multiple bonds to chlorine, but the AP exam is not going to expect you to prefer the structure on the bottom as opposed to the structure on the top. Either one of those is fine. Unless you're given more specific information, these are both valid, but don't start thinking you have to minimize formal charges everywhere you see it. Okay, I'm now going to switch and talk about VSEPR, valence shell electron pair repulsion theory. And what this means is that you have the valence shell, which is going to be the outer electrons. You have electrons in groups of 2, so they're in pairs, and then you have repulsion. They tend to repel each other in such a way so as to be as far apart from each other in three-dimensional space as possible. If I have 2, 3, 4, 5, and 6 electron domains, then they can spread out from each other to minimize their repulsion. And you have the following shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. These are all different geometries of molecules. So for example, these molecules might be linear or trigonal planar or tetrahedral. I've given you some examples of molecules that have this geometry. So we have 2, 3, and 4 electron domains. Notice that I don't count a double bond or triple bond twice. This is still considered 2 electron domains. This is considered 3 electron domains. And again, I showed you these molecules before. So the phosphorus pentafluoride and the sulfur hexafluoride have the following geometries. Now in all these examples so far, there have not been any lone pairs of electrons on the central atom. If there are, then that's going to affect your shape. So for example, this particular lone pair, the non-bonding domain on the central atom, means that the shape of the molecule is no longer linear but bent. This pair of electrons on the central atom means that we change the shape from trigonal planar to trigonal pyramidal. And here in the water molecule, these 2 non-bonding pairs of electrons in the central atom make that a bent molecule. With respect to 5 and 6 electron domains, you can have all kinds of shapes. So here we have what's called seesaw, here we have what's called T-shaped, and here we have linear. Even though we have 3 lone pairs of electrons on the central atom, the reason why this is not bent is because they all orient themselves in these positions and they separate from each other to be as far apart as possible, and then the molecule itself adopts this linear shape. So I'd like to show you some examples of these molecular shapes, and I'm going to take you now to a website. And this particular website, you can just find this on your own. You don't have to use this exact website. This is a bit.ly/phet-molecular shapes. You could just do an internet search on your own for PHET. There's lots of great simulations there, and I want to talk about how you can manipulate these molecules a little bit. So I'm going to go ahead and do a switch here. I am going to switch to this particular website, and as you can see, I've got 2 electron domains, and that would be linear. And I'm going to go ahead and show the bond angle. That's 180. So this would be 3 electron domains, and the bond angle is 120. This is called trigonal planar. I now have 4 electron domains. This would be tetrahedral, 109.5. I can also go from trigonal planar to pyramidal. So now I have changed from a trigonal planar where the molecule is flat. Now this is going to be no longer coplanar. The atoms are different. This is important to understand about molecular shape. So this is a different molecule. And you can also have something like the water molecule where you have 2 lone pairs of electrons. You can realize that no matter you draw this molecule, it cannot be a straight line. So again, a great website to kind of practice with some things here. I'm now going to go back to my PowerPoint. You can play around with that particular website. Okay, so I am going to talk a little bit more about bond angles now. I mentioned 180 for a straight line, 120 for a trigonal planar arrangement, and 109.5. Those are the most important bond angles you should know. There's also 90 and 120 depending on the arrangement of the atoms in trigonal bipyramidal, and with octahedral everything is 90. All right, what about the presence of the lone pair? Well, this lone pair right here is going to cause a little bit of extra repulsion on the neighboring bonding pairs. So that bond angle is going to be a little bit less than 120. Similarly, for molecules like NH3 and for H2O, the bond angle is probably closer to around 107 degrees for NH3 and around 105 degrees for H2O because these non-bonding pairs of electrons tend to exert slightly greater repulsion on the bonding pairs. So again, knowing 109.5, 120, 180, that's great. I would caution you though, if the question asks, what is the bond angle? The answer is a number. Do not say that. If they say the bond angle, the answer is not tetrahedral. If they say what is the bond angle, and you give an answer of trigonal planar, that is not a correct answer to this question. So make sure you pay attention to what the question is asked. If they say what is the molecular geometry, do not say 109.5. So if the question says what's the molecular geometry, tetrahedral might be your answer. If they say what is the bond angle, 109.5 might be your answer. Now I want to talk about something called hybridization. Hybridization has to do with a mixing or a blending of the atomic orbitals. You already know that carbon has 4 valence electrons, and they are located right here in the second energy level. Carbon has 6 electrons altogether, but there are 4 in the valence shell. So right now, would you say that these 4 electrons, in your opinion, are equivalent? Do they all have the same energy? And the answer is no, they don't. In fact, that's what hybridization is all about. Hybridization can be thought of as a process in which these 4 orbitals, s and then 3p orbitals, are combined in such a way to make 4 equivalent hybrid atomic orbitals for bonding purposes. So we have 4 electrons in 4 identical orbitals, but because they were created by a process in which the 4 orbitals were combined, we have s and then we have p, p, and p. The name of this orbital, we're not going to call it it's going to be a name that sounds like it makes sense. So we're going to call this sp3. So why is it called sp3? Because 1s and 3p orbitals were used to make this particular hybridization for the bonding. So when you have 4 electron domains, you have sp3 hybridization. So we do count both the bonding and the non-bonding domains in this particular process. So 4 single bonds, sp3. 3 singles and a lone pair, sp3. 2 singles and 2 lone pairs, sp3. Now in a similar way, if you have only 3 electron domains, you have what is called sp2 hybridization. So we do not count this double bond twice. That would be 1, 2, 3 electron domains, sp2. 1, 2, 3 electron domains, sp2. So sp2 hybridization, 3 electron domains. If you have only 2 electron domains, then the term we use is sp. sp. So we do not count that triple bond or that double bond twice. That would simply be 2 electron domains coming off the central atom, sp hybridization. And now the last thing I want to mention, then we'll get to the homework, is sigma and pi bonding. So here I have a hydrogen atom and I have another hydrogen atom. I bring them together and now there is overlap to form a bond. So this region of space where the electron density is concentrated in between the two atoms is known as a sigma bond. In fact, when you draw a Lewis electron dot structure, you can consider any single bond to be a sigma bond. So here we have C2H6 and there are a total of 7 sigma bonds, and that would be sp3 hybridization for those carbon atoms. Well, what do we do in situations about double and triple bonds? Would we call this right here? Do we call that 2 sigma bonds? Well, in fact, no, there's something special for that. So let's go ahead and talk about that. We're going to talk about what happens when you have overlap in a different way. This is called a pi bond. So a pi bond is when we have electron density not necessarily in between the nuclei along the internuclear axis, but in fact above and below. Here I have 2 carbons and they are sp2 hybridized. Now what happens to the other p orbital we'll talk about in just a second. So I bring them together and that is a sigma bond. As I mentioned, what about the p orbital that was not used in the hybridization process? Because there are 3 p orbitals, but only 2 of them were used in the hybridization process. Well, the p orbitals are still there, and it is the overlap of these p orbitals in a region above and below the internuclear axis. That is what we call a pi bond. The overlap of the p orbitals on adjacent carbons. So this would be an example of 1 sigma and 1 pi bond. So a double bond represents 1 sigma bond and 1 pi bond, and a triple bond represents 1 sigma bond and 2 pi bonds. All right, let me get to my debrief and summary, and then our homework for today. All right, we talked about Lewis electron dot diagrams, resonance, formal charge, valence shell, electron pair repulsion theory, and bond hybridization, and finally sigma and pi bonds. So here's your AP exam practice question. Because I'm a little short on time, I'm not going to read these questions out to you. I'm simply going to pause. There are a total of 3 screens. This is the first one, and this is the next screen, and this is the third screen. Now tomorrow I will explain the answers to these questions, but these are your homework. I will remind you about the helpful chemistry resources in the video description. I want to say thank you. Again, this has been Michael Faribault from Albemarle High School in Charlottesville, Virginia, and I want to remind you that you can go to cb.org/tech to let the College Board know if you have any specific needs for mobile tools or connectivity for taking the AP exam. Thanks for watching. Hello everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia, and we are going to talk today about Unit 3 in AP Chemistry, Intermolecular Forces and Properties. Just want to remind you that you can always go to apcentral.collegeboard.org to get more information about the support that the College Board is providing for schools that may be closed, as well as information about the AP exams. Make sure that you have access to scratch paper and a periodic table. Remember, at any time during the lesson if you need to pause, feel free to do that, and let's go ahead and get started. Today in our lesson on Unit 3, we'll talk about intermolecular forces and properties of liquids and solids, and then I'll give you a brief comment about particle diagrams for solids, liquids, and gases. So the majority of our lesson will focus on intermolecular forces and how that affects the properties of liquids and solids. As far as the science practices, you can see here, explain the degree to which a model or representation describes the connection between particulate level properties and macroscopic properties. So again, this connection between the particulate level and macroscopic, so how the actual substance behaves, will be our focus. We'll talk about the polarity of molecules today. So in earlier lessons, we talked about the polarity of bonds and the geometry of molecules. So we'll put those two concepts together. We'll definitely talk about the attractive forces in between molecules and particles and the properties of liquids and solids. For our warm-up problem today, the AP practice question from yesterday's lesson looks like this. We have a molecule, S2Cl2, that's 2 sulfurs and 2 chlorines, and in part 1 of this question, we have to complete the Lewis electron dot diagram for the molecule. So they've given us a skeleton, and we have to fill in all of the bonding pairs, which I will use as dashes, and non-bonding pairs, which I will use as dots. As far as how many valence electrons we have to work with, each sulfur has 6 valence electrons, each chlorine has 7 valence electrons. So we have 2 of sulfur and 2 of chlorine, that would be 12 plus 14, so a total of 26 valence electrons. Let's start by connecting the atoms together. Each dash is worth 2 electrons, so 2, 4, 6. Now let's put the lone pairs of electrons around the atoms and see if we can get to 26. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So unlike some of the molecules that I showed you in yesterday's lesson, which had to have double or triple bonds, we were able to satisfy all of the valence shells for each atoms with a complete octet, and we did not have to make any double bonds. The next part of the question asks, what is the approximate value of the chlorine sulfur bond angle? Now, just because a molecule is drawn in a straight line does not necessarily mean that's the actual shape of the molecule. So some students, when they answered this question on the AP exam, they thought that the bond angle should be 180 degrees. Why? Because that's the way the molecule was drawn on the paper. Now, we know that if I have, in this case, a sulfur, and there is a chlorine on the one side, and there is a sulfur on the other side, and there are these lone pairs of electrons as well. This represents what is called sp3 hybridization, and there are 4 electron domains. So when you have sp3 hybridization and 4 electron domains, the bond angle should be 109.5. Now, it might be a little bit less than 109.5 because of the compression of the bond angles with those lone pairs, but the AP exam scoring guidelines accepted any value between 104 and 110 degrees. 180 degrees was not accepted in this case. All right, moving on to our next question. We have 2 Lewis electron dot structures for something called fulminate acid, hydrogen, carbon, nitrogen, and oxygen. They have already given us that the diagram on the left is the better representation. Justify your answer based on formal charges. Now, some students did not focus on formal charge. They would say things like the following. Well, carbon normally forms 4 bonds, and so therefore they thought the structure on the left would be better because it has 4 bonds to carbon. You have to talk about formal charge because that's what the question is asking. So in this case, let's go ahead and assign formal charges to each atom in each structure. Well, the hydrogen has only 1 valence electron and has only 1 bond, so formal charge of 0. The carbon has 4 valence electrons and has 4 bonds. Formal charge of 0 as well. The nitrogen has 5 valence electrons. No non-bonding electrons, so there's no dots on the nitrogen, and has 4 bonds. Formal charge +1. And then finally, the oxygen, 6 valence electrons. There are 6 dots, so 6 non-bonding electrons and 1 bond. Formal charge of -1. Okay, let's move on to the other structure. Well, hydrogen will be 0 again. Let's focus on the carbon. That's going to be 4 valence electrons. I see 2 dots, so 2 non-bonding electrons and 3 bonds. Formal charge -1. Nitrogen happens to be 5 minus 4, so we have a +1 like we had before. And then finally, this double bonded oxygen is going to be 6, 4 non-bonding electrons and 2 bonds, so that formal charge is 0. Now, we're not done yet, but we at least have satisfied the AP exam request to talk about formal charges. I'm now going to scratch out this information because it's the same in both structures. So nitrogen is +1 in both structures. Let's focus on the differences. So we have a carbon that has a formal charge of 0. We have oxygen with a formal charge of -1. In the other structure, we have a carbon with a formal charge of -1 and an oxygen with a formal charge of 0. Now, we are not asked to make a prediction about which structure is better. They already said that the diagram on the left is better, and I gave you a big hint in yesterday's lesson. So what I said in terms of the guidelines for formal charge is that if it's not possible for each atom to have a formal charge of 0, the more favorable structure is one in which the negative formal charge, if there is one, is on the atom with the highest electronegativity value. So it's about the electronegativity of carbon versus oxygen. So as you look on the periodic table, you know that oxygen is further to the right on the periodic table. That makes oxygen more electronegative than carbon, so it is more favorable to put a negative charge on oxygen. Here are the official scoring guidelines for that question. So students earn 1 point for a correct assignment of formal charges in the diagrams, and they earn 1 point for the explanation talking about a negative formal charge on oxygen, which is more electronegative than carbon. So make sure that you read the question carefully carefully and answer what is being asked. Our next practice question from yesterday's class had to do with another Lewis structure. I'm going to go ahead and count the Lewis electrons for this, the valence electrons for this Lewis diagram. So hydrogen is 1, oxygen is 6, and we have 2 of them, and nitrogen is 5. So grand total would be 1 plus 12 plus 5, that's 18 valence electrons. Let's start connecting 2, 4, 6, and now we'll add lone pairs and see where we stop at 18, 8, 10, 12, 14, 16, 18. So I ran out of electrons, and now I'm going to have to make a double bond. So I'll just go ahead and make a double bond here. This is one possible Lewis structure. Let me go ahead and assign formal charges, not because I have to, just because I feel like doing it. So I've got 6 minus 5, that would be a positive 1 for this particular oxygen right there, and I have 6 minus 7, so a negative 1. Now this question said nothing about formal charges. I was just curious to see what those formal charges were. You might have drawn the structure with the double bond in the other position, and if you had assigned formal charges to this one, you would realize this would be formal charges of 0 for those two oxygens. Does it matter which structure you draw? No. Either one of these structures would be acceptable because the specific instructions did not mention anything about formal charges. A valid Lewis structure is on the screen. You've got 2 valid Lewis structures in this case. Now, as far as the hybridization of the nitrogen, we're focusing on this nitrogen or this nitrogen. You get the same answer either way. So we have a nitrogen with a double bond, and then we have a single bond, and we have a lone pair of electrons. If we count the electron domains, and we don't count this double bond twice, we have a total of 3 electron domains, and that corresponds to sp2 hybridization. All right, let's get into our lesson for today. We're talking about unit 3, which is intermolecular forces. And the first thing I want to mention is the polarity of molecules. It's very important that you understand VSEPR, so valence shell electron pair repulsion theory and molecular geometry. So we have 2 molecules, carbon dioxide and water. And I'm showing you what are called bond dipoles. There's a little cross in the arrow indicating the positive end of the dipole, and the arrow is pointing toward the negative end. Now, how do I know which end to draw this dipole? It always tends to point toward the more electronegative atom. So I have a separation of charge. So a carbon-oxygen bond is a polar bond. Just because you have a polar bond does not necessarily mean you have a polar molecule. In this case, we have a non-polar molecule for the carbon dioxide because the dipoles cancel out. With water, you might see a similar kind of plane of symmetry in the molecule. Therefore, you might think that somehow there is a balance between the left half and the right half of the molecule. But no, in fact, when you add those dipoles together, they do not cancel each other out. So water is polar. Now be very careful. Do not say, if someone asks you on the AP exam, well, why is water polar? The answer is, as on the screen, because all of the bond dipoles within a molecule do not cancel out. It is not acceptable to say that the reason why water is polar is because it is bent. Just saying that it's bent indicates the molecular geometry, but does not explain what is going on with the bond dipoles. Any more than you could say, for example, that the non-polar molecule, carbon dioxide, well, why is it non-polar? Because it is linear. Is not a satisfactory answer either. So to kind of emphasize that particular point, take a look at this molecule. This is hydrogen cyanide. It is a linear molecule, and as you can see, it's not symmetrical. We have hydrogen on one side, and carbon is more electronegative than hydrogen, and then we have nitrogen. These are different dipoles. They're actually not even in opposite directions. So my point here to emphasize is that the answer for why something is polar or non-polar has to do with, are the bond dipoles going to cancel out or not? If they do cancel out, the molecule overall is non-polar. If the bond dipoles do not cancel out, then it is a polar molecule. So again, because it's bent or because it's linear is not a sufficient explanation. Now, speaking of other molecules, besides linear, we have trigonal planar, tetrahedral, square planar, trigonal bipyramidal, and octahedral. I'm going to give you examples of each of these shapes. So there's carbon dioxide, here's some boron trifluoride, methane CH4, xenon tetrafluoride, phosphorus pentafluoride, and sulfur hexafluoride. Since the terminal atoms are the same and the dipoles are arranged symmetrically around the central atom, the bond dipoles within each of these molecules are oriented in such a way that they cancel out. So each of these 6 molecules that I've shown you is classified as non-polar. Again, because of symmetry would not be a sufficient answer. Because the bond dipoles are oriented in such a way that they cancel out is a more complete explanation of why these molecules are non-polar. Now, let's focus on linear, trigonal planar, and tetrahedral. Some students will tend to extrapolate what I just said on the previous slide and say anytime a molecule is linear, trigonal planar, or tetrahedral, it should be non-polar. But watch what I'm doing on these shapes. Notice how I changed the color of one of those atoms. HCN is no longer a symmetrical molecule, and the dipoles do not cancel out. For trigonal planar, I've picked a molecule. This is phosgene, has a carbon, 2 chlorines, and an oxygen. No longer symmetrical like the boron trifluoride was on the previous slide. Tetrahedral, you have to have all 4 atoms the same in order for it to be non-polar. So because I have 1 chlorine or 2 chlorines or 3 chlorines, that messes up the symmetry. So all of the following molecules that I'm showing you on this slide, the bond dipoles do not cancel out, so these are polar. Do you have to consider the shape? Yes, absolutely. Do you have to consider the actual atoms and the bond dipoles? Yes. So consider both geometry and the individual atoms involved in that molecule. Another potential misconception has to do with what I talked about yesterday. A Lewis structure does not necessarily indicate the molecular geometry. So a student will draw a molecule. I'm now going to draw a dipole from hydrogen to oxygen, and they might conclude that this is a non-polar molecule because the dipoles cancel out. Now we know that that molecule is actually bent. So therefore, a Lewis structure can give you a false sense of the actual structure of the molecule. In a similar way, I might draw dipoles and think that this NH3 molecule is non-polar. But is this trigonal planar? What does the presence of that lone pair actually do to the molecular geometry? It makes it trigonal pyramidal. This molecule is polar. So please, when you draw your Lewis structures, remember that even though you don't necessarily have to make them aesthetically pleasing with all the proper bond angles to get credit for a Lewis structure, if you're going from Lewis structure to polarity, your molecule should be envisioned in 3-dimensional space. Another misconception has to do with the tetrahedral geometry. These bond angles are not 90 degrees. It's part of the tetrahedron. So is this molecule polar? Absolutely. The corners of the tetrahedron occupy 4 spots. If we have 4 atoms that are not the same, it's going to be polar, whether it's 2 and 2 or 3 and 1. So pay attention to what these molecules actually look like. Each of these molecules is polar, and you have to consider molecular geometry. Now I will say, as we finish this conversation and move on to intermolecular forces, one last thing about shapes. All of the molecules here would be considered polar because the bond dipoles do not cancel out. So geometry that's bent, trigonal pyramidal, seesaw, T-shaped, and square pyramidal, it doesn't matter what those atoms are. The asymmetry of that shape, that geometry, makes it polar. But again, because it's trigonal pyramidal is not a sufficient explanation, try to get in the habit of saying that the bond dipoles either do or do not cancel out. You can mention the geometry, and that's a great thing to do, but go on to talk about how the dipoles interact with each other. Okay, so I want to talk about intermolecular or interparticle forces. I have a sample of water molecules here. We're going to go ahead and add some heat to these molecules. I'm going to try to boil the water. Take a look at the next particle diagram and tell me if you think this is what's happening when water boils. Hopefully you realize that that is not what's happening to water molecules, but some people think that that is what's going on because they think about you're breaking up the molecules. Now, to say that you're breaking up the molecules can be confusing. You are breaking the molecules apart from each other, but boiling water does not separate water into hydrogen atoms and oxygen atoms. Boiling water is a phase change that does not break covalent bonds. Now, you are breaking the water molecules apart, but they are still water molecules. Let's talk about when a covalent or molecular substance is heated and undergoes a phase change from a liquid to a gas. What type of attractive forces are broken? This is a very common misconception that we see year after year in AP chemistry. So I want to pay special attention to this distinction between intermolecular forces and intramolecular forces. Intermolecular forces are generally weak and exist in between molecules or particles. Intramolecular forces would be the forces of attraction that exist within a molecule, and they are much stronger. In intermolecular forces, the particles are relatively far apart. With intra, the particles are relatively close together. So for example, if I just draw a simple diatomic molecule and then I draw another one, I could talk about the attractive force between these molecules. So when I say far apart, that's what I mean. But if I'm talking about the attractive force within the molecule, the covalent bond that holds the atom together, that is much stronger than an intermolecular force. So here I have some water molecules. Intramolecular forces are these, the attractive forces that exist within the water water molecule itself. On the other hand, intermolecular forces are the attractive forces that exist between the molecules. So make sure that you have a clear understanding of the difference between these things. Okay, let's talk about how we can tell the relative strength of the interparticle or intermolecular forces based on some data. You're looking at a data table with boiling point of 87 and 165. We don't know what these substances are. They're just labeled as 1 and 2. Let me give you a little more information. Substances 1 and 2 are two different elements located in group 18 on the periodic table, so the noble gases. Which substance, 1 or 2, has the stronger attractive forces between the particles, and how can you tell? Well, you don't have any information about the identity of the elements. We can't talk about polarity, electronegativity, Lewis electron dot structures. All we have are boiling points. So it should make sense to you that if you have to change a substance from a liquid to a gas, energy is required to convert a liquid into a gas. The stronger the attractive forces between particles, the more energy is required to overcome these forces as a substance changes from a liquid to a gas. So I would argue that substance 2 has stronger attractive forces, even if I have no idea of the identity of substance 2. I'm going to go with the higher boiling point would be stronger attractive forces. I'm going to go ahead and tell you that substance 1 was argon and substance 2 is xenon. Now these are noble gases. They are not molecules. They're individual atoms. They're just individual atoms, so of course they are non-polar. But since you can have liquid versions of these elements, there must be some attractive force between the particles that would cause a gas to condense into a liquid. So how can we describe the attractive forces between atoms in a sample of a noble gas? Well, let's start with a particle diagram. Here I have an atom with a nucleus and an electron cloud. Now this is electrons indicated by these little negative charges. So as the electrons are moving around, they are in this electron cloud. At some point, if I could take a snapshot of these electrons for just a moment, for just an instant, the electrons might not be distributed evenly. Okay, well let's say that happens. Can you see in this diagram that there is a greater concentration of electrons on the right side as on the left side? That creates an instantaneous dipole, not a permanent dipole, but an instantaneous dipole. So in this instant, the electrons are not distributed evenly, and so we have a separation of charge. Well, what if this particular atom happens to be near another atom? Now the dipole in one particle can induce a separation of charge in a neighboring particle. So this instantaneous dipole in one atom can cause a neighboring atom to have an uneven distribution in its electron cloud. This is what we call London dispersion forces. So I'm going to explain a little bit more about London dispersion forces. We start with a gas, and now we're going to go ahead and take this gas and lower its temperature. In the gas phase, these particles do not experience any attractive forces. But what happens if the temperature of the sample is decreased? So as it slows down, particles start moving closer together. Eventually, the particles begin to experience attractive forces. Now with London dispersion forces, it's the interaction between particles or molecules as a result of these temporary or instantaneous dipoles. It's because of the distortion of the electron cloud. Now the electrons, are in continuous motion. So we have what is called polarizability. Polarizability is the ease with which the charge distribution in an electron cloud can be distorted. You can talk about this as an adjective as well. You can say that one molecule might be more polarizable than the other. How can you compare argon and xenon? Well, we have 18 electrons for argon and 54 electrons for xenon. So which, in your opinion, electron cloud is more likely to be distorted? Which electron cloud has greater polarizability? Now remember, we already have the boiling point data in front of us. So if xenon has stronger attractive forces, you cannot say because xenon is more polar or is more electronegative or simply that it's just larger or heavier. It's specifically about the electron cloud. That's what London dispersion forces are all about. So a larger electron cloud has greater polarizability and can be more easily distorted. The larger the electron cloud, the stronger the London dispersion forces are. Now I'm giving you more data. So here are 4 noble gases: neon, argon, krypton, and xenon. Take a look at that boiling point trend. Similarly, I have nonpolar substances such as fluorine, chlorine, bromine, and iodine. And I have methane, CH4, followed by silane and germane and cyanane. These are all nonpolar tetrahedral molecules that have a central atom: carbon, silicon, germanium, tin. Notice that the electron clouds are increasing. So the larger the electron cloud is, the more polarizable it is. A larger electron cloud experiences stronger London dispersion forces. I will say that all molecules have and can experience London dispersion forces. While they are generally a weak force, since all molecules experience them, you can mention on any AP exam when they ask you describe the intermolecular forces, London dispersion forces should be your answer, and possibly other things as well. Now be very clear. While these atoms, in fact, xenon is heavier than neon, iodine as a molecule is heavier than fluorine, and tin tetrahydride is heavier than methane. Do not say as your explanation that a molecule has stronger LDS because it is heavier or because it has a larger mass. Talk about the larger electron cloud, and you can say words like polarizable or greater polarizability. All right, I now have a discussion of 2 molecules side by side, and we have 3 sets of them. So we have nitrogen versus carbon monoxide. Now I'm going to go and put the boiling points up here. We have propane, C3H6 versus acetonitrile, C2H3N, and then we have isobutane versus propanone or acetone. Now take a look at these molecules. They are roughly the same size in terms of electron cloud. Hopefully you can realize that the molecule on the left compared to the molecule on the right has a difference, and that difference is not just the boiling point, it is polarity. So the molecule on the right is polar, whereas the molecule on the left is nonpolar. Now the isobutane is not perfectly symmetrical, but it is a hydrocarbon, so it is generally a nonpolar substance, the C4H10. All right, if that's the case, if the electron clouds are about the same size and you're talking about one polar and one nonpolar, the polar molecule, as you can see here with the higher boiling point data in front of you, tends to have stronger intermolecular forces. So what exactly are the attractions between polar molecules? Well, the attraction between polar molecules are called dipole-dipole forces. It's whenever the partial positive end of one molecule is attracted to the partial negative end of a nearby molecule. Let me show you an example. Here we have HCl molecules in the gas phase, and I've shaded one end of the HCl molecule to indicate a higher electronegativity. So there's a partial negative charge on the chlorine and a partial positive charge on the hydrogen. If HCl molecules in the gas phase are cooled, they will eventually, if they're cooled low enough, condense to a liquid, and they will start to experience what we call dipole-dipole forces. Okay, I'm going to go back and talk about something that I mentioned, and I want to highlight it even more than I already did before, and that is this part right here. I was making a specific choice by the comparisons I gave you on this slide. Electron clouds were approximately the same size. So we come to a very important student misconception. If you are given 2 different chemical formulas, and one molecule is polar and the other molecule is nonpolar, some students think that the polar molecule will always have stronger intermolecular forces, and that is not necessarily true. So is it possible that a nonpolar molecule that only experiences what are called LDS for short, London dispersion forces, will actually have a higher boiling point than a polar molecule that experiences both LDS and dipole-dipole forces? And the answer is yes. And does the AP exam occasionally ask questions like that? Absolutely. So in this example, CCl4 is carbon tetrachloride, tetrahedral, symmetrical, dipoles cancel out, nonpolar. HCl, simple, diatomic, 2 atoms and they're different, polar. Of course, CCl4 can only experience London dispersion forces because it's a nonpolar molecule, but HCl would experience both London dispersion forces and dipole-dipole forces. Now we come to the most important part, and that's the data. It turns out that at room temperature, which is about 25 degrees Celsius or 298 Kelvin, carbon tetrachloride is a liquid, whereas hydrogen chloride, I'm not talking about hydrochloric acid, I'm talking about the pure molecules of hydrogen chloride, it's a gas. So what temperature does CCl4 boil at? About 77 Celsius or 350 Kelvin. At what temperature does HCl become a liquid? Well, you have to cool it down to around minus 85 degrees Celsius. But here's the misconception. Students only focus on this, and they somehow think that HCl must have stronger attractive forces because it is polar. Let me show you the electron clouds. Here's a space-filling model of carbon tetrachloride, and here's a space-filling model of HCl. The CCl4 obviously has stronger forces. We can see that because of the boiling point data. So those London forces must be significant because of the large electron cloud. If you are given data in an AP question, you must consider the data. So here's an example, an exact question from the 2017 AP Chemistry Free Response exam portion of the exam. This is number 1 part D, and it says that there was a mixture of of CCl4 and HCl, and it was cooled to 70 degrees, at which temperature the CCl4 condenses while the HCl remains in the gaseous state. Well, let's identify all of the IMFs and HCl. You should mention LDFs, so London dispersion forces and dipole-dipole forces, because it's polar molecule. What can be inferred about the relative strength of the intermolecular forces? So many students ignored the data and said HCl had stronger forces. But clearly, if at this temperature CCl4 condenses into a liquid while HCl remains a gas, it is the carbon tetrachloride that has stronger intermolecular forces than the hydrogen chloride. So you have to go with the data. I will go ahead and put up the official scoring guidelines for this question. So 1 point for identifying all of the intermolecular forces in HCl, and 1 point for a valid justification in terms of stronger intermolecular forces because the CCl4 condenses at a higher temperature than HCl. All right, I'm now going to talk about another type of attractive force. We talked about London dispersion forces and dipole-dipole forces. All right, on this data table, we have boiling point on the y-axis and molar mass on the x-axis. I don't let molar mass become a justification. It's simply just a property of these substances. There are 4 dots on the graph, and these 4 dots correspond to the boiling points of CH4, SiH4, Ge, germanium H4, and then Sn, tin H4. So are we talking about dipole-dipole forces here? No, these are all non-polar molecules, larger electron cloud, stronger LDFs. All right, well now we come to NH3, PH3, arsenic, and antimony with H3. I'm going to start with the antimony, SbH3. Arsenic has a smaller electron cloud, lower boiling point. Phosphorus has a smaller electron cloud, lower boiling point. Now nitrogen has an even smaller electron cloud, therefore you would predict, based on this trend, that the boiling point of NH3 would be around maybe 150 Kelvin. But in fact, it's much higher. So we'll talk about that in just a moment. Here we have H2O, H2S, H2Se, selenium, and H2Te, tellurium. Let me start with the tellurium hydride. Now selenium has a smaller electron cloud, so weaker London dispersion forces. Sulfur has a smaller electron cloud. You would predict if we kept going in this trend that since oxygen has an even smaller electron cloud, that the boiling point of water might be around 200 Kelvin. In fact, it is also much higher. So we'll talk about that in just a second. And here we have HF, HCl, HBr, and HI. Let me start with the HI. Bromine has a smaller electron cloud. Chlorine has a smaller electron cloud. And then finally, you would predict that fluorine might also follow that trend and have a boiling point of around maybe 175 Kelvin. But all 3 of these molecules, H2O, HF, and H3, have higher boiling points than one might predict based on the trend in simply London dispersion forces. So what do these 3 atoms have that's special? Well, what they have that's special is they have a rather small size and they have a rather high electronegativity value. So based on that information, we have a special kind of attraction that has a different name. This is called hydrogen bonding attraction. It is a strong dipole-dipole interaction which occurs between a small hydrogen atom that is bonded to either N, O, or F on one molecule, and then that attraction between another molecule. So it is to the nitrogen, oxygen, or fluorine on another molecule. Now, if we have protein, which is a huge biomolecule, or if we have a sample of DNA, it is possible to have hydrogen bonding within a large biomolecule, like different strands of DNA or different sections of a protein between the amino acids. So you can have hydrogen bonding within a rather large molecule. But with small molecules like the ones on the screen, I'm showing a connection from the nitrogen of one molecule to the hydrogen on the other, and then the same with oxygen and fluorine. Now, watch out for the fact that I have CH3OH. Take a look at the fact that you have 1, 2, 3, 4 hydrogens. So another common student misconception is all I have to do is connect an oxygen on one molecule to a hydrogen on a neighboring molecule. So look for a moment at this particular dashed line that I have drawn. Read the information on the slide. And is this a satisfactory hydrogen bonding interaction? Well, hopefully by my tone of voice and the big red X on the screen, you can see that that would be incorrect because the hydrogen that you are reaching out with this particular connection must be, as it says, directly bonded to either a nitrogen, oxygen, or fluorine. So this hydrogen is bonded to a carbon, so therefore that is not an example of a hydrogen bonding interaction. Okay, one more thing I want to talk about, which is not exactly intermolecular, but interparticle, is the attractive force between an ion and a polar molecule. So I can't really call this intermolecular because an ion is not a molecule. You may recall a couple of lessons ago we talked about Coulomb's law, and there was an AP practice question involving comparing the attractive force between an iron cation and a polar water molecule. That's essentially an ion dipole force. So the attractive force between an ion and a polar molecule. Water is often the example. So I'm putting some water molecules around this cation, and I'm putting some water molecules around this anion. Look closely at the way I have oriented these water molecules. The negative end of the water molecule is going to be the oxygen, and the positive end of the water molecule is the hydrogen. So they tend to orient with a specific directionality, the ion dipole force. So pay attention to that if you have to draw a particle diagram, the orientation of the water molecule so that the opposite charges are attracted. Okay, so now I'm going to talk about properties of liquids and solids. Here we have 2 liquids, C5H12 and H2O. The boiling points of each liquid is listed. I'd like to talk about a property of a liquid which is known as vapor pressure. So what exactly is vapor pressure? It is the pressure exerted by a gas in equilibrium with its liquid phase at a given temperature. Now to model vapor pressure, I'm going to go ahead and put some dots above the surface of the water in this flask. I'm at 300 Kelvin. What's going to happen to the number of dots in my particle diagram if I raise the temperature of this liquid? Well, let's do it and find out. 310, 320, 330. I'm raising the temperature of the water. So as you can see, what's happening to the vapor pressure, it is increasing. Well, why is that? Why is warming a liquid going to raise the vapor pressure? I have an answer for that. This is a diagram of number of molecules on the y-axis and kinetic energy of the molecules on the x-axis. Now there are different kinetic energy values for any given sample of material, gas, liquid, solid. There's a kinetic energy which is related to the temperature. Each molecule is not traveling at the same speed. Each molecule does not have the same kinetic energy. So because there is an average, we are looking at a Maxwell-Boltzmann distribution of kinetic energies for a sample of matter. I'm now just going to go ahead and draw a line on this diagram. Now this represents what it would take to get out of the liquid phase and into the gas phase. So all the molecules are not going to evaporate at once. In fact, look at the shaded portion of this graph. Only these molecules in that shaded portion have the required kinetic energy to escape the liquid. What would happen if I raise the temperature of the sample of matter? Well, I have drawn another curve in a different color. This curve is in red. So as you raise the temperature, you increase the average kinetic energy and you also broaden out that curve a little bit. So it broadens the distribution. There's a wider distribution of energies available. And as you can see here, because of this shift in energy, there is a greater fraction of molecules that have the kinetic energy needed to escape. So now with a greater fraction of molecules that can escape, the vapor pressure above the liquid increases. Now when you raise the temperature of a liquid, vapor pressure increases, and I'm showing you a curve with vapor pressure on the y-axis and temperature on the x-axis. If I go along the y-axis at 1 atmosphere and then I intersect the curve and see what temperature that is along the x-axis, this would be the normal boiling point at 1 atmosphere pressure. There are ways of changing the boiling point of a liquid with different pressures, but for this purpose, I just want to kind of focus on that 373 is the normal boiling point of water. I have not drawn the curve for C5H12, which is called pentane, but I want to go ahead and ask you a conceptual question about vapor pressure. If you are given the boiling point of each liquid, which liquid has a higher vapor pressure? So based on the difference in boiling point, take a moment to think about which liquid should have a higher vapor pressure. If you want, you can stop the video, you can draw these flasks on your paper, and you can draw a certain number of dots above the liquid. Whichever flask you draw more dots in should be the flask that has a higher vapor pressure. So if you want to pause the video and take a moment and draw a different number of dots in each flask to represent the different vapor pressure, go ahead and do that. All right, well if you did take a moment to draw a diagram, I'm hoping that your diagrams look something like this. So what I'm showing you is because C5H12 has a lower boiling point, it has a higher vapor pressure. So I'm going to draw the curve, I'm going to draw the vertical line intersecting the x-axis at around 310 Kelvin. So you can see that we have a higher vapor pressure, and that's why it comes to a boil more quickly or at a lower temperature. So conceptually, make sure you understand all 3 of these concepts. Compare the intermolecular forces, compare the vapor pressure, and compare the boiling point for these 2 liquids. If all you have is the diagram that I'm showing you, hopefully you can see that the diagram on the left represents weaker intermolecular forces because it evaporates more easily. The diagram on the left would have a higher vapor pressure and a lower boiling point. So these are concepts that students sometimes confuse, especially vapor pressure and boiling point. As you can see, they are inversely related, so pay close attention to that distinction. I'm going to do a brief summary of particle diagrams and talk about bonding. We have 4 types of bonds I'm going to talk about with respect to the properties of solids. You've already seen this diagram before in an earlier lesson. So properties of an ionic solid: relatively high melting point because of the strong attractive forces. So here are some examples of melting points, and they're all about 900 to 1,000 degrees or more. They are hard and brittle, and what makes them brittle is because if a stress is applied and the layers of ions shift slightly, now you have repulsion between ions of like charges. So an ionic solid tends to flake apart into crystals, or it's cleaved along well-defined planes because of that. And I think I mentioned in an earlier lesson that for an ionic material, it only conducts electricity when it's either melted or dissolved in water, because the ions are free to move around. In the solid state, it is not a conductor of electricity because the ions are unable to move around. Properties of a metallic solid: we talked about how they are good conductors of electricity because of the mobile valence electrons. So it has a SEA of delocalized mobile valence electrons. As far as it being brittle, it's actually not brittle. Metals tend to be rather malleable. So if you apply stress, it tends to sort of mold and reform and flatten. You can flatten them into sheets and draw them into wires because the metal cores can easily rearrange their structures within that metallic bonding model. And I mentioned in an earlier lesson that you can have alloys, either substitutional or interstitial. And especially with interstitial, you can see that the hardness changes. So steel is actually harder than iron because the carbon atoms, as they fill in the spaces, make it more difficult for the iron atoms to slide past each other. Okay, so ionic metallic covalent network is another type of solid. Here we have a big network of atoms that are all covalently bonded in this large three-dimensional network. So 2 examples are diamond and quartz. Another example is silicon carbide. They have many strong covalent bonds, so very hard and rather high melting points because it takes a lot of energy to break all those covalent bonds. And another example of a solid is covalent molecular. As I talked about, we have these relatively weak intermolecular forces. So they're characterized by relatively low melting points, and they are not conductors of electricity because their valence electrons are held tightly within the covalent bonds of each molecule. So sugar and water are covalent and they do not conduct electricity. All right, just a comment about particle diagrams, and then we'll look at an AP practice and your homework. Solids are close together. Liquids are close together in terms of the particles, and gases are far apart. So I talked about how the motion of the solid particles is limited to vibration within the crystal structure. With liquids, they are constantly moving and colliding, and they tend to be very close together, and their properties are related to the relative strength of the intermolecular attractive forces. With gases, there are minimal or zero intermolecular attractive forces, and we can describe a gas in terms of the amount of gas, pressure, volume, and temperature. So on Monday, Mr. Byrne will talk about ideal gases and the ideal gas law, so more information about gases in the next lesson. Okay, so before I get to your homework, another example of please watch out for student misconceptions. This is from the 2018 free response, number 4, part A. You are given a table. Take a look at this table for a moment, and you notice that CS2 has a boiling point of 319. COS has a boiling point of 223. CS2 is nonpolar because of the symmetry and the dipoles cancel out. COS is polar because you don't have the same symmetry and the dipoles do not cancel out. So another example of a nonpolar molecule that actually, because of its larger electron cloud, has stronger attractive forces. How can we tell? Because it has a higher boiling point. In terms of the types and relative strengths of all the intermolecular forces, explain why the boiling point of CS2 is higher than that of COS. The College Board in the AP exam would never ask you to predict which of these molecules has a higher boiling point. That would be an unfair question because you might pick the COS because it's polar. But if you're given data, you absolutely must use the data. So here's a list of all of the misconceptions and errors that students made on this particular question. Okay, students failed to identify the IMFs in both molecules. They just talked about London dispersion forces in CS2 and did not mention anything about COS or vice versa. Some talked about the fact that the CS bond is polar and that's why it has a higher boiling point. But in fact, they forgot to mention that the 2 bond dipoles within the molecule actually cancel each other out. So saying that CS bonds are polar is not helping explain why this molecule has stronger attractive forces. The molecule overall is not polar. Some students said CS2 has stronger intermolecular forces and then just stopped there. They didn't actually identify specifically the London dispersion forces in CS2 are greater than the combined LDFs and dipole-dipole forces in COS. And then some students reversed the explanation because they were confusing boiling point with vapor pressure. So they thought that 319 was a higher vapor pressure and somehow had weaker forces. Some students said that the CS2 and the COS only have LDFs. That's incorrect because COS also has dipole-dipole forces. Some students said that both molecules have both LDFs and dipole-dipole forces. That's incorrect because CS2 is non-polar. And of course, that misconception that I mentioned earlier, some either implied or stated explicitly that boiling a liquid is breaking up the covalent bonds within the molecule. Some talked about molar mass and that CS2 is heavier. That's not a good explanation. And some, even though they had the data staring them in the face, they still managed to say that dipole-dipole forces are always stronger than LDFs. So this is the official answer. The scoring guidelines talk about the fact that you mention the intermolecular forces in each molecule and you say that the LDFs in CS2 are stronger than the combination of LDFs and dipole-dipole forces in COS because that's what the data tells us. All right, so today we talked about polarity, intermolecular forces, and properties of liquids and solids. Now, your homework question. There are 3 screens. I'm not going to read these questions out loud. This is from the 2012 AP Chemistry exam. Here is screen number 1, here is screen number 2, and here is screen number 3. So that's your homework for Monday's class. Mr. Byrne will explain these answers at the top of his lesson on Monday. Remember about the helpful chemistry resources in the link in the video description. This has been Michael Faribault from Albemarle High School in Charlottesville, Virginia. Thank you very much for watching. And again, go to cb.org/tech if you or anyone you know has needs for mobile tools or connectivity for the AP Chemistry exam this year. Thanks for watching.
Good morning, AP Chemistry fans, and thanks for joining us again for an AP Chemistry live review session in preparation for our upcoming exam. Hope you all had a really wonderful weekend and are ready to do some exciting chemistry today. I'm Mr. Byrne from Glenmore West High School in Glen Ellyn, Illinois. Our school is just coming off of spring break, so I hope you have a whole bunch of Hilltoppers that are logging in to watch us today. Today is Monday, April 6th, 2020, and we have some exciting news that we'll be able to share with you today based on some information that was released to us last week. Today's lesson will continue on our Unit 3 conversation about intermolecular forces and properties. Specifically, we're going to transition towards talking about gases and how we can both explain the behavior of gases both mathematically and explain them using the kinetic matter theory, which is a pretty awesome tool for us to understand what's happening with gas particles. As always, as we always like to remind you, make sure that you're checking back to apcentral.collegeboard.org for all of the latest information on anything to support you or your school for AP classes moving forward. We do know based on some information that was released on Friday that the AP Chemistry testing date for all of us is going to be Thursday, May 14th, 2020. And the way that it's going to work is that everybody will be taking the same test at the same time on their own devices. So whether you are back at school or you will be at your home, you will be taking the AP Chemistry testing, the AP Chemistry test at this time, whichever is your local time. So I live in Central Time, so my students will be taking the AP test at 1 o'clock p.m. But if you're on the East Coast, it'll be 2 o'clock and so forth throughout. For those of you that are watching internationally, you should be able to calculate your time based on Greenwich Mean Time down here, and so you would just calculate it based on 6 p.m. So there'll be a lot more information about what that system by which you will get the test is and how you'll submit your solutions to problems back to the readers. But what you should absolutely be doing is writing on your calendar May 14th and calculating what time it is and make your plans there. So we've got an end date in sight. We've got a target that we can be aiming for to make sure that we're all prepared by that. We realize that there are lots of reasons why students might not be able to take the test at this time. So there is an alternative testing date, which is Tuesday, June 2nd. And this is one that you would want to talk to your teacher and or the AD coordinator at your school if you needed to switch your testing date from May 14th to June 2nd. Okay, and so that's something that you would individual students should talk to their teachers about in order to make sure that they show us their best work after all of this review time and all the hard work you've done all year. We want to make sure that you are set up really well to be able to give us all of that great chemistry knowledge that's in your brain. Okay, so let's do a quick lesson overview. As always, we're going to do a review of our homework problems from last class. From yes, this time it will be on Friday. Then we're going to talk about three big topics that all surround gas laws: the ideal gas law, the kinetic theory, like I said, and then some deviations. So when we talk about ideal, I like to say that this is perfect magic chemistry land where everything works out exactly how we want it to. And deviations would be in the real world. What are some assumptions we can make about how gases are going to behave when they are not in perfect chemistry? Okay. As always, we'll continue to encourage you to stop when needed and make sure that if we're going too fast or we ask you to stop question, have a piece of scratch paper and a pencil, maybe a calculator and a variable table as well, and make sure that you know how to solve these problems on your own. You're going to see a couple of diagrams today from that OpenStax textbook that I mentioned to you last time I was on, last Tuesday. It's a great open source textbook, one of many that's out there. So if you wanted to check it out, thank that for letting us use a couple of their diagrams. Okay. So moving forward, we'll start with our warm up. Some of the problems Mr. Fairbach gave us last week, where we're looking at some intermolecular forces, IMFs. Specifically, we're looking at an analysis of these 5 molecules here: pentane, propane, methanol, methanoic acid, and methanol. And our first question asks us to explain why pentane is a liquid, whereas propane is a gas at 298 Kelvin and 1 atm. Now that's really only one part of the question. I'm going to go back to this and make sure that I highlight up here in our instructions. It says, in each explanation where a comparison is to be made, a complete answer must include a discussion of both substances. So you're going to see a series of questions here where you're asked to compare two different substances, but we want to make sure that we say some important things, some true things about both of the substances, not just the answers that because one of the molecules. Okay, so you're going to see that I like to set up my solutions by thinking about what is the same about these particles or these molecules, and then what might be different. And so for pentane and propane, they're both non-polar molecules, and I know that they're non-polar molecules because they're both a series of hydrogens and carbons. I don't see any fluorine, oxygen, and nitrogen. Those would be the 3 atoms that I want to look for that would immediately jump off the page for me as being polar molecules, because we just have carbons and hydrogens in there. Everything is very balanced around the molecules. These are going to be considered non-polar molecules. Okay, and so they both are capable of having London dispersion forces, what we call LDFs, and those are those particles those interactions, so intermolecular forces that Mr. Fairbach talked about, because of the result of electron displacement. And as the electron clouds are moved around, we can see that there is some induced polarity that's going to hold these molecules together. So it'd be a great time to stop and go listen to Mr. Fairbach's great explanation of this and his awesome diagrams from Friday. If this is not sounded familiar to you, okay, what we do know that's different about that is that pentane, because it is a bigger molecule, more carbons and hydrogens, it has a larger electron cloud, and that's a key part of this solution. That you want to make sure that we acknowledge that pentane is not just a larger molecule, but it has a larger electron cloud, and because that electron cloud is so much larger, that it will give pentane the ability to have stronger London dispersion forces. If it has larger London dispersion forces, it must have a higher kinetic energy, and kinetic energy is related to temperature. That's a conversation we'll have today to overcome these stronger London dispersion forces. And so our final conclusion might be something like, at 1 atmosphere and 298 Kelvin, propane has enough kinetic energy on average to be in a gaseous state because it has weaker LDFs, whereas pentane does not yet have enough, and so it would be in its liquid state. Here's the official answer from the College Board. So here's what I was talking about before. One point is earned for recognizing that pentane and propane both have London dispersion forces, but then the second point was earned for recognizing that pentane has a larger electron cloud, greater IMFs, and a higher boiling point. Okay, so that's why it would be liquid. All right. Second problem, in a similar way, we're doing a comparison of two molecules. At 1 atmosphere and 298 Kelvin, methanol is a liquid, whereas propane is a gas. Okay, so now we're looking at two other molecules. Give me a second, just analyze what would be the same and what's different about them. What would be the same, because all molecules have London dispersion forces, we would need to say that both are capable of having London dispersion forces. But what's different is that propane only has London dispersion forces, where methanol has hydrogen bonds because of this polar side of this molecule here. Methanol is absolutely a polar molecule because of this hydroxide group on the side, this oxygen, very electronegative, pull on electrons really well. And because there's a free hydrogen here, we're going to have some hydrogen bonds between this hydrogen right here and the oxygens on other methanol molecules. Again, Mr. Fairbach gave a great explanation of all of these intermolecular forces on Friday. I encourage you to go back and look. Okay, so hydrogen bonds are much stronger than LDFs, so more energy is needed to convert methanol from a liquid to a gas. So here we're doing a comparison where we're saying specific information about propane. It has only LDFs, methanol has LDFs and hydrogen bonds. Because those hydrogen bonds are so strong, it would still be in a liquid state. 298 Kelvin on average is not enough energy to break apart, to split those particles apart from take them from liquid to gas. Right? So 2 points: one for recognizing the intermolecular forces, and the second for recognizing that it would take more energy. Okay, this brings us to another thing that we discussed last week about the hybridization of atoms, where we look at what kind of hybridization is around the central carbon in each of these molecules. This methanol has 4 different zones of electrons around the central carbon, and so what we can say is when anytime there are 4 electron domains, that results in sp3 hybridization. I like to think that there's a 1 right here, and 1 plus 3 gives us 4, plus there's 4 electron domains. Mr. Fairbach explained the chemistry behind this in terms of why we would have our S's and our 3P's hybridized into 4 equal size bonds last week, so that's a great review from last week. Methanoic or formic acid has only 3 electron domains around it, and we find that as sp2 hybridization. Okay. Lastly, we're looking at methanoic, or this question is asking us about the methanoic anion, but it gives us the diagram of the methanoic acid. And so the first thing we need to be able to do is to relate this anion over here to this formula that's over here. Okay, and what I'm going to notice is that there's a hydrogen here that's on this side, but it's missing a hydrogen. It's an anion. This acid has a hydrogen to give. This is we call the conjugate base of this acid over here. So that's a good review from a number of lessons ago, 6 weeks ago. So we would probably want to look at a Lewis structure for methanoate that looks like this with that hydrogen missing. And we should recognize that there are resonance structures for methanoate. So there are 2 different structures, one with a double bond bonded to this oxygen, and then we switch them. We want to make sure that we recognize that the oxygen with a double bond only has 2 electron pairs, whereas the oxygen with a single bond has 3, and that's the same can be said over here. They just switch in different order. Because these resonance structures are equally possible, what we would say is that the 2 bonds have the same length. So this is an example of where having a Lewis dot diagram would be a really great part of the explanation, and recognizing that these are equally responsive or equally possible gives us the bonds with this length. Right. Lastly, this one really is last. Excuse me for forgetting that we have this one coming up. We're comparing these 3 molecules. We want to have a good practice where we talk about all of them. I'm going to talk about them left from right. The carbon-oxygen bond that is right here is a single bond, so we would call that a bond order of 1. The methanoate ion, because it has these 2 identicals, like we looked at in the resin structures from the previous slide, we would say each of these have a bond order of 1.5. And methanol over here, the carbon-oxygen bond is a double bond, which we'd say is an order of 2. Okay, so just writing this out would not be enough. We would want to make a statement because we would say because they're all the same atoms, so we're all looking at carbon and oxygen. If one of these is carbon and oxygen, it would be much harder to compare. But we're always looking at carbon and oxygen in all 3 molecules. Bond order of 1.5 is expected to have a length that would be in between a bond order of 1 and 2. Okay, if that's in the way, excuse me. I'll read this to you again because these are all between the same atoms, between carbons and oxygens. The bond order of 1.5 is between 1 and 2. Okay, so those are some warm-up problems for today. We're going to get into what you need to know and a couple of guided practice problems. Check our time. We're doing all right here. Like I said, we're looking at 3 of the lessons from Unit 3, ideal gas law, kinetic molecular theory, and then any deviations from the gas law. Okay, so ideal gas law, the important thing to remember here is that this describes mathematical relationships. So the ideal gas law is always going to be about math. We want to pair that up with 3.4, which is a kinetic molecular theory, which explains why particles behave as they do. But the ideal gas law just tells us mathematically about some relationships. Okay, and I would assume at this point that the ideal gas law is a little bit of a review for you, but just so we have it all on one slide, let's remember that P in PV equals nRT is equal to pressure, V is equal to volume, N is equal to the number of moles, and T is equal to temperature. This equation is given to you on your equation sheet when you're sitting for the exam. However, this is an easy one to remember. P equals nRT, and remembering what these variables are, it would be an important thing for you to be able to pull up pretty quickly. The last variable here we want to look at is R, which is the gas constant. Now, our equation sheet gives us 3 different versions of this gas constant, and what I want you to notice is that there are different units based on how we're going to use this gas constant. So very typically in anything having to do with the gas law, ideal gas law, we're going to use the second one right here, where our units are liter atmospheres over moles Kelvin. So these have the negative ones to indicate that they would be underneath. This format is sometimes a little strange for students, so I would encourage you to use that. I'll show you how we're going to use a couple minutes. But my hint here is always go back to this the review sheet, the equation sheet, to look at what the units are listed here, just to remind yourself, okay, which units am I supposed to be using when I report my answers? Am I reporting them in the correct units as they are here? If you were to use P equals nRT and somehow start using this number 8.314, joules is not going to fit in here really nicely, right? So it's going to, you would automatically recognize, and use the wrong number, and then you can remind yourself here. Okay, we certainly could use, if using 4 is something that's easier for you, 62.36 or something that you want to do that. I'm much more comfortable and teach my students how to use this number, so we're going to go ahead and use that for today. Okay, so a very typical problem that you have is that you have a container like this. It holds a certain amount of gas at 18 degrees Celsius and 1.08 atmospheres. Again, this is math. We're going to solve out for just the molar mass of this gas. Now we know we have a mass here. We need to get the number of moles. Okay, so that's N. If I can get a relationship or ratio between this N and these grams over here, that will get me to my molar mass. So I'm going to just write out as good mathematical practice. What's the information that I have that I know I can use, and then rearrange my equation to get me to a place where I can solve for the number that I want. So the problem tells me that my pressure is 1.08 atmospheres. There we go. My volume is 2 liters. My temperature is 18 degrees Celsius. And here's where I'm going to use my R from the equation sheet to see that it's liter atmospheres over moles Kelvin. And that Kelvin jumps out at me, right? Because I don't have Kelvins up here, and that would remind me to convert my degrees Celsius into Kelvin. It's a very common mistake that students will use degrees Celsius with this R constant instead of converting to Kelvin. I hope that we're all comfortable with adding 273 to degrees Celsius in order to get to Kelvin. So we're going to say that our temperature is 291.4. I get rid of my equation sheet now, so I have a little more room to work. I've rearranged this equation up here to say that N, our number of moles, is equal to PV divided by RT. I plug in my numbers here, do one little simplification, and should end up with a number of moles that's 0.0904. So go ahead and double check my math with your calculator if you have it. But again, the question asks us to get to our molar mass. We know that molar mass is the grams divided by moles, and so I should end up with something like 44.2 grams per mole. Turns out that this gas is with a margin of error of carbon dioxide, I think should be about 44. So I think I rounded a little differently. We've gotten closer to that. But we got to molar mass, and I would want to report that as calculate the molar mass. Molar mass is equal to 44.2 grams per mole. Okay, so I've got a number and I've got my units on it. Great. So that's how we would use the ideal gas law. There's many other versions of that, and I would encourage you to talk to your teachers. I'm sure that your teacher will have other examples of how to solve that problem or how to use that equation to solve problems. The second part that is an important piece of this lesson is to look at partial pressure of gases. Partial pressure, that means that in a sample that has a mixture of gases, the total pressure is, each component's pressure is independent of the other ones. So we're going to pretend this is again an ideal gas law, perfect magic chemistry land, that the individual gas components do not affect one another, so they're partial pressures. Okay, so the total pressure of this sample is the sum of the partial pressures. This is much easier to understand if you're looking at a picture. Okay, so if I had equal volumes of each of these 3 gases, whatever they are, okay, and I had different amounts of them, so like I have different numbers of moles in there, which means they have different pressures going from one to the other. If I were to just dump all of these into one big bottle, I would add these 3 numbers up, and that would be the pressure, the combined pressure in this bottle. Okay, this is a nice reminder that kPa, kilopascals, is another unit that we might use for gases. If we're looking at this mathematically instead of conceptually, we might have something that looks like this. So the total pressure is equal to pressure from one gas plus pressure of the other gas plus pressure of the other gas, etc. However many there are. And if we wanted to calculate the partial pressure just for one gas, you would say the total pressure times this is the mole fraction, right? However many moles A we have, excuse me, as divided by the total number of moles in the container. Okay, this is an equation. These 2 equations are taken right off the AP Chemistry equation page, and so you should know that these will be easy for you to access. There. Excuse me. All right, so let's take this off a ride and see if you're ready for some practice with this problem. We're going to pretend that we have a gas mixture that's at 0 degrees Celsius and 1.5 atmospheres, and it contains some hydrogen, some oxygen, and some nitrogen. Okay, if you are the oldest child in your family, I would like you to calculate the partial pressure for hydrogen in this mixture. If you are a middle child, what I'd like you to do is to calculate the partial pressure of oxygen gas. Oh, this should say oxygen. Excuse me, this is O2, so you calculate oxygen gas here. And if you are the youngest child, that's that one too. Would you calculate just what the partial pressure of nitrogen is? Okay? And if you are an only child, you can pick any of these 3 that you would like to do. I'll give you a minute either to pause or to calculate this out on your own. And a reminder that just because you're an oldest or middle or youngest, you can go back and practice any of these other ones however you want in the future. So I'm going to give you a solution for these. All right, so here's our equations that we're going to use, taken right off of the chemistry equation sheet. And here's a reminder that for all of us, anybody to solve that problem, you need to do is we need to know what the total number of moles are. So we're going to start by adding up the total number of moles, get 0.05 moles of gas total in that container. So if you solve problem number 1, where you're looking just for hydrogen, you're going to say the total pressure in the container times the mole fraction, so 0.01 divided by 0.5, and you should have 0.23 S. If you did problem number 2, again, we're looking for oxygen here. We're going to take that same point, or 1.15 times the 0.015 divided by our total. So here's our mole fraction here. We should get 0.35, and our last answer would be 0.15 times our mole fraction here. That's just for hydrogen. If I do a quick add up in my head, I think we get 1.6, which with rounding gives us 1.5. So then I check to see if we did this right. Do they all add up to get to our original pressure that's there? Okay. So take a screenshot of this if you wanted to look at these solutions at some point in the future. Lastly, I would like to just kind of summarize a lot of the different relationships in the ideal gas law and think about how that might look in a graph. Okay. So you have to excuse some of my pictures that I drew here. There's lots of different versions of this, but we can look at 4 different relationships basically between pressure, volume, temperature, volume, moles, pressure, temperature. Each of these relationships has a name: Boyle's law, Charles' law, Avogadro's law, and Gibbs' law. You wouldn't be expected to memorize those names, but understanding these relationships between the variables would be really important for you to know. And sometimes a graph is really going to help us with that. And so for pressure and volume, we're going to see that they are inversely proportional to one another. So when pressure is high, volume is low, and when volume is high, pressure is typically low. And so an example of this is if I had the same number of particles in a container, and the container got smaller, what I would see is I would have an increase in pressure, right? And the same thing would be true. I think we've all had that experience of where you're holding on to a balloon, and if you were to squeeze in on that balloon, you would feel that pushing back harder. It was really hard to keep in your brain. There's lots of more chemistry examples of this. If you want to think about a piston, you want to think about a syringe, you want to think about some kind of a sliding box. I'm going to show you one in just a second. But what we want to see here is the same. The number of particles stay the same. The temperature stays the same. We didn't do anything with temperature, so we just made the container smaller, and so the pressure is going to get bigger. And we'll talk about why that is. Volume and temperature, which we call Charles' law. So if I have a container that I heat up, here's my little hot plate underneath here. As I heat it up, the container should get bigger. The volume could get bigger if we're going to keep pressure the same. I live in Chicago, and it's still pretty cold outside. As I look out the window, it's sunny, but it is cold. So if I took a balloon outside, I would notice that it gets smaller. So it's the opposite of this picture that I have here, right? And then if I bring that balloon outside the inside, it would be increasing. I'm not changing the number of particles in that balloon per se, especially if it was tied up. But as I bring it from outside where it's cold, inside where it's warm, that balloon would start to fill up again because the particles are going to fill up the space. And again, this is just looking at the mathematical representation of why this is. We're going to talk about the explanations of that in just a minute. Similarly, if I am blowing up a balloon, right? When you blow up a balloon, you are adding particles of gas into that balloon, and so it gets bigger. So the volume of it gets bigger as I add more moles. So more moles means greater volume, smaller moles means a smaller volume. Okay, it's interesting that this graph, both of these graphs seem to indicate that at zero temperature or 0 moles, we get to volume. We're going to talk about that in a minute as well. Okay? And then pressure and temperature is the same thing. That if I add heat to this container, right, the volume stays the same, but there's going to be pressure that is increased inside this container. And I didn't do a good job of explaining or showing you that in this picture, but what you could imagine is if we had a pressure sensor on this, you would see the pressure going up. I will explain that to you, or show that to you in just a second. So this is maybe a nice picture to take a screenshot of. I over spring break last week was doing a lot of bike riding with my family, and I got to be honest, I couldn't help but think about gas losses. I was thinking about taking my bike inside and outside and adding gas or adding air to the tires and things like that. So this is a really good example of you just being outside and looking at the tires on your car or the tires on your bike and thinking about how gas laws are affecting those every day. I do want to jump over real quickly into a simulation that Mr. Hasselbalch showed us last week that I think is a really good one. Actually, I'll show you where I got this first. Okay? I made a couple of bit.lys for you. These PhET simulations are really awesome. Whether you're a student or a teacher, they're a great resource for all of us. So go to this bit.ly. You can just do Google search for this for PhET interactive simulations at University of Colorado. Or we made a bit.ly for you with all of the simulations. I'm going to go to this one that's just gas laws here, and we're just going to kind of explore a couple of the ideas that are here. Okay. And so what I can do is I'm going to add. There we go. We're going to add some gas particles into this container. Okay. And what I hope you're noticing is that the pressure is increasing as I add particles into the container. Okay. And if I take some of those particles out, the pressure is going to go down. So pop the balloon. Right. So the number of particles. So what do we just say here? The number of particles is increasing the pressure that's in there. Does that make sense? I can close this in. So I'm decreasing the volume of the container. What I notice is the pressure goes up again. And if I slide this out way far out here, the pressure has gone down from where it was before. Oh, you can see that the temperature is doing some kind of crazy things here. I'm going to cool this off. Right. So we get to kind of a regular temperature in here. We're just kind of playing around. And I would encourage you to do something similar. Okay. So I cooled it off and that decreased the pressure. So we saw a relationship between pressure and temperature as well. When I decrease the temperature of these particles, the pressure goes down. And similarly, I can increase the temperature here. And I'm going to notice what happens at a certain point. I think this is what my daughter was doing over a break. Yes, break off the lid because we've all had that experience of an aerosol can or a compressed container that I think it's too warm. That's why it's real dangerous to mess around with those too much. Okay, so I'm going to get this back down to a regular temperature. What we notice is the particles are here. This is a great resource for you to just remind yourselves of relationships between all the different units. Now I'm going to add in this idea of collisions here. And what we're going to look at are the collisions with a wall. And what I'd like you to do is as you're looking at these particles, obviously this is just a simulation, right? This isn't, we can't see gas particles because they're so small, but if we could, things like this are pretty common. And if we were to look at in a sample period of 10 picoseconds, we're going to press play right here, see how many wall collisions there are at 730 Kelvin. So there are 280. So write that number down, 280 wall collisions at 730 Kelvin. I'm going to cool this off now. Let's try to go to about half of that. Okay, we're at 280. Okay, we got down to 190. Now, what I'm noticing here is that at a lower temperature, there are fewer collisions. And it's very important as we transition from the ideal gas law to the kinetic molecular theory. The idea behind why these relationships, why these gas particles behave the way they do, is that we're able to look at this and see collision. And we see that these gas particles are both colliding with each other in the middle of this, and they're colliding with the walls. And one of the important things to see here is that the reason why there is pressure in this container, why there's pressure in any container that contains gas, is because there are collisions of the gas particles with the size of the container. So if we can do anything to increase more collisions, or we can have stronger collisions, that we are going to increase the pressure. And I can change temperature here, I can change the volume, and what I'm going to see is there's less area here, so that's going to increase my collisions as well. And I would encourage you to just kind of play around with this as much as you can, because you'll get to see a lot more of the explanations for why these particles are behaving as they do. Okay, let's go back into this. Okay, and we're going to go to the kinetic molecular theory, which really does a nice job. Now we're going to explain, not mathematically, but using a model and theories that are backed up by the math, but they're much more about an explanation of the particles rather than just saying, here's what the math says. So typically, when we study kinetic molecular theory, there are 5 postulates, or 5 statements that are made about why ideal gases behave as they do. And the first thing relates back to that, what I just said we saw in that simulation, that particles are colliding with one another. They're in continuous motion. They're in straight lines till they collide with either another molecule with the walls of the container. And the pressure that's exerted by a gas is the result of those motions. Okay, so none of this is difficult to understand. And certainly when we look at that simulation, it kind of jumps out at us. But to remember that anytime we're talking about gases, we really want to be thinking a lot about the collisions of particles with one another is an important underlying principle for you to keep in mind. Thirdly, we're going to say that the average kinetic energy of gas molecules is proportional to the Kelvin temperature. Mr. Hasselbalch talked to us about that last week. We're going to look at some similar diagrams today. But we know that if there's a higher temperature, there's a higher average kinetic energy for all of the particles that's in there. Fourth and fifth are 2 statements that are a little bit tricky, and we're going to dive into when we talk about non-ideal gases. But we assume that gas particles are so small that it's a negligible volume, and certainly negligible compared to the distances that are between. So that would be one way that simulation we're just looking at was not a good simulation, because those particles were so big compared to the container. We know the gas particles are much smaller when we compare them to this overall volume of the container. Okay, and we also make this assumption that there's no attractive or repulsive forces. So based on our conversation last week, we know that polar molecules are going to be attracted to each other in some ways and repelled by one another in other ways. We know that real gases, real particles, sometimes are attracted to one another and sometimes repelled by one another. But we're going to pretend, at least right now, again, perfect magic chemistry land, that none of those things exist. And so once we have that, we're going to have a little bit different explanation for each of these relationships between our variables. Okay, so what you see here is I've got a similar set of diagrams from that earlier slide, and our explanation has to talk about either collisions or particles or both. And excuse the small font here, but take a screenshot and you can zoom in later. We know that when the volume of a container decreases, the particle is going to collide with the sides more often. So I started to do that right at the end of our simulation, and you'd be able to play with that in the PhET simulation. If there's more collisions with the sides of the container, there's going to be more pressure within that container. Right? So here's an explanation of a relationship between pressure and volume. It doesn't just say what the graph looks like, it doesn't just say a mathematical representation. It talks about the particles are doing. It talks about how more particles are colliding with the sides. They're doing it more often. They're doing it probably stronger, and so the collisions will increase the pressure on the container. Secondly, we could look at a relationship between volume and temperature. When the temperature increases, the particles move faster, so that we know that the Kelvin temperature is related to the average kinetic energy. So we have a greater velocity in there on average. So there's more, and there are stronger collisions. So you know, so you have both more and stronger collisions besides the container. So the volume has to increase to keep the pressure constant. So what we're saying here is, if volume and temperature are the only 2 that are allowed to change, but the pressure is going to stay the same, the volume has to get bigger in order to get to the same pressure. If we add more particles, like we're blowing up our balloon, there are obviously going to be more collisions with the sides of the container. If the pressure is not able to increase, so the pressure needs to stay the same, we're going to increase the volume in order to keep the pressure constant. So that's a great example of why when you blow up a balloon, you're inside your house or outside your house, the pressure in the room is not going to change. So the volume of the balloon needs to change in order to come to the same pressure as what's inside. And lastly, the pressure inside this container increases with higher temperatures because the volume stays the same. So we did not increase the volume in that relationship between pressure and temperature. And so we have more collisions because there's higher temperature, the pressure increases in there because the volume does not change. So here's an added explanation of these relationships. Excuse me, go back to this. It's a great thing to take a screenshot of as well. On Friday, I believe believe Mr. Fairbaugh talked to us about Maxwell-Boltzmann diagrams. This is a different version of that same thing, okay, where we're looking at any given temperature, right? So this is oxygen at 300 Kelvin. We have the most probable speed, so the speed that has the most number of particles on it, which would be right here. And then we have what's called the root mean squared velocity or root mean squared speed. This is, we're not going to have time to go into this today, but this would be interesting to look at and talk about with your science teacher, maybe with your math teacher, the significance of that number that's right there. This gets interesting when we look at the same gas at multiple temperatures, right? So here's nitrogen. And what we see is the most probable speed changes, but what's really important about this higher temperature is, yes, the peak moves over to the right, but it also moves down, and that we've spread out the possibility of all of these different speeds. So just because a sample of gas is on average, it has a temperature of 1,000 Kelvin, doesn't mean all of the particles are moving at 750 meters per second. We still have some that are moving at a very, very slow speed. We just have some that are very high, so they average each other out. So just knowing the speed of any given particle doesn't tell you the temperature of the overall gas sample, because you can see down over here we have multiple gas particles within each of these groups. We need to look at the average of all of the particles that are there. And if you're ever asked to consider how one of these graphs would change as temperature changes, you want to make sure that lower temperatures have a much more compact curve, whereas higher temperatures have a much more spread out curve. Okay. Lastly, for the last couple of minutes, we just want to talk about deviations from the gas law. So as I've said, everything up until now that we've talked about has been in perfect magic chemistry land, and now we want to talk about the real world. So where are some ways we can deviate from the ideal gas law? We want to have some reasoning. We want to justify the claim that we're going to make that the gas, ideal gases, not ideal gases, real gases, will behave differently than ideal gases. So we know that the ideal gas law doesn't explain actual behavior of real gases, that there are deviations from interparticle attractions, right, in particular conditions where they are close, and then there are also deviations or changes from gas particles, especially at high pressures. So what I like to do when I'm thinking about this is I like to go back to our ideal gases or our kinetic theory and say, okay, if these are the 5 things that describe ideal gases, what might actually be different for a non-ideal gas or for a real gas? And I'm going to tell you that collisions still happen for all gases, and so the collisions are the particles are bouncing off of one another, they're bouncing off of the walls. We also know that the pressure within a container is caused by the collisions. And we also know that average kinetic energy of gas particles stays proportional. So these three statements here do not change when we talk about non-ideal gases. What do change is these last two. So let's talk about them just for a second. If we said that the molecules composing gas are negligibly small, well, what we know is that gas particles actually do have volume. It's not a negligible volume. And so at high pressures, which is typically low temperature or low volume, or both, the volume of the particles is no longer negligible compared to the volume of the container. And so the volume of space compared to the volume of the particles, that ratio is going to change between the particles in the container, and that's what throws off our calculations. Secondly, we know that some gas particles do attract or repel one another. And at high pressures, when they're really close to one another, the attractive or repulsive forces can impact the strength of the collisions. Right? We can say that they're either going to stick to each other a little bit more so they don't bounce off each other as hard, so those collisions aren't as hard, or because they're repelled from one another, we have positive sides or negative sides that are knocking into one another. They may actually push off each other even stronger in a way that would make it hard, that would make it deviate from the expected way for particles to react. Okay, so the way that this might be asked in a question is something like comparing argon to neon, where we're given a statement similar. Make sure you mention both information about both gases. Argon deviates more from ideal behavior at extremely high pressure than neon does. Okay, and so what we want to jump into immediately is where neon and argon are on the periodic table, and noticing that neon is directly above argon on the periodic table, or we could say that argon is below neon. So going back to the trends that we talked about last week about the size of these particles, we know that argon, because it's lower on the periodic table, because it has more occupied electron shells, it would have a larger atomic radius, and because argon atoms have a larger atomic radius than neon, at high pressure and low volume, the volume of the atoms is no longer negligible. Okay, so this is where it gets a little weird though. The volume that is actually occupied by the gas is less than predicted by the ideal gas, because the atoms themselves take up space. So the empty space is less because the space that's filled up by the gas particles is more. So the volume is decreased. The observed pressure is actually greater than predicted. The pressure is greater than we thought it was because the volume that was available to the particles to move around is less. Okay, so this is pretty complicated stuff. But anytime we're talking about real gases, of course, it's going to get a little more complicated. Okay, and I'm going to jump into our solution here real quick for our last one, because I know we're running short on time. We're looking at the pressure of a sample of methane is closer to the pressure predicted by ideal gas than a sample of ammonia. What we're seeing here is ammonia is a polar molecule, right? So here we're going to talk about both particles. Methane is nonpolar, ammonia is polar. Much stronger IMFs present in a sample of ammonia than a sample of methane. We may want to name those that we have hydrogen bonding that's happening here in ammonia that's not happening in methane. IMFs cause molecules to be more attracted to one another, cause fewer collisions. The size of the container, actual pressure of ammonia is less than the free pressure. Okay, because they're sticking to one another and not hitting the containers on the sides as much. So there's just two of a couple of different examples of how we could do, or we could talk about deviations from the ideal gas law. That brings us to the end of our lesson for today, where we talked about ideal gas law and kinetic molecular theory. This is really where these first two, where you want to spend the majority of your time looking at some practice, some math problems, and then being able to do some explanations. Using that FET simulation is a great way to do that. And then if once you're feeling really comfortable with 3.4 to 2.5 deviations, really where it starts to get interesting. Your exam practice problem for tomorrow has 4 parts to it. It's a really good summary of multiple different ideas that we've talked about over the course of these 2 weeks we've had together, a little more than 2 weeks now. So make sure you take a screenshot of this. We're looking at magnesium and hydrochloric acid reacting. This is some of you may have already done a reaction or an experiment like this in class. If not, we're going to walk you through what this experiment would look like and how we would solve each of these problems tomorrow. Okay, calculate the number of moles of magnesium, moles of hydrochloric acid. Here we're going to get vapor pressure just of hydrogen, and then calculate volume in liters of hydrogen gas. Okay, one more second just to make sure you've written that down and taken a screenshot. And remember that we'll start our class tomorrow with a warm-up solution to this problem. Make sure you're going back to apcentral.collegeboard.org for any questions that you have, any information that you need. We've given you a whole lot of links right below here. We've given you a tiny URL here for other resources and other simulations if you would like to play around with them. And lastly, make sure that if you or somebody you know is having trouble with the internet or having a device, now that we know that May 14th date, we want to make sure that everybody has a device and internet access by then. If you know somebody, please have them reach out to cv.org/tech to be able to let us give them the help that they need. Okay? Thanks for sticking with us for today. Had a great time sharing this information with you, and we'll see you again tomorrow. Have a great day. Good morning, AP Chemistry fans. I hear the church bells going off across the street, which must mean it's 9 o'clock here in the Chicagoland area, and it's time for another great AP Chemistry lesson. Hope you all are doing well and staying safe out there. Mr. Fairbaugh and I have some great things to share with you today. Today is going to be real lab heavy. We've got 3 different lab techniques that we're going to get to talk about that I'm really excited about, and I think that you're going to enjoy. So just a quick couple of reminders for what this is going to look like. Today's Tuesday, April 7th. I'm Mr. Byrne from Glenbard West High School. Go Hilltoppers. Thanks for joining us today. We're going to continue our discussion of Unit 3, which is generally on intermolecular forces properties, but like I said, we're going to be looking at some solutions today, and specifically some different labs that we can do in order to analyze the solutions. For all your questions moving forward, just a quick reminder to go back to apcentral.collegeboard.org and check there for the most up-to-date information. If you haven't had a chance to look at yesterday's video yet, you know that you may not know that the dates for our tests were released on Friday. So the AP Chemistry exam will be on Thursday, May 14th. Remember that everybody will be taking the exam at the same time, so you would want to find the time zone that corresponds to where you live and go ahead and mark your calendar. So I'm in Chicago in Central Time, and so we'll be taking the test at 1 p.m. But if you're on the East Coast, you get 2 p.m. and so on. International students, the best way for you to probably calculate your time would be to look at Greenwich Mean Time and then calculate from there. If for some reason you have a conflict with that first date, you want to talk to your teacher or whoever your AP coordinator is at your school about using one of these the alternate dates. I'm sorry, not one of them. There's only one alternate date for AP Chemistry, and that would be on Tuesday, June 2nd. One piece of information we did not specifically talk about yesterday was the format of the exam. Again, all of this is on apcentral.collegeboard.org. I just wanted to highlight two things for you. There will be 2 questions that will be completely free response. So remember that there's no multiple choice questions on our exam this year. The 2 free response questions, one of them you'll have 25 minutes to read and respond, and then 5 minutes to upload your response. And once you've uploaded it, you can go back. Then you'll look at question number 2, which is a little shorter, 15 minutes to read and respond, and then 5 minutes to upload. The format of the questions will give you some sort of chemical system, some data, and we're going to look at your ability to explain phenomena using models. I'm not going to read through each of these bullet points, but I hope that these bullet points look very familiar to you, because these are ones that Mr. Fairbaugh and I are going to highlight, have been highlighting often in these lessons, and will continue to highlight. You notice we've not given you any multiple choice questions to answer as we've gone through these either for practice or for homework, and we try to keep coming back to these skills to make sure that you're really feeling confident on them for when exam time comes. Okay, so this is a great slide if you want to take a screenshot of it, or if you want to just, like I said, go back to apcentral.collegeboard.org. All this information is going to be available there for this exam and for all of your exams. So like I said, today's lesson is going to be similar to our lessons, the format at least of our lessons from previous days. We'll start out with a review of yesterday's homework problems, and then we're going to look at 4 lessons that are really all around solutions. That's the thing that we're looking at here is around solutions. Friendly reminder that you may stop any time that you need to re-listen to something that I'm saying if you want to try to work ahead and come to a solution to the problem before I give you my solution. I have some pencil and paper available. And there are just a couple of diagrams today from OpenStax, but that's a great resource for you. If you are somebody who likes to read about these topics before you go into our explanations of them, it'd be a great time to stop right now, pull out your textbook, look up any of these vocabulary words here, solutions, mixtures, chromatography, solubility, any of those things will appear in your chemistry book as well. You can read up on them, and then look at some of our explanations about how they would be applicable on the AP test. So our warm-up was asked you to look at this problem from a practice exam where we're analyzing magnesium reacting with some hydrochloric acid to make magnesium ions and some hydrogen gas. So this is strongly connected to what we talked about yesterday because we're going to be producing gas. However, our 4 problems here are a really nice reminder of multiple parts of lessons we've talked about over the past couple of days and weeks. So we'll attack each of these problems independently and then go from there. Okay. So this first step I hope is a pretty straightforward one. We calculate the number of moles of magnesium in a sample. So we're going to start with the number that's given to us in the problem. We're going to use the molar mass off of the periodic table that was given to us. We use a nice dimensional analysis here where we have our moles on the top, grams on the bottom. We're going from grams to moles. And so our final answer is straightforward 0.00148 moles magnesium. This is a great example of how a pretty complicated problem can have a simple start to it and maybe even build up your confidence as you're trying to attack a problem like this to just start working on it, and you'll slowly get to the point where you're feeling really good about your overall solution to the whole problem. The second part asks us to calculate the number of moles of hydrochloric acid that's needed to react completely with the sample of magnesium. So here we're going to start with those moles of magnesium we have here. So this is essentially just a stoichiometry problem. We know how many moles of magnesium we start out with. We're going to be able to tell how many moles of hydrochloric acid are needed to react completely with it. Okay, so we're going to use stoichiometry, perfect magic chemistry land. If we have this many moles, exactly how many moles of hydrochloric acid we need there. We have 2 moles of protons for every 1 mole of magnesium. This is identifying that hydrochloric acid is a monoprotic acid. It has 1 proton in it. So we're going to need 2 moles of H pluses for every 1 mole of magnesium, our mole ratio from that balancing equation. And that gives us 0.00269 moles of protons that are needed to react completely. Excuse me just for a second. Right, so hopefully those 2 steps were pretty straightforward. This next step is a lab that many of you may have already done in lab in class before you left for this extended break. Just in case some of you have not, I'm going to just go through one of the procedures for how you might have done something like this. There's a couple different ways that you could collect it. This method of gas collection by water displacement is a pretty common one. There are multiple different explanations of it online, so if you'd like to see another example of it, feel free to just do a Google search, find some other videos of this. But what I have here is a setup of this long, tall piece of equipment. Is called a Eudiometer. A Eudiometer is essentially either a large upside-down test tube, it could be a large upside-down graduated cylinder. It would have graduations on here. It would have markings that tell us what the volume of solution is. In a lot of ways, it looks a lot like a burette, whereas a burette would be open on both sides of it. This is open just on the bottom. For this setup, what we've done is we've put a rubber stopper in it, but this rubber stopper has a small hole in it, and that hole is going to allow water to be displaced if we produce gas. And so or liquid to be produced. What I'm going to show you is that in this experiment, what we would do is we would put a piece of solid magnesium at the bottom of this container, and we put some sort of solution of aqueous hydrochloric acid. So here is our magnesium and acid from our equation. Okay. Some setups you will put a little bit of hydrochloric acid in the bottom, fill it with water, and then when you turn it upside down, the hydrochloric acid will fall down towards the bottom, and then when they meet, what you're going to see is that bubbles start to form. I saw one experiment where the teacher had used put some food coloring in the hydrochloric acid, so the hydrochloric acid was green, the water was clear, and you could watch the green hydrochloric acid come down until it meets up with the solid magnesium. There's multiple different ways that you can do this, but what we do know is that as gas is produced, because it is less dense than the aqueous solution in there, we know that the bubbles are going to float to the top like so. And so if this was an experiment you were doing in your class, you would see the solid magnesium at the bottom, you would see it reacting and probably getting smaller, a lot of bubbles that are around it. And as those bubbles start to reach the top, what we're going to see is that it collects a certain volume of gas at the top. Here's where that hole at the bottom of the stopper is important, because as we displace the water, as this gas is produced in here, some of the solution can come out into this beaker of water, and we would see this the level of the water rise in this because it was being displaced. So we would continue to watch this experiment while the magnesium is reacting until the magnesium is all used up. Okay, so what just happened there is at some point the magnesium is completely used up. Okay, and we know how many moles, right? We put a piece of magnesium that was 0.0360 grams in here. We know how many moles that was. There's still going to be some bubbles that will continue to go in, and they'll be collected up at the top. Now, oftentimes what we will do is we use a giant beaker so that we can put the water level here equal to the water level here, and then we know that the pressure inside the container is equal to the room temperature, the room pressure. Right? This experiment was actually a little bit easier because it told us what the pressure of the gas in this collecting tube was. They had some sort of measuring device. They were able to measure it directly. So it's not necessary for this experiment. If you did this in your class, you may work to get this liquid in here, even with liquid that's right here, so that the pressure inside there is the same as the pressure in the room. Okay. So the question that we have to ask ourselves as we're looking at this is what gas or gases is inside the Eudiometer at that point. I want to give you a second just to consider that before we move on, because all of this is just set up for what is part of the problem that was explained to us. It's all set up to look at what this question is ultimately asking us about. And the key understanding for this kind of a lab is that we absolutely have hydrogen gas in that container in the Eudiometer at that point, because we produced hydrogen gas over here. Right, here's our product hydrogen gas. You'd have a solution in here that would include some magnesium ions. But because of the way this is collected by water displacement, we will also have some water vapor in there. And if we were to zoom in really closely on there, you would actually see some condensation on the side of the Eudiometer. You would see that there are maybe some droplets of water in there, and then the assumption is that the water vapor is trapped in there as a gas. And that makes sense. It makes a lot more sense when we read the next step in the problem. If we connect this back to what happened with what we talked about yesterday with the laws of partial pressures, we know that the total pressure in there, which was 749 torr, is equal to the pressure of one gas, which is hydrogen, and plus the pressure of the other gas, which is water. 749 is equal to the sum of both of those. Right. So then we look at question C. Says given that the equilibrium vapor pressure of water is 21 torr at 23 degrees, and I think if we go back maybe to Friday or Thursday of last week, Mr. Fairbaugh talked about how this vapor pressure of water is dependent upon temperature. So this would change only at different temperatures. So our problem is telling us at 21 torr we have 23 degrees Celsius. It is 21 torr at 23 degrees Celsius. So we can just plug that in right here for our vapor pressure for water, and that tells us that our pressure for hydrogen is equal to 749 minus 21, and our final answer, right, calculate the pressure that hydrogen gas produced. So just the pressure of hydrogen, if it were dry, is 728 torr. Right. So that's relatively straightforward if you understand this experiment, right? Like many things we've talked about over the past couple of weeks, the math here is not necessarily challenging math. It's understanding the chemistry that's involved in the setup that's going to help you to be able to get to the problem set up in the proper way. The partial pressure equation per se is on our equation sheet, but you just have to know that we have multiple gases in there to be able to solve it. And the last part of this is to go from all this information that we have here to calculate the volume. And here you want to understand that based on all this information we have, we've talked about moles, we've talked about pressure, we have some temperature information in here, we're trying to get the volume, that we must have to use the ideal gas law. PV equals nRT. Pressure times volume is equal to the number of moles times our gas constant times the temperature. I'm going to just list out the information as it's given to us in the problem. We're going to use the partial pressure just for hydrogen because this question is asking us about the partial pressure or about the volume of just the hydrogen that's in there. So we would use the pressure of hydrogen. I'm sure that was a common mistake for students to just go back to this, but we want to make sure is that students are using the partial pressure just for hydrogen to solve this problem. We're looking for volume. Our number of moles of hydrogen. So here again we have some similarity here. The pressure of hydrogen and the moles of hydrogen, which we had from earlier on, is these are the number of moles of hydrogen that's produced, right? So that would be the same number of moles. We just do the stoichiometric analysis here. How many moles of magnesium do we start with? That's how many moles of hydrogen. I can see a student also getting confused that they should use the protons of the H plus ions, but no, we need to know the moles of hydrogen here. So that's why this is 0.00148. Not the double number. Our R stays the same here, right? And our temperature as given to us in the problem is 23 degrees Celsius. So one of the things that I suggested yesterday is that we use our equation sheet to remind us what our units need to be. And while we have a gas constant down here that gives us that where we could use for, so if that's something that you're used to doing, you might want to use this gas constant, 62.36. In my class, we always go back to 0.08206 liter atmospheres over mole Kelvin. It's just the way that I was taught to do it and what makes sense to me. So I'm always going to convert back to these. But there's multiple ways that you can solve this. It's nice that this equation right here, or the conversion between atmospheres, milliliters of mercury, and torr is right there. So the first thing I need to do is to convert my torr into ATMs, and then I also need to convert my degrees Celsius into Kelvin. Okay? Again, there are multiple ways that you could do this. If you felt more comfortable using this equation or using this gas constant, you certainly could do that. I'm going to rearrange my equation to say that volume is equal to nRT over P. I plug in my numbers, do a quick solution, and then my final volume is 0.0375 liters. This is another example where you want to make sure that you include your units. And look, we go back to the problem. It says we need to give a solution that is in liters. Okay, and so giving it in milliliters would not be appropriate because it says in liters. And so we leave it here. Of course, this number seems way too small. This is like 37.5 milliliters. So it seems a pretty reasonable amount of gas for something like that. Whew, that was a really long problem. Okay, this is a good example of an extended kind of a problem and how Calboard loves to give us problems that have multiple steps in it and to test our knowledge of multiple aspects of chemistry. And so I hope that you're feeling confident after looking through this. But feel free to stop and go back and listen to a couple of things I said as we went through here. Okay, we'll go through a couple of quick lessons on each of the topics coming up and some practice problems moving forward as well. We're going to talk about solutions and mixtures and how we can represent them. Talk about two separation techniques and then look at the solubility, how we would talk about solubility per se in solutions. Okay, so for this first topic, 3.7 solutions and mixtures, we're really going to get into the math. This is a lot of making sure that we have some really clear ways of calculating out the molarity of a solution. Right, and I assume at this point that most of you are pretty familiar with molarity, but we'll just do a quick review of it to make sure that we're all feeling confident. Two vocabulary words that are listed in this topic are homogeneous mixture. So when we think about a homogeneous mixture, we should think about the fact that their properties do not vary throughout the sample. So if I took a piece of the sample or I took a piece of the sample, wherever I take it, the makeup of this solution would be the same. Okay, so a solution is a homogeneous mixture. It can be a solid, liquid, or gas. We're going to spend a lot of time talking about liquid, but we know that air around us is a mixture of gases. There are certainly some solids that would, especially metals, that would be homogeneous mixtures that we could look at as well. A heterogeneous mixture, to compare homogeneous with heterogeneous, we know that the macroscopic properties depend on the location of the mixture. That's just a fancy way to say that if I take a sample from one side versus the other side versus in the middle, the properties or the makeup of that solution is going to be different. So these two mixtures are actually made up of the same kind and number of particles, if I did that correctly. However, the way that they're distributed throughout the sample is different, and that's what makes this a homogeneous mixture versus this being heterogeneous. Okay. Solution composition we can mathematically represent in multiple different ways, but the most common thing that's used on the AP chemistry exam is molarity. And this is one of the foundational equations that we use time and time again. I think you've seen Mr. Fairbaugh and I refer to this several times already, and so make sure that you are feeling really confident in this moving forward. Okay? So I put out 3 problems right here, and I want to encourage you to break yourselves into some groups. And today what we're going to do is we're going to consider what kind of pizza you like to eat. So if you're somebody like me who likes to eat pepperoni pizza, I'm going to encourage you to do problem number 1. Stop problem number 1, and then join us again. If you're somebody who likes to eat sausage pizza, then you can go ahead and do problem number 2. And if you're a classic cheese pizza or you're from New York and you call it plain pizza, you want to do problem number 3. Stop what you're doing right now. Solve out your problem number 3 and then come back to us in a couple minutes once you have a solution to your assigned problem. I'll give you 5 seconds here to pause. Okay, and now we're back and I'm going to look at each of the solutions that I came up with how to solve these problems. They're all a little bit tricky in their own way, and what I want to point out is that it's going to be very rare that somebody's going to ask, or on an equation on the AP test that we're going to be asked direct what's the molarity of something just based on moles and liters. That may be a way for you to warm up and for a way to do some simple practice, but these problems are they're always going to be a little bit more complex as we try to solve. So for problem number 1, we're going to remember that our equation is molarity is equal to moles of solute, right? So whatever is being dissolved in the liters of the overall solution. So it's not the liquid that's added, but it's the liters of solution. So you notice that this tells us 1.65 liters of solution, right? It's not that we added 1.65 liters of water. We made sure that the final volume of the solution is 1.65 liters. So I'm going to start with moles of solute, 56 grams of SrI2 strontium iodide. The molar mass of that is right around 341. I think there's a couple decimal points if we use the periodic table. And then what we also want to recognize is that in this compound, there are 2 moles of iodide ions for every 1 mole of strontium iodide. So that was the key of the trick here, that we're going to do a conversion from grams to moles, and then we have to double that to make sure that we're taking into account the fact that strontium iodide, when it dissolves, produces 2 ions of iodide. And so we should come to a solution, with the number of moles of solute is 0.328, and then we can go back and we can plug that into our equation for the top. Moles of solute over liters of solution, we get something like 0.199 molar. Okay. Problem number 2, we're going to start out with our same equation, but we need to rearrange it because we're looking for our number of moles, right? So moles of sodium ions. Again, this is going to be a little bit tricky. I hope that our sausage pizza fans out there are people that you recognize that we have 3 moles of sodium for every sodium ion for every 1 mole of sodium phosphate. Okay. And so even though our overall solution had a concentration of 0.1 molar, our concentration of sodium ions was 0.3. Right? And so when we plug that in, we're going to get our final answer would be our number of moles of sodium ions is 0.0735 when I multiply those numbers together. Then our cheese pizza fans out there had a pretty complex formula up here. We have we call a hydrate. So this is not just copper 2 sulfate. This is copper 2 sulfate. We call it pentahydrate. And so what that means is that when this copper 2 sulfate is in its solid form, it actually absorbs water, and it absorbs water at a predictable rate. So for every 1 particle or 1 molecule of copper 2 sulfate, there would be 5 molecules of water that are incorporated into the crystal structure. And so that's going to affect the molar mass. Because if I go, the molar mass, if I go into the lab and I have to measure the mass of copper 2 sulfate pentahydrate, I can't take the water out. So in order to get the copper 2 sulfate, I have to take those water particles in there. I look at it, it would still look like a powder. It's not going to necessarily look like it's wet, but the molar mass here is going to be different. And that's what we need to consider here. So we're looking for the mass. We're going to solve for moles first. Okay, so the moles are going to be our molarity times our liters of solution. It tells us we need to get this many moles, 0.043 moles copper sulfate, copper 2 sulfate. But our molar mass is going to be a huge molar mass, 249, because it is copper sulfate, plus 5 waters involved in there. So our final answer should be 10.9 grams. Okay, so those are just multiple different types of problems that you could do in order to solve something about solutions. We also know that we're looking at particle pictures. We spent a lot of time talking about particle pictures, and so if I wanted to look at something like aluminum nitrate here. So aluminum nitrate would be a solid in crystal form that would have one aluminum atom or one aluminum ion for every 3 nitrate ions. Yes, the anions that are there. So aluminum with the cations, and these would be nitrate NO3 minus. And if we try to put this into water, what we know is that these would spread apart completely, right? And so this problem is a little bit tricky in that it says it's added to distilled water to produce a solution of a concentration of nitrate that is 0.1 molar. Well, what's the concentration of the aluminum plus 3 in the solution? Well, we want to recognize that our equation or our dissolution equation would have aluminum nitrate dissolving into 1 aluminum for every 3 nitrates. And so with stoichiometry, a conversion of 1 mole of aluminum for every 3 moles of nitrate would give us 0.033 moles of aluminum ions. This is one where it would be very easy for us to quickly look at this and say, oh, there's 3 aluminums for every 1 nitrate. So we would just triple this. Many students would get this wrong by saying that the answer is 0.3 because they didn't take the time to write this equation out set of the problem to say, no, it's the conversion is from nitrates to aluminums, not aluminums to nitrates. And so we divide by 3 and multiply by 3. So that's understanding what the picture would look like in your brain and taking a look at and taking the time to write out the math on a piece of paper is going to be a really important practice for you to do. All right. Our next topic talks about 2 methods of separation, and we're going to be looking at the argument between the particles and the macros, like what we see from the outside and how that tells us what's happening on the inside. Okay. We're going to look at 2 methods of separation where we're saying that we have a liquid solution that cannot be separated by filtration. Right. So this is not a sand and water kind of separation. This is something where I look at the solution because it's a homogeneous mixture. The way that I separate out the 2 different parts is going to be really is going to be a lot more difficult, and I have to take advantage of the differences in the intermolecular attractions. Right. So that's why we spent some time talking about IMS earlier on at the end of last week, and they just keep coming back. So it's a really important topic. First one is chromatography. There's a couple different forms of it. I'm going to speak today mostly about paper chromatography, but we're going to look at the difference in the strength of intermolecular forces between the particles and the surface on which they interact. And then we're going to look at distillation, which looks at the difference in the boiling points of substances in order to separate them. So in a chromatography setup, you would have something that looks similar to this. So let me just explain some of the different parts to what's happening in this lab here. Okay. So we have 3 different mixtures to be analyzed. And remember that chromatography, each of these 2 solutions that each of these 2 methods we're looking at have to be a way of analyzing a mixture. So we have at least 2, if not multiple different substances. Take a second just to look even at those 3 colors that I chose should be colors that stand out to you as something that are mixtures of colors, and that's how we can analyze it. So a typical thing that you may have done in class is that you looked at food dyes and you looked at how to separate out the food dyes into each of the pigments that are found in between or inside of them. They don't jump out right at you when you just look at them, but chromatography will help you to understand. We put them on a piece of we call chromatography paper, and chromatography paper would be defined as a stationary phase because the chromatography paper is not necessarily going to move. We're going to set it up either we tape it to the side of the beaker, we hang it over a stirring rod. There's all sorts of ways we can get it to stand up straight in the beaker like this. But what you would want to know is we have a piece of paper that part of it is sticking in at the bottom. We call a solid, which is the mobile phase. There are 2 different kinds of solvents going back to our intermolecular forces. We have a polar or a non-polar solvent, and we can talk about why you would use each of those. But what's going to happen is that as the mobile phase moves through the stationary phase, that's really fancy terminology for saying as the solvent moves up through this paper. Right? The solvent is if you've ever put a piece of paper towel in water, and you know that the water will move through the piece of paper or through the paper towel. Same thing happens here. Right? As the solvent is moving through this paper, it's going to pick up particles from the mixture to be analyzed. And what we'll see is that the component parts of the mixture will travel at different rates. That some of that's a little bit is based on size, but it's mostly based on the polarity of the particles. So the larger particles move more slowly, and the particles with a polarity which matches the solvent will move farther. So if we had a polar solvent, the components in here that are polar would stick to those polar solvents more strongly and move farther with them. If we had a non-polar solvent, the parts of the mixture that were non-polar would stick to the non-polar solvent and travel further. Right? So this is a key understanding here. The particles in our mixture that have a polarity which matches the polarity of the solvent will travel farther. Okay. So here's the setup. Let's look at how this would look over time. So we would start. This is the beginning of our experiment, and after I just made up some arbitrary time, so let's say 30 seconds. What we're going to notice is that our solvent started to move through the paper. Okay, and as it passed this line where we initially had our mixtures, it started to separate out the 2 components of the purple, the 2 components of our orange, and the 2 components of our green. And as another 30 seconds goes by, we have more of our solvent moving through the stationary phase, and we see further separation of the component parts of our initial mixture until we get to a point where the solvent is somewhere near the top of our chromatography paper. We would not want it to go off. We certainly don't want the pigments or whatever our samples are to go off of the paper, and so we would probably stop the experiment. 90 seconds seems a little short. Maybe it could be something closer to 5 minutes. We would just take a note of what the time is, and we'd be watching this to make sure that our solution here doesn't go off the top of the paper. Okay, so this shows us that we absolutely had mixtures to begin with, and these mixtures had component parts that seem like they're kind of similar to one another. Right? If I looked at this purple seems like it's made up of a red and a blue, and it seems sort of to me like I could probably make an argument that because these look like they've traveled about the same distance, they seem like this red that came from the orange and the red that came from the purple seem like they're pretty common or pretty similar. But I could take it a step further by trying to do some mathematical analysis of this. Right? So some measurements I would make is first of all I would be really clear on where the origin is, and so typically you would make a mark on your chromatography paper with a pencil or with some sort of a mark on there so that it's clear to see what is there, but it doesn't have to be with ink that's going to travel along with whatever your sample is. And then we're also going to measure the line up here, which we would call the solvent front. So how far did the solvent travel? And we would come up with the measurements here, and then we're going to calculate something that we can measure the distance that each of the pigments travels here, right? And we're going to measure something we call the R factor, okay? And this is defined as the distance that's traveled by a sample. So here would be, we're going to calculate just for red, the distance that's traveled by red as compared to the distance traveled by the solvent. Okay? These numbers always going to be less than 1, and what we would see is if we measure these 3 different things, we should probably get 3 different numbers that are each kind of a percentage or a fraction of the total distance that was traveled. Okay, so if we wanted to find what is the R factor for the red pigments, the distance traveled by the red sample divided by the distance traveled by the solvent, right? And what we would do is we could calculate for both of these samples, and if the numbers were within an acceptable margin of error, then we'd say that that's further evidence that those dyes are the same, or that those samples are the same. We could do the same thing for yellow. We would just take the distance that was traveled by the yellow sample as compared to the distance traveled by total distance by the solvent, and we would compare our answers here, say are these similar? And finally, we could do the same thing for blue. Okay, so that's how chromatography works. We're going to calculate an RF. We said earlier there's a couple different ways to do it, but this is the most common way that students would do it in chemistry classroom, and I've seen a couple of different versions of this asked on AP chemistry tests in the past, and they're all related to this form. So I thought that this would be a good lab technique for us to review together. The second experiment, the kind of separation technique that was suggested that we review here today is distillation. In our distillation, we're going to be looking at a mixture, but again, this mixture must have 2 different component parts that have different boiling points. And what we're going to do is we're going to be able to separate them based on the fact that they have different boiling points. And so you have a setup that looks something like this setup over here on the right-hand side of the page. You have a heat source over here. Your sample goes into this container on this side. And what we're going to do is we're going to slowly heat this mixture to a temperature that is in between the boiling points of the 2 liquids. And I'll give you an example in just a minute, so stick with me. And what will happen is the solution that will boil first, the solution that's at the smaller temperature, not the solution, sorry, the liquid that is at a lower boiling point will boil first. As it rises through here, will reach its temperature, and then this is called the condensation tube. It has cold water coming in here and then being released out here. So you've got a continual source of cold water, and it's going to continue to cool off our gas vapor. As it cools off, it will fall down into here. So we have gas that's boiling here, it's condensing as it falls through here, and then it collects over here. And so now we've had a separation of our two different solutions. Let's look at a little bit more specific example in this picture. So let's say we have a mixture that has solution 1 with a boiling point, liquid 1 with a boiling point of 75 degrees Celsius, and the second liquid has a boiling point of 150 degrees Celsius. What I would probably do is heat the solution to something like 85, maybe 90, something that is certainly above the boiling point of the first part, but below the boiling point of my second part. And what I would see as I did 85 degrees Celsius, I would notice that I would see some gas vapor that starts to rise, goes past our temperature, our thermometer, and we would notice the temperature on here probably staying pretty solid at 75 degrees Celsius. This temperature is not going to get above 75 till all of that has boiled off. And then it will start to condense in here. And that condenses again because we have some cold water coming in through here, and the cold water is then released out on this side. We have a tube that's probably connected to a sink on this side, and then it goes down the drain on this side. Just continual stream of cold water that keeps this cold, keeps our gas condensing over here, and it finally falls into our receiving flask over here. So we end up ultimately with, if we did this perfectly, what we talked about yesterday, perfect magic chemistry land. In perfect magic chemistry land, you would have solution 1 is all in the receiving flask on the right, and solution 2 all be in this original flask. Okay? And now we can continue to analyze them, or we could just say that we have separated our two different solutions using distillation. Okay. Here's a problem that came off of a recent AP test, I believe. Student performed a distillation. In this case, instead of having just one, go back here, instead of just having one receiving flask, what the student did is they collected up all of the solution or all of the liquid. They call it the distillate. Thank you. There's that vocabulary word I was missing. The distillate from temperatures from, let's say, 15 through 100, and then they switched out real quickly the flask and they collected a different sample. All of it was at about 100 degrees, 98 degrees Celsius. They had a third sample that was for anything that was produced while the thermometer read 100 or 98 to about 125, 128. And then lastly, all of the solution was here. Okay, so this would be the same setup, but 4 different flasks that collect up the data. So I collect up the solution, the distillate. Over what range should the student collect the distillate of the compound with the stronger intermolecular forces? I told you we're not going to get away from these stronger intermolecular forces. So we should be able to read this and say, all right, we have clearly two different boiling points here. So this is one of the liquids has a boiling point that I would say is about 99 degrees Celsius. Okay, it looks to me like it's a little below 100, maybe 98. But this part right here is the first solution we're going to want to focus in on the second one as well. That is a boiling point I would say of about 128. And so our choice is really between those two. These are either some sort of mixture, maybe some impurities, all sorts of things that are happening in both of these diagonal sections. What we want to focus in on is the flat lines. So then we're just going to compare: is solution B or flask B have stronger intermolecular forces, or does flask D have stronger intermolecular forces? Think about that just for a sec. And the answer should be clear that the second solution, this one, has a higher boiling point, has stronger intermolecular forces. The reason why it has a higher boiling point, it takes more energy to break apart the molecules, or to change the molecules from liquid into gas. So that stronger intermolecular forces, would equate to a higher boiling point. All right. Lastly, we can talk about solubility, and I'm going to pick up on a little bit of this tomorrow, looking at what our time is here today. But our big learning here is that substances with similar intermolecular interactions tend to be miscible, which is just another word for soluble, or able to mix together with one another. Okay. So we look at a classic experiment like this. If I was in my chemistry lab and I had access to all of these things, I would show these to you so we could mix it up, because it is kind of a fun activity to watch happen. If I put a piece of iodine, solid iodine, in water and I shake it up, we're not going to see that iodine really dissolve well in water. So you would typically just see the piece of iodine sitting at the bottom of the container. It would be in a colorless solution. We would just have water, right? So it doesn't appear to be a lot of mixture that's here. Whereas I put the same piece of iodine in a solution of C6H14, that's a liquid, and I see that the iodine mixes in, dissolves in, and makes a completely purple solution. And so the learning here is that iodine is a nonpolar molecule and water is a polar molecule. So we would not expect a nonpolar molecule to be soluble in a polar solvent. However, when iodine is mixed with C6H14, this is another nonpolar molecule. We do expect the two nonpolar molecules to be able to interact better and to be soluble in one another. So iodine and C6H14 are both nonpolar substances, and the water is polar. So the diagram shows that the iodine dissolved in the CH4 but did not dissolve in the water. So this is a great example. Remember yesterday we talked about when you're giving an explanation for a diagram like this, we want to make sure we talk about all of the chemicals that are present. So we're not just going to talk about the solution on the right. We're going to talk about both or all three of the chemicals here: iodine, C6H14, and water, to make sure that we're really showing off all the chemistry that we know. Last question for today would be to look at which of these we've got three pairs of molecules, and you probably have a picture of my head up here on the top over here. So I'll tell you that this molecule in the top right is a nonpolar. It's just a hydrocarbon, carbons and hydrogens. There's no oxygens left in there. So of these three pairs of molecules, we call this A, B, and C. Which would we expect to mix together? Which would we expect similar to what we saw in the last? If we put them both in a test together, which would we expect to mix together? And the answer is that we would expect just this middle solution, this middle mixture, to be able to mix together, because both of these are non-polar molecules. Right? Here we have an OH with a hydrocarbon, so this is a polar with a non-polar, would not mix together. This is actually a non-polar as well. The only has the chlorines because the chlorines and the electrons are equally distributed around the molecule. This would this would behave much more like a non-polar molecule than a polar molecule, and so they would not mix together. And that brings us to the end of our lesson for today. That was a lot of, like I said, a lot of lab techniques that I thought were some pretty cool ones that I wanted to share with you. So apologies for rushing through a couple of explanations, but seeing what chromatography and distillation look like, and the use of the Eudiometer, we're collecting gas over water, I think are three important things for you to have some experience with before we end this year out. So I want to make sure we put some time into those. Great practice problems for today, for tonight to look at will be our warm-up for tomorrow. I will be going through the solutions of this. This is from the 2017 free response exam. I hope this looks familiar to you. The two quick questions that are there at the bottom. So I would take a screenshot. We're going to ask which of this dye is least polar, and in the unknown, how are we going to compare the unknown to one of these three over here? Okay? And then I would like you to take a look at these two practice problems and see if you can solve each of those using the molarity equation. Okay. Quick reminder to go back to apcentral.collegeboard.org anytime that you need to get any questions. Those will be continued. That's where it's continually updated. Also remind you that we have some links at the bottom of the page for any other resources that you need. Lots of other resources. And remind you or your friends, anybody who has internet access, or that has a question about internet access, or is not able to use a device on a consistent basis, go to cv.org/tech, and they will be able to get some help directly from College Board. Thanks so much for watching us today. We had a great time sharing this information with you. I hope you're doing well, and we'll see you again at this time tomorrow. Have a great day. Bye. Good morning, AP Chemistry fans. Thanks for joining us for another live lesson in AP Chemistry. This is Mr. Byrne coming at you from outside Chicago. I teach at Lombard West High School, and I know there's a lot of Hilltoppers out there that are taking part in these lessons throughout the past couple of days and weeks. Today is Wednesday, April 8th, 2020, and we're going to, I think, finish up our conversation of Unit 3 on intermolecular forces and properties. We started this by talking about gases, then we talked about solutions yesterday, and we're going to talk a little bit more about atoms and molecules, and do another great lab experiment today, talk about one of the classics that is important for you to have experience with. Okay, so some great stuff planned for you today. Quick reminder to make sure you're checking apcentral.collegeboard.org for all the latest updates. Here's our testing date, Thursday, May 14th. We have a big star on the calendar for that day. Here in Chicago, we're in Central Time, so we'll be taking it at 1 o'clock. Remember, we all will be taking the same free response response test at the same time. So these times are local times. So you just want to make sure that you are aware of when your local time is associated with each of these. The alternative test is something you want to talk to your teacher about. Excuse me. Just make sure if you are not able to make the main test, you'll talk to your teacher or administrator of your school about getting your testing date switched to one of these dates. Our format that we went over yesterday, but just to repeat, remember there will be 2 questions that you'll have a total of 45 minutes to look at. We have 25 minutes to read and respond to the first question. That gives us to 30 minutes. Once you submit that first question, you'll be given the second question, but you'll not have time to go back. You'll have 50 minutes to read and respond to question number 2, and then another 5 minutes to respond. Okay? Or, I'm sorry, to upload your response. We're still waiting on some more information on exactly how that will be distributed to us, and as soon as we have that, Mr. Fairbar and I will share that with you. But what we do know is that the format of the questions that we've been giving you for homework, we fit really nicely into each of those kinds of questions. And then one of the reasons why we're being really clear to talk to you about the skills that are necessary to be successful in chemistry is because we know that the questions will give you some sort of system, some data, so that you can shine in your ability to explain the phenomenon using models, theories, and representations. You're going to be able to draw conclusions from the experimental results, to identify and explain procedures that are aligned to question. You'll analyze a system with quantitative reasoning, so we'll do some numbers. We're going to look at sources of error. Don't forget that one. We're give you experience of that today. And then we're going to work clinical evidence and reasoning. So all of these skills are things that are important in all of our science classes, and you'll have a lot of opportunity to talk about those today. So let's get into our lesson overview for today. We will review our homework problems from yesterday. Then we will be looking at some pretty heady stuff in these 2 topics: spectroscopy and the electromagnetic spectrum, the photoelectric effect. I'm going to apologize already to our physics teachers out there in our physics class. If this is something that you're really excited about, you should absolutely make sure that you register for physics next year or some class in the future. Do some more reading on this. For time I had to condense this into 45 minutes on all 3 of these topics. We certainly could spend more than an hour on probably each one of them. So we're going to go through exactly what we need to know to be successful on our exam and do some little background so it makes sense to us. At any point I'm speaking too fast or you want to take a breather, feel free to stop. Make sure you have a pencil and paper next to you to be able to take some notes and maybe do some of the practice problems as we're going to that. So let's get to our warm-up, which is our review of our homework problems from yesterday. We were looking at a free response question from 2017 on paper chromatography. We had 3 pure dyes. Okay, so since we were given to this test was a pencil and paper, of course we didn't have colors here. So you may want to go back and review the version of this that I gave you yesterday where we had 3 different colors. Okay, this says that these are pure dyes, and so in this case we didn't necessarily have mixtures. We're just going to do a comparison of what's happening to each of the 3 dyes that are here. So there'll be a difference between what we did yesterday and what we did today, but the same principles are going to apply. And then you have a non-polar solvent that is going to travel through the paper to what is identified over here as the solvent front. Okay, so we talked about the stationary phase and the mobile phase. Those are words that would be nice for you to know, nice for you to remember. But the fundamental principle here is that we have 2 chromatography chambers. We have 3 knowns that are going to be left in here. The knowns will distribute themselves like this. The unknown will travel up the paper like this. We are aware where the origin is. 2 other important pieces of information that this problem gives us: that the chromatography paper is a polar material, and that the solvent is non-polar. Okay, so you can see how we're really building on a lot of the themes, a lot of the ideas that we've been talking about over the each of these lessons throughout kind of a mini review of the entire year. So remembering what a polar or a non-polar material is, how that would affect itself in a non-polar or in a solvent. This is important idea for maybe you to take a second to stop, review, and go back and look at the previous lessons on that. So our first question asks which dye, A, B, or C, is the least polar. When I want to identify our answer in terms of, or justify our answer in terms of the interactions between the dyes and the solvent, or between the dyes and the paper. So I'm going to zero in on the data that we had here, or the diagram that we have here, and I want to remember that I have identified that we have a non-polar solvent. So when we're looking at the 3 dyes over here, and we see how they traveled up the chromatography paper, we know that the non-polar solvent traveled from here all the way up to the top. And so what we want to consider is which of these 3, A, B, or C, is the least polar. Sometimes I like to think about it as which is the most non-polar, which is going to be most attracted to this solvent, right? So the one that's attracted to the solvent most would be dye C. It travels the furthest with this non-polar solvent as it travels up the paper. Dye B was not as attracted to the non-polar solvent, or was more attracted to the paper, which we were told was polar, and so it didn't travel as far up the paper. So our good response here would be dye C is the least polar. We're going to be really clear on our answer is this is because it traveled farthest with a non-polar solvent. A non-polar dye is more strongly attracted to a non-polar solvent. A non-polar dye is least strongly retained by the polar paper. Okay, so any of that, you definitely need to include both of these sentences in the scoring guidelines. Either of these 2 sentences, either saying that the non-polar dye is more strongly attracted to the non-polar solvent or least strongly retained by the paper, was acceptable, but you did need to identify clearly what the dye is and then give a clear explanation of why. Okay. Our second question asks us which dye is present in the unknown sample. So we're told that this unknown matches up with one of these guys over here, and you can see that because the solvent front did not travel as far, this unknown did not travel as far as well. We can suggest a couple of different reasons why this solvent front did not travel as far. Perhaps it was left in the solvent for a shorter amount of time. A couple of other reasons. I would suspect for this one they wanted to make it interesting for us. We couldn't just draw a line across and match up. If we drew a line across and match up, we would be left with something that's right in between. And so we want to have more of a quantitative way of analyzing what's happening in the unknown and comparing that to what's happening in each of our knowns, dye A, B, and C. And that's where we would come into our measurements of the distance that the unknown dye traveled as compared to the distance the solid front traveled. And what we call that is the retention factor, or R sub f. And here, even without an exact number, without a ruler in front of me, it seems pretty reasonable that this is pretty close to 0.5. And so I would suggest that we would let's estimate that number right now. 0.5 doesn't have units. It would be distances that would cancel each other out, right? So it's just a straight up number. We're going to estimate it for right now and see if that helps us to get to a clear answer compared to dye A, B, and C. And if we need to get more specific with it, then we would get a ruler out or something like that. So I'm just going to go from right to left on our known dyes, and I would look at dye C. Okay, and this to me, I would estimate at about 0.75. It's clearly significantly more than 0.5 to me. And drawing out my arrows like this makes that pretty clear. The next one over dye B, I would estimate as about 0.25, so clearly less than half. I can see where this is going. The dye A looks very clearly the ratio of the distance that dye A traveled as compared to the distance the solid front traveled is very similar to what our unknown did. And so a really good explanation for this would include 2 pieces of information. First, that dye A is present, so we've correctly identified what is the unknown. And then here are the 2 different ways that the scoring guidelines justify the answer. The unknown sample moves to a position that is midway between the origin and the solid front, and so does dye A, right? So that's a little more qualitative, not quite as quantitative, saying the same thing as we said. But I like that second explanation. Dye A has a retention factor that's close to 0.5 on the chromogram with the with the 3 dyes, and the unknown also has a retention factor close to 2.5. So I would have gone, I'm comfortable with that second one a little bit more, but we need to have some clear justification that is there. And it would have to be in terms of the relationship between the distance traveled from the origin by the unknown and the solid front. You wouldn't want to say something like, oh, this would keep traveling up, and so this dye would keep coming up, and then it would match up with dye A or something like that. That would not be an acceptable answer here. We want to have something that's a little bit more in line with what we do, what we know happens with that retention factor. Okay, so there you go for your first exam or warm-up question. Our second one had to do with aspirin that's dissolved in enough water to produce 200 milliliters of solution. So what's the molarity of aspirin in 50 milliliters of this solution? So we're going to start handle the first part first. Let's look at the fact that we know molarity is equal to moles of solute over liters of solution. We reviewed that yesterday. So our moles of solute are 360 grams. I made a mistake there. Look, I just checked on that. So we're going to do some quick math in our heads, and let's see if we can. We're going to edit this live as we're going through here, guys. And so we're going to have 0.002 moles of our solution. So we're going to convert that milligrams into grams right there. And we divide it by 180 grams, gives us 0.002. That's going to change this answer up here to 0.002, right? And so I'm going to move my decimal point over because, guys, we're going to be talking about this. That we're not changing our answers last week. Okay. So I will go back and we'll get a note out to you guys to make sure that I did that correctly. Sorry about that. So we've got 0.02 moles. We're going to fill that in up here. We get a 0.010 molar solution of aspirin in that original solution. Right now, the question though asks, what's the molarity of aspirin in a 50 milliliter sample of the solution? And that sounds like it's a trick question. It sounds like we're going to have to do some more calculations. But what we want to remember here is we were just pouring out 50 milliliters of this 200 milliliter solution that was already there. So whatever the molarity of the solution is, the molarity of the 50 milliliter solution stays the same, right? It would be as if we had a beaker with 200 milliliters. When I pour 50 milliliters of that out, the molarity does not change. The molarity stays the same. The molarity would only change if I added water to it or if I evaporated some water out of it. But because the way it's written, I read this as we're just pouring out 50 milliliters of the same solution. We're going to say that our final solution here is 0.010 molar. That's the molarity of the aspirin in the solution. And we're going to jump through that slide real quick for my mistake. I apologize for that. Here's the mass. This looks very similar to what we did before. I just wanted you to have another experiment. What we did as one of the practice problems during class yesterday. I wanted you to have an experience of this pentahydrate, copper 2 sulfate pentahydrate. So we know that moles are equal to molarity times liters solution. So we're going to end up with 0.025 moles of CuSO4 is what we're looking for, but we need to multiply that by the molar mass of copper 2 sulfate pentahydrate, right? So we're going to make sure that we include all of this in here, and we should get to something like 6.24 grams. All right, that was exciting, making some changes on the fly, but hope that we got the right answer out there to you. Let us know if we made a quick mistake there. But let's go into our discussion of our 3 topics and a couple of guided practice problems. We'll talk about the spectrum, talk about the photoelectric effect, and then what's sometimes referred to as Beer's law or the Beer-Lambert law. Both of them are pretty familiar. Let's look at some spectroscopy and electromagnetic spectrum. We're explaining chemical properties here. Okay, we're explaining phenomena. We go back to what we'll have to do on the AP test, given some theories, models, representations. We want to make sure that we understand what's happening in this phenomena as a way to explain what's happening in the model. Okay, so one of my favorite days in chemistry classes when we get these glass tubes out. And what's happening here in these glass tubes, I hope that you have an experience of something similar to this. It looks a lot like a neon light, right? But instead of being neon on the inside of this, this is hydrogen gas, and a current is run through it. So this is put in an apparatus that's plugged into the wall. It would look to you, if you were in a classroom, very much like just a kind of a straight boring neon light that doesn't have any shapes or letters or anything in it. But what your teacher would probably do would be either give you some glasses that have prisms in them, or give you another apparatus that will help you to spread out this light, put it through some said prism. And what you would see on the side of this is these really cool bands, these cool bands of light that are at very specific ranges. And what we know is happening as we put this energy through here is that electrons are jumping around inside the atoms of hydrogen, and they're producing very specific quanta of light that we're not getting out all sorts of the whole broad spectrum of light. As these other colors in between here would just be some sort of interference. Well, we can see if we look at this at through a prism, as you have a band here that's kind of purple, one at blue, one at teal, one at red. And if this was done in a classroom, it would look almost, I'm not going to say I did not take this picture, but I have seen pictures from my classroom or when we've done this experiment in my classroom. It looks very much like this with the interference in the background. If it is done under much more controlled settings, what you would see is something that looks much more like this. And I'm going to have you zero in. I'll come back to this slide in just a minute. But if we zero in on just the electron spectrum for hydrogen, what we can see is those same bands. So here's a purple, here's a blue, here's a teal, and here's a red. So this is obviously a stylized and a perfect magic chemistry land kind of version of what was happening in hydrogen. But what this is telling us is something very specific about how atoms work, and very specifically about how energy works when it interacts with an atom. And what we know can happen is that as a photon of light, okay, a photon of energy, in this case that would be the electricity that was given to the sample, comes in and hits an electron. Here's our nucleus. Here's an electron. This one happens to be on principal energy level 2 here. Okay, so its energy is this electron absorbs an energy, a specific amount of energy. It can jump up to a higher principal energy level, right? So it goes from 2 to 3, and then after a certain amount of time, it will emit that. It will release that energy. Will fall back down to its ground state. We would call this the excited state for the electron. Jumps up here to the excited state, hangs out here for a little while, and then when it falls back down to its ground state, it would release the same amount of energy that it absorbs. Okay, and so what we see here is that there are very distinct amounts of energy that hydrogen absorbs because it only releases specific distinct amounts of energy. It releases, at least within the visible range, the visible spectrum of energy, it only releases these 4 bands of light, which would correspond to what we would a lot of experimentation has found is jumping between some very specific energy levels. Turns out that the distance or the difference in energy between principal energy level 1 and everything else is such a great amount of energy that it releases ultraviolet light when that electron falls back to the ground state in principal energy level 1. When electrons from the second principal energy jump up and fall back down, they have this is where they release the visible amount of light, and we have 4 different bands here that correspond to the 4 bands that are right here. And then we know that electrons could jump back and forth between other energy levels, and this could continue going on forever. Now I hear some of you out there saying, well, we know hydrogen only has 1 electron, so isn't that 1 electron always in the first principal energy level? We would typically say, we went back to electron configurations from last week, we'd say it was 1s1. We'd say that if we draw a Bohr model, we put it here. So this is what's happening here is that electrons are absorbing more and more energy, or multiple atoms of hydrogen are absorbing energy. They take it up here and then come up here and they're falling back down in predictable ways. And so to get up here might absorb some energy, to get up here would absorb a little more energy, would release this, and then it would release this. And because in a sample of hydrogen that's as big as we have a huge number of atoms of hydrogen, we're going to see all of these things happening. So this 1 electron that's happening here would be releasing energy every time that it fell from any of these different places. I like to give my students the analogy of like stairs in the school, and we're a school that is 5 or 6 stories tall, and so I can jump from the first step to the second step, I can jump from the first step to the third step or to the fourth step. I can't jump directly from the first step to the 7th step, but the 7th step is still there, right? And if I had a couple of extra, if I did 2 or 3 jumps, I could probably get there. And a similar analogy would be at like for electrons. Hydrogen typically only has filled energy levels that are at the lower levels, but when we give it extra energy, those energy levels are still there and can be briefly occupied by electrons at the excited state. So let me go back to this picture from before. We have hydrogen right here in the middle with our 4 bands. Sodium has more bands, calcium. So as our atoms get much more and more complicated, they have more energy levels, they have more electrons. They can be jumping out all over the place. We're going to see some that match up, but we're not going to see electrons that or bands that match up precisely every single time. But what we see time and time again in all of these diagrams is that the energy is released in very discrete amounts of energy, and that we don't have just a full spectrum that says the electrons can jump up any amount and jump down any amount. We see there's a big hole that's right here that says, at least for these 4, there's not an energy level that's being filled. So these diagrams they seem pretty simple with just a couple of bands in it, but the understanding the chemistry behind them is pretty complex, and kind of cool thing helps us both to understand how the atoms work. It tells us actually why like a Bohr model in some cases is a nice model. If we think that electrons travel around the nucleus like the planets travel around the sun, well, no, we know that doesn't happen. But if we want to be aware of the distinct amounts of energy that electrons have as they're going out on these energy levels around the nucleus, this helps us understand those distinct energy levels. Those are not places in space, but they are energy levels. I think are cool and a nice part of our nice understanding comes from the Bohr model. Here's the entire electromagnetic spectrum. I imagine that this is something that you have seen multiple times in other places. We know that the spectrum is arranged all the way from wavelengths that are very, very small. So our peaks would be very, very close to each other over here. So wavelengths that are very, very long, 10 to the 5th series of 1,000 meters between the crests, the peaks or the crests. We know that increasing wavelength, so the distance between waves is longer on this side. There's a greater frequency over here, so more waves are hitting when the waves are closer to one another. And then over here, we would have more energy. The waves would have more energy, right? So this is typically what we call gamma rays, X-rays, ultraviolet rays. You can read this yourself, but just understanding how these are all connected to one another is something that would be great for you to have. This infrared, I always connect infrared with red light and ultraviolet with violet light. Most students have that down, but any still check. Okay. The learning that the College Board identified for us in this topic was how the difference in absorption or emissions of photons in molecules will relate to the type of motion. And so I want to jump over real quick and encourage you to do this again. We've used these simulations a number of times where we look at the FET from the University of PGT from University of Colorado. I think there's some really interesting things, and you could spend an hour just playing around with this and get some really good learning on it. And so what I'm doing is we can select different molecules over here. But I'm going to just look at carbon monoxide, and we're going to imagine what it's like if we bombard this carbon monoxide with microwaves. Okay, and we know that microwaves don't always behave as don't have those results like that, but it's a little bit easier for us to see how they interact. Even so, the sound you see what just happened there, that one absorbs a microwave, and what's it making it do? Oh, that molecule is now spinning around, it's rotating. The other microwave is just kind of going past it, okay, until it emits. So it absorbs the microwave, it then emits it, and it stops rotating until we grab onto another one, and then it can rotate and rotate again until it emits it. Okay, let's see what happens when we instead bombard this with infrared waves. Oh, so a similar thing is happening in that it is absorbing and releasing this amount of energy. Okay, but the type of motion that's possible here is different. Now this molecule is vibrating instead of rotating. Wait for one more to do it. There we go. We got some vibration happening there. Okay, just super interesting thing to see. I'm going to turn this off before I change my amount of energy. You can look at visible light. Okay, there's one infrared particle that was left, infrared wave that was left there. That's where that last was shaking. But we see visible light is not causing either rotation or vibration, and ultraviolet is similarly not rotating or vibrating this molecule. Okay, but jump down to water. Let's turn this off. Just remember, we're going to go back to microwaves. Okay, we're going to change our water molecule. We're going to bombard this with microwaves and see what happens. Oh, look, that looks very similar to what happened to carbon dioxide or carbon monoxide, right? So we're going to see that this rotational motion is happening here. What I predict might happen with infrared. Based on what we saw with carbon dioxide, I might predict that infrared is going to cause some vibrational motion again, and that's what we see happening here. Okay, visible and ultraviolet light are not doing anything similar. Now, because we have just a second here to analyze this a little bit more, I'm going to pull up nitrogen and go back to our microwaves. And what we saw happening with microwaves and carbon monoxide was some rotational motion was happening, that these microwaves are causing the molecules to spin around or to rotate in predictable ways. And that's not happening for nitrogen. Interestingly, would not happen for oxygen as well. So thinking about a difference between carbon monoxide here, so carbon monoxide and water are both spinning around in a microwave, but nitrogen and oxygen are not. So it'd be great to think about what's a difference between the molecules of what's similar about carbon dioxide and water versus what's happening with oxygen and nitrogen. Let's just for fun, let's look at infrared as well. We see a similar thing happening, no changes, but carbon monoxide is vibrating and water is vibrating as well. Okay? And the answer here is that we know that nitrogen and oxygen are nonpolar molecules, and so they're not affected by these waves in the same way as carbon dioxide and carbon monoxide. It's like water and carbon monoxide, because water and carbon monoxide are both polar molecules. Okay, so the learning here that microwaves are causing transitions on rotational levels. That's what we just saw in those molecules. Infrared radiation is causing transitions on vibrational levels. That ultraviolet and visible radiation are causing electron energy levels that we were not able to detect, at least in that simulation, but would still be happening. So we would connect. These are let's go back. Excuse me, just for 1 second. Okay, so infrared and microwaves as compared to ultraviolet rays. So when we get to those ultraviolet rays, these are the higher energy rays. They're going to get deeper down into the electrons instead of rotating or vibrating the entire molecule. Okay, so this would be a great opportunity for you to stop and go into that and play around with that activity. That one is called molecules and light. We're going to look at another one in a couple of minutes. So feel free to pause and go into that, and we'll see when you come back to join us in a couple of minutes. The photoelectric effect is going to help us again get a better understanding of the calculations behind some of the observations we just saw. So there was no quantitative data that we really looked at here up to this point, but we're going to talk about absorbed and emitted photons. What's the relationship between their quantities? And we have a couple of equations that we're going to want to take a look at. So we know that a photon is absorbed by an atom or molecule. The energy is increased or decreased by the amount of energy equal to the photon, right? So that's kind of a common theme that we've seen in a couple of different ways over the course of these two different simulations that we did. Either those pictures or the simulation. The wavelength of the electromagnetic wave is related to its frequency and the speed of light by the equation here. So this is an equation that's given to you on our equation sheet. So C, which is the speed of light, lambda. So this is not an upside down line. This is the Greek letter L. This is the wavelength. So I'd like to think of wavelength and lambda go together. So that V is the frequency, and the energy of a photon energy is related to the frequency of the electromagnetic spectrum through Planck's constant. So V is consistently frequency. So H is Planck's constant. Again, the speed of light and Planck's constant are two things that are given to you on the equation sheet. We're going to see how we would use those. So here's a question that came from a sample set that I have. Diagram to the left represents the photoelectric effect for a metal. Okay, so this also kind of explains what the photoelectric effect is. Metal surface is exposed to light with increasing frequency, and what we would expect is increasing frequency and energy of photons, right? So as this energy gets greater and greater, increasing frequency, at a certain point, electrons will first start being emitted from that metal. There is a FET simulation on it, but it wasn't working on my computer, so you can certainly go and play with this. But I think this diagram does a nice job of explaining it as well. We've got energy coming in here. We have to get to a certain threshold amount of energy before we can emit electrons. For the sample that was given to us here, that threshold is 3.3 times 10 to the minus 19 joules. So we're asking, if this is the amount of energy, what's the frequency of light that's associated with that energy? We're going to look at our equation sheet. We have both of those equations here. We even have those equations spelled out in terms of what their meaning is. And so the uninteresting thing here is that we can just solve for the math. So we're going to say the energy is equal to Planck's constant times the frequency. So we have two of the values we're looking for the frequency. So we're just going to rearrange our equation to say that frequency is equal to E over H. And we are left with a frequency that is in 4.99 times 10 to the 14th wave per second, right? So this is the units on our inverse seconds. So we divided this by joules times seconds. The units on Planck's constant here are sort of strange, so just take a note of that up here. But the joules will cancel each other out, so we're left with inverse seconds because the seconds are on the bottom. And we would expect frequency to have a number per second, right? We can take this a step farther and say, well, what color, what's the color of this light? So if our frequency is 4.99 times 10 to the 14th, what color would that? So we need to correspond that. We have to be given, right? You wouldn't be expected to memorize this, but if you were given a chart like this and said, here's the wavelength of light, what color is the light that has this frequency? We're going to use the speed of light, and what our frequency is, again, our wavelength is equal to C divided by V, and we get to something like 6 times 10 to the minus 7. The tricky thing at this point would be to remember what our conversion between meters and nanometers are. This is what we just got here in this answer. Meters here would carry down, so we have meters. How do we convert from meters to nanometers? Well, we know that there are 10 to the 9th nanometers in a meter, and so 6.0 times 10 to the minus 7 meters is equal to 600 nanometers, and so we have orange light. Now let's get into Beer's law for a quick couple of minutes here. I'm going to zoom through this screen because I think we can do a little bit better job of explaining what Beer's law, the Beer-Lambert law, relates absorption of light by a solution to three variables, and we have that equation that's right there. Typically, we'll not have to use this equation as much as you would have to interpret data for Beer's law kind of a lab. So I'm going to jump ahead to this next screen. We're going to look at the FET for just a quick minute, and then I'll give you your homework, and we'll do a couple practice problems before I give you your homework. So here's our equation that talks about this idea of absorbance. So absorbance is a measurement of how much light. So here in this setup right here, we have our testing solution is right here. We're testing a solution of cobalt 2 chloride, and we want to know when a specific wavelength of light is shined through this sample, how much of it is absorbed by the sample. So what this is saying is, in this particular experiment, with everything set up the way that it is, when a wavelength of light, when light with a wavelength of 549 nanometers is shined through the sample, how much is absorbed by the sample? So we're going to compare how much went in to how much came out, and in this case it's 0.72. Okay, there's a constant that is related to every different solution. We don't typically use that as much. We look at one solution at a time, and so because that's constant, we just leave it alone. B is always related to the length of the sample, and I'll show you how that might make a difference. And then C is concentration. And so what an experiment will typically do is we will leave this epsilon and B the same. We won't change what the solution is. We won't change the length of the solution. We'll use what's typically called a cuvette, which is like a very small test tube when we put it into this detector. And because the length of this doesn't change, these two variables stay constant. We can say that there is a direct relationship between the absorbance and the concentration, and that's how we set up an equation like this. So just for fun, for a minute, I looked up, I guess on Beer, they call it Beer's law. We'll go to the same solution. We can look at multiple solutions that are here. Okay, I'm going to put my concentration all the way down at 0. I'll leave this as preset, but you can play around with what would happen if you changed the wavelength of light. They choose a wavelength of light that's optimal here. We have 100% of the light is transmitted, which means that 0 of it is absorbed. Okay, so transmittance and absorbance are versus one another because our equation looks at absorbance. We're going to keep it here. And I'm going to come down to the bottom over here, and I'm going to increase my concentration of cobalt chloride in my cuvette. And what I should notice is that my absorbance, you can just see that the color of the solution is increasing, and we should see that the absorbance is increasing as well. Okay, and for this setup, we can actually get to an absorbance that's above 1.0. But we'll leave it alone right there for just for a second. What we would notice if we increase the length of this, right, more of the solution, more of the light is absorbed because we have more solution here. And if we decrease the length of this, we would see that less of the light is absorbed, which seems to make sense because there's less particles in here that would be absorbing this light and preventing it from getting over to our detector that is over here. And it's important to note that as we're looking at all of these solutions here, okay, even if we have Kool-Aid mix or whatever, all of these have different colors. And this type of experiment is only for solutions that have a color. We cannot use this method of analysis on a sodium chloride solution or something that would be clear without having a color on it. Okay, so this is something we could play around with. The kinds of questions that you might be asked to consider would look like this. So a student is trying to determine the number of moles of iron 3 in a solution, and so they add potassium thiocyanate to the solution, and they convert it to potassium thiocyanate. So they convert all of this stuff into iron thiocyanate, which is FeSCN, and this stuff has a dark red color. Okay, so here's the key. What the student does is they make let's see, 1, 2, 3, 4, 5 solutions that have very known concentrations, right? So they know exactly how much of each of these concentrations they put in here, and they measure the absorbance at 453 nanometers. So we looked at a different wavelength of light in that simulation. Here is one that they represented or they determined was optimal, and we're able to see the linear relationship, right? We even have another data point down here. When there's no solution, we make sure that there is no absorbance, right? So if it was just plain water, here it would be our control. And so here's where we see this direct relationship between the absorbance and the concentration. And so the kinds of questions that we would want to ask is the absorbance of the unknown, right? So we have an unknown solution is 0.2. So what's the concentration of FeSCN at that point? And so this is just an exercise in reading the graph in order to answer that question. So we would see that here is absorbance 0.2 where it meets our trend line, and we would read down and we would estimate that the concentration of FeSCN is 4.0 times 10 to the minus fifth. Okay, and then the second question is how many moles of Fe3 plus were present in the sample. So we know that moles is equal to molarity times liters of solution. So we're going to convert that in milliliters into liters, and we're going to say that our moles of FeSCN is 5.0 times 10 to the minus 6. And in this case, because our mole ratio is 1 to 1, right, we can say that that's equal. I didn't put in my conversion factor right here, but that might be a good idea to add that in, or just make a statement in here to say that that's equal to this, and then maybe write a sentence. We have a 1-to-1 relationship between FeSCN. Another interesting question that I saw was to think about experimental error, right? So the student did a similar experiment, and where they had some standards, so they knew what the concentrations of the solution were, or at least they thought they did, and they got a graph looks like this. And look, we have 4 data points that are really clearly on the line, and one of these seems like it's kind of off, right? And so the question is, like, what's a possible experimental error that could have caused this point to be so far off the line? Now looking back, I'm going to go to here. We clearly have some estimations happening. We have this is not perfect magic chemistry line over here, but when we look at this data, we got 4 pieces of data, one that's pretty far off, and we want to think about what is a possible source of error that might make that happen. And it turns out that there was probably some distilled water that was left in the cuvette, that was left in our container in the middle. And let's try to explain why that would happen, or how the student was probably just cleaning it out and didn't dry it out completely afterwards. And so what would happen there is the student, let's call this 0.05 molar. The student thought they put 0.05 molar cobalt 2 chloride into the cuvette, but because when the water mixed with it, and because that is such a small container, a couple of drops of distilled water is really going to have an effect, and so it dropped the concentration right here. Right? That we increase the volume, decrease the concentration, drop over there. So that's an interesting way to think about how we might be asked about experimental error. In a lab, that's a tough question to ask in a relatively simple setup. So just be practicing thinking about things like that as we're moving forward. So that brings us to the end. It was kind of a rush through a lot of big topics, and I apologize. Hopefully you took some time to stop and think. Certainly go back and play with those simulations we have there. Pull out your chemistry book and read through some of the explanation of all of these different topics, because there's a lot more to it that I was able to present just in 45 minutes for today. Your AP practice problems are here. The analysis, the explanation that's up at the top is very similar to everything that we've looked at in the past. So if it's cut off with my face up there, I apologize. But the questions are asking what's the cobalt 2 concentration, and then calculate moles and mass percent. So here's a good. This is clearly related to what we did today. B and C are connected to lessons earlier on in the year. And then 2 questions to piggyback on that. What's the approximate energy of one photon of this light if they gave you the wavelength and the frequency? And then can you tell me what the color of that light is as well? Okay, so just real quick, I'll give you a second to get a screenshot of this if you need to, a screenshot of this one if you need to, and then just say thank you for joining us again today. We have so much fun presenting these lessons to you, putting them together. Hope that they're useful for you. If you continue to have questions, check out apcentral.org. Check out the resources that we have below in the links, or check out this tiny URL. And please reach out to anybody you know who may have internet or device issues, and have them contact us at cb.org/talk. Thanks so much, guys. Have a great day. Be safe and enjoy chemistry. Have a good one.
Hello, everyone, and welcome to this AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, I am going to be talking to you about Unit 4, which is chemical reactions. Before I start the lesson today, I just want to remind you that students, you can visit the website apstudents.org/exams2020, and you can get more information about the online AP exam format this year. You can find information about the content, about the length of the exam, the structure and format, so all kinds of helpful information about the AP exam will be at apstudents.org/exams2020. Before we get started, hopefully you have access to scratch paper and something to write with, and a periodic table. If not, feel free to pause the video and get those materials. And if you're ready to go, let's go ahead and get started with today's lesson on Unit 4. So in this particular lesson, I will talk about topics 4.1 through 4.4, and that includes physical and chemical changes, reactions, net ionic equations, and representations, particle diagrams to represent reactions. So selected topics are listed here, as well as the science practices, including formulate a hypothesis or predict the results of an experiment, determine a balanced chemical equation, represent chemical substances or phenomena with appropriate diagrams or models, and support a claim with evidence from experimental data. So we'll talk about physical versus chemical change. We'll talk about writing a balanced chemical equation, net ionic equations, and using particle diagrams to represent reactions. For our warm-up today, let's review the homework problem that Mr. Byrne assigned in yesterday's lesson. And it looked like this, we have a graph of absorbance versus concentration. And this is for a solution of cobalt. So we have the concentration of cobalt 2+, and different solutions were prepared, and the absorbance of each solution is measured to generate this calibration plot. So we can see the direct relationship between absorbance and concentration. Part A of this question asks to figure out the concentration of cobalt in a solution if the absorbance is 0.74. So let's go ahead and just draw a line on our calibration plot at approximately 0.74 on the y-axis, and then where that intersects the line, we can trace that down to the x-axis. So estimating from the graph, if the absorbance of the solution is 0.74, then the concentration of cobalt in that solution would be approximately 0.013 moles per liter, and they would have accepted values in the range of 0.0125 all the way to 0.0135. So based on our answer to part A, let's move on to part B so we can calculate the number of moles of cobalt, the cobalt 2+ aqueous ion, in this solution that has a volume of 50.00 milliliters. Well, we know that since molarity is moles per liter, we're going to use our answer to part A as a conversion factor to convert from liters to moles. Of course, we should also know from the metric system that there are 1,000 milliliters in a liter. So if we do this as a conversion factor, we're going to take 50, divide by 1,000, and then multiply by the molarity in such a way that liters cancels out, and we have moles in our final answer. And if we do this math, I'm going to go ahead and round off my answer to 3 significant figures just based on my estimate of the concentration. I have 6.50 times 10 to the minus 4 moles of the cobalt ion. So that takes care of the answer to part B. In part C, they're asking us to calculate the mass percent of cobalt in this 0.630 gram sample of the ore. So that means that only a small fraction of that sample is actually cobalt. So we have to do a ratio of grams of cobalt divided by grams of the ore. On the periodic table, we see that the molar mass, which comes from the atomic mass of cobalt, is 58.93. So we'll take our answer to part B and we'll convert from moles to grams using the information off the periodic table. And then this answer, which is the grams of cobalt, will be divided by the mass of the ore. So we have a ratio of grams of cobalt divided by the grams of the sample of the ore, multiply that by 100%, and that will give us the mass percent of cobalt in this sample of ore. In this case, if we do this math, we get approximately 6.08% cobalt by mass. All right, moving on to the next part of the homework problem from yesterday's lesson. It says that the student in the previous problem used a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers. It also tells us that a wavelength of 510 nanometers corresponds to an approximate frequency of 6 times 10 to the 14 hertz, which is also inverse seconds. What is the approximate energy of one photon of this light? So you have access to an AP exam equations and constants sheet. Let me go ahead and show you a portion of that. And we can see that under atomic structure, there's energy and speed of light and frequency and wavelength and equations on the left, and then we have various constants on the right. So we're going to focus on the relationship between energy and frequency. Since we are given the frequency in this problem, we can calculate the energy, and they also tell us that Planck's constant is 6.626 times 10 to the negative 34 joules seconds. So we'll take our frequency that was given to us in the problem and multiply by Planck's constant, and as the seconds cancel out, we have our answer in joules. Now this will be joules per one photon. If we needed to do joules per mole, then we would have used Avogadro's number again, which is also listed on the equation sheet. But we're just doing a joule for a single number of joules in a single photon, so this answer 4 times 10 to the negative 19 joules is correct. Now for the color of the light, you would have to be given more information to determine whether this was red or orange or yellow or green or blue or purple. So I'm going to give you a chart that shows you the wavelength ranges for various colors of the visible light spectrum. As you can see, 700 would be the long end of the spectrum, the longer wavelength corresponding to red light. The short end of 400 to 450 nanometers is violet light. So 510 would fall somewhere between green and blue. So the color of that light would be sort of greenish blue or cyan. All right, let's get into our lesson on Unit 4. Again, we're going to talk about physical versus chemical changes. And you probably already know this, but I'll tell you that a physical change occurs when a substance undergoes a change in properties, but not a change in composition. So one example of physical change is a phase change. For example, the melting of ice, the freezing of pentane, the evaporation of methanol, the condensation of hydrogen chloride, the sublimation of carbon dioxide, or the deposition of iodine. As you can see in all of these phase changes, the chemical formula on both sides of the equation remains unchanged. So all we have is a change of phase. That's a physical change. Another example of a physical change would be separating a mixture. So for example, if we had a solid and we were separating it from a liquid using filtration, or if we had a mixture of two substances that had different boiling points, we might separate that mixture using a technique known as distillation, or possibly a chromatography experiment to separate two or more substances on the basis of how well they interact with a mobile phase and travel up the paper. All of these separation of mixture techniques involve physical changes. So in contrast, a chemical change involves a transformation of one substance into a new substance that has a new composition. So rather than, let's say, simply evaporating water, if we undergo electrolysis where water is transformed into hydrogen gas and oxygen gas, those substances are completely different. That would be a chemical change. Other examples might include the combination of carbon monoxide and hydrogen gas to make methanol, or the reaction of sodium metal and water to produce aqueous sodium hydroxide and hydrogen gas, or possibly a reaction between two chemicals that are aqueous silver nitrate and sodium chloride, and we produce aqueous sodium nitrate and silver chloride. So we can have conversions of one substance to another. That's a chemical change. Now if we think about what's happening at the particle level during physical versus chemical changes, if the only attractions that are broken or formed are intermolecular or interparticle forces, then it is likely that a physical change is occurring. For example, if we're just evaporating water, we're breaking the intermolecular forces between the water molecules. But if chemical bonds are broken or formed, then it is likely a chemical change is occurring. So here we are forming and breaking bonds as we transform hydrogen and oxygen to produce water. Now the course and exam description describes the fact that dissolving salt in water, for example, arguments could be made for that process being either a physical or a chemical change. Chemical because ionic bonds are broken as the salt dissolves, possibly a physical change because we are producing interparticle forces such as ion dipole forces. So the AP exam would not ask students to classify the dissolving of salt in water to be a physical or a chemical change. That's too ambiguous. So again, focusing on phase changes and simple breaking of intermolecular forces would be physical. Breaking chemical bonds to produce new substances, chemical change. The next thing I'd like to talk about in this lesson is writing a balanced chemical equation. So I'm going to give you a description of a chemical reaction and we'll turn this into a chemical equation. Now you don't have to memorize chemical formulas by and large. The AP exam, when they ask you a question, they typically give both the name and the chemical formula. So if I say calcium hydroxide and you can't remember the exact formula of calcium hydroxide, they're not going to try to put a naming question along with a writing a chemical reaction. So I'm telling you that calcium hydroxide is Ca parentheses OH2 and that hydrobromic acid has the formula HBr. So we have solid calcium hydroxide reacting with a solution of aqueous hydrobromic acid and it produces water, so H2O, liquid water, and aqueous calcium bromide. Now on the AP exam, if you are asked to write a balanced chemical equation, in your answer you are not going to be required to include the phase of matter, such as solid, liquid, gas, or aqueous. I'm going to go ahead and rewrite this equation without the phases of matter, and that would still be correct. However, you should double check your final answer to make sure that each chemical formula has been written correctly and that your equation has been balanced correctly. So we have 2 bromine atoms on the right side of the equation, so we'll add a coefficient of 2 on the left. And now, as you can see, we have a total of 4 hydrogen atoms on the left and 2 oxygen atoms on the left. So we'll add 2 as a coefficient in front of the water, and now this equation is completely balanced. All right, here's another example of a chemical reaction that we can turn into a chemical equation. We have phosphoric acid, H3PO4. It reacts with potassium hydroxide, KOH, and it produces water along with potassium phosphate, K3PO4. So considering the left side and the right side of the equation, there's a variety of ways you might consider balancing this equation. If I start with, let's say, oxygen, I can see that there are exactly 5 oxygen atoms on both sides of the equation. With respect to phosphorus, there's only 1 phosphorus atom on each side of the equation, but hopefully you can see that there are 3 potassium atoms on the right, and there is only 1 potassium atom on the left. Let's go ahead and add 3 in front of the KOH to balance the potassiums. Now this certainly changes our total for oxygens and hydrogens. We now have a total of 6 hydrogens on the left, so therefore therefore, if we need 6 hydrogen atoms on the right, if we add 3, this will also give us a total of 7 oxygen atoms, and the entire equation is now balanced. All right, here's another example. We have a chemical that is undergoing combustion, and the formula of that chemical is C5H12O, and it's reacting with oxygen to produce carbon dioxide and water. Now, I bring up this particular example because it illustrates a point that some students might make a mistake, even if they are very good at balancing equations and they've done it for years and they've practiced it and they understand how to do it. They still might make a mistake either because they're not quite paying attention or they're going too fast. So I'm going to start with the carbon. I see 5 carbons on the left, so I'll balance the carbon by putting 5 in front of the carbon dioxide. I see 12 hydrogen atoms on the left, so I'll balance the hydrogen by putting a 6 in front of the water on the right. So at this point, a student might take a look at their right side of the equation, and they might recognize that 5 times 2 is 10. This is for oxygen atoms, and 6 times 1 is 6. So there are clearly 16 oxygen atoms on the right. So they put 8 in front of the O2, and they say, okay, we're done. Now, I'll give you a moment. Hopefully you've already figured this out. I'll give you a moment to take a look and decide, is this equation in fact balanced? And if not, what you might do to solve this problem. Well, hopefully you can realize that we do have to count all of the oxygen. So in fact, if we put 8 in front of the O2, we now have 17 oxygen atoms on the left side of the equation. So we'll have to solve this problem by getting exactly 16. So this is how I might do it. And I might use 15 over 2 as a fraction, or 7.5. Now at this point, the equation is balanced because we have a total of 16 oxygen atoms on each side. And depending on the specific information given to you in question, this might be your final answer. Now, if they go on to say that you should balance this equation using lowest whole numbers, and you can't have a fraction for a coefficient, you just go back to each and every coefficient and multiply by 2. So the coefficients might be, instead of 1, 7.5, 5, and 6, multiplying by 2 might give us coefficients of 2, 15, 10, and 12. And of course, the equation is now still balanced. If the equation said, write a balanced chemical equation for the combustion of exactly 1 mole of C5H12O, then the top equation would be considered correct, and you'd be allowed to have a fractional coefficient. But if they say balance the equation using lowest possible whole numbers, then you want to use the bottom version of this equation. All right, here's another example of a chemical equation. This involves magnesium nitrate, so Mg parentheses NO3 2. It reacts with sodium phosphate. Sodium phosphate is Na3PO4, and the products of the reaction are sodium nitrate, NaNO3, and magnesium phosphate, Mg3 parentheses PO4 2. Now I would call your attention to the parentheses because some students might balance this equation in a way that might make it more work for themselves. So yes, if you look at, let's say, oxygen for a moment, there are 3 oxygen atoms with the sodium nitrate, and since 2 times 4 is 8, we have another 8. So trying to balance the individual oxygens might be problematic because oxygen is featured in each and every formula. So I would say it might be easier to balance the NO3 and the PO4 as one group of atoms. Might be easier to go ahead and attack it that way. So I see 2 PO4, 2 phosphate ions on the right. I'll definitely want 2 phosphates on the left. And then over here, I could consider what's going to happen if I end up with 3 magnesiums and I have 3 magnesiums on this side. That's going to give me 6 of the nitrate ions. So balancing it might be easier than thinking of it as 18 oxygen. So I'm going to go ahead and put a 3 in front of the magnesium nitrate to balance the magnesium. I now have 6 nitrate ions. I have PO4 multiplied by 2 on the right. I'll go ahead and get the 2 as a coefficient on the left. And now I have 6 sodiums. So 6 sodiums and 6 nitrates. The equation is balanced. Again, a variety of ways to balance an equation, but sometimes if you can balance polyatomic ions as a group when they appear on both sides of the equation, that might be a little easier than the individual atoms. All right, let's move on from writing a balanced chemical equation to net ionic equations. A sample of solid calcium chloride is dissolved completely in water. When this solution is tested for conductivity, it is observed that it does conduct electricity. Write the net ionic equation for the dissolution or dissolving of calcium chloride into water. Now, when a student first sees this, calcium chloride and water, this might be how they envision it. Now, the problem with writing the reactants as calcium chloride plus H2O is it might lead you down the path to assume that somehow water is reacting with the calcium chloride to produce other substances such as hydrogen or hydroxide. So it turns out that when an ionic solid dissolves in water, unless you're given more specific information about acid-base properties or you recognize something that would normally happen in terms of acid-base chemistry or oxidation reduction, we can assume that an ionic solid that is simply dissolving into water would just break up into aqueous ions. And so therefore, the water is not itself a reactant, but rather the medium in which the calcium chloride dissolves. So I'm going to go ahead and write calcium chloride on the left, and then that's it. I will show calcium and chlorine on the right side of the equation. Now, a student might write this because they want the formula to be broken up. However, these are the symbols for the elements, not the ions. Remember that calcium chloride contains calcium ions and chloride ions. Some students will stop here. So remember that while these are the correct symbols and charges, make sure that you balance the equation. So we have to put a 2 in front of the chloride ion. So now it is completely balanced. Here's another example of the dissolution of an ionic solid. This is magnesium nitrate. Now, students might be confused because they might not know the difference between monoatomic and polyatomic ions. So some students might break up the magnesium, the nitrogen, and the oxygen into 3 separate ions. But since a polyatomic ion, in this case nitrate, NO3 minus 1, is different than a monoatomic ion, the reaction should be balanced in terms of both atoms and overall charge. Hopefully you can see that on the right side of the equation, we have a total charge of +2 for magnesium, -6 for the 2 nitride ions, and then -12 for the 6 oxide ions. That's not going to be balanced in terms of charge. So magnesium and nitrate, those are the correct formulas. And again, don't forget to put 2 in this case in front of the nitrate to balance both the atoms and the charge. All right, here's another example of a substance. And notice that the light bulb is on in this picture, but now it is off. A sample of methanol, CH3OH, is added to water, and the solution mixed completely. When the solution is tested for conductivity, it is observed that it does not conduct electricity. Now, students might be tempted when they see OH, and they're so familiar with acid-base chemistry, potassium hydroxide, KOH, or sodium hydroxide, NaOH, they might be tempted to break up the formula into a positive and a negative ion. CH3OH is a covalent or molecular substance. It does not split into a positive and a negative ion like this. We also know that since it was tested for conductivity and it's not an electrolyte, it's going to remain intact. So a covalent or molecular substance like sugar or water, or in this case the methanol, if it is soluble in water but does not react with water, it will exist in solution at the particle level as molecules, and it does not dissociate into ions. Now, if we're going to write net ionic equations, it's helpful to know the difference between whether something breaks up into ions or does not. So here are some guidelines for writing net ionic equations. It can be helpful to do the following. Start with a molecular equation, which you simply write the chemical formulas for all of the substances involved, and then you can make the transition to a complete ionic equation. So what that means is split up any chemical formula into ions that should be split up, and then leave together as is any chemical formula that does not dissociate or break up into ions. Then you can cross off what are called the spectator ions, which are the ions that appear on both sides of the equation. And then now you have the net ionic equation. So this second bullet point, the make the transition to the complete ionic equation, you might be asking yourself, how would I know whether a chemical formula should be written as is or should it be split up into separate ions? In tomorrow's lesson, I will talk more about different topics of Unit 4, and one of them is topic 4.7. And in topic 4.7, they say specifically that sodium, potassium, ammonium, and nitrate salts that contain these ions are soluble in water. But memorization of solubility rules other than these are not going to be assessed on the AP exam. That's a good thing to keep in your head. Sodium, potassium, ammonium, and nitrate, those compounds are always soluble. Something we talked about a week ago, actually a couple of weeks ago, about strong acids and strong bases. There are 6 strong acids, and there are strong bases which are soluble metal hydroxides, including group 1 and group 2. So these would also be 100% split up into their ions in solution. So in general, how do we know whether we should split the formula up into ions or not? If it is a strong acid or a strong base or a soluble ionic compound, then go ahead and split up the compound into ions in solution. Now, if they say it's solid, you would leave it as a solid. But if they say it's aqueous, dissolved in water, would be split up. But if it's covalent, like I mentioned before with the CH3OH, compounds like sugar, a weak acid or a weak base would be left together as one formula. A gas like carbon dioxide or oxygen or hydrogen, a pure liquid like the methanol that I mentioned, or other types of pure liquids like water, a pure solid or an insoluble ionic solid would not be split up. So calcium hydroxide happens to be a strong base that would be split up into ions. Hydrobromic acid is a strong acid that is split up into ions. And in this chemical reaction, we're going to produce water. But water is just a covalent or molecular substance that's not going to be split up. And it turns out that calcium bromide happens to be aqueous. So again, the AP exam would tell you that by using AQ or saying a solution of calcium bromide, so that would be split up into ions. And like I mentioned before, there are what are called spectator ions. So we have a molecular equation, Ca parentheses OH2 plus 2HBr, and it produces 2H2O plus CaBr2. That's the molecular equation. Now, if I cross off the spectator ions like calcium and bromide on both sides of the equation, I get the net ionic equation. And while this equation might be acceptable on the AP exam, I think just to be on the safe side, if I have the ability to reduce all of the coefficients and still get the lowest possible whole numbers, I should do that. So I'm going to go ahead and divide each of these coefficients by 2. And again, that is my net ionic equation. Let's take a look at a few more examples of converting a molecular equation into a net ionic equation. Here I have H3PO4, which is phosphoric acid. So we saw this equation earlier. We have potassium hydroxide, and it produces water and potassium phosphate. So H3PO4 is not on your list of 6 strong acids. So I would leave that together. Potassium hydroxide is a strong base. Also, it contains the potassium ion, which is soluble. That's a soluble ionic compound. Water is just a covalent compound, and it's molecular. We're not going to split that up. And potassium ions are soluble in ionic compounds. So we have potassium and phosphate. Notice that I have 3 potassiums because of the subscript 3. And on the left side of the equation, I have 3 potassiums because there was a coefficient of 3 in the balanced equation. I'm going to cross off my spectator ions, and now I have that. So on the AP exam, if you had written, for example, the following H3PO4 plus OH minus to produce H2O and PO4 3 minus, take a look at what I've just written and compare that with the information at the bottom of this screen. Notice that the ion hydroxide does not have that 3 as a coefficient. The total charge on the left side of the equation is -1. The total charge on the right side of the equation is -3. So make sure that when you are writing a net ionic equation that is balanced not only for atoms but also for charge. All right, here's an example of magnesium nitrate and sodium phosphate. We saw this one earlier. Everything in this particular equation is soluble except for the magnesium phosphate. So nitrate ions are soluble. Compounds that contain sodium is soluble. So we have magnesium nitrate broken up into ions. That will be 3 magnesium ions and 6 nitrate ions. Then we have sodium phosphate, also soluble. We have 6 sodium ions and 2 phosphate ions. On the right side of the equation, we have a soluble compound that's going to be 6 sodium ions and 6 nitrate ions. And again, it turns out that magnesium phosphate happens to be an insoluble or slightly soluble ionic compound, so we're not going to break that up into ions. Once we cross off our spectator ions, that's going to include the nitrate on both sides and the sodium on both sides, we are left with the net ionic equation. So again, had you written this on the AP chemistry exam, magnesium plus phosphate to produce magnesium phosphate, that would be incorrect because the formula of magnesium phosphate is not MgPO4. And had you written the correct formula of magnesium phosphate but did not balance the equation in terms of the atoms, that would also be incorrect. So watch out for how you balance net ionic equations. All right, so in this example, we have sodium hydroxide and copper sulfate reacting together. And I told you that they are aqueous with the symbol AQ. On the right, we have copper hydroxide and sodium sulfate. So this section of my lesson is entitled Mistakes to Avoid When Writing Net Ionic Equations. Because I've given you the AQ or the S as a phase of matter, it should be very straightforward and obvious in this case that copper hydroxide is the precipitate because it has an S next to it for solid. So if you had to write the net ionic equation, you would not need to include AQ or S in your answer. But you should recognize that the copper hydroxide is in fact going to be the precipitate, whereas sodium and sulfate, because they are soluble on both the left and the right, sodium and sulfate are the spectator ions. So I'm now going to go through several wrong answers to this net ionic equation. And these are all very common mistakes that we see at the AP reading on the AP exam when students are writing responses to net ionic equations. So pay close attention to these examples and make sure that you can work hard to avoid making these kinds of mistakes. All right, so net ionic equation for the formation of copper hydroxide. So what did the student do wrong? Well, hopefully you can see that they did not balance their equation. Okay, here's another mistake. We're trying to make copper hydroxide. So what did this student do wrong? Well, they have balanced the equation, at least on the left, in terms of 2 hydroxide. That looks good. However, they have written their formula on the right side of the equation without the parentheses. That would also be considered incorrect. So that does not show 2 oxygens and 2 hydrogens without those parentheses. Okay, here's another mistake. Let's see what this student did wrong. He did a good job with the balancing, but the charges on the ions are missing. So again, make sure that you don't fall into these traps or these mistakes. Here's another mistake that the student made. Looks like they have attempted to balance the equation and they have charges on their ions. But if you look closely, the charge on the copper ion should be +2, not +1. So again, pay attention to these little subtle mistakes that students can make. Here's another one that might happen. They have charges on their ions, but unfortunately the signs of the charges on the ions are reversed. So copper should be +2 and hydroxide should be -1. Again, these are all mistakes that students might make. Hopefully you don't fall into these categories with your answers. In this case, it's very clear that copper hydroxide is a solid. So here's another example of a student mistake. They have written a correctly balanced equation for the wrong product. So we know that sodium sulfate is aqueous, therefore it would be split up into separate ions. The product should be the insoluble ionic solid, not the aqueous ionic solid. And then this person tried really hard to get all of the information out there, but this as their final answer would be marked incorrect because the spectator ions were not crossed off on both sides of the equation. So the correct answer would look exactly like this as far as the net ionic equation is concerned. Here's another example of mistakes to avoid when writing net ionic equations. I have a different reaction for you. It says a strip of solid aluminum metal or aluminium metal is added to a solution of copper 2 chloride. The products of the reaction are solid copper and aqueous aluminium chloride. So we have to look at aluminum or aluminium reacting with copper 2 chloride. So there's the correct formula. That's a solution of, so it's aqueous. And we have solid copper as a product and aluminium chloride, which happens to be +3 for aluminum or aluminium. So we have not balanced the equation yet. We're going to need 6 chlorines on both sides because the least common multiple of 2 and 3 is 6. So we'll balance the chlorides and then we'll balance the aluminium and the copper. So I have not written the net ionic equation. This is the molecular equation. Let's go ahead and transition to the net ionic equation. Well, here is a student's mistake. They focus on the aluminium chloride, which is AlCl3, and this is what they wrote. It's a fine equation with respect to the formation of AlCl3. It's balanced in terms of atoms and charge, but look at the aluminum or aluminium on the left. The charge on the Al on the left side of the equation is 0. It's not +3. So it doesn't start off as ions, it starts off as atoms. And since AlCl3 is a soluble ionic compound, it would not be written together, but rather broken up into ions. So watch out for making mistakes like that. Here's another mistake the student made. They have written everything correctly in terms of what should be remaining together and what should be broken up, but they forgot to cross off the spectator ions on both sides of the equation. So again, watch out for that mistake. All right, now I'm going to go ahead and give you another example. We have aluminum reacting with copper ions to produce copper metal and aluminum ions. So do you see the problem here? It is balanced in terms of atoms, but it is not balanced in terms of overall charge. We have +2 on the left and +3 on the right. This is incorrectly balanced with respect to the overall charge. So this one looks really good in terms of atoms and charge. Hopefully you can see what they did wrong. It's a fine equation except for one important detail. It is written backwards. So the aluminum should be on the left in the form of 0 or no charge, and the aluminum ions should be on the right. Copper solid should be on the right and copper ions on the left. So again, the correct answer would look like this, where the chloride ions have been eliminated. So again, pay attention to how to write net ionic equations as well as what mistakes that commonly are made on the AP exam, how you can avoid those mistakes. All right, before we get to our homework, I'm going to talk about particle diagrams. So here is an example of a chemical reaction involving 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water. So how would particle diagrams be used to represent this reaction? Well, here's one example. So I have 4 water molecules in the box on the right, and I have 4 hydrogen molecules in the box on on the left and 2 molecules of oxygen in that same box. So particle diagrams can be used to represent the reactants and the products in a chemical reaction. You can see that there is a 2-to-1 ratio between the molecules, just like there is in the coefficients in the balanced equation. So on the left, we have 4 molecules of hydrogen for every 2 molecules of oxygen. Now, you can also use particle diagrams to illustrate the concept of limiting reactants. So in this case, I have not given you exactly a 2-to-1 ratio between hydrogen and oxygen. So here are 2 molecules of hydrogen and 1 molecule of oxygen. That would make 2 molecules of water. Here's another 2 molecules of hydrogen and 1 molecule of oxygen. That would make another 2 molecules of water. So as you can see, we're actually going to run out of hydrogen. I've got another 2 molecules of hydrogen, 1 molecule of oxygen. I've got 2 more waters, but I've got this particular oxygen now is left over. So you could use particle diagrams to indicate the ratio and what might be considered leftover, excess, at the end of a reaction. All right, in terms of particle diagrams to represent reactions, here we have silver nitrate, which is a soluble compound, reacting with sodium chloride, also soluble, to produce silver chloride and sodium nitrate. Since sodium and nitrate are always soluble, we have a precipitate of silver chloride in this case, and I'm going to show you that with the phases of matter. So everything is aqueous except for solid silver chloride. All right, here's an example of particle diagrams. A dilute solution, so not very concentrated, of silver nitrate is combined with excess sodium chloride to form solid silver chloride. Which of these diagrams best represents the ions that are present in significant concentrations in solution? Justify your answer. Well, before we look at these diagrams closely, let's try to get the net ionic equation for this particular reaction. So for the net ionic equation, I'm going to go ahead and split up the silver and the nitrate because it's soluble. I'm going to split up the sodium and the chloride because it's soluble. I'm not going to split up the silver chloride because it is insoluble, that's a solid, and I'm going to split up the sodium and the nitrate. Cross off my spectator ions on both sides of the equation, and here is my net ionic equation with the spectator ions being sodium and nitrate. So what I'm looking for is solid silver chloride on the bottom of this beaker and sodium and nitrate in solution. This looks like a very attractive and possibly correct answer. It's got sodium and nitrate in the solution still dissolved, and there is the solid silver chloride on the bottom. The only problem with this particular diagram is if I didn't read carefully, I might have ignored this particular phrase, with excess sodium chloride. So what does that mean? Well, what it means is that if sodium chloride is the excess reactant, there's going to be excess left over, and silver nitrate is the limiting reactant. All of the silver ions will have been converted into solid silver chloride. So in terms of particle diagrams, I need to cross off any diagram that still shows silver left over. So all of the silver would need to be consumed, and therefore I can get rid of these. Now down to these 2 diagrams that I have left, as far as which of these diagrams is correct, the excess sodium chloride means that there should still be excess chloride ions present in solution, so that makes this diagram the correct answer. So the correct answer is this one right here because of the excess chloride ions that are present in the particle diagram. The diagram over here would have only been correct if we had exactly the perfect 1-to-1 mole ratio of these 2 reactants. All right, looking at another example of particle diagrams here, we have 1 liter of a silver nitrate solution reacting with 1 liter of a magnesium chloride solution. You can see particles representing the ions in the diagram, and then that combination produces 2 liters of a final mixture of silver chloride solid, which is on the bottom of the beaker, and magnesium nitrate still dissolved. So we have silver nitrate reacting with magnesium chloride to produce silver chloride solid and magnesium nitrate aqueous. After examining the particle diagram shown above, a student made the claim that the concentration of silver nitrate is the same as the concentration of magnesium chloride. Do you agree with the student's claim? Justify your answer based on the information in the particle diagram. So do not use the balanced chemical equation to justify your answer. Use the specific particles that are featured in the diagram. So do you agree that the concentration of silver nitrate is the same as the concentration of magnesium chloride? This would be a good time to pause the video and see if you agree with the claim before you press play and reveal the answer that I'm about to tell you. Okay, well, if you look closely at the diagram and we start counting the positive ions here, this is silver. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 silver ions. Now for the cations, Mg2+, 1, 2, 3, 4, 5. So therefore, I disagree with the student's claim, and here's why. Each of the solutions has the same volume, so they're both 1 liter. But since there are twice as many silver particles as there are magnesium particles, the concentration of silver nitrate should be twice as much as that of magnesium chloride. Another example of particle diagrams, or a question that could be asked about this particle diagram, is the following. A student made a claim that the value of concentration of magnesium in beaker Y, which is the middle beaker, is twice as much as the value of the concentration of magnesium in beaker Z. So do you agree? Justify your answer based on the information in the particle diagram. So do you think that the concentration of magnesium in beaker Y is twice as much as that of beaker Z? Okay, well, if you had a chance to think about that, let me go ahead and tell you the answer. As you can see, we have 5 particles of magnesium in each beaker. So 1, 2, 3, 4, 5, and then we still have 1, 2, 3, 4, 5. So the number of moles of magnesium is the same, but the volume in beaker Z is twice as much. So I would agree that since we have double the volume in beaker Z, that concentration should be half as much. So there are the same number of magnesium particles in each beaker, but since the volume in beaker Y is essentially half as much as that of Z, the concentration of magnesium is twice as much. All right, here's one more quick particle diagram, and then I promise we'll get to our homework. This was a net ionic equation for a reaction between sodium carbonate and calcium nitrate. The products of the reaction are sodium nitrate, which is soluble, and calcium carbonate, which is insoluble, and you can see the solid down here at the bottom of the beaker. Now, if you take a look closely at the language of this question, they mentioned the word excess again, so we'll think about that. All right, the net ionic equation would be if I see an aqueous ionic compound, let's split it up. I see 2 aqueous ionic compounds, we'll go ahead and split them up. And I see an aqueous ionic compound on the right, let's go ahead and split that up. And then finally, calcium carbonate, they say S for solid, that is insoluble, that's a precipitate, so I'm not going to split that up. Cross off the spectator ions. So part A, write the net ionic equation for the reaction that occurs when these solutions are mixed, and there is your answer. The spectator ions are sodium and nitrate. Now let's focus on that word excess as it relates to the particle diagram. So draw in the species that need to accurately represent the major ionic species. It says the diagram is incomplete. So if the calcium nitrate is the excess reactant, then that means that sodium carbonate is limiting. And so all of the carbonate should be consumed and turned into solid calcium carbonate, but there should be an excess of calcium ions. So many students on this question did this. Well, hey, they wanted to show an excess of calcium ions. So is there a problem with writing 1 versus 2 versus 3 versus 4? Take a look at what I mentioned before about the overall charge. So if you count up all of the ions that are positive in this diagram, we have a total charge of positive 6 because we have 2 sodiums that are +1 each and 2 calciums that are +2 each. But I only have 4 nitrates, and that would be -1 each. So unfortunately, if students put 2 calcium ions into their answer, they did not receive credit because the charge balance was not taken care of. So this would be a correct answer. Only 1 calcium ion should be added because now we have a total charge of +4 and -4 in this diagram. So what if you really want to put 2 calcium ions in that diagram? Well, you could. If you want to add 2 calcium ions, then you also have to add 2 more nitrate ions to get a total charge of -6 to balance the +6. Okay, well that wraps up this particular lesson. We'll now go to our homework. So again, in today's lesson, we talked about chemical reactions as well as physical and chemical change. We talked about net ionic equations, and we took a good look at particle diagrams to represent reactions. So for your homework for tomorrow's lesson, there are 2 screens. I'll go ahead and just pause momentarily so you can get a screenshot of each of these. So this is the first slide, and the homework problem has to do with a chemical reaction involving potassium iodide and lead nitrate. And this is the second screen. So I will explain the answers to all of these questions in tomorrow's lesson. Just a quick reminder about the helpful chemistry resources at the bottom in the video description. Thank you very much for watching. Again, this has been Michael Fairbaugh from Albemarle High School in Charlottesville, Virginia. Again, go to cb.org/tech if you or anyone you know needs assistance with mobile tools or connectivity. Thanks for watching. Hello everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, in this lesson, we're going to continue our discussion of Unit 4, Chemical Reactions. I just want to remind everyone that you can always go to the College Board website. In this case, the address is apstudents.org/exams2020 to get more information about the at-home online AP exams this year. So feel free to check out that resource. Make sure that you have access to paper and pencil and a periodic table. Let me give you an overview of today's lesson. So we're going to finish up Unit 4 on chemical reactions. So we'll talk about stoichiometry, we'll talk about titration, various types of chemical reactions, including acid-base reactions, oxidation, reduction, or redox, and precipitation reactions. So as you can see here, also there are a variety of science concepts and skills, including balancing chemical equations and describing the components of quantitative information from models and particulate level and macroscopic level properties. So in today's lesson, we'll talk about stoichiometry, titration, acid-base reactions, redox reactions, and precipitation reactions. Let's begin with the problem that I had set for homework from yesterday's lesson, and it involved a laboratory experiment in which a tablet containing potassium iodide, Ki, was analyzed to determine the iodide content. And so the tablet was dissolved in distilled water, and an excess of 0.2 molar lead nitrate was added. A yellow precipitate forms, which was then filtered, washed, and dried. So we have this data, and then we have parts A through F. So we'll go ahead and start with part A. For the chemical reaction that occurs when the precipitate forms, write a balanced net ionic equation for the reaction, and explain why the reaction is best represented by a net ionic equation. So as you recall from yesterday's lesson, if you have a soluble ionic compound, we're going to split that up into ions. So each of these chemicals, the potassium iodide and the lead nitrate, are soluble in water. It's going to be a reverse kind of double replacement reaction where you switch partners. So now the potassium bonds with the nitrate, so we have potassium nitrate, and then the lead iodide. So I said in yesterday's lesson, as I balanced this equation, putting 2 in front of the Ki and a 2 in front of the KNO3. In yesterday's lesson, I said that all sodium, potassium, ammonium, and nitrate salts are soluble in water. So that means that potassium iodide, lead nitrate, and potassium nitrate are soluble, and our precipitate happens to be the lead iodide. So if we're going to write a balanced net ionic equation, let's go ahead and convert this molecular equation into the complete ionic equation where we split up everything that we can. So I have 2 potassium ions and 2 iodide ions. I have 1 lead ion, which is +2, and 2 nitrate ions. And then on the product side of the equation, I have 2 potassium ions and 2 nitrate ions. And because lead iodide is our insoluble or slightly soluble ionic compound, we'll go ahead and leave that formula together. And once I cross off the potassium and the nitrate as our spectator ions, this now becomes our net ionic equation. So that takes care of part A, Roman numeral 1. In Roman numeral 2 of part A, explain why the reaction is best represented by a net ionic equation. So you might wonder, why exactly do we cross off the spectator ions? Well, it's because they're not changing in this particular reaction. They are the same on both sides of the equation. So the net ionic equation shows the formation of the solid lead iodide from the aqueous lead and iodide ions, and the spectator ions are eliminated from the equation because they are unchanged by this reaction. In part B, explain the purpose of drying and weighing the filter paper with the precipitate 3 times. Well, as you might imagine, it says a yellow precipitate is filtered, washed, and dried. That is a solid. So the precipitate being a solid, it should be as dry as possible. We don't want to put lead iodide that is wet with water on the scale because it would not give us an accurate mass of just the solid itself. So the filter paper and the precipitate must be dried several times to make sure that all the water has been removed. And as you can see, between the second and the third drying, the procedure is repeated until eventually the mass remains essentially constant. All right, that takes care of part B. Part C is a little confusing at first. In the filtrate solution, is the concentration of potassium greater than, less than, or equal to the concentration of nitrate? So you might wonder, what exactly is the filtrate and what does this procedure look like? There wasn't an actual setup or an experimental diagram other than a table. So let's go ahead and talk about what actually happened. So this is a tablet, and this tablet contains potassium iodide as well as a inert water-soluble sugar as a filter. So we're going to take this tablet and dissolve it in 50.0 milliliters of distilled water. So to give you an idea of what that looks like now, so a particle diagram, we now have a solution that contains some sugar, which is not going to react in this case, and then some potassium ions and some iodide ions. Now remember that the iodide is part of the net ionic equation. The potassium is a spectator ion that will just remain in solution. So now we add this excess amount of lead nitrate. And so in our particle diagram, you can see that we still have the sugar and the potassium and the iodide, but here come lead ions and nitrate ions. Now this is sort of frozen in time because the moment that that lead nitrate hits the solution, there would be an immediate formation of this solid yellow precipitate, which I'm showing on the bottom of the beaker here. So consider we have some potassium ions that still remain, but all of the iodide ions are now sitting at the bottom of the beaker and the form of solid lead iodide. So the question was asking essentially about the filtrate. So if we take the solution and we pass it through a filter, then we can collect the solid lead iodide in the funnel and the filter paper, but we have filtrate, which is what passes through. That's all the soluble ions. So as you can imagine, potassium ions and nitrate ions are not going to have the same concentration. So the key word there in the stem of the question is the word excess. So because the source of the nitrate ions in the solution is excess lead nitrate, then the nitrate concentration should be much greater than the concentration of the K+. So the official answer to this question is the concentration of K+ is less than that of nitrate. All right, now time to look at your periodic table, because in part D we have to calculate the number of moles of the precipitate that is produced in this experiment. So on your periodic table you can find the formula for lead, which is Pb, and it has a molar mass of 207.2. And on the periodic table the molar mass of iodine is 126.9, and we have 2 of them in the formula of the precipitate, which is lead iodide. PbI2 has a molar mass of 461.0 grams per mole. We can subtract the mass of the filter paper from the final mass of the filter paper and the precipitate after it was dried several times. So that difference is 0.236 grams of lead iodide. Let's convert that from grams to moles. And now we have 5.12 times 10 to the minus 4 moles of lead iodide. That is our answer to part D. Part E asks us to calculate the mass percent of iodide in the tablet. So since the mass of iodide comes from the lead iodide, which we already know the moles of, let's convert moles of lead iodide into grams of iodide. Now remember, there are 2 moles of iodide for every 1 mole of PbI2. Again, the periodic table tells us that there's 126.9 grams of iodine for every 1 mole. And it doesn't matter whether it's I, the atom, or I minus the iodide ion. That's not going to change the mass. A single electron is not going to make a difference. So if we do this math, we get 0.130 grams of iodide. So the percentage of iodide in the tablet is going to be a mass ratio. 0.0130 grams of iodide divided by the mass of the tablet times 100, and that gives us approximately 30.6% iodide by mass. All right, the next part of this question said, if we had used, instead of 50.0 milliliters of distilled water, if we had used 55.0 milliliters of distilled water to dissolve the tablet, is that going to affect the mass percent of iodide? And if so, is it going to be greater than, less than, or equal to the amount that we just calculated in part E? We'll go back to that procedure. Dissolving the tablet in a larger volume of water, we're still going to add the excess lead iodide to react, lead nitrate to react with all of the iodide. We're still going to take that precipitate and filter it. So effectively, whether that is a larger volume of water to dissolve the tablet, it's not going to make a difference. We're still going to dry the precipitate. So the mass percent of iodide should remain the same because lead was added in excess, ensuring that all of the iodide reacted. Any additional water is going to be removed by filtration and drying, and the mass of that dry precipitate should be the same. All right, let's go on to our lesson. We're going to start with stoichiometry. And with respect to stoichiometry, I'd like to talk about conversions of moles to moles, grams to grams. I'd like to connect stoichiometry to molarity, the ideal gas law, as well as talk about limiting reactant and theoretical yield. So I'm going to come up with an unbalanced chemical equation that will deal with all of these concepts. Here we have a reaction between aluminum or aluminium and a solution of hydrochloric acid. It produces a solution of aluminum chloride and hydrogen gas. This equation is not balanced. I see 2 hydrogens on the right, so I might put a 2 here to balance the hydrogens. But upon closer examination of the chlorine, I realize that I have 2 chlorines on the left and 3 chlorines on the right. So the least common multiple of 2 and 3 is going to be 6. So I'm going to have to get 6 chlorines on both sides. Now that I have 2 aluminums on the right, let's go ahead and balance the aluminums. And then finally 6 hydrogens. There's a 3 right there for 6 hydrogens. So we're going to do moles to moles. Moles to moles involves the coefficient coefficients, and the ratios 2, 6, 2, and 3 represent the relative number of moles of each substance. Here's an example of a moles to moles question. Aluminum or aluminium and hydrochloric acid react together according to the chemical equation shown above. If 0.36 moles of aluminium chloride is produced in this reaction, how many moles of hydrogen are also produced? So what you would do to convert from moles to moles is you would put the units you want to get rid of on the bottom. So in this case, moles of aluminum chloride on the bottom. And then we want moles of the other chemical, which in this case happens to be hydrogen on the top. We don't need the periodic table to do moles to moles. We just need the coefficients. So the coefficients from the balanced chemical equation are what I would use to convert moles to moles. So you can go ahead and do this math and see if you get the same answer that I do. Feel free to pause the video anytime during this lesson to stop, check your work, then you can press play to make sure that your answer is consistent with the answer that I'm giving you in the lesson. So hopefully if you did this math already, you have gotten 0.54 moles of hydrogen. Now let's move on to a grams to grams conversion. So same reaction, but now aluminium and hydrochloric acid react. How many grams of aluminium are required to produce 75 grams of hydrogen? You can assume that the hydrochloric acid is added in excess. So we have 75 grams of hydrogen, and we're going to try to figure out how many grams of aluminum or aluminium are going to be required for 75 grams of hydrogen to be produced. This first step will be what I call a periodic table step. This second step will involve the coefficients as I was just showing you in the example from moles to moles. And then this last step will also be what I call a periodic table step. So here we're going to involve the periodic table and approximately the number of grams of aluminum in 1 mole, about 27 grams according to the periodic table. This is also a periodic table step. Approximately for every 1 mole of hydrogen, that is about 2 grams. So I got that information off the periodic table, but this comes from the coefficients. So I would put moles of hydrogen on the bottom, and I would put moles of aluminum on the top, and I would use the coefficients in this case 2 and 3. So that is the setup for this problem. Again, you can take the time to do that setup on your own. You can use the periodic table and the coefficients, and you can pause the video and see if your answer agrees with mine. So here are the 3 steps: grams to moles, moles of hydrogen to moles of aluminium, and then finally moles to grams. So when I did this on my calculator, I got 670 grams of aluminum or aluminium. All right, moving on to my next example, I'm going to connect molarity. So molarity is moles per liter. This question says, how many milliliters of 5.0 molar hydrochloric acid are required to react completely with 4.25 grams of aluminum? So if I have 4.25 grams of aluminum, I have to somehow get to volume of hydrochloric acid. Remember that this capital M, so right here, this capital M, that means moles per liter. So there are 5.0 moles of hydrochloric acid for every 1 liter. I can use that as a conversion factor if I need to. Let's convert grams to moles using the periodic table. Let's convert from moles of aluminum to moles of hydrochloric acid using the coefficients. And then now we're not going to convert to grams like we did before. We're going to convert to volume. So I'm going to use that conversion factor, but it's going to be upside down. 5 moles of HCl on the bottom and 1 liter on top. If I stop right now and did the math, my answer would come out in units of liters. So I'm going to add milliliters, and you should know that there are 1,000 milliliters in 1 liter. All right, if you've done this math, you've done 4.25 divided by 26.98 times 6 divided by 2 divided by 5 times 1,000. Hopefully you got the same answer that I did. 94.5 milliliters of 5 molar hydrochloric acid is required to react completely with 4.25 grams of aluminum. I want to connection to the ideal gas law because again, stoichiometry involves moles, and moles are connected to a variety of topics. So with respect to the ideal gas law, PV equals nRT, where P is pressure, V is volume, and N is number of moles. And then R is the ideal gas constant, which you can get off the formulas and equation sheet on the AP exam, and then T is the Kelvin temperature. So here is our problem. 35 grams of aluminum reacts with excess hydrochloric acid. What is the volume in liters of hydrogen gas produced at a temperature of 345 Kelvin and a pressure of 1.12 atmospheres? So if I'm looking at what is the volume of hydrogen gas at a certain temperature and pressure, I'm going to write V equals nRT over P. They've already given me the pressure in atmospheres, the temperature in Kelvin. I can use the ideal gas constant, that number that we'll see on the equation sheet 0.0H206, which has the appropriate units of liters and atmospheres. But what I have to figure out is the moles. So where's the moles going to come from? That is going to be the stoichiometry. I've got to connect 35 grams of aluminum into moles of hydrogen. So we'll start off this problem by converting 35 grams of aluminum into moles. That's just the periodic table. Let's convert from moles of aluminum into moles of hydrogen. But now I'm not going to go grams. I'm going to take that number and plug that into the ideal gas law. So when I did this math, I got 1.95 moles of hydrogen, and that will be the N in my expression V equals nRT over P. And looking at the units, the ideal gas constant has units of liters, atmospheres, moles, and Kelvin. Everything will get crossed off except for liters. So if you do this math, 1.95 times 0.08206 times 345 divided by 1.12, you should get your answer in units of liters. And I did this on my calculator, and I got 49 liters of hydrogen. All right, next thing I want to talk about in the category of stoichiometry is limiting reactant and theoretical yield. So we're given a problem involving 2 different reactants, aluminum and hydrochloric acid. 125 grams of aluminum reacts with 2.50 liters of 3.20 molar hydrochloric acid. Which chemical, the aluminum or the hydrochloric acid, is the limiting reactant, and what is the theoretical yield of hydrogen in units of grams? So there's 2 ways to solve this problem. I'm going to show you both ways. I'm going to start with this particular method. I'm going to convert each of these reactants into grams of hydrogen. And when I do that, then we can compare and see which mass of hydrogen is smaller. So let's start off by converting from grams of aluminum into moles. That's the periodic table. Let's convert from moles of aluminum to hydrogen using the coefficients. And now let's convert from hydrogen moles to grams, periodic table. So while this number, 14.0 grams of hydrogen, is not necessarily my final answer, it is a point of comparison. So I'll start the same process over again, but using the other reactant. Now I can't begin with grams of hydrochloric acid. I'll begin with the volume. Let's use 3.20 moles per liter as a conversion factor. Let's put moles on the top and liters on the bottom so they cancel out. Now let's convert moles of HCl into moles of hydrogen using the coefficients. And then my final step back from moles to grams, and I get, okay, so I've got 2 numbers here, 14.0 and 8.06. So by definition, the limiting reactant limits how much you can produce. So therefore, the limiting reactant in this case will be HCl because it produces a smaller amount of product when I do my stoichiometry calculations. Now, the theoretical yield is the maximum amount of hydrogen gas that I can produce from these 2 reactants. So the theoretical yield of hydrogen in this case is the smaller of the 2 values. So 8.06, that's my theoretical yield. Let me show you the other way to solve this problem, and it has to do with converting each reactant into the other reactant. As far as converting one reactant to the other, it's going to be the same principle of stoichiometry and mole ratios, but now I'm going to convert aluminum into hydrogen. I'm sorry, not hydrogen, hydrochloric acid. So I'm going to convert aluminum into the other reactant, so hydrochloric acid, and now we'll go to volume by using the 3.2 moles per liter, that ratio upside down. So I have moles on the bottom and liters on top. If I do this math, I get 4.34 liters of the hydrochloric acid needed. Now let's compare the amount that we need with the amount that is available. Hopefully you can see that HCl is the limiting reactant because the amount you need to react with all of this aluminum is greater than what you have available. So you're going to run out of the hydrochloric acid. You don't have enough hydrochloric acid to react with all this aluminum, so therefore it is the hydrochloric acid that is going to be limiting and to be consumed completely. If we go the other way and start with the hydrochloric acid, convert that from liters to moles using molarity, convert to moles of aluminum using the coefficients, and then finally to grams, periodic table. Notice that the amount of aluminum that I need is less than what I have available. So it is the aluminum that is present in an excess amount because I have more aluminum available than I need to completely react with the hydrochloric acid. Now I like both methods. They're both fine methods. I think I have a slight preference for the method that I showed you first. And the reason I like this method is because if the question follows up with the theoretical yield, then you already have those numbers right there. You've already done the work. If instead they ask you for the theoretical yield of hydrogen, you still have to convert all of the hydrochloric acid into hydrogen. So I feel like the first method kind of accomplishes both of those at the same time. It tells you the limiting reactant and it gives you simultaneously the theoretical yield. All right, moving on to the next topic in today's lesson, titration. Here we see a burette and a flask. So a titration is an experiment that can be used to calculate the amount of moles or the concentration of one chemical by reacting it with a known quantity of another chemical. The standard solution, that is the concentration that you know, is called the titrant, and the solution with the unknown is called the analyte. So in this case, for the little setup here, I've got the titrant in the burette, that's the one I know, and then the analyte in the flask, that's the one I don't know. It might be backwards. You might have a known amount of chemical in the flask, and you might fill the burette with an unknown solution. So it's still possible that the chemical that is unknown could be in the burette. I'm just going to go and show you this particular example. So the titrant is slowly added to the analyte by using the burette, and then the equivalence point is reached. And the equivalence point in a titration is the point at which just enough titrant has been added. So based on whatever chemical reaction you're doing, it could be an acid-base reaction, it could be an oxidation reduction or redox reaction, even a precipitation reaction. There's a variety of reactions you could do. The equivalence point is when enough titrant has been added to react completely with all of the analyte. And this point may be indicated by a color change. And if that color change happens, then the observable event would be called the end point. And you want the end point to be as close to the equivalence point as possible. So we normally design our experiment so that the color change happens very close to the equivalence point. All right, so for titration, I'm going to give you an acid-base reaction to start. So the chemical on the left is called acetic acid, also known as ethanoic acid, and that's found in vinegar. So we have a solution of vinegar that contains an unknown amount of acetic acid, HC2H3O2. That is a monoprotic acid, has one H plus that is given off as an acid. A 25.0 milliliter sample of vinegar is titrated with 0.650 molar sodium hydroxide according to the equation above. If it requires 32.04 milliliters of the titrant to reach the equivalence point, what is the concentration of the acetic acid in the vinegar? So we'll convert milliliters to liters, and then because 0.650, that's the number of moles in 1 liter, we now have converted from liters to moles using molarity as a conversion factor. Notice that the equation above is balanced. Monoprotic acids require 1 mole of sodium hydroxide to reach the equivalence point and neutralize it. That's a 1-to-1 ratio. So right now, this is not my final answer, but that's how many moles of acetic acid I have. I'd like to figure out the concentration, which is moles divided by liters. So 25.0 milliliters, that would be 0.0250 liters. Oh, that should say liters. Sorry about that. That should say liters right here. So we're going to do our conversion factor to get concentration by doing moles divided by liters. And if we do this math, we get 0.833 moles per liter, or capital M. Now, there is another way to solve this problem. And the second way to solve this problem is a little easier. And I caution you to use this carefully. This is a shortcut. If there is a 1-to-1 mole ratio between the acid and the base, you can also use the following equation as a shortcut. So capital M is molarity, capital V is volume. So we have molarity times volume for the acid and molarity times volume for the base. Because molarity times volume is moles, the moles of acid equal the moles of base. So if you plug in everything we know from this problem, we don't know the molarity of the acid, at least not yet. 25.0 was the volume of the acid. We were given the molarity of the sodium hydroxide, that's the base, and we were given the volume of the titrant, the base, required to reach the equivalence point. You might wonder, do I have to put volume in liters? In this case, no. As long as those units are the same, they're going to cancel out either way. So we have just a simple mathematical or algebraic equation, 0.65 times 32.04 divided by 25, and you're going to get the same number we got before. So again, it's a great equation to use, but I caution you to only use that equation when you have a 1-to-1 mole ratio between your reactants. Otherwise, you might want to do the traditional volume times molarity in moles, and again, paying attention to the specific coefficients to convert from moles of one chemical to another. All right, here's another 1-to-1 mole ratio between an acid and a base. This is also a titration experiment, but instead of calculating the concentration of a chemical, this question asks you to calculate the molar mass of this substance. Benzoic acid is a monoprotic acid. A sample with a mass of 0.180 grams is dissolved into water and titrated with 0.125 molar potassium hydroxide. It requires 11.79 milliliters of the titrant to reach the equivalence point. So what is the molar mass of the benzoic acid? Well, now we have to convert from milliliters to liters, from liters to moles. There's a 1-to-1 mole ratio, but this time we're not going to do concentration, we're going to do molar mass. So molar mass is grams per mole. So I have moles of benzoic acid, which I'm not rounding off just yet because it's not my final answer. 0.180, that's my mass. Divide that by the number of moles I have, and our molar mass works out to be about 122 grams per mole. So you can use a titration experiment to do calculations for either an acid-base reaction or possibly an redox. In fact, I think you'll see that redox titration in your homework problem today. There are a variety of types of chemical reactions. One of them is acid-base. For more information about acid-base reactions, you can go back and watch the first video that we launched back a couple of weeks ago, and that would be topic 8.1, Introduction to Acids and Bases. In that video, I had mentioned that a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Also in that video, I had shown you an AP free response question in which we had an acid, propanoic acid, and it was reacting with water. So this chemical right here is called the conjugate base. I'll just say CB for short, and we'll call this the conjugate acid. Water was behaving as a base, so we'll say CB for conjugate base, and then the hydronium is the conjugate acid. So these were examples of conjugate acid-base pairs from that video 8.1 that I showed you earlier in the series. So let's go ahead and practice that a little bit. In the left, we have conjugate acid, and in the right, we have conjugate base. So how do you convert an acid to a base? You have to remove the H plus. So take off H plus from HF, and you get F minus. F minus is the conjugate base of HF. Take off one hydrogen from H2S, and you get HS minus. The hydrogen sulfide ion is the conjugate base of dihydrogen sulfide. Ammonium, the conjugate base would be ammonia. Notice that we go from +1 to 0 as far as the charge. And then the hydrogen carbonate or bicarbonate ion, its conjugate base would be carbonate. Notice I went from -1 to -2. So removing H plus. How do I go from the conjugate base back to the conjugate acid? All you have to do is add H plus to the formula. So this is acetate, C2H3O2 minus. There is acetic acid, the conjugate acid. Notice I have no charge now on the formula because I was -1 and I added H plus. HPO4, that's hydrogen phosphate. It has a 2- charge. If I add one more H, now it has a -1 charge. This is called methylamine. We've seen that before in other videos. This is the methylammonium ion. So I added the hydrogen to the nitrogen and I changed the charge from 0 to +1. And then sulfate is a base. The conjugate acid would be hydrogen sulfate. So I added hydrogen and I changed the charge from -2 to -1. For more practice with acid-base reactions, I'm giving you the following. Each of the following reactions contains hydrochloric acid, HCl, as a reactant. However, only one of these reactions is classified as an acid-base reaction. So which of these three reactions is an acid-base reaction? Justify your answer. So feel free to pause the video, figure out which one you think is an acid-base, and then press play when you're ready to check your answer. Hydrogen is transferred from the HCl to the OH, that's a hydroxide ion, to produce water. So this is an acid-base reaction. And I will teach you in this lesson today that this first one is an example of redox or oxidation reduction, and this one here in the middle is an example of a precipitation reaction. And if I don't want to write out the word precipitation all the way, I might just write that as PPT for short. So that one at the bottom, the barium hydroxide plus the hydrochloric acid to produce barium chloride and water, that was an example of an acid-base reaction. A Bronsted-Lowry acid-base reaction always involves the transfer of H plus or proton from the acid, the proton donor, to the base, the proton acceptor. Often, a Bronsted-Lowry acid-base reaction involves the formation of water, but not always. An acid-base reaction always involves the formation of an ionic compound or salt. So here, for example, we have a base that does not contain OH minus. This is ammonia. Here we have the acid. So when the proton is transferred from the acid to the base, we get the ammonium chloride as our product, and that would be a salt or an ionic compound. So sometimes we produce water in an acid-base reaction if we have H plus and OH minus, but not always. If there's no OH minus, then you're not going to make water. All right, another example of practice. Feel free to pause the video when you're ready to check your answer. Which one of these three reactions that contains sulfuric acid, H2SO4, is actually an acid-base reaction? All right, if you've paused the video and hopefully had a chance to think about this before I reveal the answer, we can see a similar transfer of a proton from H plus to OH minus to produce water. So this was an acid-base reaction. This was another example of redox, and this was an example of a precipitation reaction. All right, let's talk about redox. So oxidation reduction or redox involves the transfer of electrons from one substance to another. There is one species that loses electrons and that is said to be oxidized, and then then another species that gains electrons is said to be reduced. So another way of thinking about this in terms of oxidation is there's something called the oxidation number, and the oxidation number will go up in value when it's being oxidized, and the oxidation number will go down in value that's being reduced. All right, here's an example of a redox reaction. This is a piece of magnesium, and magnesium is being burned in the presence of oxygen gas, and the product of this reaction is magnesium oxide. Here's your balanced chemical equation, so Mg plus O2 to make MgO. The magnesium is being oxidized from 0 to +2, and the oxygen is being reduced from 0 to -2. Another example of a redox reaction is the reaction between sodium metal and chlorine gas to produce sodium chloride. In this reaction, sodium is oxidized from 0 to +1, and chlorine is reduced from 0 to -1. Now there is a helpful mnemonic device that you may have already learned in your chemistry class for the difference between oxidation and reduction as it has to do with losing or gaining electrons. So here's a picture of what you might recognize to be an oil rig. An oil rig is our mnemonic device. Oxidation is the loss of electrons, reduction is the gain of electrons. Now I'm talking about oxidation numbers. It is an important skill for you to be able to examine a chemical formula and assign the oxidation numbers to each element within that formula. So let's talk about some rules for assigning oxidation numbers. If you have an atom in its elemental form, the oxidation number is always 0. So hydrogen, lithium, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminum, etc. These are all 0 in their natural state. For a monoatomic ion, what you see is the oxidation number, that is the charge on the ion. So nitrogen in this case is -3, oxygen -2, fluorine -1. These are all monoatomic ions, +1, +2, +3, etc. Now for a compound, fluorine being the most electronegative element on the whole periodic table is always -1 no matter what it bonds with. You might wonder about this particular substance over here, these substances. Nitrogen actually carries an oxidation number of +3 in that compound because fluorine is -1. Oxygen would carry an oxidation number of +2 in oxygen difluoride, again because fluorine is always -1. Now for halogens such as chlorine, bromine, iodine, they are usually, but not always, -1. If chlorine, bromine, or iodine are bonded to oxygen or fluorine, then they will have a positive oxidation number. So here this is normal. This is HCl. H is +1, Cl is -1. This is also normal and typical. Sodium is +1, bromine is -1. Another example of a normal, typical, magnesium +2, iodine -1. But these are a little strange. So chlorine here would actually be +1, bromine here is going to be +5, and iodine here is going to actually be +7. I'm going to give you some practice with how you can figure out the oxidation number within a compound because I did that really fast and didn't break it down for you. So if you're confused about why is chlorine +1 or bromine +5 or iodine +7 in these compounds, let me give you some practice a little bit where I can slow that process down. All right, here we have more examples of some rules and I'll give you some practice. Hydrogen is normally +1 except when it's bonded to a metal. So in this situation, the alkali metal sodium is going to be +1 and that makes the hydrogen -1 when it's bonded to a metal. The alkaline earth metal calcium is +2 and that makes the hydrogen -1 when it's bonded to a metal. So in general, in terms of rules, hydrogen is usually +1. In general, oxygen is usually -2 except for that weird example I showed you earlier where oxygen was +2 because it was bonded to fluorine. Here's another weird example and that is right here. So if hydrogen is +1, that means that this half of the formula would be +2. That makes this half of the formula -2. So if you have what's called a peroxide compound, H2O2 is hydrogen peroxide, then oxygen would actually be worth -1 in that particular compound. All right, let me go and break it down for you. I've got KMNO4. Now potassium is obvious and oxygen is obvious, but manganese is we don't know. So potassium is +1, alkali metal. Oxygen is normally -2. Manganese is we don't know. Well, how many oxygens do we have? We have 4 of them. That's -8. That's going to make the manganese in this particular compound +7, since in a neutral compound, the sum of the oxidation numbers of all the atoms equals 0. All right, another example. Sodium is normal, oxygen is normal, and chlorine is going to be a little different. Okay, you can't have chlorine being -1 in this particular example because it is bonded to oxygen. So sodium is an alkali metal +1, oxygen is normally -2. Nothing strange about that. So what is our chlorine's oxidation number? Well, if you do the math to get a total charge of 0, that's going to make the oxidation number of chlorine within this formula +1. So what happens if you have not a neutral compound, but if you have a polyatomic ion? Well, if you have a polyatomic ion, then the sum of the oxidation numbers is not going to equal 0, but rather the overall charge on the ion. So here I have bromine, which I'm not sure what its oxidation number is yet. I think it's +, something, but I'm not sure. And I've got 3 oxygens, that's -6. Now, if you think the bromine is going to be +6, remember that the overall charge of this ion, the bromate ion, is -1. That's going to make bromine +5 in this case to make the overall charge equal to -1. Here we have another example of the dichromate ion. We've got oxygen, which we know is typically -2. Here we have chromium, which we don't know. There are 7 oxygens, so 7 times -2 is -14. The 2 chromiums together are not going to be +14, but rather +12. That means that the overall charge of each chromium, or the overall oxidation state of each chromium, is going to be +6. All right, continuing with redox. A student made the claim that the reaction shown below is a redox reaction. Do you agree with the student's claim? Justify your answer in terms of the oxidation numbers. So let's break it down one at a time. Okay, now iron can sometimes be +2 or +3, but sulfur as a monoatomic ion is typically, sulfide is -2. That forces the iron to be +2 in that particular formula. Hydrogen is normally +1, so we'll go ahead and say +1. Oxygen is normally -2, and we have 3 of them, so that's -6. That makes the nitrogen +5. Now on the other side of the equation, we still have that same NO3 ion. Nitrogen will still be +5 in the nitrate ion. So nitrogen is not changing. The iron is bonded to 2 nitrates that are each worth -1. That means that the iron has to balance the 2 nitrates. So iron is not changing either. And for hydrogen and sulfur, it's looking like each hydrogen is worth +1, and each sulfur in this case is -2. So having done a quick little analysis of the oxidation numbers, I disagree with the student's claim. This is not a redox reaction because the oxidation number of each element remains constant in this reaction. Now earlier in this presentation, I showed you 3 reactions, and we called this one acid-base, and we call this one a precipitation reaction, and this one is redox. So it's zinc that is changing, and it's hydrogen that is changing. It's kind of obvious that hydrogen is changing because it goes from a compound to an element, and it's kind of obvious that zinc is changing because it's going from an element to a compound. So zinc is being oxidized from 0 to +2, and hydrogen is being reduced from +1 to 0. If you recall earlier in this lesson, I showed you another set of 3 reactions. We called this one acid-base, we called this one a precipitation reaction, and now here we have another example of element to compound and compound to element. So another example of a redox equation. Here the hydrogen is being reduced from +1 to 0, and the aluminum is being oxidized from 0 to +3. Now with respect to redox reactions, you can split them up into what are called half reactions. So here's an oxidation half reaction, and here's a reduction half reaction. Remember, oxidation is the loss of electrons, and reduction is the gain of electrons. But notice that when I balance this equation, to get the charge and the atoms balance, I have a different number of electrons. So I have 2 electrons lost in the oxidation half reaction, and I have 4 electrons gained in the reduction half reaction. So if you're going to add 2 half reactions together to get an overall equation, the number of electrons lost should be equal to the number of electrons gained. So I'm going to have to multiply my oxidation half reaction by 2, so now it looks like this, to get the electrons to cancel out. And if you add these 2 equations together, I get 2Mg plus O2 makes 2 formula units of magnesium oxide. All right, so more example with oxidation reduction. Here I have iron that is being reduced from +3 to +2. I have tin that's being oxidized from +2 to +4. Now, as a result, I'm going to have to multiply the top reaction by 2 to get the electrons to cancel out. And now when I add these equations together, the electrons cancel out. Notice that the total charge on the left side of the equation would be +8, and the total charge on the right side of the equation is also +8. So don't forget when you're balancing equations that you balance both in terms of atoms and charge. Now, this reaction also features oxidation and reduction, but these are a little more complicated. Here we have nitrogen going from +5 to +2. That's going to involve 3 electrons. Here we have arsenic going from +3 to +5. But since 2 arsenic atoms are being oxidized from +3 to +5, that means I need a total of 4 electrons. Now, if you're looking at this equation, we have to multiply to get the electrons to cancel out. The top reaction is multiplied by 4, and the bottom reaction is multiplied by 3. Then when I add these equations together, the electrons should cancel out. What do you think I'm going to do with the fact that I've got water on both sides of the equation, and that I've got H+ ions on both sides of the equation? Well, all we do there is we simplify. So 15 minus 8 would be 7 waters on the left. I still have the 4 nitrate ions. 16 minus 12 would be 4 H+ ions on the left. I still have my 3 units of As2O3. And on the right, I have those chemicals there. The total charge on each side of the equation happens to be 0 because I have 4 -1 nitrate ions and 4 H+ ions. So total charge is 0 on both sides. That equation is fully balanced. All right, we talked about in the lesson yesterday about precipitation reactions in which you form an insoluble or slightly soluble compound. I've already said that the solubility rules include sodium, potassium, ammonium, and nitrate. These compounds are always soluble in water. So here are 4 examples of precipitation reactions. The common feature in a precipitation reaction is that there should be a solid product. And as I gave you lessons yesterday about net ionic equations, you could pause the video right now and write the net ionic equation for each one of these 4 reactions, where the compound that I circled is going to be the only chemical that is featured on the right side of the equation. So if you pause the video to write the net ionic equations on your own, I'm now going to reveal the answers. So net ionic equations look like the following. And again, notice that these are balanced in terms of both atoms and charge. All right, final debrief and summary. We talked about stoichiometry, titration, acid-base, redox, and precipitation reactions. Here is your AP exam practice problem for homework. So I'll give you a chance to take a screenshot. There are several screenshots here, several slides. So this is the first one. Here is the next one. And what I have done is I've zoomed in on the next slide here because it's kind of hard to read those burettes. So here is a zoom in of that. And your final screenshot is this one. Okay, well again, this comes to the end of the virtual chemistry lesson for today. Remember, there is a link to helpful chemistry resources in the video description. This has been Michael Faribault from Albemarle High School in Charlottesville, Virginia. Don't forget to go to cb.org/tech for any needs of mobile tools or connectivity. Thanks for watching. Hello everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, the topic of our lesson will be in Unit 8, Acids and Bases, and we'll be talking about buffers today. I want to remind you that you can visit apstudents.org/exams2020 for more information about the at-home online AP exams. So get more information at apstudents.org/exams2020. Hopefully you have access to a periodic table and some scratch paper and something to write with. Let me give you an overview of today's lesson. This topic, which is from topic 8, or Unit 8, I should say, from the AP Chemistry curriculum, covers acid-base reactions and buffers, pH and pKa, properties of buffers, and Henderson-Hasselbalch equation. Just a note about this particular topic. This will not be included on the AP Chemistry exam for this year. So the AP Chemistry exam covers Units 1 through 7. However, if you plan on taking any courses in college on chemistry, general chemistry, organic chemistry, this is a very relevant topic. So some of the topics that we present in these virtual lessons are topics that, while they may not be featured on the AP Chemistry exam for this year, are nonetheless important for concepts in chemistry as well as you might need them in your courses in college. All right, so we'll talk about the definition of a buffer today and examples of buffer solutions, the relationship between pH and pKa, how to prepare a buffer solution, the addition of a strong acid or a strong base to a buffer solution, how exactly does a buffer solution resist changes in pH, and the Henderson-Hasselbalch equation. For our warm-up problem today, this will be a review of the homework problem that I set for you during the last lesson. And if you recall, it had to do with a reaction involving oxalic acid, H2C2O4. It reacts with potassium permanganate, KMNO4, which has a dark purple color. And there is a titration reaction. This particular reaction happens to be oxidation reduction or redox. So part A asks you to identify the species that was reduced in the titration reaction. So we'll start with identifying the oxidation numbers of each element on the left and on the right. Then we can figure out which species was oxidized and which species was reduced. So starting on the left, we have hydrogen, which would be +1. And then we have the permanganate ion, which has an overall charge of -1. Now, within this particular polyatomic ion, oxygen is normally -2 in most of its compounds. So if I have 4 oxygens, that will be -8 altogether. That makes the manganese +7, so that the oxidation states, when added together of all of the atoms, equal the overall charge, in this case, -1. So we have manganese is +7 and oxygen is -2. And then for the carbon in this particular formula, which is called oxalic acid, if we go ahead and say that oxygen is -2 and hydrogen is +1, then this portion of the formula, the 2 hydrogens, would be +2. This portion of the formula, which is the 4 oxygens, would be -8. The overall charge is 0. That means that together, the 2 carbons would have to equal +6. So each carbon has an oxidation state of +3. Now, moving on to the right side of the equation, we have carbon dioxide. So if oxygen is -2 and we have 2 of them, that would be -4 for this half of the formula. That makes the carbon have an oxidation state of +4. Hydrogen is +1. The manganese on this side of the equation has an oxidation state of +2. Oxygen is -2, and again, the carbon would be +4. So as you can see, looking at the left and the right side of the equation, it is the manganese that is being reduced. The carbon is being oxidized from +3 to +4, but the question says, identify the species that was reduced in the titration reaction. Justify your answer in terms of oxidation numbers. So you might say something like this. Manganese is reduced from +7 to +2. The permanganate species, or the manganese itself, the element, is what is actually being reduced. All right, moving on to part B of this question, we have a titration. So we're given a before and an after, an initial and a final view of the burette. And so we have to read the volume, write down the initial reading and the final reading, and use them to determine the volume of permanganate, potassium permanganate, that was added during the titration. So here's a close-up view. So this particular reading here on the burette, we're going to go with the bottom of the meniscus. So somewhere in this range right here, it's going to be between 3.3 and 3.4. So I would estimate that to be 3.35. We go to 2 decimal places when we read this burette. And then over here, I would say that looks like it's kind of halfway between the 2 hash marks, between 29.5 and 29.6. So the bottom of the meniscus, I would read that at 29.55. So the volume of KMNO4, the aqueous potassium permanganate that was added during the titration, is simply the difference between these two readings. So based on the readings that I have given you, I said 26.20. The AP exam would accept a range of answers that, depending on that final digit, had you said, for example, 29.54 or 29.56, then they would accept anything in that range is fine, but 2 decimal places for sure. Now, what are we going to do with this particular volume of potassium permanganate? Well, we are given that the concentration of the potassium permanganate was 0.0235, and that's moles per liter. Let's calculate the number of moles of potassium permanganate, or just permanganate ions, that was reacting in this particular experiment. So we take our volume from part B, we convert milliliters to liters, and then convert liters to moles using the molarity as a conversion factor. So 0.0235 moles of potassium permanganate for every 1 liter. Now, the permanganate itself is essentially present in the formula potassium permanganate. So there is 1 permanganate ion, MnO4 minus, for every 1 formula unit of KMnO4. If we do this math, 26.20 divided by 1,000 times 0.0235, we get our answer, which happens to be 6.16 times 10 to the minus 4 moles of permanganate. Now, that was used in this experiment. If we were asked to calculate the number of moles of oxalic acid, then we could do a mole-to-mole conversion involving these coefficients. Or we could also convert to moles of carbon dioxide, or water, or the manganese 2+ ion. Essentially anything else in this equation we could use based on that mole-to-mole ratio. But the question is asking us in part D, a student proposes to perform perform another titration. Now they're not changing the amount of the oxalic acid, but this time they are using a potassium permanganate solution that is different. And if you look carefully at this concentration, you will notice it is much more dilute than the solution that was used in part C of this problem. So here's the question. Would this titrant concentration, this 0.00143 moles per liter, would that be a reasonable choice to use if the student followed the same procedure and used the same equipment as before? Now when we say same equipment, remember that these burettes, they only hold 50 milliliters. That's the volume of the burette, 50 milliliters. So let's think about what our answer is to part D and if this is reasonable. So in part D, I'm going to take the number of moles I obtained from part C and simply convert from moles to volume using the molarity in this problem as a conversion factor. Now when I do this math and I go from moles to liters to milliliters, I get an answer that is rather large, 431 milliliters. So the answer to this question, would this be reasonable? No. This titrant concentration would not be a reasonable choice. The solution is very dilute and the volume of titrant needed in this titration is much greater than the 50 milliliter capacity of the burette. All right, well that takes care of the homework problem. Now let's go on to what you need to know about buffers. So we'll start with the definition of a buffer. So a buffer, a pH buffer, is a solution that resists changes in pH when a small amount of a strong acid or a strong base is added to the solution. Typically, a buffer solution contains a weak acid and its conjugate base. Well, if you don't remember what exactly a strong or a weak acid is, let's talk about that. I'm going to give you 8 examples of acids: hydrochloric, hydrobromic, hypochlorous acid, hydrocyanic acid, hydrofluoric, acetic acid, nitrous acid, and nitric acid. Which of the following are strong acids and which of the following are weak acids? So take a moment to consider that question. Now, if you don't remember the strong acids, I will tell you that the strong acids, the 6 strong acids, are the following: HCl, HBr, HI, HClO4, H2SO4, HNO3. So these are the 6 strong acids. That's going to make HCl, HBr, and HNO3 examples of strong acids, and the other 5 acids are examples of weak acids. You may recall in an earlier video when I was talking about acid-base reactions from Unit 4, we had talked about the conjugate acid and the conjugate base. So this table might look familiar from an earlier video from Unit 4. Now that I've given you these 8 acids, and we know how to figure out the conjugate base by simply pulling off the H+, let's take a look at the conjugate base for all 8 of these acids. So the conjugate base would be chloride, bromide, nitrate, nitrite, NO2-, the hypochlorite ion, OCl- or ClO-, the cyanide ion, Cn-, fluoride, and acetate. As far as making a buffer solution, it is better to use a weak acid, weak base combination. So since these 3 are strong acids, this combination would not make a good buffer solution. And I'll explain more about why a strong acid would not be appropriate in a buffer solution a little bit later in this lesson. But for right now, let's take a look at these 5. So these are weak acids, so that combination would make a good buffer solution. So where are we going to find a source of NO2-, or the hypochlorite ion, OCl-, or the cyanide ion, or the fluoride ion, or the acetate ion? Well, we might find them in the sodium salt of that particular compound. So if I want to make a buffer using a weak acid and its conjugate base, then I could combine a solution of, for example, nitrous acid and sodium nitrite, or hypochlorous acid and sodium hypochlorite, hydrocyanic acid and sodium cyanide, hydrofluoric acid and sodium fluoride, or acetic acid and sodium acetate. Now you don't have to use sodium, you could use another ion, for example, potassium or lithium. I just picked sodium as a simple example of a common alkali metal cation. Now that I have created a buffer, 2 questions that I have to make sure that I explain in this lesson. How would you figure out the pH of these buffer solutions? And then why exactly do they behave as a good pH buffer solution? How exactly does a buffer work? So I'll start with the first one on that list. So we have HNO2, which we know is a weak acid. That's called nitrous acid. And here's an example of why nitrous acid is a weak acid. As it reacts with water, notice the double arrows indicating equilibrium. It produces the hydronium ion and the nitrite ion, NO2-, and there is a Ka, which is an acid dissociation constant. Now the magnitude of that Ka is rather small, indicating that it's a weak acid. So in general, weak acids tend to have rather low values for the Ka. We can write the Ka expression, that would be products over reactants, and then we can talk about plugging in the numbers for this particular buffer. Well, the concentrations are 1 and 1. Well, since they cancel out, that means that the hydronium concentration is exactly equal to the Ka of this particular acid. So 4 times 10 to the minus 4. If that is the concentration, recall that we go from hydronium concentration to pH by taking the negative log of the hydronium concentration. So the negative log of 4 times 10 to the minus 4. If you take a moment to do this on your calculator, negative log of 4 times 10 to the minus 4, you should get a pH of approximately 3 point something. So if you're following along with your calculator and you've done this math, your pH of this buffer solution is 3.40. So something important to mention here is that when the concentration of the acid, the weak acid, is the same as the concentration of the conjugate base, because of these numbers canceling out here, the pH will be equal to the pKa of the acid. That is an important concept as it relates to buffers. So I have a table here with the Ka values listed for nitrous acid, hypochlorous acid, hydrocyanic acid, hydrofluoric, and acetic acid. If you take the negative log of these numbers, you will get the pKa of the weak acid. So the negative log of 2.9 times 10 to the minus 8 is 7.54. The negative log of 6.2 times 10 to the negative 10 is 9.21. So again, if you need to pause the video to go ahead and take the negative log of these Ka values, feel free to do that. The negative log of the Ka for hydrofluoric acid works out to be 3.17, and the negative log of the Ka for acetic acid is 4.74. Since each of these buffers has the same concentration of both the acid and the conjugate base, then that means that the pH of these buffers would be the same as the pKa of the weak acid. Well, what if they're not the same? Let's talk about that. So if the concentration of nitrous acid is the same as the concentration of nitrate, then H3O plus or hydronium equals the Ka and the pH equals the pKa. But what if they are not the same? So we have some examples here where the concentration of the weak acid is not the same as the concentration of the conjugate base. So make a prediction. And again, feel free to pause the video to do this. Will the pH of these other 2 buffer solutions in which the concentration of the weak acid is different from the concentration of the conjugate base, will the pH be less than or greater than 3.40? All right, well, assuming that you have had a chance to make your prediction, in this next buffer we're looking at in the table, it looks like we have more acid than base. So when you have a greater concentration of the weak acid compared to the weak base, then your pH should be less than the pKa. But if instead you have a concentration of the weak base that is greater than the concentration of the weak acid, then your pH should be greater than the pKa. Now that's just a prediction. That's just based on a conceptual understanding of more acid than base, pH is less, more base than acid, pH is greater. But let's go ahead and do the math. Let's plug in the numbers 1.2 and 0.8 into the Ka expression and see if our predictions are correct. So we have 0.8 for the concentration of the NO2-, and we have 1.2 for the concentration of the HNO2. So pay attention to why I put the numbers 0.8 and 1.2 into those positions. Now we'll go ahead and do the math and see what we get. So H3O plus or hydronium is equal to 6 times 10 to the negative 4. If you do this math, multiply both sides by 1.2, divide both sides by 0.8, take the negative log, and we get a pH of 3.22, which is exactly what we predicted. We thought it was going to be less than 3.4, and it is. Now let's go ahead and flip-flop the 1.2 and the 0.8 because now we've switched those concentrations around. So plugging those numbers into the expression, now we have more base than acid. Multiply both sides of the equation by 0.8, divide both sides of the equation by 1.2. Now we get a hydronium concentration, which is 2.7 times 10 to the minus 4 moles per liter. Take the negative log, and hopefully the pH will be greater than 3.4. And in fact, it is. So let's kind of summarize here the relationship between pH and pKa in general terms. So we have a generic Ka expression. If the concentration of the weak acid HA in general is equal to the concentration of the conjugate base A minus, then the pH equals the pKa. If you have more acid than base, your pH will be less than the pKa. And if you have more base than acid, your pH will be greater than the pKa. So that relationship is a very important concept for you all to understand. And you don't have to do any math to actually understand that concept. All right, how would you prepare a buffer solution? Where there are 2 common methods to prepare a buffer solution. Method number 1, you simply take 2 different sources. One solution that contains the weak acid HA, and then another separate solution that contains the conjugate base A minus, and you mix them together. So for example, I might start with 500 milliliters of 2 molar molar acetic acid. I might find another solution, 500 milliliters of 2 molar sodium acetate. If I combine these two solutions together, I will have 1 liter of a solution that now has a concentration of 1 molar acetic acid and 1 molar sodium acetate. Simply because I diluted it by mixing equal volumes, I have now cut the concentration of each of those components in half. So I made a good buffer by simply mixing two solutions together. Now the two solutions do not have to have the same concentration necessarily. So for example, I might pick a solution that has 2.4 molar acetic acid and combine that with a solution that is 1.6 molar sodium acetate. I would get 1 liter of a solution that now has a slightly greater concentration of acetic acid as compared to sodium acetate, but I would still have a good buffer solution. So method number 1 is to mix two solutions together, one that contains the weak acid and the other that contains the weak base. Another method you can use to make a buffer is you start with a solution that contains the weak acid and then you start to neutralize. Now to neutralize the weak acid, you don't want to neutralize it all the way. In other words, you don't want to convert all of the HA into A minus. So you'd like to have a reaction between the strong base that will neutralize some, or in this case, let's say half of the weak acid. If you can neutralize half of the weak acid, then you will have a mixture that contains some HA and some A minus. So you're starting with a solution that contains a weak acid and adding a strong base until half of the weak acid has been neutralized. So I might begin, for example, with 100 milliliters of 2 molar acetic acid, and I might add 100 milliliters of a solution of 1 molar sodium hydroxide. Now because the concentration of hydroxide is only 1 molar, it's not going to neutralize all of the acid. It's going to neutralize half of the acid. I would finish with a final solution that has a volume of 200 mils, and the concentration of the weak acid and the conjugate base will be equal. You might wonder, where exactly did I get the 0.5 molar? Let me go ahead and show you this. I'm going to remind you of something I had presented in an earlier lesson. This is called a Rice table, which stands for reaction, initial concentration, change in concentration, and equilibrium concentration. So if I have 100 milliliters or 0.1 liters of a 2 molar solution of acetic acid, 0.1 times 2 is 0.2. I would start off with 0.2 moles of acetic acid. If I had 100 milliliters or 0.1 liters of a 1 molar solution of sodium hydroxide, 0.1 times 1 is 0.1, I would have 0.1 moles of hydroxide ions. Now initially, let's assume I don't have any acetate because the reaction hasn't occurred yet. Well, the concentration of acetic acid would go down by 0.1. The concentration of hydroxide would also go down by 0.1. And because I'm producing acetate, the concentration of the acetate would go up by 0.1. I'm writing moles as opposed to molarity, but it could be the same thing. I'm just using moles to keep it simple here. So as you can see in the final row of this Rice table, the concentration of the acetic acid would be the same as the concentration of the acetate. But where did I get that 0.5 from? Well, the total volume is 200 milliliters. That would be 0.1 moles of solute divided by 0.2 liters of solvent. So that's where I got that 0.5 in my calculation. So again, method number 2 would be to start with a weak acid, add a strong base until half or approximately half of the weak acid has been neutralized, and now you have a good buffer. Now, since we're talking about neutralizing an acid, let me remind you of something that I had presented in Unit 4 on chemical reactions. Here is a setup for a titration. Suppose we have a sample of a weak acid HA in a flask, and then we put sodium hydroxide, a strong base, in a burette, and we do a titration. You'll notice I have particle diagrams on the left side of the screen. The particle diagrams indicate molecules of HA, ions of the conjugate base A minus, and then we have sodium hydroxide ions as well. So let's look at a particle view, a close-up view of what does the flask look like before the titration starts. Well, before the titration starts, we have a predominant species in solution, and that is the HA, the weak acid, because we haven't done the titration yet. The major species present in solution besides water molecules would be the HA, the weak acid molecules. So what's going to happen when we reach the equivalence point in the titration? Well, at the equivalence point in the titration, all of the HA should have been converted into A minus. That means it will also have not sodium hydroxide, but just sodium ions present because the hydroxide, OH minus, reacts with the HA and it produces A minus. So you're seeing A minus and sodium ions present. I'm not showing water molecules present. The major species present in solution at the equivalence point besides water molecules are the ions, sodium, and A minus, the conjugate base. Well, what happens if you are halfway to the equivalence point? If you halfway neutralize this weak acid, you should have, and you can see here, 1, 2, 3, 4 molecules in the particle diagram of HA, and 1, 2, 3, 4 molecules, 4 ions of the A minus. So as you can see here in the particle diagram, we have an equal number of HA and A minus. So at the halfway point in a acid-base titration, the concentration of the weak acid is equal to the concentration of the conjugate base, and the pH equals the pKa. So this particular region right in here is considered the buffer zone. Now what I'm looking at is a graph where I'm plotting pH along the y-axis and the volume of the titrant, in this case the sodium hydroxide added to this flask, along the x-axis. So the pH does not change very much in the buffer zone because the buffer is doing its job. It's maintaining the pH to stay approximately the same. At the beginning of the titration, you have essentially HA. At the equivalence point, you have essentially A minus. And at the halfway point in the titration, which would be approximately 20 milliliters. So the equivalence point occurs at around 40 milliliters. The halfway point would occur at around 20 milliliters. So at the halfway point, we have this mixture. Since we know that the pH equals the pKa at the halfway point, this is one method for estimating the pKa value of an acid. So you could look at a titration curve, pH versus volume of titrant, and you could find that the sharp rise in pH, this is where the equivalence point occurs. And at the halfway point in the titration, this is where the pH equals the pKa. So this is a method for estimating the pKa of the weak acid. In the region to the left of the halfway point, there would be a greater concentration of HA compared to A minus, and your pH would be slightly less than the pKa. In the region on the pH curve that is to the right of the halfway point, you're going to have a greater concentration of the conjugate base, A minus, than you have HA, and your pH would be slightly greater than the pKa. All right, let's talk a little bit about pH range of a buffer. And there is a pH range, and that is the effective range over which the buffer acts effectively. So buffers come in lots of different varieties, and there's lots of different pH values that you might choose to use. For most buffers, this buffer range, this pH range, tends to be plus or minus 1 unit on either side of the pKa. So for example, if I have a buffer solution that is made from nitrous acid HNO2 and the nitrite ion NO2 minus, then the pH range of that buffer would be approximately between 2.4 and 4.4. In other words, plus or minus 1 unit on either side of the pKa value. If I wanted to make a buffer of around pH 7 or pH 10, I would not choose a nitrous acid sodium nitrite combination. That would not be a good buffer because it would be outside the range. Now, if instead I made a buffer out of hypochlorous acid HOCl and sodium hypochlorite, then based on the pKa value of that weak acid, then my pH range would be approximately between 6.5 and 8.5. If instead I wanted to make a buffer out of hydrocyanic acid and sodium cyanide, then my pH range of that buffer would be approximately between 8.2 and 10.2. Okay, next thing to take a look at is what happens when a strong acid or a strong base is added to a buffer solution. We'll go back to the nitrous acid sodium nitrite example. We know that nitrous acid is a weak acid and the NO2 minus or the nitrite ion is a weak base. So suppose that a small amount of strong acid, in this case, a small amount of hydrochloric acid is added to this buffer. And you could add nitric acid, hydrobromic acid, hydroiodic acid. I just use hydrochloric acid as an example. Write the net ionic equation for the reaction that would occur between HCl and one of the components of this buffer. Now, the HCl is not going to react with the other acid. If you're doing an acid-base reaction, typically you have to have an acid reacting with a base. So the HCl would react with the component of this buffer that behaves as a weak base. On the right side of the equation, I would get HNO2 along with the chloride ion. But remember that we're doing the net ionic equation, so this actually should be split up. Chloride is not going to be featured in this overall net ionic equation. Chloride is a spectator ion. So in fact, the hydrochloric acid can be envisioned as just H plus ions. It is a source of H plus or hydronium ions. It reacts with the weak base to produce the weak acid. So effectively what makes a good buffer is that one of the components is slightly consumed and then the other component is produced use, but we're trying to keep this ratio approximately the same. So the weak base, NO2 minus, will turn into HNO2 molecules of the weak acid. What happens if we had a small amount of strong base? In this case, sodium hydroxide. You also could have used potassium hydroxide or calcium hydroxide. So focusing on the hydroxide and not the sodium as a spectator ion, the hydroxide would react with the weak acid, producing water and the weak base, NO2 minus. So the message here is that when you add either a strong acid or a strong base to a buffer solution, one of the concentrations will go down slightly and the other concentration will go up slightly. So if I add a strong acid to this buffer, the red and the blue rectangles are to indicate same concentration of these two components. After the strong acid is added, the concentration of HNO2 goes up slightly and the concentration of NO2 minus goes down slightly. If instead we add a strong base to this buffer, then the concentration of the weak acid will go down a little bit and the concentration of the weak base will go up a little bit. So how will the pH be affected? When a strong acid is added to the buffer, the pH will go down a little bit because we have more acid than base. How will the pH of the buffer be affected if a strong base is added to the buffer? The pH will go up slightly because now we have more base than acid. So in terms of how exactly a buffer works, we have to talk about the slight change in pH that occurs when either a strong acid or a strong base is added to the buffer. Here, you might be thinking this only works for HNO2 or NO2 minus. No, in fact, on this slide, I just generalized it. So when you have a solution of HA, the general formula for a weak acid, and then the A minus, the general formula for the conjugate base of that weak acid, you can see that adding acid causes the pH to go down a little bit, and adding a base causes the pH to go up a little bit. Let's explore more of the math. How exactly does a buffer solution resist changes in pH? So in this example, we have 1 liter of a buffer. The concentration of HNO2 and NO2 minus are 1 molar, and the pH equals the pKa, which is 3.40. Let's add 1 milliliter of a concentrated solution of HCl to the buffer. Now we know that the acid concentration will go up slightly, so we're going to have more HNO2 than NO2 minus, and our pH will go down, but by how much? Well, if I have 1 mole of each of these buffer components, let's do the math here. I have 1 milliliter, or 0.001 liters of a solution that has a concentration of 10 moles per liter. Well, 0.001 times 10 is 0.01. So we have added 0.01 moles of H plus to this buffer. This concentration will go down a little bit. This concentration will go up a little bit. In fact, by a change of 0.01. So there are the new concentrations after the strong acid has been added. They don't look that different. Let's see what the math works out to be. I'm going to plug these numbers. 1.01 on the bottom because that is the concentration of the nitrous acid, and 0.99 on the top. I'm going to go ahead and solve for the hydronium concentration. And when I do that, take the negative log, I get a pH of 3.39. Did the pH go down? Yes, but that was a very, very small change in pH. So to further emphasize how amazing this buffer solution is, watch what happens if we had added that same amount of hydrochloric acid to pure water. Now, pure water is not a buffer. 0.01 moles of H plus in 1 liter of water is going to have a concentration of 0.01, and when you negative log that number, you get a pH of 2. So think about that. The pH of the buffer went down by 0.01. Now, in pure water, that same amount of acid would cause the pH to go down by 5 pH units. So that was a pretty amazing buffer in that it did not change the pH very much at all. Whereas normally, if that amount of acid had been added to water, the pH change would have been dramatic. Okay, well, just to sort of drop the other shoe, let's go ahead and do that same calculation for what happens if a little bit of sodium hydroxide is added to the buffer. So same kind of calculations as before. In this case, though, our HNO2 will go down slightly, and our NO2 minus will go up slightly. We still have 0.01 moles, but now we have 0.01 moles of hydroxide ions. So again, this concentration will go down a little bit, and this concentration will go up a little bit. So now we have the numbers 0.99 again and 1.01, but they have been reversed. If we plug the numbers in and we do the pH calculation, you can see that the pH goes up, but only slightly. And as you can imagine, what I'm about to show you is what would happen if we had added that same amount of sodium hydroxide to pure distilled water. So pure water, 0.01 moles per liter. Take the negative log, that's the pOH, which is 2. 14 minus the pOH gives us the pH, which is 12. Again, the pH would have changed very dramatically had we added this amount of strong base to pure water, and yet the buffer was able to resist changes in pH. So to summarize graphically, as long as you can keep this concentration of HA and A minus approximately the same, you can get your pH to stay approximately the same. So buffer solution does a good job of resisting changes in pH. All right, I had said earlier that you cannot use a strong acid and its conjugate base to make a good buffer solution. Now, hopefully this will make a little more sense. Here's why. So I'm going to go from nitrous acid, which is HNO2, to nitric acid, which is HNO3. HNO2 is a weak acid, whereas HNO3 is a strong acid. Notice that I have a single arrow here as opposed to a double arrow indicating that this happens 100%. So on the left, we have a weak acid and we have a weak base. On the right, we have a strong acid, and what can we say about the nitrate ion? Well, it's not a base. In fact, it's essentially neutral in solution. It's negligible. That reaction, NO3 minus, does not reverse. So because a conjugate base of a strong acid is essentially neutral or spectator ion, it's not going to be a good buffer because in a buffer you need both the acid component and the base component. So when you use a strong acid and its conjugate base, it will not create a good buffer because you don't have both of those components present in solution. All right, I mentioned we're going to talk about what is known as the Henderson-Hasselbalch equation. What you are looking at right now is the Ka expression for a generic weak acid. I'm going to go ahead and rearrange this equation and isolate H plus on the left. So I'm going to multiply both sides by HA and A minus. I'm now going to take the negative log of both sides of the equation. And when I do that, on the left side of the equation, the negative log of the concentration of H plus is the pH. On the right side of the equation, I have the negative log of this product. You may know this from math class. When you take the log of A times B, it's the same as the log of A plus the log of B. So when you take the log of a product, you can split it up into two separate log expressions separated by a plus sign. That's just one of the properties of logs. So therefore, that's what I'm going to do now. I'm going to split this up. And the negative log of the Ka happens to be the pKa. And now I'm going to go ahead and do another property of logs, which is if you flip a quotient, you can change the sign. So what I'm looking at right now in this white rectangle, this is known as the Henderson-Hasselbalch equation, but you should realize that it can be derived from the Ka expression. And on the AP equations and constant sheet, you will see not only the generic Ka expression, you will also see the Henderson-Hasselbalch equation. So is the Henderson-Hasselbalch equation essential and necessary to use? No. In fact, you could use either one of these. You could use either the Ka or the Henderson-Hasselbalch equation for certain calculations. And in fact, I'm going to go ahead and show you both. So in this example question, it says using the Ka expression to calculate pH, we have a buffer that contains 1.2 molar nitrous acid and 0.8 molar sodium nitrite. The Ka for nitrous acid is 4 times 10 to the negative 4. Let me plug in the 1.2 on the bottom and the 0.8 on the top. I'm going to go ahead and solve for H plus. So I'll multiply both sides by 1.2, divide both sides by 0.8. And when I solve for H plus and I negative log it, I get a pH of 3.22. Now, if the student has a preference for using the Henderson-Hasselbalch equation to do this kind of buffer calculation, the Henderson-Hasselbalch equation doesn't always solve all your problems, but in this particular situation for a buffer solution, you could use it. So here is the Henderson-Hasselbalch equation. The pKa is the negative log of the Ka, which works out to be 3.4. If I plug in my 0.8 on the top and my 1.2 on the bottom, I do the log on my calculator. The log of 0.67 works out to be negative 0.17. And sure enough, I get the same answer. I get the same pH value that I had before. So I've just shown you could solve the problem two different ways. You are not required to use the Henderson-Hasselbalch equation to use. That equation is a fine thing to do for buffers and for other types of calculations, but it's not necessary. Here's another example. I'm going to start with Ka. A buffer solution contains a mixture of acetic acid and sodium acetate and has a pH of 5. If the concentration of acetic acid is 2 molar, what is the value of the concentration of the acetate ion? And incidentally, the Ka for acetic acid is 1.8 times 10 to the negative 5. Well, I can plug in my 2 molar on the bottom, but I can't plug in a value for the acetate concentration since I don't know what that is yet. I do know that the pH is 5. So if the pH is 5, then the H plus concentration is 10 to the minus 5. If the concentration of acetic acid is 2 molar, let's go ahead and plug in what we know. I still don't know the concentration of the acetate, but I know everything else. So I'll go ahead and solve just a little algebra here. And when I get the concentration of acetate, it works out to be 3.6 molar. So could I have used the Henderson-Hasselbalch equation to do the same problem? Yes, and you get the same answer. So the pKa is the negative log of the Ka, which works out to be 4.74 in this case. The pH was given as 5. I know the concentration of the acetic acid on the bottom. I put 2 in there, but I don't know the concentration of the acetate. Let me go ahead and take the take the 10 to the power, raise 10 to the power on both sides. So 10 raised to the left will get rid of that log expression. And on the right side of the expression, I have 10 raised to the 0.26. So what I have done is rearrange the equation by doing 10 to both sides. And when I solve for the acetate concentration, sure enough, I get the same value. All right, last comment I want to make, and we'll get to our homework. We have seen some examples in this lesson of buffers where you start with a weak acid and you combine it with a conjugate base. You might be wondering, what about a weak base, such as ammonia or methylamine? Could you start with a weak base and combine it with the conjugate acid, for example, ammonia? And the answer is yes. So what I'm showing here on this table is 4 examples. We have 2 examples of a weak acid and we have 2 examples of a weak base. I'm giving you the Ka for the weak acid, and let's see if I can figure out what the Kb for the weak base is. So using this equation, 10 to the negative 14 is equal to Ka times Kb. I can do that math. 10 to the negative 14 divided by the Ka value. And I've done that on my calculator, and this is what I got. Also, pKa plus pKb equals 14. So 14 minus 3.4 will get you 10.6. Similarly, if I'm given the Kb, I can do 10 to the negative 14 divided by the Kb, and I will get the Ka value for the conjugate acid. So 9.25 plus 4.74 equals 14. So any one of these 4 combinations would be a good buffer. Nitrous acid plus nitrite, hypochlorous acid plus hypochlorite, ammonium and ammonia, the methylammonium ion and methylamine, and the pH of those buffers, assuming you have a 1-to-1 mole ratio. The pH of the buffer would equal the pKa of the conjugate acid. All right, well, that concludes our lesson on buffers. I talked about the definition of a buffer and examples of buffer solutions today. We talked about the relationship between pH and pKa, how to prepare a buffer solution, what happens when you add either a strong acid or a strong base to a buffer, how exactly does a buffer solution resist changes in pH, and we looked at the Henderson-Hasselbalch equation. So now for your homework lesson for tomorrow, I have 4 problems. They are parts A, B, C, and D. Answer the following questions that relate to a buffer solution that contains a mixture of hydrofluoric acid, HF, and sodium fluoride, Na. I'm giving you the Ka value for the hydrofluoric acid. So this is part A, this is part B, this is part C, and this is part D. So that is your homework question for tomorrow. Mr. Byrne will be teaching the lesson tomorrow and go over the answers to that particular homework problem. Again, a reminder about the helpful chemistry resources. You can find that link in the video description. Thanks for watching. This has been Michael Faribault from Albemarle High School in Charlottesville, Virginia. Reminder to go to cb.org/tech if you need mobile tools or connectivity. Thanks for watching.
Good morning, everybody, and welcome to Tuesday, April 14th lesson on AP Chemistry. We're very excited to have you back today. Lots of great material for you about kinetics. Moving on to a new chapter, and we're really excited to share with you. My name is Mr. Byrne. I'm coming at you from Glenbard West High School, just outside Chicago in Glen Ellen. Go Hilltoppers. Like I said, we're moving on to Unit 5 today, which is all about kinetics. Really nice, neat look at some equations, some connections back to your math classes, and some new ways of looking at equations from what we've looked at before. So, like I said, I'm really excited to share this with you. Just a couple of quick reminders, like we want to tell you about at the beginning of every lesson. apstudents.org/exams2020 is your go-to for all sorts of information on all these topics that I listed over here on the right-hand side. If you have any questions, either check these out, send it to your teachers. You can log into this FAQ page and get lots of information about any questions that you have. Get ready for our exams coming up. Hope you have a big smiley face target on Thursday, May 14th, 2020 for our testing date here in Chicago. We're going to be taking it at 1 o'clock, but based on your time around the world, you're going to be adjusted to a different time. We're all going to be taking the test at exactly the same time, so we're excited to tackle that in just exactly a month from today, right? There you go. Very excited. The format, just to remind you, you got 2 questions. You'll have 25 minutes to read and respond to the first one, 15 minutes to read and respond to the second one, and the focus really is going to be on your ability to explain phenomena, draw conclusions, analyze systems, support claims. So I hope that you've seen a lot of examples of how we're having you practice that over the past couple of weeks, and we'll continue to do so as we are planning more and more lessons for you. Okay, so let's get to our lesson overview. We'll start today just like we start most days with a warm-up and a review of yesterday's lessons from Mr. Faribault. We'll go through what you need to know and some practice, and then we'll finish up with some AP exam practice. Feel free at any point, like we remind you every day, you can stop this and review something that we said. If we're going too fast, if I ask you to do a problem, then you should absolutely stop, try to do it, have a piece of paper, scratch paper. Today, you shouldn't need a periodic table, but never hurts to have one. If you have a copy of your equation sheet from AP Chemistry, that would be a great thing for you to have next to you too, so I'm going to point out a couple of things. And as you probably noticed over the past couple of days of my lessons, I've been relying on this open source textbook, OpenStax. Just a couple of images for today, but a couple of ideas that were really good in their text, and I want to share them with you as well. If you don't have your textbook at home, this is a great one to look at, but as usual, refer back to your textbook as a good resource for you, usually whenever you need it. Okay, so the topics we're going to look at are the first 3 topics in Unit 5 on kinetics, reaction rates, rate laws, and concentration changes over time. We'll be looking at integrated rate laws, how they differ from the rate law proper. And the skills we're looking at, you can see listed over here on the side. Provide a reasoning to justify a claim, relationships between variables. So we've hit this one a lot lately. That was a great one. And then identifying theories, definitions, and mathematical relationships. There's going to be a lot of connections between 5C and 5B. So our warm-up is just a review of those problems from yesterday. If you have not had a chance to try these on your own, it's a great idea to stop at this point. Go back and look at yesterday's lesson. You can even, if you just want to look at the homework, zoom to the end and pick up those homework. I will project just the problems, so this would be a great opportunity for you just to stop and take a look, try to answer the question on your own before you move on. So all the questions, I think we have 4 of them today, have to do with a buffer solution. There's a great lesson yesterday from Mr. Faribault on buffers. And this particular buffer contains hydrofluoric acid and sodium fluoride. So you remember the best buffers are going to have a weak acid in them and a salt that contains the conjugate base of that weak acid. The Ka is given to us here of HF. The pKa, which is be the negative log of this number, is equal to 3.17. So they gave us that number for us. And then the diagram is shown here as a particular representation of a buffer solution. Based on the information in the diagram, do you predict that the pH of the solution should be less than, equal to, or greater than 3.17 and justify your answer? So one of the key things that I heard from Mr. Faribault yesterday was this idea that we can analyze the concentrations of the acid and its conjugate, and that we know that if we have gotten to a position in this may be a titration, this might be just analyzing a solution where the concentration of the acid is equal to the conjugate base, then the pH is equal to the pKa. So we're looking at a comparison between the 2 concentrations. If we have more acid than conjugate base, we know that the pH is greater than the pKa, and if we have more conjugate base than acid, we know the pH is greater than the pKa. I think maybe I said that the wrong way. We know, and go back here. If our acid is greater than our conjugate base, our pH is less than, and if our conjugate base is greater, then our pH is greater. Okay. So what we would want to analyze over here is what is the ratio of hydrofluoric acid, excuse me, which is our weak acid, as related to our conjugate base. So we would count them up: 1, 2, 3, 4, 5, 6, 7, 8. We have 8 fluoride ions for only 4 HS for hydrofluoric acids, and so we can conclude that the fluoride ions are greater than the concentration of HF, and so therefore the pH of the solution should be greater than 3.7. Okay. Moving on to number 2, buffer solution is made by mixing equal molar amounts of these things. And when a small amount of 12 molar nitric acid is added to the buffer, seem to remember a couple of problems like this from yesterday, the pH of the solution changes from 3.17 to 3.15. We're to balance an ionic equation that accounts for the fact that the pH does not change significantly when the HNO3 is added to the buffer solution. And so our answer here talks about how we have a few fluoride ions that are floating around in solution, and the hydrogens are going to be eaten up by those fluorides to create HF. This HF, because it is a weak acid, that means there's a strong bond between the hydrogen and the fluoride, And so they are hydrogen fluoride or hydrofluoric acid is going to stick together more than it's going to be separated. And when they're given the opportunity, they're going to bond to one another. So there is our balanced net ionic equation. So we know we have our ions here. Okay, the sodium would be a spectator ion here. The nitrate would be another spectator ion here. So you may have started this by looking at the complete ionic equation and then broke it down to the net ion. But those spectator ions, they're just watching what's happening. They're not really involved in the reaction per se. Third question, determine the volume in milliliters of 10.0 molar NaOH that should be added to 1,000 milliliters of 1.0 molar HF to create a buffer solution that has a pH of 3.17. Justify our calculation. So the first thing we want to remember is that the desired pH is 3.17, so it's equal to the pKa of hydrofluoric acid. And so how do we get there? If we want the pH to be equal to the pKa, we need to prepare a solution in which our concentrations of HF and our concentrations of fluorides are equal to one another. So that goes back to a couple things I said a couple of slides ago. We discussed that kind of pretty thoroughly yesterday. So half of the moles of HF must be converted to F minus, right? And then here's the equation. This is the neutralization equation that's going to tell us how we convert HFs into fluorides, right? So for moles of HF, how did we get this? Let's look back up at our equation up here. We have 1 liter. 1,000 milliliters is 1 liter of 1 molar HF. So we have 1 mole of HF. So the moles of HF or NaOH that are needed would be half of that, right? So we want half of them to be used up. So HF is equal to 2.5 moles of NaOH. And how are we going to get that volume of 10 molar NaOH that's needed? We would take the moles times the inverse of molarity to get to the liters. Okay? And then if this is our liters, we're going to convert that into milliliters because the question up here asked us to do it in milliliters. So 0.05 liters is equal to 50 milliliters. And that would be our final answer for this one. Lastly, we have a buffer that has the following concentrations. The solution prepared with 500 milliliters above, with 500 milliliters of distilled water. Okay, so we're diluting that buffer. Do you predict the pH of the final solution to be less than, greater than, equal to, or greater than? So we've seen a pattern here of this common kind of question. So the dilution of the buffer with distilled water will decrease the concentration of each component, but the final concentrations will go to 0.5 and 5. Since they are still equal to one another, the addition of water decreases the concentration of both of them, right? We should maybe put the emphasis on this each. So because the concentrations, yes, they have been diluted, the concentration was decreased, but they are still relative to one another, equal to each other. The pH of the final solution stays at 3.17. Okay, so there's our solutions to our homework from yesterday. We're going to move on from buffers into this conversation about kinetics and reaction rates and how we could use a reaction rate and a rate law to describe what's happening in a chemical reaction. Okay, so if I were to give you just a very general equation like this, where I have some reactants, so two reactants react with one another in order to produce two X's and a P. Okay, this is very, very basic. I'm trying to keep the letters pretty simple for you. What we can say is that we could look at how the concentration of this reactant changes as a function of time, and we would call that the rate of decomposition. So how is this decomposing? How is this breaking down in order to make our products over here? And we say the rate of decomposition is negative because it's decomposing. We're losing reactants. Change in concentration of reactants over change in time, which we could simplify that way. And we could write with our deltas over here, delta R over delta T, so delta R concentration over delta T. What's very common is for us to get data tables that share this data with us, right? That tell us what's happening as a function of time. So if you were to do, we'll look at an equation you might have done in your class this year before you were dismissed, where you probably didn't have 24 hours to connect or to collect data, but maybe you did this in minutes, or this is probably too quickly to do seconds, but maybe your time was in seconds. You're going to look at how the concentration changed over time. You're going to calculate the delta R. So what's the difference between these two? What's the difference between these two? 0.25. You see how our changes over here. This is our change in concentration of our moles. Our change in time is consistent, right? That's good laboratory technique that we always had the same time difference, and then we calculate our rate of decomposition in moles per liter per hour for this one, right? And we can see that our rate here is it's always negative, but the rate is actually getting smaller. And so if we graph it, what we would see is we have initially the slope of this line right here. And your math teachers will be really excited if we talk about a rate and a slope is the same thing. Your physics teachers will also be excited if we talk about that way. You see that the slope of the line over here is much greater, and it's starting to gradually get closer to zero right here. So it's going to flatten out at some point, or theoretically flatten out. It would continue to go on until we had absolutely no reactants. We could write a reaction rate similarly for the rate of appearance of a product, right? So what you notice is missing here is our negative signs. So this would be positive numbers, right? It's pluses over here. And what's interesting about this is that we can use stoichiometry to relate the rate of disappearance of R to the rate of appearance of P, right? And so these numbers probably look familiar to you, but they are because we're making every time we use up two reactants, we're only making one product. These numbers are going to be smaller, even though they are similar. The math that we would do to calculate any of these things would be the same, right? So in class, you may have collected some kind of data like this, and then, or maybe you count bubbles, or maybe we'll look at a couple of examples in a minute. But you would collect these two columns of data in class, and then you would have to calculate everything over here from there. But my point here is talking about the fact that we can talk about the rate of disappearance or the rate of decomposition of a reactant, or the rate of appearance of a product. Both of them are going to be related to one another, and obviously connected. So here would be a graph of the rate of appearance of a product. Again, we have a pretty high positive slope here with decreasing in itself. So if we imagined a tangential line right here, that would give us the instantaneous slope, and as we move that along this line, it would be getting closer and closer to zero. So then it's interesting if we put the two of them together. And this graph R is our reactant that's decreasing, product is the P that's increasing, right? And we can go so far as even add in that other product in there, the X product, the second product, the third species in this reaction. And what we see is that the rate of the reactant decomposing or disappearing and the rate of the products appearing are all stoichiometrically connect to one another, but they're not necessarily exactly the same, right? So if we had sort of a complicated equation like this, okay, that we're told that the rate of disappearance of bromide ions at a particular moment during a reaction, okay, so this is instantaneous, right? I talked about if we're looking at this graph and say the instantaneous slope that's going to change, we would want to compare apples to apples, okay? So we're looking at the same time for all three of these situations. At a particular moment, the rate is 3.5 times 10 to the minus 4th moles per liter per second, okay? So that's for bromide. Can you tell me what the rate of appearance for bromine is over here, or what the rate of disappearance for hydrogen, or the rate of disappearance for BRO3, bromate? What I'd like to do is let's talk about your favorite. Have we done ice cream yet? I don't think we've done ice cream. So if your favorite ice cream is vanilla, let's go with you do problem number 1. If your favorite ice cream is chocolate, go ahead with problem number 2. And if you have a different favorite kind of ice cream that's neither vanilla nor chocolate, why don't you go ahead and do problem number 3? You can pause the video here, write out your solution, and I'll give you your answers in just a second. Okay, so what I would do in solving each of these is I would just multiply these numbers by the mole fractions of what from the equation. So we started out with the reaction over the rate that was given to us, okay? And we're going to say that every time that 3 moles of bromine are produced, 5 moles of bromide are used up. So I can multiply by 3/5 to get to 2.1 times 10 to the minus 4th. The disappearance of hydrogen would be 6/5, so 6 moles of hydrogen for every 5 bromide. So I get an answer like this. And the disappearance of bromate is 1/5. So you may have been able to do some of these in your head, but I would imagine you need to calculate for some of them. Now let's think about what the signs on these should be, right? So we have some inconsistency in terms of our signs. If this is the disappearance of bromide, we would probably talk about this as a negative number. I should have included a negative here. If we're talking about the appearance of bromine, I would probably have a positive here, and these because the disappearance is also being negative. So that's something that we would want to be a little more consistent on when we're looking at our answers. Okay. Now we know that, and this is probably another lab that you either have done or would have done in class with your students, or sorry, with your teacher, where you would talk about what are some of the factors that are going to affect the rate of a equation or of a reaction. If we're talking about this one, how could we, if this is the rate at a given moment in time, what could we do in order to speed it up or slow it down? And we know that there are generally considered 4 different factors that we're going to look at that would affect whether the speed of a reaction. Okay, and that would be the concentrations of the reactants, the temperature, the surface area, and catalysts. And without giving too much away for what we're going to talk about on Thursday. The bottom line is that it all comes down to collisions, and we talked about collisions a lot when we were talking about the gas laws. So I'd like you to go back and think about kinetic molecular theory really only relates to gases in a closed container. So I'm not saying that this is the same as kinetic molecular theory, but the idea that collisions are a central idea in what's happening in chemical reactions is something that's very, very important. And we'll get into some more examples of that and some more explanation of that on Thursday. But what I'd like you to do just for today is to think, if any of these things are able to increase collisions, they will increase the rate of a reaction. If the molecules of the reactants can collide with one another more often or more strongly, then we are going to have a faster rate. And the inverse is also true. If you have fewer reactions or weaker reactions, fewer collisions or weaker collisions, then that's going to cause the rate of the reaction to go down. Okay, so let's look at these individually. So the reactant concentrations, if I increase the concentration, if I have a higher concentration, it would make sense that I would have a faster rate, right? That means that I'm going to increase the likelihood of the collisions. There are probably going to be more collisions because the reactants are not as far away from each other as they were at lower concentrations. So how do I increase the concentration? Well, I could have something that is a more concentrated solution, less water. If it's an aqueous solution, I could lower the volume if it's a gaseous reactant. Anything, I could add more of the solute to the constant volume of solution. Anything that's going to have the reactants closer to one another so that there will be more collisions will lead to a faster rate. We know that temperature is unique, and I'm going to encourage you to go back and look at our conversation earlier. I think it was last week where we talked a lot about the Maxwell-Boltzmann diagrams about what happens to the average speed of molecules as the temperature changes. But we know that temperature is proportional to kinetic energy. So at a higher temperature, you're going to have the molecules moving faster. Well, moving faster does two things. It either means that there's more collisions, or it means that those collisions are even stronger with one another, which we'll go into more specifically on Thursday. But either way, more collisions and stronger collisions is going to lead to faster rates. So an increase in temperature means increase in the rate of the reaction. Surface area is sort of a unique one for rates, something that we talk about. We don't talk about many other places. But what you'll see typically here is whether you added a larger piece of the molecule of the substance to the beaker, or you crush it, whether you dissolved it in water. I guess that's not a good one. But if you have like one chunk versus two chunks of solution, so if you have a box sodium per se that's in a block like this versus we cut it in half, well, now the surface area on those boxes in the middle is twice as big. Right? So increasing surface area just increases the likelihood of collisions. I'll show you a diagram in just a second of that because the reactants can connect with one another if there is more surface area. I like to talk in my class about if I did have a big chunk of sodium and the water was trying to react with, the water can't travel all the way to the center part of those molecules. So in essence, those molecules are blocked by all the molecules on the outside. And so we want to give collisions a possibility to happen by breaking up molecules into the largest amount of surface area, right? Which means the smallest pieces, the smallest particles. So greater surface area is going to lead to faster rates. And catalysis is kind of a unique situation. So I'm not going to say too much about that. I'm just going to encourage you to stay tuned for Thursday. It's important that we talk about catalysts in terms of their effect on a rate of reaction. And these are the four big things that are going to affect the rates. But I don't want to get too much into the specifics of how catalysis is going to react, except right now just to say it depends. And so let's put that off. Typically, catalysts are going to increase the rate of reaction, but we'll look at all of the permutations of that on Thursday. Okay, so this will be a great slide here to take a screenshot of, either a mental screenshot or take some notes, just to remind yourself of the four things that are the four factors that are going to affect the rate of a reaction and how they do so. In general, higher concentrations, higher temperatures, and greater surface area are going to lead to faster rates. All right. So let's look at a couple of different examples of comparing two different experiments to one another. So what I have here is calcium carbonate reacting with some acid to make calcium, water, and carbon dioxide. I want you to look at this reaction and think about the idea that the initial rates of formation of carbon dioxide gas from the chemical reaction are studied. So think back to some of the lab practices that we've looked at already this year, and think about in these review lessons, and think about how could I study the rate of formation of carbon dioxide gas? What would that look like in a lab? Just give you a second to ponder that. Now, I hope you came up with something that looks a little bit like this. Again, going back to our gas law conversation where we were collecting gas over water. There's a couple different ways you could do that. This one, maybe because you have a piece of solid, it could look very much like that Eudiometer example that I showed you when we were talking about the you may just have something that looks like this, where you have a reaction producing gas. You have a glass tube that's going to run underneath some water, and as the gas is produced, it's going to displace some of the water. Now, if we wanted to be very specific, we may put a graduated cylinder here. We may put something like Eudiometer so we can measure the volume. But there's multiple different ways to do it. Just wanted to remind you, because this is a unique situation. How are we going to measure this rate of formation? Oh, well, we would probably do something like volume of gas produced. We also could do something pressure. A couple different ways we can do. Go back and look at your gas laws for a further conversation of that. All right. So if we're looking at these two experiments, experiment number 1 and experiment number 2, the question is which one, if any, will have the faster initial rate of formation of carbon dioxide gas? So which one might react faster, at least at the beginning? We see the bubbles of carbon dioxide gas being produced faster. And so what we're going to look through here, this is a very common theme today. We're going to try to find what's the difference between experiment number 1 and experiment number 2. We have the same mass and they're in the same format of one of the reactants. We have the same volume of the other reactant. Here our concentrations are different, so that says to me maybe that's going to be the key to what I'm looking at. But let's just make sure. Oh, yeah, the temperature stays the same. So what I'm seeing here is a larger initial concentration of acid at the same volume. Now, if the volume was different, this would obviously be a much more complicated problem. We're just doing this for a review. So a larger concentration of the same volume means that my concentration, when I have a higher concentration of a reactant, what that means is that would give me a faster or higher rate. And so the answer here is that experiment number 2 would have a faster initial rate because there will be more collisions between the reactants when the concentration of acid is at a higher, when we have a higher concentration of the acid. Okay. Here's experiment number 3, experiment number 4. So we're going to do the same thing. Let's try to identify what is the thing that's different. You notice I changed our concentrations. They're equal temperatures, the same volume is the same. So now I have our mass of one reactant is a powder and one of them is pellets. It's a word that we use a lot in chemistry. Where we talk about pellets would be much larger pieces. They may look like little stones, little rocks, maybe like BBs. Oops, I went backwards. Sorry about that. So pellets just means that they are relatively small pieces, but much bigger than a powder would be. And so the faster rate of the reaction would be the powder. And here's a diagram that might show you why. If these are the reactants on the inside here, and this is one of the reactants. This would be like the calcium carbonate maybe. And we have the acid on the outside that's trying to connect with the reactant. What you see here is these molecules on the inside can't react with the other reactant because they're blocked, right? Whereas if we break it up into little pieces, so this is the same number of particles on the side that we have on this side. Now we have room on the inside here for both reactants to mix, and so the rate of the reaction would be much faster here. Okay, so the answer to this one is which one would be faster? The one that is in powder form, not the one that's in pellet form. Experiment 5 and number 6. What are we going to see here? Let's scan through our two experiments. What's different? And here we should identify that our temperature is different here, and so a higher temperature should give us a faster initial rate. Why is that? Because our particles will be moving around faster, which means they will have more collisions, and we probably want to point out also that they would have stronger collisions, but more and stronger collisions. And again, like I said, we're going to talk about that a lot on Thursday. So just getting these ideas kind of down in the back of your head is getting comfortable with these is a good idea. Okay, I'm going to move on to talking about some more mathematical representations. Okay, so we've just spoken very much in general about particles and what's happening on a macroscopic level. So now let's look at the variables and try to relate these same ideas to a mathematical representation of what's happening in a rate. Right? And so we have this idea of a rate law. So if I have given you an equation, again, I'm going to stick with just a general one for right now. X plus y is equal to or creates z plus w. We'll look at some specifics in just a minute, but this is a general one. What we can do is write what we would call a rate law, and rate law has kind of 3 important parts to it. This is a very general rate law for this reaction up here. First thing I would like you to notice is that it includes the reactants only. Okay, we can talk about the rate, we can define, we can know what's happening in any kind of equation, calculate like we did earlier today for reactants or product. We talk about the disappearance of reactants or the appearance of products if we wanted to, but by definition, if we're going to look at a rate law, we're only going to look at the reactants. Okay, so look at we have concentration of both of the reactants here. Okay, we're going to put exponents on those reactants that we'll talk about what we call the order. So in this example, M is the order with respect to X, N is the order with respect to Y. And then we could actually add M plus N together to say what's the overall order of the reaction. And that's going to be important as we get to the end of today's lesson where we look at a number of ideas. And then the last important part of the rate law is the fact that there's a rate constant. So this is going to define for us how fast this rate goes. It's going to define, help us understand what's happening. We want to remember that it's at a specific temperature. And we're going to spend some time today actually looking at units where we are able to define the units on this K, and it would be specific based on what the order is. I know that sounds a little weird, and I'm going to walk you through a couple exercises on how we would derive the units here. But it's important to remember that unlike some of our other constants we've looked at over the past couple weeks, K in our rate law always has units, and it's really important we get those units correct. So you're going to see questions when we're defining the rate law, we need to know the value for K and what the units are on that K. So let's look at a specific example. Okay. I'm sorry. No, I just want to double check with you if we could write if we filled in M and N. I'm sorry, with some specific numbers. Okay. If we look at this first one, the order with respect to X is 1, the order with respect to Y is 1, so the overall order is 2. We could have the rate with respect to X being a 2, the rate with respect to Y being a 1, and that gives us an overall order of 3. We switch the numbers to get an overall order of 3 as well. It's important to point out, guys, at this point that we could also have a 0 order. So you would have a 0 in here, which means that that reactant actually doesn't, the concentration of that reactant is not important in the overall rate law, or the overall rate of the equation. We'll look at a couple of examples of that today, I think, or at least look at some of the math behind that, but we could include that in this chart if we wanted to. Okay. So giving you some specific information about ozone here. We know that ozone reacts with nitric acid. What I'd like to do is to consider, I'm going to give you a whole lot of data here, and we want to use that data to determine the rate law and the rate constant for the reaction at 25 degrees Celsius. So it's nice that temperature's not changing, so we don't need to worry about the rate law changing or the rate constant changing. Sorry, once we get to that rate constant, we will be good. The only way it changes is with a different temperature. Okay. So when we're given a whole set of data here, this is a very typical data set for what you might see in a problem like this. Okay. And what we're looking for here, just like we did before, we have 4 trials along the left-hand side. And what we want to do is to identify places of difference between each of these trials. And even more so, we want to find places of difference and places of similarity where we can compare those two different things. Okay? Our goal here is to identify, first off, the exponents. What is the value of M? What is the value of N? Once we can identify them, then we're going to use our numbers. We're going to plug them in to solve for K, and then we'll plug in our units in order to solve for the units on K. So this is sort of a 3, maybe even a 4-step process. If we say first we're going to solve for M, then we're going to solve for N. I'm actually going to do that opposite. So I'm going to solve for N first, then M to exponents. You can do either order, but we need to know our exponents before we can solve for K, and then we can get our units as well. Okay. So if we were to just analyze the first 2 trials, so I'm going to isolate the first 2 trials. And if this was me and I had this on a piece of paper in front of me, I might even take a second sheet of paper, just cover up trials number 3 and 4, just so they don't confuse me. Okay. Because I want to be able to look at these trials and make some conclusions from them without getting distracted by the other ones. We could make similar conclusions about any of the trials, but we're going to start with a simple example here. And what I noticed between trial number 1 and trial number 2 is that the concentration of NO was not changed in those 2 experiments. Okay. So when the experimenter set up trial number 1 and set up trial number 2, they put the same concentration of NO into their reaction vessel. But the change that they did make was that they doubled the concentration of ozone. So 3.0 times 10 to the minus 6 is we double, we get to 6 times 10 to the minus 6. And so what we're going to ask ourselves is what happened to the rate when we didn't change NO, we did change O3. And if you squint or you get your calculator out, you should be able to see that when the O3 doubled, so did the rate of the reaction. So this is we're looking at the rate of production of NO2. Okay. And so what that tells us, and here's where another misconception, or we might make a little bit of a mistake, because the change is the same for both of these, this is defined as a first order. That the exponent here is 1. When this is doubled, this is also doubled. The same thing happened to both sets of data. And so because they're the same, we would put an exponent of 1 there. Now I'll show you mathematically how we might prove that if the numbers are a little bit more difficult. But here, one confusion that somebody might make is, oh, I doubled this, and because it's a double, then I have to put a 2 up here. And that's not the way we would analyze this. What I want to look at is how did the rate change when I changed one of the reactant concentrations? And because this did the same thing as the reactant concentration, whether that was double, whether that was triple, quadruple, because these both say double, that tells us that our exponent up here is a 1. Okay. Now let's look at trials number 3 and number 4. These are 2 good trials to look at because there's no change in the O3, the ozone concentration, but the concentration of NO doubled. And what we should notice over here is that the concentration of NO2 doubled as well. And because both doubled, right, we double the concentration here. This double, that's going to give us our order for NO of a 1 as well. Okay. So don't make the mistake of seeing the word double or thinking that means that you're going to have to put a 2 up there. All right. Now we need to solve for the value of K. And this is relatively straightforward. The math is a little bit wonky because you have scientific notation, but we're just going to plug in. We could actually do any of the 4 trials. So I'm going to start with number 1 as an example, and then encourage you to do 3 or 4 to confirm if it's a constant to be true at all situations, right? As long as the temperature does not change. So what I've done here is I plugged in my rate on this side. I plugged in my concentrations. I'm going to solve for K first, and then I should get to a value for K of 2.2 times 10 to the 7th. It's a very large number, which is fine. So be comfortable with that. So I'm going to flash these up on the screen. I'm going to encourage you to stop the video and pick number 2, number 3, or number 4. Just pick one of those numbers, whatever your favorite number is, and confirm that you got 2.2 times 10 to the 7th. And then the last step here, which is where it gets a little bit tricky, is that we want to be able to determine the units. Okay, and I'm going to show you how I would be able to calculate them, and then I'll give you a chart which says basically we can maybe just remember some of those, and you can decide what your style is to either memorize or to be able to derive these each time. So we've gotten to a point where our rate, we've identified this as our rate for this reaction under these circumstances. Okay, and our units, which we came right off of our data table. Okay, the rate is moles per liter per second, right? So molarity per second. The K that's in here is K just stays in there, but this concentration is moles per liter, right? So we should be able to say that K is moles per liter seconds. Just brought these down, I divided both sides and brought the moles per liter times moles per liter over this side, and now I'm just going to cancel out. And so one of the moles cancels out with the other moles. One of the liters to the minus 1 cancels out with the other liters to the minus 1, and nothing else cancels out. So then I'm going to simplify into liters over moles times seconds. And typically in AP land we would write those all with exponents. We'd say that that's equal to liters times moles to the negative first times seconds to the negative first. Okay, so take a second and listen to that again. I'm running short on time here, so I'm going to keep moving on. But if you want to see my derivation of that again or how I calculate that, please stop and rewind and go ahead and watch that again. Okay, so our final answer here is that our rate is 2.2 times 10 to the 7th liters moles to the negative first seconds to the negative first times the concentration of NO times concentration of O3. So there's our final answer where we have the rate law and we have the rate constant with our units on it. Okay, let's walk through one more where the numbers are a little bit more complicated. Okay, here I'm going to look at reactions number 1 and number 2, and I'm going to see that the first when I doubled the reactant, I quadrupled the rate. Okay, and so this is an example of where they're not the same, and so because our the relationship here is the rate is twice as much as the change in the concentration, I'm going to put an exponent on our rate up there as a 2. Now you might get to the point where I would actually confirm the same thing would be right there. Like I said, this is the rate law. It should work in all circumstances. If your numbers are such as that, you're a little bit harder to see. You might want to have more of a mathematical way to break this down. So you certainly could take 2 different sets of data and plug them into your equation and then solve for X. The math here is a little bit trickier because we have to use some logs in order to isolate that X over there. But if we set, let's look and see which experiments we use. I used trial 1 and trial 2, I believe. But again, you could use 2 and 3. Any of them should work. This rate law is a law. I'm going to simplify both sides. The K cancels out. I haven't calculated K yet, but it cancels out in this circumstance because K over K, whatever it is going to cancel out. I can take the log of both sides in order to isolate the X, or the X down from the exponents. X is then equal to natural log of 2.5 to the 10 to the minus 1 minus first. Did I say 1? Excuse me there. Divided by the natural log of 5 e negative 1, and that is equal to 2 as well. And so that we're just confirming there what we sort of already knew. What I'm giving here is just a methodology where you might want to be able to solve for x when the numbers don't jump off the page that you have in those other two equations. Those other two problems. Okay. And there is, let's look at our units. Okay, so we're going to solve both for k and for our units. Okay, so we've confirmed that it is a second order reaction. We're going to plug in, we can plug in any of our numbers that include our units here, and we come up with an answer of 6.73 10 to the minus 6. And you notice that there's those units, while they're weird units, they are actually consistent with what we had before. That other reaction was also an overall second order reaction that had the same units. And you'll see that if we can identify whether it's a first zero or first or second order, that units are consistent across those. Okay? Now so there's our final solution to that problem. Okay, looking on in this last couple minutes that we have together, what happens if instead of looking at a rate law that compares the rate to the concentration, I want to look, that's what is happening here, right? The rate law, which we know looks like that, relates the rate of the reaction to the concentration of the reactants. Yes. Okay. So what we could do is we could integrate this, and your math teachers would be more than happy to talk to you about how to take the integral of any of the rate laws in order to relate the concentration of a reaction to time. And the whole purpose to the section and to the integrated rate laws is to relate concentration of a reaction to time. So we can do problems where you say how much of this do you have after a certain amount of time, rather than what is the rate as a function of the concentration of this reaction. Okay. So if I gave you a reaction, A turns into D, and I told you that the rate law was K times the concentration of A to the first. I hope you recognize that as a first order rate law. Yes, a first order rate law. That's a reaction is first order. Okay. And if I integrated it, again, talk to your pre-calc, your calculus teacher about how we would go from this initial reaction to the natural log of A is equal to negative KT plus the natural log of A, the initial concentration of A. All right. This is a pretty cool derivation of it, but we don't have time for that today. One of the many reasons why we do this is because this looks very much like y is equal to mx plus b. I'm writing it in this line formation because we will look at some graphs. If we were to put the natural log of A at a specific time, okay, on the y-axis, and we put time here on the x-axis, we should get a straight line. And even more so for a first order reaction, we can see that the slope m here is equal to negative k. So this is super useful for being able to solve problems. And the part of your homework today is to be able to look at what kind of a graph is forming a straight line. And if we take some data and we from an experiment and we manipulate it in several different ways to make 3 different kinds of graphs, only one of them would be a straight line, and the one based on what's a straight line, we will know whether it's a zero order, first order, or second order. So let's be real clear. This is a first order reaction, and the straight line is great. The linear relationship is great only when we look at the natural log of A at time t as a function of time. If I were to look at C, just a different reaction, just give me a different one, different color, and I tell you that x1 here is 2, you know that this is a second order reaction. So our integrated rate law is actually 1 over the concentration of C at time t is equal to negative KT plus 1 half of the concentration of C. Again, our y is equal to mx plus b, and so our m is actually equal to k, and that should say positive k right there, right? Our m is equal to k. No, m is equal to negative k. I'm sorry. Lastly, if we had a zero order, and this is the first time I've introduced a zero order in here for you. So zero order, we have if this is zero, we know that the concentration of E is just 1. Anything to 0 is 1. So our rate is equal to k. This is our equation, and our m is equal to negative k. Right? On the equation, on your AP chemistry equation sheet, you do have these equations are given to you. They're written in a little bit different format. They are written in the order of 0, first, and second order. So you would always have those with you. Here, this confirms that should have been positive k. I apologize for that. So our second order reaction would look like this. First order would look like this. And so this is these are the integrated rate laws for each of these kinds of reactions. If we are looking for the half-life, and this is a very specific circumstance where we're going to say that the concentration at time t is actually 1/2 of the initial concentration, right? So we could actually plug this in here, and then we could solve this equation for t, where we look at half-life. It turns out that for a first order reaction, which is most radioactive decay, is going to have a half-life that's equal to 0.693 divided by k. And this equation is given, this part of this equation over here is given to you on your equation page as well. Okay? I'm going to run through this real quick, just recognizing that it's already 9:50, and you've been paying attention real well for a long time. We want to look at the value of k for radioactive decay of A. It's told us that's the first order reaction, and half-life is 8.5 minutes. So we just rearrange our equation to get our k, and then we plug that into our integrated rate law for first order to get how much time it would take. So this is an example of why we have this. We're solving for time. How long will it take for the concentration to drop from where we started to this final concentration? Okay, so that's just one quick example of how we might use each of those equations. I'm going to give you a sort of a different debrief today. This slide is this chart is something that is very common in multiple different textbooks. I'm sure that you've seen it in different places. This is just a summary of all of the rate law information for 0, first, and second order reactions. I'm not a big fan of just memorizing things, right? But having kind of a snapshot of this in your brain to be able to refer back to. You will have your integrated rate laws written in the other format on the AP chemistry equation page, but this is this is a different way to look at it. And this gives you the y is equal to mx plus b format, which is going to help you to understand how what plot you need in order to get a linear fit for your data. Okay, and then here's a confirmation again. I'm sorry about the mix up on that slide over there, but the second order k is equal to the slope, not the negative slope. All right, practice problems, and then you'll be on your way. Here's our first equation. What I'd like you to do is determine the rate law, the rate constant in the orders with respect to each reactant, which you're going to need in order to get the rate law for this set of data right here. Looking at laughing gas, so take a snapshot of that, and then your next one is right off of an AP test. So here's the data. I'm going to give you a second to take a snapshot of the data, and then there's multiple questions that are here. I really like this because it relates back to what we talked about earlier with colorimetry. So here are basically 3 questions that we're looking at. Here's the data right next to question number 1. Here's the data next to question number 2, and here's the data next to question number 3. Okay. Thank you so much for sticking with me. I know that was a hefty lesson today. Feel free to go back to apcentral.collegeboard.org anytime that you need, and look at our useful, helpful resources on the bottom link or at this tiny URL, and send your friends to cb.org/tech if you need. Anybody that needs help, we want to make sure that they're showing work. Thanks so much for watching today, and have a great day. See ya. Good morning, AP Chemistry fans. This is another day of AP Chemistry lessons brought to you by Sean Byrne from Glenmore West High School outside Chicago. I'm wearing my hat and gloves today because even though it is Wednesday, April 15th, this is what my backyard looks like. We got almost an inch of snow. We have these beautiful flowers that have been blooming over Easter time, and we're still going to have to break out the shovels again to try to get all this snow off. So I hope that wherever you are, whether it's in the Midwest or West, I hear there's a lot of snow too, or East Coast, you're getting ready for it. I hope that you're safe and able to enjoy a little bit of this fun weather. For the next 35-45 minutes today, we're going to take a look at some really fun chemistry from Unit 5 in Kinetics, continue our conversation of Unit 5, and then give you some homework problems, and look forward to another day of chemistry tomorrow. So just as a quick review of our website, where you should be looking to get all your information about our upcoming AP exams. You see all the 8 different things that are over here on the right-hand side. Make sure that you're checking in for students that don't have a device or don't have internet access. Look at your scoring and earning credit and things like that. All of that is available to you at apstudents.org/exams2020. Of course, we're all looking forward to Thursday, May 14th, when we're going to all be taking a 45-minute exam on our own devices. It'll be completely free response, and all of the specifics are here on this slide. This is, I imagine, for many of you, a repeat of things that you've seen multiple times before. But go ahead and check it out, or go to AP Central for any further questions that you have. Our lesson overview for today is going to be the same as the same pattern that we've talked about that we've used for our whole time together. We'll do our warm-up where we review the material from yesterday, the homework from yesterday, some AP problems. Then we'll go through some new content and give you some opportunities to practice. And then I'll give you some AP exam practice to look at tonight for homework or this afternoon in preparation for class tomorrow. Of course, if there's any time that I'm going too fast and you want to stop and rewind, I encourage you to. There's going to be several opportunities today where I'm going to ask you to stop to answer a question on your own. So feel free to hit that stop button. I hope you have a pencil and paper next to you so that you'd be able to take a look at to work out some of the problems we're asking you to do today. Okay, so let's get to our warm up. No, sorry, let's just review. Again, we're going to continue on with Unit 5, looking at kinetics and specifically kind of generally around reaction mechanisms and how that relates to the material that we talked about yesterday with rate laws. Okay, so our warm up, there were two different things we asked you to do. One was to consider some data in order to determine the rate law and the rate constant. We maybe wanted to make sure that we said including units from the equation below. And so if you haven't had a chance to look at this yet, pause, see if you can determine the rate law, can calculate the constant and then calculate the units on a constant. I'm going to go through my solution with you right here in just a sec. So what we want to make sure we do when we're looking at our data is to isolate different trials in such a way that one of the variables is changing, one of the reactants is changing, and the other one is not. So I'm going to isolate trials number 2 and 3 here because I noticed that the NO, nitrogen monoxide, is not changing. So this is the concentration of nitrogen monoxide is not changing in between those two different trials. Okay, remember each line of this data table represents a different set of data that were collected from a different experiment, right? So this experiment had 3 different trials, or at least 3 different setups, and so in between these 2 trials there was no change in the nitrogen monoxide concentration, but what we notice here is that the hydrogen was doubled in our experimental setup. So that was how the experimenter set up. That would be like their independent variable, and then the data that they collected, their dependent variable, is the rate over here on the right. And what we notice is that the rate doubled when the concentration of hydrogen doubled as well. And so what we can conclude from that is because they both doubled, because they both changed by the same variable, that the order with respect to hydrogen is a 1. Okay, remember that there's the trick here is to make sure that just because you see a 2 there, just because you see them double, doesn't mean that the order is a 2 as well, because what we're looking for is the relationship between how the reactants changed and how the rate changed. And if they're the same, then what we can say is that is a 1. Okay, if then we'll look at experiments or trials number 1 and 2, and we would do that because we see here that hydrogen did not change, but the nitrogen monoxide doubled. Okay, so double checking the future work there. You may want to look at the rates and see if you can just off the top of your head, if you can conclude how the 2 rates compare to one another there. It turns out that this is a factor of 4, which could also be considered 2 squared. What we see is that when the nitrogen monoxide doubles, the rate quadruples or goes up by a factor of 2 squared. We went through a practice yesterday where we calculated out when the numbers are not real easy how you could set up a problem. So if it doesn't jump out to you that the order for nitrogen monoxide in this equation is going to be a 2, you may want to go back to yesterday's lesson and see how we set up the problem in such a way that we were able to solve for that exponent a little bit. It's a little more of a complicated process. In this case, you may just want to say, this was a by factor of 2, 4 is 2 squared, and so that tells us that that the exponent on here, or the order with respect to nitrogen monoxide, is a 2. Okay. Our next step would be to calculate the rate constant. I'm going to do the number and the units separately from one another. Okay. Here's my math for how I would solve it. We're just going to take any of the 3 trials and we would plug in our numbers. Okay. So I took the rate, plugged it in here. I left cake, that's what I'm solving for. I plugged in my 0.7 with my exponent of 1. This is where a couple of mistakes could easily be made if you forgot to include your exponent of 2 here. 0.6 squared. We're going to solve for k, and then when we do this math out, we're going to divide 2.2 times, or 2.286 times 10 to the minus 2 divided by the product over here. Make sure either you put parentheses around both of these, or you divide twice in your calculator, just to make sure you get to a 0.09 as the value for k. Okay, and you should be able to go through trials 2 and 3 and get the same number, right? Because it's a constant, it's a constant. And then let's look at how we would calculate our units. Okay, so we have we've determined that this is what our rate law is going to be, or these are our exponents. I'm just going to plug in only my units and then solve for k. So I go back to my data table, I'm going to see that the rate is molarity per second, or moles per liter per second. Okay, and that my concentrations were in moles per liter. I'm going to distribute my exponents here as well, so that I can say, I guess I distributed my exponent, and I'm going to divide both sides here. So I brought this over to the other side, moles per liter stays the same, but I have moles squared times liters to the negative second, right? I just distributed this 2 across everything, and then I'm going to cross out where it's applicable. So moles we cancel with moles, liters to the minus 1 cancel out liters to the minus 1, and I'm left with seconds to the minus 1 over moles squared times liters to the negative second. So I'm going to simplify that to be liters squared over moles squared times seconds. And typically we write this in an AP test with negative exponents rather than as fractions, and so you get something like liters squared times moles to the minus 2 times seconds to the minus 1. Okay. Now this is a very complicated set of units for a rate law, and that's because it's a third order rate. If you go back to our review of our lesson from yesterday, you notice that I just talked to you about the units for 0, a first and a second order reaction. If you were going to memorize anything, those might be things you want to memorize. I think what I mentioned yesterday is that I'm not a big fan of just memorizing things for memorization's sake. So the reason why I gave you this one, even though it's maybe a little more complicated than you would be asked to do on a typical AP test, is so that you know this process, so that if you were something were thrown at you, a third, a fourth, however complicated the equation is, it can appear in several different equations with lots of water that's getting produced. Okay? And let's see if you identify, we have 2 actual intermediates in this reaction. One of the intermediates is there, notice that it appears as a product first in step number 1, and then as a reactant in step number 2, and then a second intermediate that is a product in step number 3, and a reactant in step a product in step number 2, and a reactant in step number 3. Okay? So whether you're able to identify what these compounds actually are or not, just seeing that they are intermediates, both this and this are intermediates, it turns out that this is N2O2 and this is N2O, but identifying both of those intermediates is important. Okay? And unfortunately, in this example, there isn't a catalyst that's there, right? We don't have something that would appear as a reactant first and then gets produced again, or is left over. Let's move on to an example where we're looking at chemical formulas rather than at particle pictures. Identify reactants, intermediates, products, and catalysts. Go ahead and stop your video just for a second to do that. Let's see, our reactants are here, products are here, we have an intermediate here, and we don't have a catalyst there. So these are 4 questions you would want to ask yourself every time you look at a mechanism, which are reactants, intermediates, products, catalysts. Okay? And then I have one last example here. Give you a hint that this one actually does have a catalyst. Go ahead and identify your 4. Pause if you need to. Here are the reactants. Notice that this is sort of a strange oxygen by itself. That doesn't happen very often. I don't want to do that last because I might mess up. You might think that I left the 2 off of there, but it actually is just a monoatomic oxygen floating around out there. Products are here. So we've got O3s turned into O2s. Okay? Here's an intermediate because it appears as a product first and then a reactant. And then finally I found you one that has a catalyst. It starts as a reactant up here, but we produced it over here again, and it is unchanged. And so that is not would not appear unnecessarily even in the overall reaction. All right. So there we go. Now I do want to take a brief minute to look at what we call steady state approximation. What we're looking at here is a mechanism that looks a little bit different from our other reactants. So I want you to just take a minute to look at this mechanism here. We've got 3 steps and consider, based on what we've done so far, what would you expect the rate law for this reaction to be? And I would suspect that many of you would notice that this second step is a slow step, and so you would write a rate that is going to say the rate is equal to k times the concentration of NO2F2. Okay. Now there's a little bit of a problem with that, and this is, and I want to tell you that the 2 reasons why we would not consider that the rate law, how this mechanism is different than the other ones we've looked at. Okay. First of all, I'm going to notice that this is actually, now that we have that vocabulary word, now I'm going to notice that this is an intermediate. Okay. And intermediates, like I said, will appear for a split second. Okay. And they typically are not used in a rate law. Okay. This can't be the rate law because it includes an intermediate, so we would not put it in there. The other thing that's different here is that we're starting with an equilibrium up here, right? So we have 3 steps here, but this first step is an equilibrium kind of reaction rather than one that we would expect to go completion. And so when we combine those 2 things, we're going to have a little bit different of a mathematical process in order to determine what the rate law is. And what we're basically going to do is determine how can we relate this intermediate back up here to the step above it in order to write our rate law. And the math is going to get a little bit wonky here, so try to stick with me. This would be a great example. I'm going to give you 2 examples, but you might want to listen to this just a couple of times so that you can, before you practice our homework for tonight. Okay, so here's our 3 steps. Okay, I just had to stretch the screen so we could fit a couple of steps in here together. Here's what that rate law is. What we might have considered the rate law was based on this slow second step, right? If I were to look at the first step, what I know is that the forward rate is equal to the reverse rate, and that's just our definition of equilibrium. We're going to get to a pretty big discussion of equilibrium over the next couple of weeks. I imagine that most of you did talk about equilibrium in your classes already, but one of the fundamental understandings of reactions at equilibrium is that the forward rate and the reverse rate are equal to one another. So if we were to write our forward rate and our reverse rate in our normal rate law form, we would see that our rate for the forward step or forward reaction would be K forward times the concentration of the reactants here, and that is equal to the K over reverse. These days, not necessarily the same. Using this NO2F2 concentration is connected to the reverse. And what's nice about this is all I've done is I've said our rates are equal to one another because equilibrium. I've used the same rate law that we've talked about for 2 days now, okay, where I looked at K, identified K for the forward reaction, I looked at our concentrations for the reactants for that reaction. And I'm going to rearrange it in such a way that I'm just solving for NO2F, right? So the concentration of NO2F2 is equal to, follow my math here, K forward divided by K reverse. So what do? I divide both sides by K reverse. So that quantity times the concentration of N2, concentration of N2 times concentration of F2. Okay, and so now I can take if the concentration of NO2F2 is equal to all of this stuff over here, I can just substitute it back in to my equation on the left hand side, and then I'm just going to probably simplify it and say that there's a new K. Say identify this as K2. This K that's here, excuse me, is equal to the product of K2 times these 2 Ks that are over here. Okay, and so this would be the rate law for this kind of a reaction. Again, it's the 2 stipulations here that we're looking at an intermediate in the slow step, and we're looking at equilibrium in the first step. Okay, so stop now, read through my explanation of the math here again if you would like, or here's another similar example that I would encourage you to look at. See if you can solve the math here on your own. It does take a couple of minutes to go through, so go ahead and pause so that you're able to go through the math. And my solution to this would be similar to what we did before. The trick here is that we would write our rate as NO-Br2. We're going to include NO times Br on this side, Br2 on this side. Okay, so our forward and reverse rates are equal to one another because it's equilibrium. We're going to substitute this back in, and we would end up with a rate law that looks just like that. Okay, and we have a similar kind of redefinition of what's happening with our K. Okay, so take a look at that. Take a look at these 2 examples that we just gave you. We ran through a number of different things about mechanisms in here, and you should be able to see had a couple of different problems or a couple of different practice problems as well. Here's some easy practice problems for tomorrow. What I'd like you to do, this is a little bit different than the way that we did it before, but you have to identify both your intermediates and your catalyst if there is one in order to identify kind of backwards. We're going to work backwards to find what is step 1, and then your AP exam practice is looking at a reaction of nitrogen dioxide. According to that reaction, what we have is a mechanism, and this is what's nice about this is that this will combine the things we've done over the past 2 days. Explain how the graphs indicate that the reaction. I'll read that to you. The reaction is second order here, so we're told us that the reaction is second order. Then write the rate law for the decomposition of NO2, and now we have 2 different mechanisms. And what we're asked to do, notice that this mechanism has 2 errors in it. This mechanism is a fast equilibrium, so we want to look at that. And you have 2 different justifications that you might answer, and what we'll do is we'll look at that in class tomorrow. Okay, so remember that if you have any questions, you want to go back to apcentral.collegeboard.org. We've got a bunch of extra links that are down there, and you have if you have students or friends that are having problems with the internet or problems with their device, go ahead and look at cb.org/tech, and we will get them the help that they need. Thanks so much for watching. I know ours is a little bit shorter than our lessons have been in the past, so you get a little break to get started on your homework for today. Have a great day, stay safe, and I hope you're staying warm out there. Go find my gloves and hat back on before I go outside. Have a good day. I'll see you tomorrow. Good morning, chemistry fans. Mr. Fairbairn and I were just finishing up a great conversation on all of our favorite movies. So I hope you guys are having an opportunity and all your studying for AP chemistry to stop and relax and watch some good movies, whether that's a nice romantic comedy or just a straight comedy or maybe an action film. There's lots of good stuff out there, so make sure you're taking some time for yourself to do that because there's lots of good stuff out there. Today's chemistry lesson is a continuation of what we've been working on. I'm Mr. Byrne from Glenmar West High School. Today's Thursday, April 16th, 2020. We're gonna I think we're wrapping up Unit 5 today on kinetics. We're gonna be looking at a number of finally look at collision theory, like I was mentioning on Tuesday, and then talk about how catalysts are going to affect some reactions. We got another great resource to share with you, and some good problems for us to practice between today and tomorrow. Just remember that all of your questions, or if you still have some questions for you, your teachers, any high school administrators that are on here, you probably want to take a look at thestudents.org/exams2020 for any of the topics along the right hand side of the screen there. We're going to keep our focus on Thursday, May 14th. So we passed the 1 month mark a couple of days ago. Now I think we're at the 4 week mark because it should be exactly 4 weeks from today on Thursday. Remember that you're going to find the time that is your local area, and we'll all be taking the test at the same time on the same day on our own individual devices. Okay, that exam is going to have a completely free response format. You'll have 2 specific questions that you need to look at that will really be focusing on the skills of explaining chemical phenomena, drawing conclusions, analyzing systems, and supporting your claims with evidence and reasoning. So we're going to just continue to hammer those skills with you as we go through each of these lessons. Okay? Our lesson overview is the same as usual. What you need to know, we got to practice will be the meat of ours, but we'll start with our warm up, and then we'll leave at the end of class today with a couple of problems from retired AP tests for you to look at. Encourage you to stop and go grab a piece of paper and a pencil and maybe a calculator if you have one handy, so that we can talk about these problems in real time. But anytime you need to review or I go too quickly through something or what I'm saying doesn't make sense, go ahead and listen to it again and see if you can figure it out. Okay. So these are the topics that we're going to hit. Like I said, we're wrapping up Unit 5 in kinetics, where we're looking at the heart of all of this is really a deep understanding of the collision model. And I think it's going to feel very comfortable for you once we can get to talking about all the parts of it. But anytime we talk about collisions, anytime we talk about a chemical reaction, you really have to be looking at the collisions of the particles with one another. And so making sure that we have that at the forefront of our brain as we're moving forward is going to be a really important thing, whether it's talking reactions or rates or mechanisms or any of that stuff. Okay. And then we'll wrap up by looking at how catalysts affect a reaction, a big part of what happens with chemistry in the real world. So that's really important. Okay. So we're going to start with our warm up, and we're going to do something a little bit different today because those of you who were paying attention to our lesson yesterday may have noticed that the second equation that we talked about right at the end, I made kind of a big error. And so shout out to Crystal in New Jersey who emailed me and said, Mr. Byrne, I don't think that this makes sense. And it turns out that my work down here at the bottom was correct, but I think that I had made a couple of typos in step number 2 equation. So I think that the arrow was in the wrong spot. I don't know what I was thinking when I was doing that. So thanks for keeping me honest, Crystal. And those of you that were confused as we were going through this example yesterday, go ahead and take a screenshot of this, and we would come to the same rate. We come to the same answer down here at the bottom of the screen. It's just you probably had a hard time getting there, not having this equation correct as it is down here. All right. So let's get to our 2 homework problems as they were assigned from yesterday. The first one was kind of a backwards mechanism problem, right? So really taking our skills out for a ride and seeing if we are able to not predict what the overall reaction is, but surmise from the overall reaction. And one of the steps, what other step would be. And particularly, it's probably going to be important that we are identifying step number 1 from the overall and step number 2, because we're going to have to identify what are 4 parts of a reaction. So you might want to review that from yesterday. We can have products, we can have reactants, we can have an intermediate, we can have catalysts in there. So you can, anytime you have a mechanism here, you might want to review those 4 parts. So my analysis of this will kind of start, and I'm going to just go through each of the chemicals that are in the overall reaction and see where they came from. And if I don't have a clear spot where they came from, if it didn't come from step number 2, well, then we're going to say it must have come from step number 1, right? So the first substance that I'm going to look at here would be NO2 gas. And so what I notice is in the overall reaction, I have some NO2 gas, but for some reason I have some NO2 in the product of about step number 2. So the only way to get to have some in the overall reaction, because remember, we're going to add together step number 1 and step number 2, essentially to get to the overall reaction. So the only way that we would be able to do that would be by having 2 NO2s in step number 1. So that these 2 NO2s in step number 1, when they balance out with one of the NO2s in step number 2, would leave us with a net of 1 NO2 in the overall reaction. Okay? Our carbon monoxides, COs from the overall reaction, we have one up there, and then we have one in step number 2. So between those two, that is accounted for, so we're going to leave it alone. We would not expect that would come in step number 1. We would look at NO, nitrous oxide gas, and we see that that is nowhere to be found in step number 2, and so we're going to include that in step number 1 as a product. And then just like with carbon monoxide, we see the carbon dioxide appears in the overall reaction and in step number 2, so we will leave that. The last thing we need to consider is NO3, nitrogen trioxide. How did that get there? Well, it turns out that that's going to be an intermediate for between step number 1 and step number 2. As it's an intermediate, what we know about intermediates is that they are used up in step number 2 because they were produced in step number 1. So we put that on the product side of step number 1, and that gives us our complete reaction. And so our solution to this problem would be that we have 2 NO2s react to make 1 NO plus 1 NO3 there. All right, give me a second just to process that, and then we'll go into our AP exam practice where we were given the reaction of 2 NO2s that are reacting to make 2 NOs and NO2. And this happens at elevated temperatures. We got a lot of different information. What we want to look at is the fact that we have graphs that are represented from this information, or the graphs that came out of the experiment. And the first question asks us to explain how the graphs indicate that the reaction is second order. And so we would zoom in here, and we should immediately recognize that this is our linear equation. And so because the linear graph of 1 over the concentration of NO2 versus time is a straight line, the graph of that is a straight line, then that indicates that it's second order reaction. I want to caution you here to remember that we're always looking for the linear reaction, and we do need to know what the axis, what the y-axis would need to be in order to indicate if it's a first or second, a zero first or second order reaction. And a couple other examples, we saw that they were listed. The first one listed was first order, the second one listed, the first one listed was zero order, then first order, and then second order, right? And so we could just maybe assume because it was listed second that means that it's first order. And that would not be an appropriate way for us to analyze this data. What we want to do is really find the one that is the straight line. Here we've got curve, this is a straight line with a positive slope, and then we would want to look at what is the y-axis here, and we know that 1 over the concentration of a reactant tells us that it's second order, not zero or first order. Okay, and so if we've identified that it's second order, we can write a rate law that is consistent with that. The rate is equal to k times concentration of NO2 to the second power. Right, and this is just a review, I think, of some things that we did on Tuesday, if I remember correctly. And then this is a review really of what we did yesterday. So we're going to look at 2 different mechanisms. This first one I think was pretty straightforward. If we've identified that this is the slow step, okay, we know that if we have a mechanism, this is slow step that is consistent with a rate law that we wrote in part B. So we wrote here that the rate is a second order with respect to NO2. So we want to see, does this step, is it consistent with that? Well, we have 2 NO2s reacting with one another, which for an elementary step would be second order, right? And so our answer here would be yes. We've identified that step 1 is slow, so it's a rate determining step. So there we go. We're using some good terminology of rate determining. The rate law of this elementary reaction is equal to k times. It's very similar to what we wrote earlier, exactly the same as we wrote earlier, and so that's consistent with the second order rate law. Okay. The second one is a little bit more complicated, right? Because we have one of these fast equilibrium problems. And so our initial reaction would be, our initial thought might be to jump to step number 2 and to say, okay, this is the slow step of the reaction. The slow step would be first order for N2O, and so that seems like it's inconsistent with what our rate law was in part number B. However, there's 2 things we want to remember. A, the fact that this is an equilibrium, and the people who wrote this problem were nice to us. They even reminded us up here that this was fast equilibrium, and that N2O4 is an intermediate here, right? It is produced here, but then it would be used up again in step number 2. And we would never want to have N2 in a rate. So what we're going to say is that as an intermediate can't appear there. So we're going to have to do a little bit of math to prove that yes, this is a possible rate law, or this is a possible mechanism. We can come up with a rate law that matches what our answer was from part B. And so this is where we'll do a little bit of that fancy math from before, okay? And double and triple check this, but call me out if we made a mistake here. Look, for step number 1, we know that if it's equilibrium, the forward rate is equal to the reverse rate. We're going to start a conversation of equilibrium, I believe tomorrow, but maybe next week, where we talk about, that's one of the fundamental principles of an equilibrium, or reaction equilibrium, is that the rates have come to equal one another. And so we can say that the forward rate is equal to the reverse rate, and then we do that, just solve for the concentration of N2O4 and plug that into our original rate over here. Okay, so we would say that the rate for this overall reaction gives us kind of a new, much more complicated K, but it would be some sort of constant here times the concentration of NO2 squared, and that would be consistent with what we saw in part B as well, right? As long as the K that we had in part B matches this K here, so we make a note of that. I came across another solution for this that's a little bit different, kind of a cool way to solve it as well. So I just wanted to share that with you too. This is the way that we've been solving these problems. We solved them yesterday a couple different times that I've seen solutions like this. I saw an alternate solution as well, so I thought I would share that with you. And this really dives into the idea that we can have an equilibrium expression, which we've talked a little bit about for acid and basis. We haven't gotten to it yet in our lessons together, but I imagine you've talked about KEQs in your own classes at home. And so if we were to write a KEQ, if this is an equilibrium reaction, we must have a KEQ that's associated with it. That would be equal to products over reactants. So it would look something like this. And then we can rearrange this in a similar way that we did before to say N2O4 is equal to KEQ times NO2 squared, and just algebra there. And then we can plug that in for our rate law, and we're just continuing to bring this K2 that's down here. So this K is a different constant again from what we had before, but because it's constant, we can say that it's that this is consistent with what the rate law was we had before because of our concentrations of NO2. So 2 different ways to solve it. We haven't talked about KEQs specifically in class together, so for this one second, that would be a valid way for you to solve this problem. Okay, great. So like I said, we're going to get into collision model today. Talk about some graphs that I think will look pretty familiar to you, but we'll just give them a quick overview and then look at a couple of complicated problems where we have a multi-step reaction, and then wrap up our conversation with some catalysts and how they would affect a solution or affect a reaction on a couple different levels. Okay, so the collision model is obviously has a lot to do with how molecules are colliding. So what we want to say, and this is very similar to the kinetic molecular theory that we talked about 2 weeks ago. For any elementary reaction to successfully produce products, the reactants must collide successfully so that we have some bond breaking, and those would allow for some bond making events. Okay? The key here is just making sure that we're always thinking about collisions of the particles with one another. Okay, and when we say successful collisions are those that have sufficient energy to overcome the energy barrier, which we'll call the energy barrier the activation energy, and that the collisions must have the correct orientation that allow bonds to rearrange. And that orientation piece is something we haven't spoken about before. The sufficient energy thing will make sense because we'll spend a lot of time talking about temperature, right? And so temperature would be connected to the kinetic energy of the molecules, and so if the collisions are not strong enough, it makes sense that we're not going to have reactions. But those orientations are really a lot of times where catalysts come in, and so that's what we'll spend some time talking about that today. Okay, I want to share a resource with you that I use in my class a lot. It's again a free resource. Teachers, if you're listening, I think that this is a great resource that for you. Students, if this is something that it's free, you're welcome to look at it too. I will find myself when I have some extra time to around on my phone or on the interwebs. I'm going to Compound Interest. It's www.compoundchemistry.com. They're a company that makes a lot of different infographics, such as this one. I think they look really great. But what I really like about it is it doesn't just look pretty. The chemistry behind it is really solid. And if you were to spend some time diving deep, which I'm going to do into this one specifically about chemical reactions, if you dive deep in there, I think that there's a lot of learning that's going to happen. It's not just looking pretty, like I said. Okay, so I'm going to break down a couple each of the different squares on here for us. But I would encourage you, even just in your spare time, to go ahead and look around. You can follow them on the social medias, or just go to the website down here and see what you can find. So let's just dive real quick. This is a nice visual representation of what's happening with the collision theory. Okay, and what do we say? The collision theory tells us that in order for a reaction to happen, so here's our products up here, and here's our reactants up here, here's our products down here. In order for them to happen, we must have correct orientation and sufficient energy. So as we look through some other parts of this, we're going to want to assess, does this allow for correct orientation? Does it improve correct orientation? Does it improve sufficient energy? Does it do both? So if this is a correct rate or correct orientation and sufficient energy for these two to hit each other in order for this reaction to occur, here is an example of the wrong orientation. Right? So if the red molecule is oriented the same way, but the green molecule is oriented in the wrong way, even if they hit each other with a correct amount of energy, no, it doesn't matter how often or how hard they hit each other, they have the wrong orientation, so we would not have a reaction. Conversely, you may have some reactants that are going to hit each other with the correct orientation, but if they just lightly tap each other or they don't collide with enough energy, you're not going to have a reaction. Now, fundamental principle here is that, especially if you have gases, but even if these are solutions that are reacting with one another, the number of collisions, even at a low temperature, is astronomically large, right? And so when we increase temperature, there are more collisions, but there are orders of 10 to the 10 to the 20 collisions that are going to happen in any one reaction. And so it doesn't mean that every single collision has to be exactly successful, but anytime we can improve the orientation or improve the amount of energy the solutions have, then the percentage of collisions will increase for our reactions. Okay, so this is a really nice just kind of summary of the collision theory, and then we can talk about some of those factors that we discussed on Tuesday and how they will improve the rate of a reaction based on some of the fundamental principles of collision theory. So we talked about increasing the concentration of reactants is something that will increase the rate of a reaction, and what that does is it increases the frequency of collisions. Right? So this is green, has an arrow here to indicate that it increases the frequency, and that makes sense. When there are more particles there, we know that there will be more opportunities for collisions to happen. Now, it does nothing to guarantee anything about the percentage of successful collisions. We haven't increased the energy, right? We have not increased the strength of those collisions. So increasing concentration only increases frequency of collisions. It leaves the percentage of successful collisions neutral. Right? There's no change that happens there. When we increase the temperature of a reaction, okay, so here's a Maxwell-Boltzmann diagram that we've looked at a couple of times together. So here's the number of particles, the energy of those particles. We could say here's the most probable amount of energy for the particles. If we were to say that the area under the curve here, the green spot, is the particles that have enough energy to react, well, what happens when we increase from room temperature to room temperature plus 20 degrees? What we've done is we've flattened this curve. Oh, there's a phrase we've used a lot recently, right? We've moved both the frequency, the most common number of particles, and we've lowered it because there's so many more particles over here, right? We still have some that are down here. We didn't just slide the whole thing to the right. We've expanded it in such a way that the apex will come down, that we have a whole lot more particles at the higher end. And if we were to compare the green area here to the green area here, at a higher temperature, there are more particles that have enough energy for collisions. I'm sorry, for reactions to happen. So enough and more particles that have there can be more collisions, right? And more of those collisions will be successful because they're moving faster, so they have a higher amount of energy, right? So this line right here, which we're going to see in a couple minutes, is activation energy, right? We haven't changed the activation energy at all. We've just increased the number of particles that are beyond that activation energy by increasing the temperature and having more particles over here. Okay, so seeing the difference between these two graphs would be a really important thing. And this is a great example of how, on like an essay type question, we could give you these kinds of graphs and ask you to explain them. And looking that up, this isn't an easy explanation. There's multiple steps that you have to go through in order to explain what's going on there, right? Increased surface area, we looked at this. We know that when we increase the surface area of reactants, that's going to increase the rate of reaction. And similar to what we did with increasing concentration, we increase the frequency of collisions. There's more opportunities for collisions, but we know nothing about we haven't necessarily increased the energy or the strength of those collisions. So more collisions happen, but the energy or the strength of those collisions stays the same. Here's increasing the pressure. So this is really increasing pressure by decreasing volume, right? So what we see here is the piston is compressing the gas particles into a smaller area. So of course that means we'll have more collisions. The temperature stays the same. We are not going to have a different energy of collisions, but we would have having more often, and so that would increase the rate. Okay. So I'm going to just zoom back to this overall reaction or this overall sheet real quick. I skipped over Catalysis for right now because we're going to talk about it in a couple minutes at the end of today's lesson. But just encourage you can download these for free and see if there's anything in here that helps you to understand how collision theory connects back to the rates of reaction that we have spoken about for this entire week. Okay. Another kind of graph that we look at that I think is probably familiar to many of you is the reaction energy profile. Okay. It looks something like this. What we're seeing is potential energy is increasing along the left-hand side of the graph like this. We typically talk about the reactants on the left-hand side, the products on the right-hand side. There are versions of this where we switch it and we talk about the reverse reaction. I'm just going to talk about forward reactions for today. And we know that there is, if these are my reactants that are happening over here on the left-hand side, that we need to put some energy in to get them to this activated complex where we have sort of bonds are starting to disintegrate and other bonds are starting to think about forming until we get to our products over here. Okay. And so again, what we need to have here is some collisions that are increasing the number of collisions so that we can get to our products over there. That's going to expect or necessitate that we get to a specific amount of what we call activation energy, right? And so if this graph is given to us, we'll see a couple in a minute that where the scale is very specific, is delineated here. We have numbers on our y-axis. We can calculate the activation energy by subtracting the energy here from the energy that was given to us at the beginning. So here we have that we could calculate just the energy of the reactants or just the energy of the products. And the activation energy would be a subtraction where we'd say how much energy did it have to begin with, and then we would subtract that from this energy up here. The second thing we would calculate from here is the overall change in energy delta H enthalpy, which we'll get into in a couple weeks. And that would be calculated from just the reactants to the products. It's independent of what happened in between here, right? So if we just wanted to look at the reactants to the products, we would just look at the difference between those two numbers right there. This is an endothermic reaction. And I know that this is an endothermic reaction because my products have more energy. We went up from reactants to products. My products have more energy than reactants, so that means that we would define this as an endothermic reaction. And then we could define this one as an exothermic reaction. However, some things are going to stay the same. This is still, we would calculate our activation energy in the same way from reactants, from the line that is extended from reactants up to the line that's tangential to the top of our curve up here. And similarly, our delta H, our change in energy, would be calculated the same way. But here we can see that we went from reactants to products, means energy was released up to the environment. This reaction would feel hot because energy was given off. That means that an endothermic reaction would typically feel cold because energy is absorbed from the environment. Okay. And so being able to identify whether something is an endothermic or an exothermic reaction just from a graph like this is an important skill. This is something taken right off of an APE test where we're looking specifically at an uncatalyzed decomposition of hydrogen peroxide. And we should just be able to identify that because the reactants are higher than the products, that this is an exothermic reaction. Okay, so energy was released. This is an example of how we don't have any numbers, so we can't really calculate this. We're not going to, there's no math that's involved here, but we are going to, we should be able to assume that this is endothermic in nature because of the difference here at this line. So, okay. There is an equation called the Arrhenius equation that connects our rate constant, our activation energy, temperature of the gas law constant. This is something that's listed in our course exam description, something that's really important for you to be familiar with. And I suspect that with you, when you go into college and if you're going to take some college level chemistry or you are certainly going to go higher than Gen Chem in college, that familiarity with this equation is something that would be important for you to spend some time with. I'm not going to do any problems with it today because the course exam description does say this is not something that's going to be directly tested on the exam, right? So you're not going to have to do this this year in the exam. So I want to focus on just on the things that we would have to practice. However, the fact that we can connect activation energy to temperature, we can connect activation energy to rate constant. Specifically using this equation, we've got just a constant here that's called the rate factor. I'm sorry, the frequency factor. This is not the rate constant that E there. Another typo for today. You know what E is the base for natural logs. I apologize there. Then the other way that you will see this equation is a range where we can compare activation energy for one reaction at two different temperatures. Okay, so if we had two different temperatures, they would have two different Ks, and we could either get to activation energy or we could solve for one variable if we had all the others. So like I said, again, this is not something that you'll have to do specifically on this year's exam. However, it is something that when you get to college, I want you to make sure that you have familiarity with and would know that you could refer back to this equation to solve for any of the variables that we've listed here. If we're going to move on to a multi-step reaction energy profile, it is very similar to what we saw for a single step. Okay, we're going to read this from left to right in a similar way that we would read our steps from top to bottom. We're also going to notice that our slow step is going to be have a peak that is much higher, because and it's this high energy, high amount of activation energy that we're going to have to put in order to overcome, get our reactants over this hump metaphorically. That's going to make this a slow step. Okay, and so what we see here is a double hump because we have 2 steps. We see that this one is much taller because it corresponds with our slow step, and then the second one would be correspond with our faster step. This is still an exothermic reaction, right? We have delta H of negative 285 because we're going from our reactants up here to our products down there. Okay, so this is we'll look at a couple of examples of how we can look at this together with a catalyst in just a minute. I suspect that in your earlier chemistry classes as well, maybe in some biology classes where there's a lot of connection to biology, you've talked about some of the stipulations of what a catalyst does. We hinted at it yesterday where we talked about catalyst is consumed in the rate determining step, but then is regenerated in the subsequent step. Okay, so it would appear as a reactant in an earlier step and then occurs as a product later on. What a catalyst is going to do on a physical level is to increase the number of collisions or provide a reaction path with lower activation energy. So it's either increasing those the effective collisions, that would be the orientation, or it's going to lower the activation energy, or in some cases it might do both. Okay, and so when we said on Tuesday that adding a catalyst to a reaction is that necessarily going to increase or decrease the rate of the reaction? Well, catalysts are very specific to a reaction, so not every catalyst is going to, by its definition, increase the rate of a reaction if it can't do one or both of these things. So adding a catalyst that's not specific to the reaction that's given to you would not change the rate of reaction. Okay, so if we define this first graph, this is similar to what we looked at before. Okay, we have one line that shows our uncatalyzed activation energy. Okay, please forgive my drawings in here. Trying to get a consistent drawing on Google Slides was my best effort, and I tried it a bunch of times. So be patient with me, okay, guys. Here it would be our activation energy for the catalyzed reaction. So we see that this amount is lower. Again, I'm doing very qualitative work here. We'll look at some quantitative in a second, just for to understand what would happen for. Can you identify this exothermic or endothermic? It's an exothermic reaction. It has less activation energy for the forward reaction. Okay, for when it's catalyzed. So what we've done is we have the same reactants, the same products. Our delta H does not change, and that's a key part of a catalyst. Is it doesn't change the overall delta H. We're still going to get the same reaction, the same delta H out of this reaction. It's just the path by which we'll get there is going to decrease. The energy we have to put in, the activation energy lowers. Okay, and we can do a similar thing. Our line is not quite as good there. Sorry for an endothermic reaction. And I just really want to point out to you that yes, the activation energy has been lowered, but our delta H has not changed for a catalyzed reaction. Okay, so a question like this, this is a really cool. This was a free response question on a test a couple of years ago, where you were given 4 different diagrams, and you were asked to identify the 2 that could represent a catalyzed and an uncatalyzed reaction pathway for the same reaction. Okay, so they separated out my lines from the earlier graph, and then indicate which of the 2 diagrams represent the catalyzed and which is the uncatalyzed reaction. So take a second to pause if you need to and take a look at this reaction. And what I would do here would be to identify which reactions are starting and ending at the same place, because if they are starting and ending in the same place, then they could be a pair of reactions for the same reaction, right? So we're going to identify our delta H. So it appears that for these 4 diagrams, they all start in the same place, but clearly we only have 2 that are ending in the same place. So the difference between our reactants to products is the same for diagram 1 and diagram number 2, but we see diagram number 3 is much more exothermic than these 2 over here, and diagram 4 is endothermic compared to these. And a catalyst is not going to change our reactants to products; it just changes how they get there. And so we would do to answer the first question is we would say diagram number 1 and diagram number 2 are the way to go. Okay, they are the ones that represent catalyzed and uncatalyzed reaction pathway for the same reaction. And now the second part is to identify which one is the catalyzed reaction. Okay, so what I'm going to do is going left to right. Here's our activation energy for the first reaction. Here's the activation energy for the second reaction. And what I'm going to say is that the activation energy for diagram number 1 is less than the activation energy for diagram number 2. And so diagram number 1 is catalyzed and diagram number 2 is uncatalyzed. Okay, so that's just very qualitative in nature, but we still can make some pretty good conclusions about what's happening in each of these diagrams in each of these graphs. Okay, here's another way of looking at that same picture that we looked at earlier, where we're saying higher activation energy is here. Sorry, this is a Maxwell Boltzmann diagram. So instead of changing the temperature, I'm sorry, this is a different graph. This is Maxwell Boltzmann, but instead of changing the temperature and moving our red line over, what we're doing is we are lowering the activation energy. Okay, so again, we're comparing the area that's underneath this curve, and we're saying that a higher activation energy, maybe the normal reaction, would be right here. And so only these particles underneath the line would have enough energy in order to produce products. Whereas if we lower the activation energy by adding a catalyst, we move the line down here, and in this way we have increased the number of particles that are underneath the line as well, not by moving our line when we increase temperature before, but by moving our activation energy to the left. So our conclusion here is that we have more particles that have enough energy to become products because we've lowered the activation energy. Okay, this is again a question that came right off of an AP test. If we are given a Maxwell Boltzmann diagram of line A, line B, and line C, which line of the graph would you change to explain the increase in the rate of reaction if the only change in experimental conditions is the addition of a catalyst? Okay, so does line A move, does line B move, does line C move? So if we're going to change temperature, that might be one answer. But this question is asking about catalyst, and what we're going to say is line B here would move to the left when we add activation energy because, when we add catalyst because the activation energy is less. Okay, so the answer to this is line B. Okay, let's look at some quantitative information here. 2 reaction diagrams represent the same reaction, one with and without a catalyst. We separate them out. Estimate the activation energy for each process and identify which one involves a catalyst. So we can look at our activation energy here. We're going to quantify. We can estimate that we have about 32 minus 6. You can argue with my numbers there, but it's somewhere close to that. And we have activation energy of 26 there. I want you to notice that we're going to start at the same place. So this number, the second number 6, and 6 better match one another. This is 21. You might want to say it's 25. I'm just going to estimate 1. Again, here, so I'll leave it at 21 and say that we have 15 joules here, which makes this a catalyzed reaction because the activation energy is lower. I'm going to continue to hammer on this idea that the delta H does not change. Okay, that it tells us that this is a catalyzed versus an uncatalyzed reaction because the delta H has not changed there. Okay, here's a 2-step problem where we're doing a similar thing, right? Where we're asked, one of them is the rate determining step, compute the activation energies for the first step of each mechanism. So I would estimate these as 90 minus 10. I would estimate this as 80 minus 10. So clearly the one on the right is the catalyzed reaction again. Okay, and then compare the second steps to the 2 mechanisms. So the second steps both the same. They both have the same amount of energy. And just to drive home this principle, I hate to keep saying the same thing, but I do think it's really important for us to remember that the delta H, the overall energy change for the reaction, is not going to change. So I'm just going to continue to review that to make sure that these diagrams are showing the same. Okay. Now, in my research and in preparing for you guys today, I kind of put our types of catalysts into 3 different groups: binding catalysts or binding catalysis, acid-base catalysis, and surface catalysis. I think the first one is probably the one you're most familiar with in terms of your studies in biology class, and so that's really specific to enzymes. We talk about either reactants are oriented in a more favorable way in order to lower the activation energy. There's a lot of help in making the reaction happen a little bit more quickly. That's where you see kind of your classic enzyme here with a substrate. This is right out of like an AP biology book, if we're honest. But a similar thing could happen where we don't have specific bond. We just have some sort of interaction. We call these binding catalysts, where they are interacting with one another in order to make our products here, but we don't have physical bonds happening between each of them. Okay, and we would think about kind of enzymes working that way. And acid-base catalysis is either where we're going to add or gain a proton. And so this is a really complicated picture that I'll leave up here for a couple minutes or a couple seconds. That came out of a source down here. And what's happening here is we're breaking sucrose down into glucose and fructose. So another probably example of something that would happen in biology or happen in the human body, where an acid would be joined onto this oxygen right here, right? So when the acid would donate a proton here, right? That's what acids do. They donate protons to jump onto this oxygen right here. here, that's going to weaken the bond that's here and allow this dehydration synthesis to come in and to break apart our sucrose into glucose and fructose. So this is a process that happens on its own. There probably is actually another enzyme that helps it to happen, but this acid catalysis is going to speed up the process even more in the presence by putting this hydrogen here and weakening that bond a little bit. Similarly, we have this is a much more general equation for basic catalysis in the presence of a base. We have this base over here that's going to grab a proton, weaken the bond over here, which has impact on all of the bonds up here as well. And so this would allow for hydrogen to jump in over here, and we went from our double bonded O to our hydroxide over here. Okay, and so this base is going to be reproduced in the end. So we still have this base that can go and repeat this process over and over again. And we would similarly we'd have a hydrogen over here, this acid that's able to continue on this process over and over again. And that would be a classic example of how a catalyst would work. Okay, so two examples, pretty complex examples. I think for our purposes, probably remembering that, oh, hey, what do acids do? They add protons, they don't need a proton. They're going to add that proton specifically onto the substrate, and then in the presence of a base, a proton would be removed because what does a base do? A base is a proton acceptor. Both of those are consistent with our discussion of acids and bases from earlier on later. Surface catalysis is something that happens a lot in industries and is a really cool thing where we talk about there's actually the surface area of a substance, typically a metal, that is going to act as a catalyst because it's going to go through some specific steps in order to help the bonds to rearrange one another. Okay, and so here's an example right off of an AP test where we're looking at the reaction of nitrogen and hydrogen to make ammonia, and there's kind of classically 4 steps to a process like this. The first step is where we have adsorption, so the nitrogen gas is coming in here to interact with the surface of the metal right here. Hydrogen was coming in and doing a similar thing. We're going to activate this by both of these elements, both these atoms. The second step would be activation by the bond here is moving from between the nitrogens to the surface of the nitrogens to the metal to the surface, and nitrogen to the surface of the metal. Excuse me. Then we would have a reaction between the nitrogen and the hydrogen, and then the last part is that it would release. So this is really happening only on the surface area of this. That's what's called surface catalysis or a surface catalyst, where the gas or even a solution is coming in and interacting with the surface. Then we have a reaction between two things, and then they get released. So surface has not been altered at all. Here's another example of using nickel, and this is one where ethylene, which is a double bond, is going to interact. Both hydrogen and ethylene come into nickel, so we would have adsorption, we have activation, we have a reaction, and then we have a release of the particles over here. Okay? So 2 different examples of the surface catalysis there. One of the 80 questions that I came across as I was preparing for today is a short answer. We haven't spent a lot of time with those today, so I figured I would throw one of these at you. We haven't spent a lot of time with those over the course of these 2-3 weeks we've been together. So I thought I would challenge you to think about this. I'm writing a short explanation for either in support or disagreeing with the statement that adding a catalyst to a reaction mixture adds energy that causes the reaction to proceed more quickly. So this is something that a student might say as they're explaining catalysts to their little brother or little sister. Would they be correct or not? And how would you explain whether you agree or disagree? So take a second to pause and maybe write out your explanation. And I would say that I would have to disagree with this statement, that catalysts do not add energy to the reaction. There's one of 2 things that a catalyst has to do. It increases the number of effective collisions, or it provides an alternate reaction path with a lower activation energy. So in order for a catalyst to be productive, it has to do one of those 2 things. We're going to talk about adding energy to cause a reaction to proceed more quickly. Well, what we're doing there is we're adding temperature, and energy is always associated with temperature, not with a catalyst. And so we would not like to conflate those 2 things. And so this would be a good example where you could tell the person that's educate them on how catalysts actually work. So that's the end of our lesson for today. A lot of theory here, and I hope it was helpful for you. Or look at collision model. I would really encourage you to go back and review that because it has a lot of applications in multiple different areas. I got into some specifics about catalysts. Those reaction energy profiles I think are pretty straightforward, but you may want to practice a couple more of those before looking at your homework tonight. Practice problems. This is right off of an AP test. To take a screenshot of this because it is multiple steps. So we're looking at carbon tetrachloride, okay, and how a graph. This graph should look familiar to you. Maxwell-Boltzmann diagram. How it's familiar to you based on what we looked before. And say the question is asking how to draw a second curve on the graph that talks about the temperature if the collisions happen at 30 degrees Celsius. Okay, and then the second question we have for you gives you a reaction mechanism. Asks you to write the rate law. So here's a couple of reviews actually from our lesson yesterday. But then draw a curve. So we're going to draw one of those potential energy curves, one of those reaction curves that we've been looking at today. That shows a 2-step process. Make sure that you include the enthalpy, the change of the reaction, and really indicate what the activation energy is. Give you a second to take a screenshot there. Okay, that's the end of our lesson for today. Thank you so much for joining us. Check out apcentral.collegeboard.org. Anytime you have extra questions, we've got lots of reviews, lots of resources there for you. If you check out that compound chemistry as another one, if you're looking for some nice diagrams and some infographics to look at. And lastly, but very importantly, make sure you're encouraging people to go to cb.org/tech for any help that they need getting internet or getting access to a device. Have a great day. All the snow melted here. If you were worried about me, no hats and gloves today. So we're going to go outside and enjoy some sunshine today. Hope you're having a great day, and we'll see you tomorrow. Take care.
Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, our lesson will start with Unit 6, Thermodynamics. Just want to remind you, as always, that you can go to apstudents.org/exams2020 to get more information about taking AP exams online this year. For AP Chemistry, your exam date is on May 14th, and as you can see here on the screen, it's going to be given at the same time. So depending on where you are in the world, you're going to be taking it at a particular time according to your time zone. There are 2 free-response questions on the AP Chemistry exam. The first one will count for 60% of the exam weight and last 25 minutes, and the second question will count for 40% of the exam weight and will be 15 minutes. And you can see here on the screen, explain chemical phenomena using models, theories, representations at the particulate and macroscopic levels, draw conclusions from experimental results, identify and explain experimental procedures that are aligned to a question, and analyze sources of error. So a lot of analysis, and so again, hopefully today's lesson will help you practice those skills. If you have a periodic table and something to write with and some scratch paper, let's go ahead and get started. So this is going to be an introduction to Unit 6, which is on thermodynamics. So the topics that I will cover today include endothermic and exothermic processes, energy diagrams, heat transfer and thermal equilibrium, heat capacity and calorimetry, and energy of phase changes. And you can see here on the screen the requisite science practices. Some of the things that I already talked about in terms of making observations and representing phenomena with graphing techniques, as well as talking about connections between the particulate and the macroscopic scales. So I will begin by talking about endothermic and exothermic processes. I'll talk about energy diagrams. We'll talk about the difference between energy, enthalpy, and heat transfer and thermal equilibrium, specific heat capacity and calorimetry, and the energy of phase changes. So typically before we dive into the content of our lesson, we start with a warm-up problem, and this would be the homework problem, the AP Chemistry problem that Mr. Byrne assigned in yesterday's lesson. So here we have number 1 says in part A, chlorine gas is initially present in the container at a pressure of 0.40 atmospheres. And the first part of this question is to calculate how many moles of chlorine are in the container. So we have a pressure, we also have a volume, and we have a temperature. So hopefully you can think about the fact that we're going to be using the ideal gas law. We'll be solving for moles. So pressure is already in atmospheres, so we can use our ideal gas constant, 0.08206, and that does have units of liters, atmospheres, and then per mole per Kelvin. Now, the fact that it's Kelvin, be careful that you don't forget this important step, and that is you cannot plug in 120 into your calculator and get the right answer. So 120 plus 273 is going to equal 393 Kelvin. So it's the Kelvin temperature that you should be using to solve for moles. All right, well, if you did that particular setup using the ideal gas law, then the math you're doing on your calculator is 0.4 times 25 divided by 0.08206 divided by 393. And we're going to go ahead and round this off to 2 significant figures based on the least number of sig figs. So I got 0.31 moles of chlorine gas. So that takes care of the first part. Now the second part says how many grams of carbon disulfide are needed to react completely with the chlorine. So we're going to have to use our knowledge of stoichiometry and the fact that there is a 1:3 mole ratio between CS2, the carbon disulfide, and then the Cl2, the chlorine gas. Also remember to use your periodic table because we'll need to go to grams, so therefore you have to figure out what is the molar mass of CS2. All right, so I'll start with the answer from Roman numeral 1. That was the number of moles of chlorine that we got from the ideal gas law. Let's use the 1:3 ratio, which is given to us by the coefficients to convert from moles of chlorine to moles of CS2. Then if we look on our periodic table, we see that carbon has an atomic mass of 12.01, sulfur has an atomic mass of 32.06, but there are 2 of them in the formula. That's 64.12. So for a grand total of 76.13 grams of CS2 per mole. So if we do this math, 0.31 divided by 3 times 76.13, we get our answer, which is 7.9 grams of CS2. Again, I'm just rounding off to 2 significant figures. All right, well now onto a part of the problem that looks more relevant with respect to things like kinetics and reaction rates. So we are told that at 30 degrees Celsius, the reaction is favorable. In other words, it is supposed to occur. However, no reaction is observed. So it is favorable but not observed. And then at 120 degrees, the reaction occurs at observable rate. It should not surprise you that when you raise the temperature of a reaction, you are going to increase the reaction rate, but you have to explain why. So explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120 degrees Celsius. It would not be acceptable to simply say higher temperature leads to a higher rate. You have to talk about the collisions. And I would probably at this point encourage you to mention activation energy. That is a key part of it. So the activation energy is going to be the energy required. And we can see that coming up on the graph that we're going to have to draw in part 2 of this question. So let me just remind you from something I talked about a while ago. This was back in unit 3 on intermolecular forces. Here we see a liquid inside a flask, and the vapor pressure is going to be the pressure of the vapor above the surface of the liquid. And according to the graph, you can see that as vapor pressure increases, as temperature increases, there is a relationship there that higher temperature leads to a higher vapor pressure. So Mr. Byrne had talked about these Maxwell-Boltzmann curves. Here's an example of a Maxwell-Boltzmann curve for a colder temperature of the liquid. And here is the minimum kinetic energy required for molecules to escape. So you can see that only a small fraction of the molecules are going to have the ability to escape the liquid. And so what happens when we raise the temperature is we increase the average kinetic energy of the molecules. And so that curve shifts, and now a greater fraction of the molecules have the kinetic energy needed to escape. So instead of talking about kinetic energy needed to escape a liquid in a physical phase change, think of it as a chemical reaction. A greater fraction of the molecules will have the required activation energy when they collide. So at a higher temperature, the molecules have a greater average kinetic energy. Again, here's the part about the collisions. The fact that there's a greater number of molecules that have sufficient energy to overcome the activation energy. So they are not only colliding more often, but with more force. And again, that greater fraction of molecules that has enough energy to overcome the activation energy, that's a key part of this explanation. Now they've already given you a graph for 120 degrees, and our job is to draw one at 30 degrees. Now many students who got this question wrong on the AP chemistry exam did this. So they just assumed that it would be lower, completely just drawing a new curve that was underneath the first one. Hopefully you can see that that would not be correct because we still have to have the same area under the curve. So we're going to be shifting this curve to the left because it's a colder temperature. Therefore, the peak of this curve, that is the average kinetic energy or the mean, has been shifted, but also this area under the curve is lower. Okay, so in terms of getting this particular question correct, this part of the question was worth 2 points on the scoring guidelines. 1 point for a student's drawing in which the curve has a peak that is above and to the left of the given curve. And then the second point is earned for a curve that is below the given curve in the region beyond the activation energy right there. All right, there was another homework problem that Mr. Byrne gave you, and that was we have a reaction that's been broken up into 2 steps. We have a rate determining step, step 1, which is a slow step, and then we have step 2, which is a fast step. So our job is to write the rate law for the reaction that is consistent with the reaction mechanism. So focusing primarily on the slow rate determining step, we can see exactly 1 molecule of C2H4 and 1 molecule of HCl. So from that elementary step, we can say that it's first order with respect to C2H4 and first order with respect to HCl. So that gives us a rate law. Rate equals K times the concentration of C2H4 raised to the first power times the concentration of HCl raised to the first power. The next part of this question is identify an intermediate. So you could have picked either the C2H5 plus or the Cl minus. Either of them would have been correct because they are formed in step 1 and then consumed in step 2. So they are intermediates. Then we had to draw a curve. Considering that the reaction is going to have reactants and products, the reactants are C2H4 and HCl. Now where should we draw the potential energy for the products? Should we draw it up here or should we draw it down here? It depends on whether the reaction is exothermic or endothermic. So we are given that there is a negative delta H. That means that it's an exothermic reaction. So we should focus on the products being at a lower energy level than where we started. So the correct curve should look something like this, but I made a mistake in that this curve that I've just drawn indicates, although it's exothermic, that the reaction occurs in a single step. Notice that we have just one activation energy, one little hill to climb over. We know this is a 2-step reaction, so we have to show that with our curve. We have to show the first step, which is going to have a higher activation energy, and then the second step, which is going to have a smaller activation energy. So in sort of colloquial terms, it's a big hill and a small hill. So this would be the activation energy for the reaction. So we're showing the activation energy for the rate determining step, and that would be that first step. The higher the activation energy, the slower that particular step is. All right, so now moving on to our information about thermodynamics today. I'd like to start with endothermic and exothermic processes. And here I have 2 little examples of this might occur. You've got a instant cold pack, and it's the kind of thing you can sort of squeeze this bag, and there's a pouch of water inside, and you squeeze the bag until the pouch of water breaks, and it dissolves a particular solid. It's an endothermic process for an instant cold pack, and it's an exothermic process for an instant hot pack. So instant cold packs are doing something with respect to energy that's the opposite of what an instant hot pack is doing. Let me just help you identify exactly what's going on in terms of energy. So for an endothermic process, energy is transferred from the surroundings to the system. So the system is the dissolving of that solid that's inside the instant cold pack into water. Now when we feel the cold pack, it feels cold because our hand is part of the surroundings. The system is going to be the water and the dissolving solid. The surroundings are everything else, the container and everything outside. So for an instant hot pack, it's an exothermic process. Now energy is transferred from the system to the surroundings. And again, since our hand is part of the surroundings, we touch the hot pack and it feels warm. So let's be clear on the direction of energy flow. For endothermic and exothermic processes, let's also define the system and the surroundings. So we define the system as the portion of the experiment on which we choose to focus our attention, which is normally the reactants and the products. For a chemical change, or even for a physical change, would be the chemicals that are changing, combining, dissolving, melting, things like that. And the surroundings are everything else, the container and everything outside. Now there's an important note which will come up later in this lesson. If you are dissolving a solid in water, the thermometer, which is used to record the temperature, is considered to be part of the surroundings. My students really struggle with this in my class when I say that something gets colder and it's endothermic, because in their mind they're thinking, well, if it's absorbing heat, why isn't it getting warmer? It is absorbing heat, but typically from the surroundings, and therefore the surroundings are getting colder. The thermometer is part of the surroundings. So when you release energy to the surroundings, the thermometer goes up, the temperature goes up, and when you absorb energy from the surroundings, the temperature goes down. All right, so we have something known as the first law of thermodynamics, also known as the law of conservation of energy. Energy cannot be created or destroyed; it can change from one form to another. And again, for an endothermic process, heat is absorbed by the system, and for an exothermic process, heat is released to the surroundings. Now, since even though this is a chemistry lesson and not a physics lesson, you all that are in physics classes or have taken physics might know that there is more than just heat. Another common form of energy, which is used in various calculations in physical science, is work. So work done on the system. Again, energy is still going into the system is endothermic. Work done on the surroundings, so energy is leaving the system, it's exothermic. We spend the majority of our time in chemistry focusing on heat and not on work, and I'll talk about that a little bit later. So this person is exercising and they are perspiring. So how exactly does sweat, how exactly does perspiration cool the body off? Well, here's a close-up view of what's happening. There's a little drop of sweat that contains water molecules, and the water molecules evaporate. That means that the water molecules are changing from a liquid to a gas. So do you think that evaporation is an endothermic or an exothermic process? Remember that perspiration or the evaporation of that perspiration is going to cool the body. So is the process of changing water from a liquid to a gas endothermic or exothermic? Well, it is endothermic because you have to absorb energy to change the molecules of liquid to a gas by separating the intermolecular forces between the liquid. So if it's taking in energy, where is the energy coming from? Well, it's coming from the body. So heat is removed from the body as perspiration evaporates. The water is part of the system. In this case, the evaporation of water involves the water molecules, and the body is part of the surroundings. So heat is flowing from the surroundings to the system. The body is losing heat, and the water is gaining heat. Now let's talk about energy diagrams. We can represent energy along the y-axis, and if you see a diagram like this or like this, you can see that the products are at a higher energy level than the reactants. Earlier, in one of the practice problems that I showed you in our warm-up, it was an exothermic process. It was actually the opposite. It was downhill, where the products were at a lower energy level than the reactants. So if you see an energy diagram, you can tell that the energy diagram is either endothermic or exothermic by comparing the reactants and the products. So endothermic looks like this, and exothermic looks like that. All right, now the words energy and enthalpy and heat are often used in chemistry interchangeably. So let's pay close attention to these words for a moment. Energy in general is the capacity to do work or transfer heat. So some textbooks define the change in internal energy as delta E, and they refer to the delta E as the sum of the heat, which we're going to call Q as a symbol, and work, W. If the change in energy is the sum of the heat and the work, what exactly are heat and work? Well, heat is the transfer of energy that takes place because of a difference in temperature. Heat spontaneously transfers from the warmer object to the colder object. So if you touch, let's say, something hot on the stove, then the energy is transferred from the stove to your hand. But if you're holding an ice cube and the ice cube starts to melt, now the heat is being transferred from your hand to the colder ice cube. Work is the exertion of a force through a distance, and sometimes represented in physics as force times distance, or it can also be represented as pressure times the change in volume. And there's a negative sign there because if work is being done on the system, well, that's a positive value. The delta V would be negative. Effectively, what I'm saying when I say the delta V is negative is if you're doing work. So for example, let's say I have a piston and I'm compressing a gas inside a piston. So I have to change the volume. By decreasing the volume, delta V would be negative, but therefore, since I have a negative times a negative, it would be positive, as in work being done on the system. Again, we're going to spend the majority of our time focusing on heat and not work. And that's because in chemistry, many phase changes in chemical reactions occur at constant pressure. That brings up the concept of enthalpy. So enthalpy is used to measure changes in energy for a constant pressure system. And because enthalpy is defined in this way, which is the sum of the delta E and then this pressure volume work, it turns out that when we talk about enthalpy, we effectively are referring to the heat. So while they are not exactly the same thing, for all intents and purposes, when you hear a chemistry problem refer to the change in enthalpy, it is essentially the change in heat energy that we're focusing on. So typically, we're not talking about pressure volume work for most processes in chemical reactions and phase changes. Now, in terms of that change, if delta H is positive, that means that the difference between products and reactants is a positive value. That's endothermic. But if the difference between products and reactants is negative, that's an exothermic process. An important point to clarify here is Q versus delta H. If an AP question asks you to calculate the value of Q, they typically are referring to the magnitude of heat that is either absorbed or released. And so for problems like that, they don't normally ask for the sign of Q. So the magnitude of Q, or the absolute value, is how much energy was absorbed or how much energy was released. And the units of Q are typically joules or kilojoules. Now, if instead the question says calculate the value of delta H, pay close attention to whether it's an endothermic or an exothermic process, because you might miss a point on the AP exam if you forget to include the proper sign, especially if it's negative and you don't include that negative sign for an exothermic reaction. That's important. Now, the units of delta H are typically kilojoules per mole or kilojoules per mole of reaction. So stoichiometry and potentially a balanced chemical equation may come into play. So be careful that you know the difference between Q, which is heat, and delta H, that change in enthalpy. All right, just a brief comment about heat transfer and thermal equilibrium. Suppose we have a sample of copper metal and we place it in a bath of boiling water at 100 degrees Celsius. So now we have this hot piece of copper metal. We take it out of the boiling water bath and we quickly transfer it to a styrofoam cup that contains a sample of cool water at 20 degrees Celsius. Now, heat transfer and thermal equilibrium. At some point, the temperature of the copper will become the same as the temperature of the surrounding water. So heat is transferred from the hotter object, in this case the metal, to the cooler object, in this case the water. The atoms of metal are slowing down, the molecules of water are speeding up, and eventually thermal equilibrium is reached, in which each substance has the same average kinetic energy, which means they have the same temperature. So when heat is transferred from a warmer object to a cooler object, eventually that transfer will continue until thermal equilibrium is reached. So that experiment of transferring a hot piece of metal to a cooler cup of water is a rather classic thermochemistry experiment. So you might have actually done this in your chemistry class, or you might have seen a demonstration about this. Here I have a data table with information about how much the copper weighs, 50 grams. The initial temperature of the copper was 100 degrees Celsius because it was sitting in a boiling water bath, and that is the boiling point of water. The mass of the water in the styrofoam cup, 100 grams. Initial temperature of the water, 20 degrees Celsius. So when thermal equilibrium was reached, the final temperature of both the copper and the water was 23.6 degrees Celsius. Okay, this is a rather easy set of questions to ask you. I'm going to ask you to agree with a particular claim that is made by a student. So here are two easy questions. First, what's the delta T? What's the change in temperature for the copper? And notice I'm talking about the absolute value of this. Don't worry about the sign being positive or negative. So I'm not worried about T final minus T initial, just the magnitude. So the delta T for the copper. Well, if you're looking at the data table, the math you're doing is 100 minus 23.6. So our delta T for the copper is 76.4 degrees Celsius. All right, what's the delta T for the water? The change in temperature, just the absolute value, the magnitude. Well, that's going to work out to be 23.6 minus 23.6 degrees Celsius. Okay, here comes the student claim. Decide if you agree with this claim. A student claims that since the magnitude of delta T for the copper is greater than that of the water, it means that the magnitude of heat Q lost by the copper is greater than the magnitude of heat gained by the water. Do you agree with this claim? And again, feel free to pause the video if you want to think about this before checking the answer. You have to make a decision. Is the magnitude of heat lost by the copper less than, more than, or equal to the magnitude of heat gained by the water? Well, earlier I talked about something called the first law of thermodynamics, also known as the law of conservation of energy. It states that energy cannot be created or destroyed. It can change from one form to another. If we make the assumption that this styrofoam cup is perfectly insulated and that no heat is lost to the surroundings, according to the first law of thermodynamics, the magnitude of heat lost by the copper must be equal to the magnitude of heat gained by the water. Now, how do we calculate this in terms of calorimetry? So on your equation sheet on the AP chemistry exam, there's lots of equations in this section under thermodynamics, but I'm focusing on this one, which involves heat, M for mass, C for something called the specific heat capacity, and then T for temperature. Let's think about what exactly is the specific heat capacity, and let's talk about units. So for water, it turns out that the specific heat capacity is 4.18 joules per gram degree Celsius. Sometimes you will see this listed as joules per gram Kelvin. Either one of those is actually fine, Celsius or Kelvin, because the change in temperature either way is the same magnitude. If the thermometer goes up by 10 degrees, it will also go up by 10 kelvins. So what this means is that it requires 4.18 joules of energy, of heat energy, in order to raise the temperature of 1 gram of water by 1 degree. Now, copper, aluminum, glass, sand, iron, all kinds of substances have their own values for the specific heat capacity, and the units are going to be joules per gram degree Celsius. I just gave you the value for water, but the specific heat capacity for copper is unknown to us. We can use the equation Q equals mc delta T to help us determine the specific heat capacity of copper. Again, a common experiment in chemistry class under the category of thermochemistry or thermodynamics. So how we're going to do this is based on the fact that the heat that was lost by the copper is equal to the heat gained by the water. So mc delta T for the copper is equal to mc delta T for the water. And we know everything except for the specific heat capacity of the copper. We know the mass of the copper is 50 grams. We know that the change in temperature of the copper was 76.4 degrees. We know that the mass of the water is 100 grams, and we know the specific heat capacity of the water that was given to us, and the change in temperature for the water is 3.6 degrees Celsius. So all I have to do is just get C, the specific heat capacity for the copper, on a side by itself. I'll just divide both sides by 50 and 76.4. My units of grams will cancel out. My units of degrees Celsius on the right will cancel out, but I will still have my final answer in units of joules per gram degree Celsius. So if you do on your calculator 100 times 4.18 times 3.6 divided by 50 divided by 76.4, you get 0.39 joules per gram degree Celsius. So that is our experimental value, and it's very much the correct value. I did this by checking the official value, and that is the accepted value for copper. So 0.39 joules per gram degree Celsius. Now, I want to ask you a conceptual question. It does not require calculation, but I will still do some math to kind of verify our prediction here. Suppose you have each of these samples, same mass, different specific heat capacity, same initial temperature, and each of these samples absorbs 500 joules of heat. So the conceptual question is, which sample, the water or the copper, will reach a higher final temperature? Justify your answer. Again, feel free to pause the video, think about this before the answer is revealed. Okay, well, before I tell you the official answer and do some math, remember that this is your focus. It's the same heat, it's 500 joules. It's the same mass, it's 100 grams. So look at this relationship between these two variables. If that is a direct relationship, that means that as one value goes up, the other value also goes up. If it is an inverse relationship, that means that as one value goes up, the other value goes down. When you multiply two variables together to equal a constant, that represents an inverse relationship. So therefore, the higher the specific heat capacity, the smaller the delta T. So if the question was asking which of these two substances is going to reach a higher final temperature, the correct answer is going to be the copper, because it has a smaller specific heat capacity, then its delta T will be larger. Now we didn't have to do any math to answer that question, but let's go ahead and do it. So we have Q equals MC delta T for the water. That's 500 joules, 100 grams, 4.18, and we don't know the delta T, so we'll go ahead and solve for delta T, and we get 1.2 degrees Celsius. So the final temperature of the water is 25 plus 1.2, 26.2. For the copper, we have Q equals MC delta T. Now we have plugged in our information. Again, a smaller magnitude of the specific heat capacity leads to a larger delta T. So the copper has gone up by 12.8 degrees Celsius for a final temperature of 37.8 degrees Celsius. Now I probably should have said 25.0 degrees Celsius. I would have the proper sig figs, but I'm focusing on the magnitude here. So again, inverse relationship between the value of C and the value of delta T. Sometimes you will see molar heat capacity, and the units are not joules per gram degree Celsius, but rather joules per mole degree Celsius. So can we take 0.39 joules per gram degree Celsius and multiply by some conversion factor that will give us joules per mole degree Celsius? So what's missing here in this conversion factor would be something that will put grams on top and moles on the bottom. So all we really have to do is consult our periodic table to do this conversion. So the periodic table tells us that copper has a molar mass of 63.55 grams per mole. If we do this math and the units of grams cancel out, the molar heat capacity of copper is about 25 joules per mole degree Celsius. Okay, next thing I'd like to talk to you about is the energy of phase changes. What I have here is a diagram involving heat on the x-axis and temperature on the y-axis. I want to focus on the phase change of water. I'm going to look at the melting point of water, which is at 0 degrees Celsius, and the boiling point of water, which is at 100 degrees Celsius. So I have drawn horizontal lines on the diagram indicating the melting and the boiling point of water. Now suppose I start off with some solid H2O, some ice, at around negative 40 degrees. As heat is added, the temperature rises. The reason why the temperature rises is because I am warming a substance, in this case solid water, and I would calculate the amount of heat required to raise the mass of water by a particular value of degrees Celsius using Q equals MC delta T. So now I'm at the melting point of water. What happens when more heat is added? Will the temperature continue to rise steadily up to 100 degrees Celsius as the ice melts? No, in fact we reach a plateau, and this particular plateau means that we are not talking about MC delta T because our delta T is actually 0, and yet heat is being added. So this is what's known as the enthalpy of fusion, and fusion is essentially a fancy word for melting. So the enthalpy of fusion involves the transfer of energy from a solid as it's converted into a liquid. Some of the intermolecular attractive forces between the solid crystal particles are broken, and now we have water in the liquid state, but we are still at 0 degrees Celsius. If we add more heat, now that we have converted the solid completely into a liquid, the temperature starts to rise again. So we're back to MC delta T, the change in temperature for a liquid. So we are warming a liquid. Incidentally, there is a different specific heat capacity for water, whether it is a solid or a liquid or a gas. Okay, well now we're at the boiling point of water and we have to add more heat. We reach another plateau. At this point, we are breaking not just some, but all of the intermolecular forces. So if we're breaking all the intermolecular forces as we go from a liquid to a gas, hopefully you can see it's going to take more heat to change a substance from a liquid to a gas than it does to change a substance from a solid to a liquid. So this is not the enthalpy of fusion, this is the enthalpy of vaporization from a liquid to a gas. Now we're at the state where all of the liquid has been converted to a gas, and we can continue to heat this gas to temperatures above the boiling point, and we're back to MC delta T again. So what I'm showing you is a phase diagram or a heating curve, and this particular heating curve has slanted lines as well as flat lines. The flat lines are when phase changes occur, and the slanted lines are when you're just warming one of the phases. So either warming a solid or the solid melts, you're warming the liquid evaporates or boils, and then you're warming the gas. You can see on this slide that we have different values for the specific heat capacity of water, whether it is a solid or a liquid or a gas. You'll also notice that when we do the enthalpy of fusion, that line segment is smaller than when we do the enthalpy of vaporization. So 40.7 is a larger number than 6.01. It takes more energy to evaporate the liquid than to melt it. So what I'm showing you for calculations along the flat regions is not MC delta T, but rather number of moles. So N is number of moles multiplied by the delta H for that phase change. So the units are typically kilojoules per mole for the enthalpy of a phase change. Multiplying by the moles will give you kilojoules. Okay, we talked about water. Here is the phase, I'll call it a heating curve, not a phase diagram, a heating curve for methane. Same kind of process. You have a slanted line, a flat line, and so forth. And so we have the enthalpy of fusion for methane is 0.94 kilojoules per mole, and the enthalpy of vaporization for methane is 8.2 kilojoules per mole. In terms of intermolecular attractive forces, again, this was methane. I said it, didn't actually write it. Sorry, methane is CH4. In terms of intermolecular attractive forces, explain why line segment S is much longer than line segment Q. Well, I've already talked about this, so I'll kind of go quickly to the answer. During line segment Q, the substance is changing from a solid to a liquid. Only some, but not all, of the intermolecular forces are broken. During line segment S, the substance is changing from a liquid to a gas. Essentially, all of the intermolecular forces are broken. So it takes more energy to completely separate the molecules from each other in the transition from liquid to gas than it does to separate the crystal into the liquid phase. Another question I can ask you that relates to water and methane is the following. We have the delta H of vaporization, the enthalpy change for the vaporization that's liquid to gas. For methane, it's 8.2, and for water, it's 40.7. In terms of intermolecular attractive forces, explain why the value of the enthalpy of vaporization for water is much greater than the value of the enthalpy of vaporization for methane. You should talk about the specific intermolecular forces in your answer and compare the relative strengths. So from an earlier lesson back in Unit 3 talking about intermolecular forces, you might recall that a molecule like CH4, which is tetrahedral, and all the dipoles cancel out, is nonpolar. It only experiences weak London dispersion forces, whereas water is polar and experiences both London dispersion forces and hydrogen bonding attractions. And so the intermolecular forces in water are stronger than those in methane. So more energy is required to convert water from a liquid to a gas, and that's why 40.7 is higher than 8.2. All right, a few more AP practice problems, and then I'll get to your homework. Here is an AP practice problem that is relevant to today's lesson. Some building materials contain small capsules filled with paraffin wax to improve the insulating properties of the materials. The melting and freezing of paraffin inside the capsules in the material helps to regulate temperature. Paraffin wax begins to melt at 37 degrees Celsius. Part A of this question says, while the wax is melting is the net flow of heat or thermal energy from the wax to the surroundings or from the surroundings to the wax. Justify your answer. Again, feel free to pause the video because I'm going to go relatively fast from the question to the answer. So if you don't have enough time to think, then feel free to pause the video before I reveal the answer. Okay, so the answer here is that melting is an endothermic process. So therefore, thermal energy flows from the surroundings to the wax. Again, the wax is absorbing heat from the surroundings as melting occurs. Part B of this question says, calculate the amount of thermal energy that is required to melt 15.2 grams of solid paraffin wax. So again, that's at the melting point. We have the molar mass of paraffin is given to us, as well as the molar heat of fusion. All you really have to do is 2 conversion factors to get from grams of wax to kilojoules. So you're going to have to first go from grams to moles, and then you're going to have to go from moles to kilojoules. You're already given the molar heat of fusion, that's going to go right here, and you're also given the molar mass, and that's going to go right there. So we're going to go from grams to moles, and then moles to kilojoules. So here's my first step, and there's my second step. If you do this math, 15.2 divided by 282.62 times 48.78, your final answer in kilojoules, 2.62. All right, the next part of this question, when paraffin wax melts, its density increases. Provide a particle level explanation of this observation. So density is mass over volume. So why is the density going down? Hopefully you can realize that when you melt something, you are not changing the mass, but we are changing the volume. So think about in what way would the volume be changing as we go from a solid to a liquid if they're telling us that the density decreases. And the correct answer is the following. In liquid paraffin wax, the average distance between the molecules is greater than in the solid state. So they're taking up more space as a liquid than as a solid. So the same number of molecules now occupies a larger volume in a liquid state, so the density of a liquid would be less than the density of a solid. All right, moving on to our next AP practice problem. Again, relevant to this lesson. A student investigates the enthalpy of solution, so there's delta H of solution for 2 alkali metal halides, lithium chloride and sodium chloride. In addition to the salts, the student has access to a calorimeter, which for most laboratories, that would be a set of styrofoam coffee cups for insulation, a balance with a precision of 0.1 gram plus or minus, and a thermometer with a precision of plus or minus 0.1 degrees Celsius. We're going to focus on the lithium chloride. It says in part A, to measure the delta H of solution for lithium chloride, the student adds 100.0 grams of water, and there's the initial temperature of 15.0 degrees Celsius. Then they add 10.0 grams of solid lithium chloride, and they stir to dissolve. Now, did the dissolving process represent an endothermic process, in your opinion, or an exothermic process? In other words, was heat released to the surroundings, as in exothermic, or was heat absorbed from the surroundings, endothermic? Remember that the thermometer is typically considered to be part of the surroundings. That's important that you understand that because they're going to ask you for the delta H in Roman numeral 2, and if you get the wrong sign, you might not get credit for this. Okay, so consider what we have. Calculate the magnitude of heat absorbed. Let's use MC delta T. Now it does say by the solution, and they say the specific heat capacity is of the solution. So the most common mistake that students make is this. They put M as in mass of water. Well, that's not the solution. That's just the water. We still have a solution that contains both solute and solvent. So you have to consider the mass of the solution, not just the water. So the correct answer is going to have 110 grams. That's the mass of the solution, the specific heat capacity which they gave us, and then the delta T, 35.6 minus 15.0. That's a difference of 20.6. Our answer will come out in joules. So 110 times 4.18 times 20.6 is 9,470 joules when I rounded this off to 3 sig figs based on the least number of sig figs in my measurement. And you could write that as either 9,470 joules or 9.47 kilojoules because it didn't give you a specific unit. It just said calculate the magnitude of heat. No sign is important right now, but now the sign is important. So we're going to have to figure out the number of moles because it's kilojoules per mole. And since 10 grams of lithium chloride, let's go ahead and add up. Lithium chloride would be 6.94 plus 35.45. 42.39 is the molar mass of lithium chloride. This gets us part of our answer. So 9.47 kilojoules. 9.47 kilojoules divided by 0.236 moles. Okay, if I do this math, I'm going to get an answer. Is it going to be the correct answer? Well, that depends. Is it a positive or a negative? Is it an endothermic process or an exothermic process? Remember, when a solid is dissolved in water to form a solution, the thermometer is considered to be part of the surroundings, and the surroundings got warmer. It's an exothermic process, so delta H should be negative. The correct answer is not 40.1, but rather negative 40.1. You could say kilojoules per mole or kilojoules per mole of reaction. All right, next part of this question that I want to talk about is actually part F. I'm skipping B, C, D, and E. So in part F of this question, they had asked the lattice enthalpy of lithium chloride is positive, indicating that it takes energy to break the ions apart in lithium chloride. However, the dissolution of lithium chloride in water is an exothermic process. Identify all particle-particle interactions that contribute significantly to the dissolution process being exothermic. So remember that forming a bond is an exothermic process. Breaking bonds is endothermic. We're focusing on the exothermic process, so therefore it's going to be the bonds that are formed, the attractions that are formed between the solute and the solvent, and those are known as ion-dipole interactions. You cannot talk about the strength of the ionic bonds or the hydrogen bonds between the water molecules because those are being broken, some of them, in the formation of the solution. So it's going to be the formation of the attractive forces in this case that would release energy, and those are ion-dipole forces. All right, another quick AP practice, then we'll get to our homework. Aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. Calculate the amount of heat needed to purify 1 mole of aluminum at 298 Kelvin by melting it. The melting point of aluminum is 933 Kelvin. So first we have to actually warm up the aluminum from 298 to 933. That would normally be MC delta T, but they've given us a molar heat capacity. So it's not joules per gram Kelvin, it's joules per mole Kelvin. The change in temperature is going from 298 to 933. That's a difference of 635 Kelvin. So it takes about 15,240 joules to warm 1 mole of aluminum from 298 to 933. It's about 15 kilojoules. And then it takes an additional 10.7 kilojoules of heat to melt it. So a total of 15 plus 10.7, and rounding off to no decimal places when you add two numbers, that would be 26 kilojoules to essentially purify and recycle this aluminum. Here they give us a chemical equation for extracting it from aluminum oxide, the ore. Now, it requires 1,675 kilojoules for every 2 moles of aluminum. So 1,675 kilojoules for every 1 mole of reaction, which is for every 2 moles of aluminum. That's 837.5 kilojoules. Since 26 kilojoules, which is the recycling, is much less than 837.5, recycling requires less energy than extracting. All right, well, thank you for hanging in there with me. We talked about endothermic and exothermic processes today, energy diagrams, heat transfer, enthalpy, specific heat capacity, and calorimetry, energy of phase changes. So these 3 slides will be your homework. This is slide number 1, this is slide number 2, and this is slide number 3. I will be going over the answers to this question in my next lesson, which will be on Monday. Don't forget to check out the helpful chemistry resources in the link in the video description. Thanks for watching. This has been Michael Faribault from Albemarle High School in Charlottesville, Virginia. And I want to remind you that if you haven't already contacted the College Board, if you need mobile tools or connectivity, please let them know by Friday, April 24th. That's 1 week from today. That is the deadline. All right, have a good rest of the day and a good weekend. I'll see you back here on Monday. Thanks for watching. Hello, everyone, and welcome to another virtual lesson. This is Michael Faribault from Albemarle High School in Charlottesville, Virginia. And we're going to be continuing our discussion from Friday's lesson, which was on thermodynamics. So we'll wrap up thermodynamics, and then this week we will talk about Unit 7, which is on equilibrium. Reminder to students to check out apstudents.org/exams2020 for more specific details about taking the AP exams online. A reminder that for AP Chemistry, the first testing date is on May 14th, and you can see there are a variety of different times in which, depending on where you live, you'll be taking the AP exam. There are 2 free response questions on the AP exam, and again, the information that I had presented on Friday is playback, again, talking about the types of things to consider for your free response questions, explaining chemical phenomena using models, theories, and representations at the particulate and macroscopic level, again, in terms of drawing conclusions from experimental results, analyzing sources of error. Hopefully you guys have access to scratch paper, something to write with, periodic table. In today's lesson, which will wrap up thermodynamics, we will talk about enthalpy of reaction, bond enthalpies, enthalpy of formation, and Hess's law. And again, you can see the topics as well as the skills or the science practices, so including things like explain the connection between particulate level and macroscopic properties using models and representations, calculate, estimate, or predict an unknown quantity from known quantities, identify quantities needed to solve a problem. So again, we'll talk about enthalpy change, bond enthalpy, enthalpy of formation, and Hess's law. For our warm-up problem, this would be the AP practice problem that I had assigned for homework on Friday. And so this particular laboratory situation involves calorimetry. A student was assigned the task of determining the enthalpy change for the reaction between solid MgO, magnesium oxide, and aqueous HCl, hydrochloric acid. Notice that the hydrochloric acid is HCl, but the net ionic equation is shown above, so chloride ions have been eliminated as spectator ions. The student uses a polystyrene cup calorimeter and performs 4 trials. Data for each trial are shown in the table below. So part A, which is the limiting reactant in all 4 trials. Now, for limiting reactants, we have to convert the given information into moles. So since for the hydrochloric acid, we are not given grams, we are given volume. 100.0 milliliters is used in each trial. We can convert milliliters to liters by dividing by 1,000, and then 1.0, that's capital M for molarity, that would be 1.0 mole of HCl for every 1 liter. So in each trial, 0.10 moles of HCl or H plus ions were used. Now, with respect to the magnesium oxide, the MgO, some trials use 0.25 grams and some trials use 0.5. Let's go ahead and pick a higher value to see what's the maximum number of moles of MgO that was used. So for 0.5 grams, convert that from grams to moles. The periodic table tells us that magnesium weighs 24.3 and oxygen weighs 16. So the sum of those 2 atomic masses give us the molar mass. So 0.5 divided by the molar mass, 0.012 moles of MgO. Now we have to consult the coefficients in the balanced chemical equation at the top here. So you can see that there is a 1:2 ratio between MgO and H plus or HCl. So if I have 0.012 moles of MgO, then I would need at least twice as much. That would be 0.024. Well, hopefully you can see that since HCl is much larger than that, it is the HCl or the H plus ions that are in excess. So the amount of moles of HCl is more than twice the amount of moles of MgO. That makes MgO our limiting reactant. So the answer to part A, magnesium oxide is the limiting reactant, and these calculations and explanation justify our answer. In part B, here we have a problem. There is an error. This is again a classic style of AP question where there's laboratory situation. The error is that one of these 4 trials is inconsistent with the data in the other 3 trials. We don't have to explain why the mistake was made, but definitely some trial involves data that there must have been an error either in how to read the thermometer or just maybe just a quick calculation or something was done that was just written down wrong. So which of these 4 trials is inconsistent? And we do have to explain how we identify the inconsistent data. Now in part A, we discovered that MgO is a limiting reactant. So therefore the amount of heat produced in this experiment, because the temperature is increasing in all 4 trials, the amount of heat produced should be directly proportional to the amount of the limiting reactant MgO. Since the total volume of the solution is essentially the same, it's 100 milliliters and there's a small amount of solid dissolved in that. Essentially the delta T is going to be proportional to the Q and therefore the amount of magnesium oxide used. Let's calculate the delta T for all 4 trials. So for trial 1, 26.5 minus 25.5, that's a difference of 1. 29.1 minus 25.0, that's a difference of 4.1. And then the other delta T's are 2.1 and 4.0. So essentially what we're looking for is the trial that is inconsistent. Let's focus on for a moment trial 3 and 4. So in trial 3 and switching to trial 4, they doubled the amount of MgO and the delta T is essentially doubled. So that seems like trial 3 and 4 are consistent. Now going from trial 1 to 2, they also doubled the amount of MgO and yet the delta T has changed 4-fold from 1 to 4. Okay, so something is probably wrong with either trial 1 or trial 2. Now something else we can do is we can calculate the ratio of delta T to the amount of magnesium oxide in grams. So the ratio of delta T to grams of magnesium oxide would be 1 divided by 0.25, that's 4. 4 essentially divided by 0.5 is 8. And we realize as we go down this list here that it's trial 1 that is going to be inconsistent because this ratio of delta T to the grams of magnesium oxide should be the same in all 4 trials. So we have now eliminated trial 1 on the basis of that ratio being different than the other 3. Our next task in this question in part C is to calculate the magnitude of Q. So we're going to use trial 2, although we could also use trial 3 or 4. I just picked trial 2 because it was the next one on the table. And we're going to do Q equals MC delta T. Now the C is the specific heat in this case of the contents of the calorimeter that is given to us as 4.18 joules per gram degree Celsius. Now these numbers right here, this is in volume in milliliters. It's not in grams, but luckily we're assuming that the density of HCl is 1 gram per milliliter. So we have effectively 100 grams of solution. And then we have to also add either 0.5 or 0.25 to that total. So if I'm doing trial 2 and I add the 0.5 grams of MgO, that brings my total mass of the contents of the calorimeter to 100.5. And our delta T as calculated by the difference in temperature is 4.1. So we'll do this math and we get 100.5 times 4.18 times 4.1. I get 1722. I'll round that off to 2 significant figures because of the delta T. So approximately 1700 joules or 1.7 kilojoules. Notice that this is Q and not delta H. So I'm not worried about the sign being positive or negative, just the magnitude of heat. And again, this is heat released because the surroundings are getting warmer. When the temperature goes up, that's an exothermic process. Had you done the calculations for either trial 2, trial 3, or trial 4, you would have done the same basic setup. So mass, total mass, times specific heat capacity, times the delta T. And then your answer would have been either around 1700 joules or around 880. Now this is a different number for trial 3, but again, you could have picked any one of those trials. All right, so moving on from Q to delta H. So now remember, delta H is essentially going to be in units of kilojoules per mole of reaction. And we should be focusing on the moles of the limiting reactant, which in this case is the magnesium oxide. So the limiting reactant, magnesium oxide. All right, so we have in trial 2, 0.5 grams of magnesium oxide. We can convert that to moles. And I'm going to go ahead and use a few extra digits here. I'm not going to round this off yet. So 0.01241. Now the 1.7 kilojoules, that's how much heat was released. Now the thermometer, as I said, is part of the surroundings. Since the temperature increases, we have an exothermic reaction. So the correct answer should have a negative sign for delta H. So I have negative 1.7 kilojoules divided by the moles of the limiting reactant, and I get negative 140. Again, I'm going to round that off to 2 significant figures. So had you used the data from trial 3, you would have had a smaller amount of heat, but also a smaller amount of moles. In fact, you would have had half as much in terms of Q and half as much in terms of moles. You would have gotten the same answer. So as you can see in trials 2 and 4, you would have gotten around negative 140 kilojoules per mole of reaction. But even in trial 3, because you have half as much heat and half as much moles, you still get a delta H. And again, that negative sign is important to get the correct answer. You had to know that this was an exothermic process. This negative 140 is our experimental value. Now, in our next part, we're going to calculate the theoretical or the accepted value from the data. And this comes from the delta H of formation. I'll be talking about an equation today in which the delta H is determined from the sum of the delta H of formation for the products minus the sum of the delta H of formation values for the reactants. So I can squeeze that in there. Okay, so that equation, by the way, is on the equation sheet that you can use for the AP exam. So products minus reactants, and again, this delta H of formation is given to us in the table. So these are the products, Mg plus and H2O liquid. So we have those calculations. So again, these are our products. And then these are our reactants. We have MgO solid and hydrogen ions. Again, these are our reactants. So as you are putting this data into your calculator, just getting it from the table, we can then calculate our accepted value. So the experimental value was negative 140 kilojoules per mole of reaction. If we do this math, the accepted value is negative 151. So there is a difference between negative 140 and negative 151. All right, in the next part, the accepted value and the experimental value do not agree. If the calorimeter, so again, our calorimeter would look like this. We have some kind of a polystyrene coffee cup. We have a thermometer in here that's recording the change in temperature. Inside the cup is the solution. If for some reason heat somehow leaks out of the calorimeter and into the environment, okay, so if somehow heat was lost to the environment, would this help to account for the discrepancy between the values? Well, considering that the magnitude of heat that we measure would actually be less, then yes, this would account for the discrepancy. So if the calorimeter leaked heat energy to the environment, then yes, this would help to account for the discrepancy between the accepted value, which is negative 151, and the experimental value, which is negative 140. So because the delta H has a smaller magnitude when we did the calculations from the experiment, if heat had leaked out, the value for delta T would be too small. This would lead to a value of Q that is too small. And again, the magnitude of delta H would be smaller than expected. All right, well, that was our warm-up problem. And now on to today's lesson, wrapping up thermodynamics. So the enthalpy change for a reaction, the delta H, is typically either positive or negative. So positive for an endothermic process and negative for an exothermic process. These are energy diagrams. You could just be given a balanced chemical equation with a delta H, so we should know what that means in terms of the sign of delta H. So here is a reaction, a balanced equation for the combustion of methane gas. So CH4 plus 2O2, and the products are CO2 and 2H2O. Our delta H is negative 802 kilojoules per mole of reaction. When this reaction occurs, is energy absorbed or released by the system? So we know that the negative delta H means it's exothermic, and energy is released. The reaction is exothermic because the sign of delta H is negative. Notice that we should pay attention to the phase of matter. So we have CH4 as a gas, O2 as a gas, CO2 as a gas, and in the first reaction I gave you, we have water vapor. So would we get a different value of delta H if we had used liquid water in this experiment as a product instead of water vapor? If this reaction had been written with 2 moles of liquid water on the right instead of 2 moles of water vapor, would the magnitude of delta H be less than or greater than 802 kilojoules? Again, the magnitude. So I'll give you a moment to think about that. And if you need to pause the video, feel free to do that. All right, well, hopefully you've had a chance to think about it. There is a difference between liquid water and water vapor in terms of energy. Remember that evaporation is an endothermic process in which energy is absorbed to go from a liquid to a gas, and the reverse process, condensation, is exothermic as you go from a gas to a liquid. So evaporation is endothermic, condensation is exothermic. So what does that tell us about the relative energy values between liquid water and gaseous water? Well, gaseous water should be at a higher energy level than liquid water. And it doesn't matter whether the arrow is going up or down in these diagrams, it still shows that water vapor is at a higher energy level. So we come back to the original question. Here is a difference of 802 kilojoules going from the reactants, CH4 and O2, to the products. So if we decide to change from a gas to a liquid, then what that is going to do, it's going to put the products at a lower energy level relative to where they were before. So the answer is that it would have a greater, the delta H would have a greater magnitude than 802. Now I can tell you this, that essentially the difference between 2 moles of water vapor and 2 moles of liquid water is approximately about 88 kilojoules. So in fact, the delta H would be around negative 890 kilojoules. What I'm just showing you here, and the fact that I can add these two steps together, negative 802 and negative 88, and get negative 890, that is actually an example of a concept that I'll be talking about at the end of today's lesson, which is called Hess's law, where you can take 2 different steps, add those 2 steps or those 2 reactions together, and you can add the delta H values together. Something else I'd like to mention with respect to a thermochemical equation where you have coefficients and you have a delta H is that we can do essentially stoichiometry. And now we can use, in our stoichiometry calculations, we can use the delta H as a magnitude of heat. There are 802 kilojoules of energy released for every, for example, 1 mole of CH4. Or you could say that there are 802 kilojoules of heat released for every 2 moles of oxygen consumed. So we're just using mole ratios to convert from one chemical to another, but we can also use the ratio of the heat. So when it says mole of reaction, that means it's not specific to moles of one particular chemical, but all of the coefficients in the balanced chemical equation with their coefficients relating to number of moles. You can then relate it back to this negative 802, the change in enthalpy. All right, so in this problem, in terms of stoichiometry, suppose that we have 7.50 grams of methane, CH4, and it reacts completely with excess oxygen according to the equation shown above. How many kilojoules of heat or thermal energy would be released? Again, feel free to pause the video, work this problem out on your scratch paper, and then press play and check to see if your answer is correct. The first thing that I'm going to do is convert grams to moles. So the periodic table tells me that carbon weighs approximately 12.01, and hydrogen weighs 1.008, so I have 4 hydrogens and 1 carbon. So my molar mass, CH4, is 16.042. But now I have to convert into kilojoules of thermal energy. So I'll put 802. I'm not worried about the negative sign right now because it's the amount of heat that is released. 802 kilojoules on the top, 1 mole of CH4 from the coefficient of the balanced equation on the bottom, and then I would do this math. So 7.5 divided by 16.042 times 802. And I get my answer. All right, we'll try one more like that. This time I will give you grams of a different chemical. Suppose that 45.0 grams of oxygen reacts completely with excess CH4 according to the equation shown above. Again, how much heat is released? How many kilojoules of thermal energy? There are 32 grams of O2 in 1 mole. Now the most common mistake that students would make is, especially after they saw this last example that I showed you on the previous screen, all right, and they would do that and get their answer, but it would be incorrect. So if you're going to talk about kilojoules per mole of reaction, you have to focus on the coefficients in the balanced chemical equation. So be careful that you don't make that mistake, which is to neglect the coefficients from the balanced chemical equation. All right, so we have to then get 2 moles of O2 for every 802 kilojoules like that. Now I could show this a little bit differently and get the same answer. So watch me do it like this. There are 2 moles of O2 for every 1 mole of reaction, and there are 802 kilojoules for every 1 mole of reaction. That way you might, if the bottom method is easier for you, you can try it that way. It's the same example in terms of numbers, but just kind of remind you why we do that. All right, well, we're given the delta H for the combustion of methane. Now we have the combustion of a different chemical. This is propane, C3H8, but now we don't have the delta H. So this is going to be a review of some concepts that I had explained on Friday's lesson talking about calorimetry. Suppose that 1 gram, 1.00 gram of propane is combusted or reacts completely with oxygen according to the equation shown above. The heat that is released from this combustion reaction is completely transferred to a container with 250.0 grams of water inside. The temperature of the water increases from 20.0 degrees Celsius to 68.2 degrees Celsius, and they give us the specific heat capacity of water. So if you remember, MC delta T, Q equals MC delta T. Let's calculate the amount of heat released in this experiment and the delta H. Okay, so we'll start with the Q. So Q equals MC delta T. We know that the mass of water was 250.0 grams. We know the specific heat capacity was given to us as 4.18, and the delta T would be 68.2 minus 20. That's a difference of 48.2 degrees Celsius. I will do this on my calculator, and when I did this, I got 50,369. I rounded this off to 3 significant figures based on the delta T. So 50,400 joules or 50.4 kilojoules. I'm not worried about the sign being positive or negative. This is just simply the amount of heat released. Now, 1 gram of propane was not used in this calculation, but that is how much propane was burned. Let's convert that into moles. So for the delta H, let's convert grams of propane into moles, and I did the conversion using C3H8, so 3 times the molar mass of carbon and 8 times the molar mass of hydrogen gives me 44.094. I'm not done yet, but that is my first step, is to convert grams to moles. We go back to the amount of heat that was released. I'm going to go ahead and put a minus sign because this is an exothermic reaction. How can we tell? Because the temperature increased. Thermometer is part of the surroundings. Combustion reactions are typically exothermic, and we end up with negative 50.4 divided by the number of moles, which, by the way, even though there is a 1 that is understood to be a coefficient here, there are other coefficients as well. So this delta H that we're talking about is not necessarily per mole, but rather per mole of reaction. Okay, I did this math and I got negative 2,220, rounding off to 3 significant figures, and that's kilojoules of energy release per mole of reaction. Okay, so our next topic in today's lesson is on bond energy or bond enthalpy. So what you're looking at right now are a variety of chemical bonds. We have single bonds, double bonds, triple bonds, and then there is bond enthalpy listed next to each bond. So what exactly is bond enthalpy? It is the energy required to break that particular bond. It can also represent the amount of energy released when that bond is formed. So it is endothermic to break a bond. It is exothermic to form a bond. So the magnitude of energy either absorbed or released depends on whether you are breaking or forming the bond. Here we have the combustion of methane. Again, we saw this earlier in the lesson, and the delta H is given to us. Let's see if we can get the delta H from bond enthalpy values. So I have to actually draw out the Lewis structure of these molecules to decide what exactly do the bonds look like on both the reactant side of the equation and the product side of the equation. Well, CH4 is a rather simple molecule with 4 single CH bonds. The oxygen molecule happens to be, if you draw the Lewis structure, an oxygen-oxygen double bond, and with a coefficient of 2, that means we have 2 oxygen molecules for every 1 molecule of methane. On the product side of the equation, we have 1 molecule of carbon dioxide, which contains 2 carbon-oxygen double bonds if you draw that Lewis electron dot structure. Each water molecule is just H2O, but we have 2 of them, so for a grand total of 4 oxygen-hydrogen single bonds. So I have bonds that are being broken, and again, that is an endothermic process, so a positive value. I have bonds that are being formed, and that would be an exothermic process or a negative value. So what I can do now is I can consult a table of bond enthalpy values, and I can find the particular bonds that I'm dealing with in this particular problem. So we have a CH single bond, 413. This is the bond enthalpy in kilojoules per mole. We have oxygen-oxygen double bond, 498. We have a carbon-oxygen double bond, 799, and we have an oxygen-hydrogen single bond, 463. So how many CH bonds do I have? Well, I have 4 of them. So I'm going to do the math, and you can kind of follow along here. 413 times 4 is 1652. It can always be in units of kilojoules. I have 2 oxygen-oxygen double bonds. That's 498 times 2 is 996. So my grand total, 2,648 kilojoules of energy absorbed when those bonds are broken. All right, on the product side, I have 2 carbon-oxygen double bonds. So 799 times 2 is 1598. I have a total of 4 oxygen-hydrogen bonds. So 463 times 4 is 1852. That's a grand total of 3,450 kilojoules. Now remember that since the energy is released when bonds are formed, I'm going to put a negative sign on that value. So we have to add the negative sign to the bonds formed total because forming bonds is an exothermic process. So 2,648 minus 3,450. That's the math that I'm doing. So effectively the delta H is going to equal the total sum of the bond enthalpies for the bonds that are broken minus the sum of the bond enthalpies for the bonds that are formed. Now if you do this math, 2648 minus 3450, you should get, hey, look at that, negative 802. That was the number we already had earlier. So negative 802. This is a good estimate of the delta H for the combustion of methane. All right, let me jump to some AP practice problems on this particular topic. So you're looking at part of a question. This is part B of an AP response question, and you can tell that we're going to be using bond enthalpy values because there's a table given. It says in part B of this question, using the Lewis electron dot diagrams of fulminic acid and isocyanic acid as shown in the boxes above, and the table of average bond enthalpies below, determine the value of delta H for the reaction of fulminic acid HCNO to form isocyanic acid HNCO. So I'm going to go ahead and highlight. Here's our equation: bond enthalpies for bonds broken minus bond enthalpies for bonds formed. I'm going to highlight the HC bond in yellow. I'm going to go find that in the table. That's 413. I'm going to write that down. I'm just going to keep track of all of my bonds, kind of going one bond at a time. The next one I'm going to highlight is the CN triple bond. I find that in the table. That's 891. So I'm going to write that down. And then in the fulminic acid, we have a nitrogen-oxygen single bond, and there it is in the table. That's 201. So that would be my grand total of energy absorbed because those bonds are broken. Okay, moving on to the other molecule, the isocyanic acid. I have an NH single bond, which comes in at 391. I have a nitrogen-carbon double bond, and that is listed as 615 in the table. And then I have a carbon-oxygen double bond, which, according to the table, comes in at 745. So we have a total of 1,505 for the energy absorbed, and we have a total of 1,751 for the energy released. So 1505 minus 1751 gives me my answer. In this case, the delta H is negative 246 kilojoules per mole of reaction. All right, let me jump to another AP practice problem from a different AP exam. And in this one, they actually tell us the delta H. It's 1.6 for this reaction here. What we don't know is the bond energy or bond enthalpy for the bromine-chlorine bond. So we're going to still use the same equation, but just plug in everything we know and solve for what we don't know. So it would be on the left side of the equation, there are 2 BrCl molecules. So we're going to be breaking 2 BrCl bonds. And on the right side of the equation, we have a Br2 and a Cl2. So we're going to be forming a Br-Br bond and a Cl-Cl bond. All right, they gave us the delta H was 1.6, and that is equal to 2 times whatever the bond enthalpy of a BrCl bond is. We don't know that yet. That's the question mark in the table. Minus 193 plus 243. So we'll go ahead and just combine the numbers. So 2 times the BrCl bond, which we don't know yet, is equal to 1.6 plus 193 plus 243. Now, be careful that you don't get to this point and say, okay, I've got my answer. My answer is 437.6. So again, sometimes when students are going too fast, they forget little details. So in this case, that is not the answer because we still have the math to do. We have to divide by 2. So the correct answer is actually half of that value. Okay, so the correct answer is approximately 219 kilojoules per mole for the bond enthalpy of the BrCl bond. All right, so again, those were AP practice problems. The next concept I'd like to talk about is enthalpy of formation. So now you don't see bonds, you actually see entire formulas of chemicals. We have carbon monoxide, carbon dioxide, water vapor, liquid water, hydrogen, oxygen, CH4. These are actually substances. So what is the enthalpy of formation? Well, the standard enthalpy of formation, which has the symbol delta H with a superscript 0 for standard conditions and a subscript F for the word formation, this value represents the change in enthalpy associated with the formation or synthesis of 1 mole of that particular compound from its elements. Now, if you're forming a compound from its elements, for example, carbon monoxide would be formed from carbon and oxygen. CH4 would be formed from carbon and hydrogen. NH3 at the bottom of the table there would be formed from nitrogen and hydrogen. It might stand to reason that what if you already are an element? So I've got 2 elements in the table, hydrogen and oxygen. It's impossible to form an element from an element. You already are an element in your standard state. So by definition, the standard enthalpy of formation for a pure element in its standard state is equal to 0. All the other values in this table are non-zero because they are referring to compounds as opposed to elements in their standard state. All right, let's give you some specific examples of what does it mean when I talk about the formation of. So this is carbon monoxide. It would be formed from 1 mole of carbon and half a mole of O2. So the delta H is the energy that is associated to change with the formation of 1 mole of that substance. If it were carbon dioxide, 1 mole of carbon plus 1 mole of O2, again, the energy associated with that particular synthesis reaction. For water, 1 mole of hydrogen plus half a mole of O2 leads to 1 mole of water vapor. If it was methane, 1 mole of carbon plus 2 moles of H2, again, CH4 is being produced, and that's the delta H associated with that. So as I mentioned before in the warm-up problem, you have an equation, again, that would be delta H of formation for the products minus the delta H of formation for the reactants. So if I was given a equation, in this case, the combustion of methane, and I had to calculate the delta H not from the bond enthalpies like we did earlier, but from the delta H of formation, the standard enthalpy of formation, then what I'm doing here is I'm calculating, again, these are delta H of formation values. I'm doing products minus reactants. So CO2 is right there. There are 2 moles of water vapor, so I got that. And then minus the reactants, I have the CH4, which is right here. And then since oxygen happens to be by definition an element, which is 0, then I really just have 2 times 0 here. So I have the products minus reactants. Again, this is not about bonds broken minus bonds formed. This is about the delta H of formation for the products minus the delta H of formation for the reactants. So again, it's one of the differences between those two equations. equations is that we are talking about bonds versus the entire substance as a whole. All right, if I go ahead and finish off this math, no big surprise, we get that negative 802 that we have seen earlier. So again, this is the combustion of methane. Now earlier in this lesson, I had given you the combustion of methane, and I had said if this reaction had been written with 2 moles of liquid water instead of 2 moles of water vapor, and we had talked about how the delta H would be greater in magnitude. In fact, it was roughly about 890 when I was trying to show you earlier on the slide. I was talking about how the difference between liquid water and gaseous water is about 44 kilojoules. So if I have 2 moles of liquid water and 2 moles of gaseous water, that difference between these two is around 88. Let's go ahead and do the calculations. Notice that we have to pay attention to the phase of matter. So we are not using negative 241.8, we're using negative 285.8. And again, that came from the table of standard enthalpy of formation. And sure enough, I get a magnitude that is different than 802. I get around negative 890. So if you are given a table of bond enthalpies, okay, do not confuse the bond enthalpy with heat of formation. Those are two different equations, okay? So we're going to be careful that we're not confusing these two concepts. So it's an example of heat of formation, which is different than bonds broken minus bonds formed. Heat of formation is products minus reactants. Okay, so we can tell that this is referring to standard enthalpy of formation. These are not bond energies, but the enthalpy of formation for the formation of the entire substance. And they gave us an equation at the top, and they already gave us a delta H. They give us another equation, and it says, will the combustion of 2 moles of C3H6 release more or less heat than the combustion of 2 moles of this vinyl chloride, the C2H3Cl? So we're going to do products minus reactants for this particular equation. So 6 times CO2 is right here, 6 times water vapor is right here. I'm just taking this from the table. Then we have minus the reactants, 2 times 21, that comes from this, and again 9 times 0 because that was just oxygen. So we have now gathered all of our data. We have now plugged in the information for this particular equation in the red box, and we get a delta H that is larger in magnitude than the other ones. The question had said, determine whether the combustion of 2 moles of propene, which is C3H6, releases more or less energy than the combustion of 2 moles of vinyl chloride. So again, because 3858 is a larger magnitude than 2300, the combustion of 2 moles of propene releases more energy. Okay, so again, do not confuse delta H of formation and bond enthalpy. Okay, so here you can definitely do the products minus reactants if you are given delta H of formation, but over here it's going to be different. It's going to be bond energy. So you have the bonds broken, which is a positive number, minus the bonds formed. So a common mistake that students make on the AP exam is they confuse these two equations. So make sure you are clear in your mind about what you're doing with the data. All right, Hess's law has to do with adding 2 or more reactions together. And if you add reactions together, you can also add the delta H values together. So the delta H is simply the sum of the individual delta H values for the reactions that you are adding together. There are some simple rules associated with changing these thermochemical equations, and these are kind of obvious rules. If you decide to reverse the direction of a reaction, you have to change the sign of delta H because now it changes from being endothermic to exothermic or vice versa. If for some reason you have to go into ED coefficients and multiply each and every coefficient by a particular constant n, then you would have to also multiply the value of delta H by that same value n. And as I mentioned, when you add two equations together, you would add the total of the delta H values. Here you can see a Hess's law problem. This is not from a particular AP chemistry exam, but it's simply a good example of the different manipulations you have to do. So we're going to call this equation number 4. This is our target equation. This is an equation for which we don't know the delta H, but can we combine equations 1, 2, and 3 in such a way that when we add them together, they will equal equation 4. So I'm going to go ahead and analyze the chemicals that are in equation 4. We have 2 moles of carbon. I definitely see carbon up there in equation 2. We have 1 mole of hydrogen. I definitely see hydrogen up there in equation 3. And we have 1 mole of C2H2, which is called acetylene. I see that chemical featured in equation number 1. So what I'm going to have to do with equation number 1 is that I've got the C2H2. It's on the wrong side. It needs to be on the right side of the equation as opposed to on the left side. I'm going to have to reverse equation number 1, which means when I flip the equation around, the magnitude will remain the same. It'll still be 1256, but when I switch the location of reactants and products, I change the sign. So as I flip equation 1, now the delta H is positive 1256. Okay, there is carbon featured in equation 2, but unfortunately it's not the right coefficient. So I need there to be 2 moles of carbon in my target equation, equation 4. I'm going to have to take equation number 2 and multiply each and every coefficient by 2, which means that now the delta H will still be negative, but instead of negative 394, it's going to be negative, well, twice that, so negative 788. So I multiply each coefficient by 2 as well as the delta H. And now in my third equation, I see the hydrogen, but unfortunately it's not the right coefficient either. So I'm going to have to take that third equation and multiply each and every coefficient by 1/2 or 0.5. So when I do that, the negative 484 will also be multiplied by 1/2. So now I'm going to have negative 242 when I multiply equation 3 by 0.5. So to verify that everything looks good, let's cross off all of the things that are not going to be showing up in the final equation because they are featured on both sides. Kind of like when you eliminate spectator ions in a net ionic equation. I see 2 moles of CO2 and there's 2 moles of CO2 on the other side of the equation. So that gets eliminated. I see 1 mole of water and 1 mole of water on the opposite sides. I see 2.5 or 5/2, 2.5 moles of oxygen. There's 2 and there's another half. So 2.5 moles of oxygen on opposite sides. But everything else, the 2 moles of carbon, the 1 mole of hydrogen, and the 1 mole of C2H2 acetylene, those are the only chemicals that are left. So if I add 1256 plus negative 788 plus negative 242, I will get, in this case, the delta H for equation 4, which works out to be positive 226, and that's kilojoules per mole of reaction. So that's an example of Hess's law. You can manipulate equations by flipping them or multiplying by a certain value and then adding them together to equal a new equation. You just add the delta H's together. So in today's lesson, which again covered thermodynamics or thermochemistry, we talked about enthalpy change for a reaction, talked about bond enthalpy, again that's bonds broken minus bonds formed, talked about enthalpy of formation, so products minus reactants, and talked about Hess's law. So now, before I finish, here is your homework problem for tomorrow. So tomorrow, Mr. Byrne will go over the answers to these questions from an old AP exam. So this is the first slide. You want to take a screenshot of that or pause the video. So we're going to do several parts of this question. This is the first one, and then here is the next one, and here is the next one. So we're doing parts C, D, E, and F. All right, so again, tomorrow's lesson, we will talk about the answers to this particular question and introduce equilibrium, which is unit 7. So reminder to check out the helpful chemistry resources in the video description. This has been Michael Faribault from Albemarle High School in Charlottesville, Virginia. Thanks for watching, and remember, if you have not contacted the College Board about your needs for either mobile tools or connectivity, the deadline for contacting the College Board, you can go to cb.org/check. The deadline is April 24th. All right, have a good day. Thanks for watching.
Good morning, chemistry fans. Welcome back to AP Chemistry live streaming lessons. This is Sean Byrne here. I'm excited to have you back. Just because the last time we were together, I was sharing my weather reports. Everything is beautiful and sunny here in outside Chicago, Illinois. I teach at Lombard West High School, remember, outside of Chicago in Glen Ellen. Today is Tuesday, April 21st, 2020. We are going to start our conversation of Unit 7 on equilibrium. As I was preparing today, it really seemed like so much of this is review. So to say that we're starting our conversation of this seems a bit strange because we've looked at a lot of the principles that are at play here in equilibrium throughout the course of these lessons. We're coming kind of to the end of our review material, and next week we'll be looking at some FRQs for you. So a lot of the things today are going to seem very, are going to seem like review for you. And if that's the case, that's great. I really want to make sure you have a good foundation of the theory behind equilibrium. Maybe not as much with the math. We will do some of that. And then as you're looking back through earlier lessons on acids and bases and several of the topics, you'll see where a lot of the math that we've been looking at comes through. Our daily reminder of where to go if you have any questions on apstudents.org/exams on any of the information over here on the right-hand side of the screen. We've got our calendars highlighted and a big target on Thursday, May 14th at whatever your local time is for the AP chemistry date. Remember that we'll have a 45-minute exam, 25 minutes for the first question and 15 minutes for the second question. The first one will be 60% of the weight and second question will be 40% of the weight. And this is really going to be a skills-based exam. So as we look through a lot of our materials today, what we really want to be trying to do is explain chemical phenomena, draw conclusions, analyze systems, and support our claims with evidence, and make sure that it's not just about getting an answer per se, it's about being able to explain how and why we got that answer. So lesson overview is the same as always. We'll start with a warm-up for today, run you through a couple of what you need to know and give you some opportunities to practice those skills. Feel free to stop at any point and review or solve a problem that's right in front of you. And you should have a stretch piece of paper and a pen or a pencil and probably a calculator at your side if you can, because that's going to help you to be able to review all of the work that we are doing today. Okay? We have lots of topics that we're going to go through today. I've kind of chunked these into groups of two, so don't get too overwhelming all around this topic of equilibrium, so that we're feeling really comfortable with this going into some of the more complex parts of it tomorrow with Mr. Faribault. All right, so our warm-up is a review of the homework problems that Mr. Faribault gave us yesterday. And so the first question asked us to look at this experimental data where we have an oxidation reduction reaction that is listed up here at the top. Na2S2O3 is reacting with NaOCl and some sodium hydroxide. We have our concentrations and volumes right here. And so the question asked us at the beginning, nice review question, kind of get us warmed up, our feet ground, make us build up our confidence when we're solving problems like this, right? Is to determine which reactant is a limiting reactant and to justify our answer. And so what we're going to want to do is compare what we have here in the solution to the ratios that are necessary given to us in the balanced chemical equation. Give us a little bit of a hint there. That's where we should look. We're going to look at the ratios of the coefficients to one another. So I'm going to just start out by noticing that all of the concentrations and the volumes are the same. So we really only need to do one concentration or one calculation here. The scoring guidelines don't ask us to necessarily spell out this calculation, but for me, I just feel better having the numbers in front of me. And to practice this idea that moles is equal to molarity times volume, which of course comes from the definition of molarity at mole divided by volume. You notice that I converted volume into liters here. So 5 milliliters is the same as 0.005 liters, and our concentration stays the same. So in effect, we have 0.0025 moles of all three of the reactants. And so I just put those in a chart so I compare what is required stoichiometrically from the equation that we have 1 to 4 to 2 as our ratio of moles to one another. What we actually have is equal numbers of moles of everything. And because we're going to use 4 moles of NaOCl every time we use 1 mole of Na2S2O3, and every time we use 2 moles of this, the NaOH, the NaOCl is going to run out first because we're going to use it at a much higher rate. We're going to use 4 moles for every one of the other and 2 of the second. So that one would run out first because we have equal numbers of moles of everything to begin with. Right? Part D asks us to analyze the graph. So this is a good skill. This should be a pretty straightforward skill for you. But we kind of need to know, I guess, what part of the graph we're looking at. So we want to know what's the temperature change for this reaction. So we're going to look at the difference between our initial temperature, which is down here. This is a really good exercise in making sure we read the problem carefully. The problem told us that the original temperature was 20 degrees Celsius. Now, if we read it carefully, we would see that this is clearly at 20 degrees Celsius. But we might want to just confirm that from the information that's given to us. It'd be a silly thing to make a mistake about. And then I would read this graph as about 32.5. Okay, you certainly want to be above 32. You certainly want to be below 33. This line right here, the solid line would be at 33. The solid line below our curve is 32. So you want to be in between those two. I would suspect that there's probably plus or minus 0.1 here. So it looks pretty close to the middle for me. So I would put this at 32.5. If you had said 32.6, 34, I'm sure you're pretty close. If you had said just plain 32 or plain 33, you probably would have gotten some points taken off of there. We know that we can, because our measurements are to individual into the one place we want to estimate a little bit beyond that, right? One decimal place beyond that. And then our temperature change is just going to be final minus initial. So 32 minus 5 minus 32.5 minus 20, excuse me there. And we get a temperature change of 12.5. That would be a good point also to just kind of remind yourself, right? The temperature went up when this reaction was happening. So this is happening in probably in a styrofoam cup or in a beaker or something where the temperature is going to be controlled really well. Calorimeter here, that's insulated calorimeter. There we go. So definitely not a beaker then. An insulated calorimeter keeps the temperature all contained within that calorimeter. And so if the temperature is going up in there, that tells me that this is an exothermic reaction. That when our chemicals get together, we go back over here. When our chemicals get together, they release energy. Tells me that that's an exothermic reaction because the temperature is going up. We don't necessarily need that to answer this part of the problem, but we would probably need it later, and it's just a nice thing to remind ourselves as we move forward. Okay. Next part asks us to calculate the magnitude of heat in joules that is released during the reaction. So we assume that the specific heat is given to us here. So I just like to use the specific heat as a way to remind myself of our units. So we have joules, grams, and degrees Celsius here. So my equation is going to be Q is equal to MC delta T. Many of us MCAT, but however you put it in there, this equation is given to you on the test, and this C specific heat fits in here, and our units are kind of told to us in what we need to use for our mass and our change in temperature. So we can just plug in our 15.21 grams, which is given to us in the problem, our 3.94 joules per gram degree Celsius times 12.5, and we get Q that's equal to 7.949 joules. Okay, so here our units are consistent with what's asking us to do. We've got 368, which looks pretty good there. We're not concerned about a sign here. This is the heat absorbed by the calorimeter. Okay, and so we are going to say that this is the amount of energy that's released by the reaction. So we don't have to worry about a sign here. We'll leave it as positive. We're going to look to the next part, right, where we're going to say using the equation we want to get the delta H of the reaction in kilojoules per mole of reactant, and we need to include the appropriate sign here. And this is where that conversation that we had earlier that this is an exothermic reaction is going to be important. Okay, we know that the number of moles, we already calculated that from the first part of this way back at the beginning of our lesson. Okay, so we know that this is the number of moles of NaOCl that we have to begin with. Okay, but we need to divide that by 4 because our balanced equation said that for every one time that the reaction runs, we use 4 moles of NaOCl. So we're going to divide our total number of moles by the number of moles of reactant to get 0.00625, and then our delta H is just the amount of energy divided by the mole, our answer from up here. Okay, and notice I did 2 things to our energy here. I made it negative, okay, because in this case we're again going to have that conversation. This is an exothermic reaction. It's giving off energy. We feel warm. We saw the temperature rise, and then I also changed it to kilojoules from what was previously joules because our question asked us to get to report our answer in kilojoules. Okay, so this is just for you to be very careful in your reading. The math here is not necessarily complicated. It is just making sure we keep track of signs and conversions between joules and kilojoules. And we end up with an answer of negative 1.2 times 10 to the third kilojoules per mole. Right, and that would be our final answer for this question. Lastly, very nice typical AP question. Magnitude of enthalpy calculation results is the same, even though what happened that we doubled the volume of each of the reactants. How can we explain this result? So here, go back to what I said at the beginning of today's lesson. We don't want to rely just on being able to solve the mathematical problems. We want to be able to explain what's happening in the chemical reactions in front of us. And so what I notice is happening is that I'm doubling the volume. Concentration stays the same. So that means that I have more of each of the reactants. Well, of course, that means that I'm going to make more energy as well. And because our delta H is a ratio of energy to the number of moles of reactant, the ratio will stay the same. The energy goes up and the number of moles go up. Okay. So I might write something like this: when the volume of reactants is doubled, the number of moles of reactants is doubled as well. This causes the amount of energy to double, and the delta H remains the same because the ratio of energy to reactants is the same. Okay, so that would be one way you might answer it. If you did want to do something a little bit more mathematical, this was the second response that was given in the scoring guidelines. The second experiment, we have 2 times MC delta T, okay, so, divided by 2 times the number of moles, and that equals the 2's essentially cancel out. Right? 2 over 2 is equals 1, and so we would end up with the same delta H. The magnitude is the same as that. So our numbers might be different, but because this is a ratio, we're going to end up in the same place. Okay, so let's get to what you need to know and give you some practice as we're going through these today. I'm really going to take a big step backwards and talking about an introduction to equilibrium, the direction of reversible reactions, and things like that, and then get into a little bit of the math. Like I said, I doubled these up just for simplicity's sake, because we're going through this so that we have a little bit more focus on what we're doing rather than jumping between these. Obviously, all of the topics run together in a pretty significant way for a lesson on equilibrium. Okay? So I want you to think about a container that just has only water in it, and maybe some air above it, but it's a closed container. Now, we've looked at a couple of examples of this, whether we were talking about eudiometer, whether we were talking about vapor pressure in gases, in a couple of Dalton's laws of partial pressure, things like that. But we know that if we close off a container like this, that a certain number of particles are going to evaporate, right? And that they will continue to evaporate until there are enough particles above the container that some of them will start to condense again. So we start out with, if there was nothing, when I'm looking at this picture right here, there is very little in that, very little water in the space, water vapor in the space above the liquid water, right? And so more and more particles are going to evaporate until we get to the point that there are enough particles up there that they can start to condense again. And that what we will see is that we will eventually get to a point where the number of particles that are evaporating and the number of particles that are condensing is equal to one another. And what we would call that is equilibrium, right? So this is an example of an equilibrium that is with evaporation and condensation. This is a physical change, just of the particles evaporating and condensing, but it's a dynamic equilibrium because the number of particles that is evaporating and the number of particles that's condensing would be the same. This is a very simplified version of what's happening here, right? But I think that the principle is a good one and makes sense for as an example of what's happening for equilibrium. Now, be careful here in remembering that this is a closed container. Okay, if you were to have an open container, what you know is that the evaporation, the particles would evaporate, and then they would move throughout the entire room. They would disperse throughout the entire room, diffuse throughout the entire room. Okay, in Chicago in winter, it gets really dry. The air gets really dry, and so we have humidifiers in our bedrooms to keep us from getting sick. Those humidifiers use this principle by having a fan on the top and blowing off these particles, so that you continually have particles that are evaporating. Equilibrium happens in a closed container like this because the number of particles are staying close to the surface of the water. This is what happens. This equilibrium is achieved in the closed surface with in a closed container at the surface of the water. Okay, now a similar thing could happen with I left the words evaporation and condensation in here. I'm sorry about that. This is would not be evaporation condensation. This is for a salt that's dissolving, right? So this is particles. If I put a solid into water, and I would have some solid particles that are dissolving into the solution. Okay, and similar here we go. At the beginning, we have a rate of dissolution that is much larger than any sort of precipitation. We just have particles that are dissolving into and filling up the liquid, moving around until we have a solution. Until we eventually get to a point where we have so many particles that some of them will again start to precipitate. Okay, and when we get to what we call a saturated solution, especially if there's particles at the bottom, the rate of dissolution and the rate of precipitation are equal to one another. Okay, so we would just see this dynamic equilibrium where the number of particles that's dissolving and the number of particles that is precipitating are equal to one another. Now, you've also seen equilibrium anytime you've used an indicator. So I kind of got stuck in a YouTube tunnel last night looking at videos of the blue bottle experiment. And if I had the materials here at home to run this for you, I absolutely would. I don't have them, but I encourage you to look at this. This is a pretty great example of equilibrium between oxidation and reduction between indicators. When we have just this one hydrogen, this big huge molecule of methylene blue makes this entire molecule colorless. And when that hydrogen is removed, when this whole molecule is oxidized, just that one hydrogen gets removed, this turns into a blue solution. And so we can play with the fact that these are two different colors by increasing the amount of oxygen in the container, increasing. There's all sorts of different variations on this experiment that are really cool to watch. But you are probably familiar with looking at any sort of indicators in acid-base reactions, right? And those are examples of equilibrium as well. We know that if we are using where's one that we might be phenolphthalein is probably something. Phenolphthalein is probably one that you're used to. You have a colorless solution at a pH roughly less than 9, and then right at 9 it starts to turn into pink. So you're doing a titration. You might have used phenolphthalein. You might have used other indicators to look at different changes at other pHs. Okay? And so when we talk more about titrations, we'll talk about which indicators are the best to use why. But the idea that we can change this molecule back and forth by adding or subtracting protons or by adding acids and bases is a great example of equilibrium and how the molecules can switch back and forth based on what we have there. I would imagine that many of you have seen a picture or a graph that looks like this, and this is kind of the classic example of what happens in equilibrium, where we have a gas N2O4 and O2 are in a closed container. Okay, an evacuated container just means a solid container that had nothing else in it, right? Some of it is put in there, and the concentration is measured over time, right? So we started with 10 moles per liter, or 10 to the negative second moles per liter of N2O4 from the reactants, and 0 of the products at NO2, and measured the concentrations of each of them over time. And what you notice is our concentration of reactants goes down, but it doesn't go down to 0. It doesn't just finish off down here. It levels off at a point where we have a concentration of some of the reactants, and the concentration of the product increases to the point where we have both we have some concentration of reactant here and product here. Many students will think that when we say equilibrium, what we mean is that we have equal amounts of reactants and products. And that is a really, really big misconception. You can see in this graph, there is a moment right here where we have equal amounts of reactants and products. However, that is not the moment of equilibrium. The moment of equilibrium, or the time at which equilibrium is reached, would be about 60 minutes here, and then beyond it stays in equilibrium. You see that the concentrations of the reactants and products do not change at all. Okay, the amount that we have here stays the same; they stay constant, and that would be an example. That's the definition of what happens in equilibrium. Okay, we can measure the rates a little bit here. We can see that the rate at which the reactant is getting used up is it would be a negative rate, but the magnitude here and the magnitude at which the products are being made is different, and that's because of the coefficients. Right, we see that we have coefficients, a coefficient of 2, so the 2 out of the concentration here is going to go up much more quickly than the concentration of the N2O4 goes down. But eventually they even off, and we get to the point where we have zero. We have zero change in concentration, but the rate of the forward rate and the reverse rate are equal to one another. Another example of this, and we see a lot of these graphs in different textbooks, is I was doing research, and I'm sure that you have something similar to this in your own researches, where we're looking at the reaction of SO2 and oxygen to make SO3. Why that says CO3, that should say SO3 right there. Obviously, what I would like to compare here is how we started, where this reaction started. Okay, we had some of our reactants and none of our products. So this would be similar to that earlier reaction. Okay, where we have only reactants, no products, and we end up at equilibrium. Okay, and here we have none of the reactants and some of the products, and we end up in the same spot for equilibrium. We have equilibrium reached here. We have a consistent or constant amount of reactants and products. Now, this is dynamic equilibrium, so we still have reactions happening back and forth and back and forth. However, the forward and reverse reaction are equal to one another, and so we do not have an overall change in concentrations here. Okay, so this would be another very common experiment or common equation that you would see. I hope that my head up here is not cutting off the fact that we have a reaction of carbon dioxide and water, carbon monoxide, water, carbon dioxide and hydrogen. Want to find out just a different way of looking at the same thing. Here we have for trial 1 what our initial concentrations are. So we have some reactants that we're going to put into again a closed container that would have nothing else in it. And after we have let it reach equilibrium, we notice that we're going to have some concentration of each of the species, both reactants and products. We could do a different experiment where we start with only the products, like that second graph we just looked at, and we would end up with a reaction. We would end up with a mix of reactants and products at equilibrium. Okay, we're going to get to in just a minute how all this math might work out and look at each of the specific concentrations in there. I'll tell you how we might calculate each of those things. But just for right now, what I'd like you to see is we're starting out with in this experiment only reactants. We end up with a mix of both. Here we end up with products. We end up with a mix of everything. Here we can start out with a mix of everything, and we end up with a mix of reactants and products. Okay, something interesting happens when we put all of these graphs on one axis. That you see that the overall number, overall concentrations for these are gases, the overall pressure there is not going to change, which we compare back to Dalton ball partial pressure, which we looked at earlier on this in these reviews. So you see that the overall number of particles, the concentrations are staying the same. So really like this graph just as an example of multiple different ways of looking at where we start, but how we would always end up with a mix of everything. And I'm about to tell you, I think you can probably predict what the mathematical value of these numbers are, how we could get those. Okay, so just to be very clear with you before we move on to that math, like I said, when equilibrium is reached, the reactants and products are simultaneously present, and that's what we saw. Excuse me, just for 1 second. That's what we see here at equilibrium. Reactants and products are simultaneously present. We have 3 good examples here. We're not saying that they're present in equal amounts. We're just saying that they are all present. Okay? The concentrations of partial pressures of all species remain constant at equilibrium. Right? There's no observable changes to the system. So from the outside eye, even though we can draw some nice particle pictures of particles evaporating or condensing, or we could have them dissolving and precipitating, that we're not going to see that inside of a container with just anything. Okay, but we know that those things are still happening. And what that means is that the equilibrium state is dynamic. The forward and reverse processes continue at equal rates, resulting in no net observable change. So these are just kind of the bullet points of what we mean when we say equilibrium. equilibrium. And we've done a lot of math with it, but I think it was important for us to spend a couple of minutes just looking at exactly what the equilibrium position means. Okay? And so then we can get into this idea of either a reaction quotient or an equilibrium constant. Mathematically, we would typically say that we are looking at products over reactants, right? So if this is our general equation up here, we have the small letters are coefficients, and each of the capital letters is some sort of chemical. Okay, we can look at Q, and Q is what we call the reaction quotient, and that's a quantity that we can calculate at any time. We don't. We're given a set of data, and we want to know something about what the ratio of reactants to products is. We can calculate that Q. We oftentimes will compare that Q to what we call K, which is the equilibrium constant. Q is typically reserved for equilibrium constant for concentrations of reactants and products, and then Kp we can talk would be about partial pressures, but you can see that if these are gases, these would be partial pressure. Sometimes you still will be given gas quantities in concentrations of a container. Excuse me. So just be comfortable with the idea here generally throughout all of these is that we're going to look at concentrations of products over reactants, and that any of the coefficients are going to be exponents on our calculations. Okay, so let's just look at what that might look. We're given an equation here. We're told what the value of K is, and we're asked to calculate the reaction quotient, and then to determine if we're at equilibrium and then how the system will proceed to get equilibrium. Okay, so I'm going to write out my equilibrium. I'm going to start with the Q, equilibrium constant, where I have N2, the concentration of N2, the concentration of H2 raised to the third power because of the coefficient here. Okay, and our divided by the concentration of ammonia, NH3 raised to the second power because there's a 2 on the equation. Right? But the 2 is a coefficient on a react. Okay, so I can plug in my numbers that are here. My concentration of N2 is told me to be 1. My concentration of H2 is 1. My concentration of H3 is 0.2. Okay, and you want to be very careful with how you put this in your calculator so that you get an answer that is 25. It's exactly 25. It's not even a rounded number. And so we can say we're going to compare. Right, this is our Q. This is our K is told to us. Our Q is greater than our K, so that means that we have more reactants than we would need at equilibrium, and so our system will proceed in the reverse direction. Okay, we're going to compare. We're comparing our Q. Right, this is we don't know for equilibrium. So hey, here's what we have. Here's some measurements we have. Is this at equilibrium? No, it's not, because Q is not equal to K. And we can even go further to say that the system will proceed in the reverse direction because Q is greater than K. Right. So here are 3 other examples that I'm going to ask you to stop and look at A, B, and C. Let's say that if you are the oldest, you should do letter B. If you are a middle child, you should do letter C. If you're the youngest child, you should do letter D. Or just pick any of the numbers that you want to do here in order to get some practice. Go ahead and stop the video just for a second, and then I can go through each of my solutions for each of these. Okay, so for number 1, I said that our Q is equal to 0.222. Our Q then is less than K, so it's going to proceed in the forward direction. For letter C, we end up with a 0 on the bottom here, right? You see that there's a 0, and typically I think we define dividing anything by 0 as approaching infinity or getting close to infinity. That's important because it means we have a really large number. We can say Q is greater than K, so reactions can proceed in the reverse direction. Now I would point out here, we should know it's going to proceed in the reverse direction because we have to have, if it's at equilibrium, if this is a system that wants to get to equilibrium, one of the things we said is we have to have some of all of the reactants in the products, right? So if we start out with 0 of these reactants, okay, our concentration is 0, we're going to go in the reverse direction to make some of those, right? So that definitely makes sense that we want to fill in this 0 by moving in the reverse direction. Okay? Last one, we got all 1s in there. The math there is pretty easy. Sorry, letter D, friends. But making that conclusion, we got to a Q that's equal to 1, so the Q is less than K, so it's going to proceed in the forward direction. Okay? I hope that those calculations made sense to you. Let's just look at an even simpler version. If we are given, here are the concentrations at equilibrium. So a general equation of A, 2 A's plus a B makes 2 C's. These are gases. Okay, we're given a container that's a rigid evacuated vessel. It means it's solid. The volume's not going to change. There's nothing else in it. We are the container is injected with enough to make a 0.01 molar concentration of A and B and C to begin with. Do you think about that graph where we might have all 3 of our points at the same spot on the y-axis? Okay, and then we're going to see what happens to our concentrations at equilibrium. Right, so we're told this is the concentrations after an unknown amount of time. We're not concerned with the amount of time it takes to get to equilibrium. We're just concerned that is at equilibrium at this point. Can we calculate the value of K? Well, sure we can. We know that K is equal to our concentration of our products squared. Notice we've got squared here because of the 2, the coefficient, divided by the concentration of A times concentration of B, but we're going to bring down the coefficient of 1. You may want to just be in the habit of bringing down all of the coefficients, right? So if you have a 1 here, that 1 would be filled in right here. Yes, it's not going to hurt anything to have an exponent of a 1. We would fill in our numbers here. We should get something that is like 0.88. Okay, now it's important to remember that concentration is going, or sorry, K is going to be constant, but only constant at a particular temperature, right? So we may be given a set of circumstances with the same experiment where it's repeated at a higher temperature. Kc, we're told that it's found to have a larger value. Okay, so describe the effect of the temperature change in the concentration of the gases in the equilibrium. So what can we say if K is larger? Take a second to stop the video and just jot down a couple of notes of what can you say if K ends up being having a larger value. And I would say a couple of different things. I would say that a larger K means that we have more products. Okay, so we're going to expect there to be more letter C's or product to C if the K is larger. Concentration of A for A will be twice that of B, right? So this is going to go up by, or sorry, go down by twice the value of B. If we're making C's, we're going to go down by a lot more because the stoichiometry is 2. And that the changes in magnitude for A and C would be the same because of these coefficient here, but they would be opposite in direction. So we're going to add C and we're going to lose some A. This is, again, some explanations of some of the things we might see for this kind of a reaction. Okay? The last thing to remember about the reaction quotient and equilibrium constant at the same time is that they are, we would not include any substances that are not in the same state as everything else. And typically that means that we're not going to include solids in pure liquids. And we've seen multiple examples of this in our work together as we've been doing ice tables. I didn't include a single ice table today because we've done so many of them. But you know that we typically in an equation like this, so here's the combustion of methane. If we're making liquid water, if we said that liquid water was produced here, that would not be included in our K expression. Okay, because it is liquid, because we have 3 gases here. We have no, and this is liquid, so it would not be included on our K expression. Okay, why don't you go ahead and take a look at this? This is another example where we have multiple different states of matter. What's our K going to look like? This is a very unusual one, and then we have no denominator. So we just have NO2 to the fourth and O2 to the first. Both of these are solids, and so they would not be included in our K expression. So here's 2 examples. One, a complicated base problem. So I'm going to give you practice on that. We've looked at some KBs over the course of our lesson, so you should be sort of a review. And then here's a solubility problem. We're looking at a solid dissolving into its components. Take a second, pause the video, and see if you can adjust the K expressions. Don't have to do calculations, just write the K expressions. And for both of those, I would have made sure that I eliminated the liquid from our beginning, or from our first one, right? So we just have this is actually a base. Here's the conjugate acid making some OHs, and then I'm going to exclude the solid, and we call this a KSP, solubility product constant, because this is a solid here, and we include our 3 because we made 3 nitrates in there. Okay. Now let's just go in real quick into a conversation about the magnitude of equilibrium constant and a couple other quick properties. You may have seen some charts that look like this. I like to just show these as an example of how many substances have Kas or Kbs. We'll look at some KSPs in a minute, but we can see the wide range in values for each of these. Okay, and so this is a really, really tiny number. 1.8 times 10 to the minus 12 means that it's 0.11 zeros and then 1/8, right? So it's a really, really small number. And so what that tells us is that for hydrogen peroxide, right, this is what we would call a very reactant-favored substance, right? That there's not a lot of products. That the numerator, the number that's at the top, is going to be very, very small. The number on the bottom would be very big. And when we divide that out, we end up with a really small number. We can compare that to ionic acid up here that has a relatively small number, 0.16, but in comparison to 1.8 times 10 to the minus 12, it's a really big number, right? By a magnitude of 11 here, the difference, that's a really big difference, okay? And so we would say is that this is much more product favored than the hydrogen peroxide is if we're going to compare our ionic acid to hydrogen peroxide. And we could do a similar thing down here with our bases. This number for aniline 7.4 times 10 to the minus 10 is very small, especially in comparison to diethylamine. Excuse me. Same thing for solubility product constants. Again, you would never be expected to memorize any of these things. Okay, this is just for these are reference guidelines that you can look up at any point. I just want to give you an example of like look at Bi2S3. I'm amazed by this. 1.6 times 10 to the minus 72, right? So really like incredibly small number, okay? And then we could compare that to 5.0 times 10 to the minus third. Like barium hydroxide is something we probably talk about it being pretty insoluble in water. We'll compare that to bismuth sulfide. Is that how we would say that? Bismuth sulfide, how we would compare those two numbers is just sort of incredible. A couple of these down over here as well. Okay? So the magnitude, the number here is going to tell us a lot about how comparing our reactants and products. So this would be could be a typical AP problem that you could get. You're given two equal reactions at a specific temperature. You see that it's given to you there. Told you how this is set up. Okay? Based on the fact that we're going to add the same amount of moles to the containers, what can we tell about the concentrations of bromine chloride or an O gas, nitrous oxide gas, is compared to one another based on our KEQ value? So pause the video here for just a second and see if you can come up with a good solution to that. And I think that the best thing you can say here is that the amount of bromine is going to be way more than the amount of NO, right? Because it has a much larger KEQ. So the much larger KEQ for reaction 1 means that you have a lot more reactants than you have products. And any of these kinds of problems would absolutely just be comparative problems where we're looking at comparing the two KEQs of one another rather than just kind of an arbitrary number off the top of your head. Right? And you have to be given these numbers or given a set of data to calculate the numbers and then in comparison, right? We could certainly, but you would never be expected to memorize numbers like that. Lastly, just looking at a couple of different properties of what we can do if we're going to play around with these equilibrium constants and put some reactions together. This feels a lot like Hess's law, which is something that we talked about with Mr. Faribault yesterday, where he was talking about, in this case, reaction 3 was your goal reaction, or the reaction that we're trying to get to. So if we're going to say that reaction number 1 has a K that looks like this, and reaction number 2 has a K that looks like this, can we compare how reaction 1 and 2 look to reaction 3 in order to come up with a good, with an estimation of what how K3 would look in comparison to K1 and K2? Okay, so the chemical equation here is the two they're given to us. What are we going to have to do here to our values up here to get to K3? Well, one thing would be maybe we just write K3 based on our numbers here, and then we compare it up here. What I'm going to do is I'm going to look at similar to what we would do in Hess's law. Look, I have some methane as a product in reaction 1, but it's a reactant in reaction 2. I have 1 water. I've got 2 waters. I'm going to have to worry about that in a minute, but look, some carbon monoxide. I'm going to have to probably get rid of that, some hydrogen. So it seems like I'm going to have to reverse the first reaction, and when I do that, then I'm going to have to reverse the second reaction as well. And by reversing it, then I get all 4 of my hydrogens to the product side. I'm going to end up with 2 waters on the reactant side. And by reversing them, by reversing the reactions, I'm going to take the inverse of the K's, right? So when a reaction is reversed up here, our rule is that the K is inverted. And then if I add reactions together, the K's of the resulting overall reaction is the product. Okay. So the simpler way to say this is that K3 is equal to the product of 1 over K1 times 1 over K2. Okay. So this is a pretty classic AP type question that as I'm doing numbers, which actually makes it a little bit harder, right? Because it's much more conceptual. So just kind of think through what's happening here. The stoichiometry, coefficients of a reaction multiplied by a factor of C. K is raised to the power of C. So that's it's sort of obvious, I think, that if we look at the difference in reaction 1 and reaction 2, right? When we add these coefficients, so this is the same reaction just with larger coefficients. So we doubled everything in reaction 2. We could rewrite this as K1 squared. Okay. That our exponent properties would just allow us to factor out that 2 by making an exponent of that. Okay. Let's take a look at this. This is our last guided practice problem for today, where we're looking at 2 reactions are given to you. What would be the correct expression for the equilibrium constant for reaction 3? Pause your video if you need to. And as I was looking at this, I got K3 is equal to K2 over K1. And I think what that means is that we reversed reaction 1, but we left reaction 2 where it is. Okay. Let's check my work there and see if you're able to do that. All right. So that's our lesson for today. Lastly, we ran through a lot of theory kind of at the beginning about just making sure that we see that equilibrium is more than just ice tables and that it appears in a number of different places in chemistry. And that's really important, I think, for us to see that equilibrium really spills over into gases, acids, and bases, into solubility in lots of different places. And so I want to give you examples of those and give you a picture in your brain of what's happening there. Okay. Let's take your new skills out for a ride on 3 practice problems we have for you today. Take a screenshot of this. If any of that's cut off at the top, it's the same setup as before, but what I'm asking you to do is say, do you agree or disagree with the statement below based on the graph that is there? The statement says the reaction was about to reach equilibrium at time equal A because the concentrations of X and XY were almost the same. So do you support that or not? And give us a short explanation of why or why not. Here we'd like you to draw a particle picture. We've got equal moles here, so here's time equal to 0, time is increasing to go from left to right. And what we'd like you to do is to draw a particle picture in box T, or box with T equals 400 seconds, that's consistent with the conclusion that equilibrium was reached for this reaction after 300 seconds but before 400 seconds. So somewhere right in between here we got to equilibrium. Okay. And so what would the particles look like in this box in order to say that we got to equilibrium? All right. And then lastly, right off of the 2017 test, write an equilibrium expression for a reaction as it's given to you there, and then calculate the value of K based on the K expression that you got based on the information that is there. Okay. This one looks like you might need to have an ice table set up, but you may be able to do it in a different way as well. So have fun with that. And Mr. Faribault is going to have a solution to that for you when we come back tomorrow. All right. That brings us to the end. Our good reminders to keep checking apcentral.collegeboard.org. Look in the links in the description below for extra helpful chemistry resources. And then continue to reach out to your friends, family, anybody you know that needs some extra help with devices or with internet access. We're asking people to go to this site cb.org/tech by this Friday, April 24th. So just gives you a couple of extra days. Please make sure to reach out to that, even if you're not sure of all the information. Just get that process started. It's going to be really important. Thanks so much for watching. Have a great day, and we'll see you tomorrow. Thanks so much.
Hello, everyone, and welcome to this AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, we are going to continue our discussion of Unit 7, Equilibrium. So in yesterday's lesson, Mr. Byrne talked about a variety of concepts involving equilibrium, and we'll continue that today. Just to remind you, you can go to apstudents.org/exams2020 to get updates and information about taking AP exams online this year. Remember that your AP Chemistry exam will be given on May 14th, and there are 2 free response questions. So again, this is information about when to take the exam, but again, feel free to go to apstudents.org/exams2020 to get updated information. Hopefully you have access to a periodic table and some scratch paper and something to write with. In today's lesson, we'll be talking about Unit 7, and so topics 7.7, calculating equilibrium concentrations, and 7.8, representations of equilibrium, introduction to Le Chatelier's principle, and the reaction quotient. And again, you can see both the topics and the science practices involved. So things like representing visually the relationship between the structures and interactions across multiple levels. So we'll definitely see particle diagrams today. And again, with Le Chatelier's principle, explaining the connection between experimental results and chemical concepts, processes, and theories. So again, we'll talk about Rice tables and calculating equilibrium concentrations, the reaction quotient, and Le Chatelier's principle, as well as particle diagrams. In yesterday's lesson, Mr. Byrne had presented you some questions related to equilibrium. So here we have a equilibrium involving the reactants X and Y, and then the product XY. And so a student made a claim that according to the information in this diagram, you can see we have A, B, C, and D. So down here at the bottom on the X-axis, we have different points in time. So the student made the claim that at time A, equilibrium was going to be reached because the concentration of X and XY were almost the same. So they were focusing on this particular point in the diagram. Well, hopefully you understand that equilibrium has to do with the concentrations or the pressures not changing over time. So we would disagree with this claim. Equilibrium is going to be first achieved right around here at point C, because from this point onward, you can see that the concentrations or the pressures of the reactants and the products no longer change over time. But the concentration of a reactant does not need to be the same as the concentration of a product. So equilibrium does not mean equal in terms of amount of reactants and products. It simply means that those concentrations are not changing because the rate of the forward reaction is equal to the rate of the reverse reaction. In the other question that was asked to you in the lesson yesterday, we have an equal molar mixture of X and Y. So at time 0, you can see here in this first diagram, we have 1, 2, 3, 4, 5, 6, 7 atoms or molecules of X, and then we have 1, 2, 3, 4, 5, 6, 7. So again, it would be equal molar of X and Y. Now, if you look over time, what is happening is we're starting to form molecules of XY. So there are an increasing amount of molecules of XY, and as a result, the concentration or the amount of X and Y is going down. So now we get to this point at 300 seconds. We have 1, 2, 3, 4 molecules. I'm sorry, 5 molecules of XY, and then we have 2 atoms or molecules, I guess depending on what the substance is. We have atoms of X and Y. So draw a particle picture in the box for time equals 400 seconds that is consistent with the conclusion that equilibrium was reached. So equilibrium was reached at some point between 300 and 400 seconds. So what I've chosen to do in my particle diagram is to show that if equilibrium has been reached, then the concentration should not be changing. So therefore, I have essentially copied the exact same particle diagram that we have at 300 seconds. So therefore, we know that equilibrium has been reached when the concentrations of reactants and products are no longer changing. All right, other question that was asked for your homework in yesterday's lesson. It says we have an equilibrium between nitrogen and oxygen and nitrogen monoxide. So we have N2 plus O2 and it produces 2 molecules of NO. It says write the expression for the equilibrium constant. Now I'm going to show you 2 different equilibrium constants. One of them has brackets and the other has parentheses involving the letter P, where P stands for pressure. So you have to read this question carefully because it says to write the expression for Kp. This is what the question was looking for, not the Kc. So it'd be a shame for a relatively easy question for a student to miss because they weren't paying attention to the difference between brackets, which means concentration, and P for pressure. Now, had you done the following, had you written Kp like this, so NO squared over N2 and O2, this would not have earned the point because the readers would not see the letter P indicating pressure. So parentheses is not the most important part here. It's the fact that you have P for pressure. Now, we've seen lots of strange answers on the AP chemistry exam for questions like this. I'll show you an example of a rather strange one, and I would think this would still earn credit, but just again, try to be careful with your symbols. So I've seen students do things like this. So they're writing the pressure of the NO and the pressure of the O2. So that subscript is still present, although it's outside the parentheses. I think this would be fine. I would still give that student credit because it's clear they understand P for pressure and they have the appropriate squared symbol there in the exponent. So that's a little bit different than what I'm showing you on the screen, but that would consider be correct. But just watch out for the fact that Kp involves pressure and Kc involves concentration. All right, the next part is going to involve what I call a Rice table. So we're going to use R, that stands for reaction, and then I is the initial amount, C is going to be the change, and then E is what happens at equilibrium. So a student injects nitrogen and oxygen into a previously evacuated rigid vessel. So the pressure inside the container was 0 initially, and now we have a pressure of nitrogen, which is 6.01 atmospheres. We're being given that information, and then the pressure of oxygen is listed as 1.61 atmospheres. But that's it. So initially there is no nitrogen monoxide. This reaction will proceed toward equilibrium by shifting from left to right. In other words, the concentration or the pressure of nitrogen will go down by a certain quantity x. Because there's a 1-to-1 mole ratio between the nitrogen and the oxygen, the concentration or the pressure of O2 will also go down by x. But since there is a 2 as the coefficient for the NO, then the increase in pressure for the NO would be 2x, since 2 moles of NO are formed for every 1 mole of O2 or N2 that is consumed. So at equilibrium, we have 6.01 minus x for N2, we have 1.61 minus x for O2, and we have 2x for the final pressure of the NO. Now we are told that the partial pressure of the NO at equilibrium is 0.122 atmospheres. So now we can solve for x. So 2x equals 0.122, x equals 0.061. So on your calculator, if you do 6.01 minus 0.061, in other words, if you do this math, substituting in the value of x, you get 5.95. I'm just using 2 decimal places for my pressures. If you do 1.61 minus 0.061 on your calculator, you will get 1.55, again rounding off to 2 decimal places. And again, if I look at these 3 values, I can take these 3 pressures and I can plug them into the Kp expression, the expression that we wrote in part A, because now I have to calculate the value of Kp. So we had to figure out the final pressure of each substance at equilibrium, and we can now plug those values into the Kp expression. So 0.122 squared divided by the product of 5.95 and 1.55 gives us our answer. So Kp works out to be 0.00161. Okay, well those were the answers to the homework from yesterday's lesson. So now we're going to focus on Rice tables and calculating equilibrium concentrations. So I have an equation involving hydrogen reacting with iodine to produce hydrogen iodide, and this is in the gas phase. Suppose that we are given that at equilibrium the concentration of hydrogen is 0.1 molar, the concentration of iodine is also 0.1 molar, and the concentration of Hi is 0.714 molar. If we had to calculate the value of Kc with these numbers, just plug them into the K expression. So you have hydrogen iodide on top, that would be squared because of the coefficient. Then we have hydrogen iodide on the bottom, so we just plug in our numbers. And if you do this math on your calculator, 0.714 squared divided by 0.1 squared, you get 51.0. So Rice tables are going to be used if we are trying to find the final concentration of each substance. Now that we know the value of K, we can set up a Rice table for a new problem. A sample of hydrogen and iodine is added to a previously evacuated reaction vessel. The initial concentrations are hydrogen equals iodine equals 2 molar. Calculate the concentration of all 3 gases in the reaction vessel at equilibrium. So we start with concentrations of 2 molar for each reactant and then 0 for the product. Well, of course, because we have 0 product, we're going to have to shift this equilibrium position will shift toward the right in order to reach equilibrium. So the concentration of hydrogen goes down by x, concentration of iodine goes down by x, and because of the 2 as the coefficient, the concentration of Hi goes up by 2x. Notice that in the change portion of this table, so when you are writing your x's, the change in x needs to be proportional to the coefficients. So we're going to get 2 minus x, and 2x. So just a comment, there is no such thing as the law of conservation of moles. A student might be thinking that somehow the change in x has to be the same on both sides of the equation, but there is no such thing as the law of conservation of moles. It just so happens that coincidentally we have equal number of moles of gas on each side of this particular equation. But suppose we had an equation involving 3 moles of hydrogen reacting with 1 mole of nitrogen to produce 2 moles of ammonia, NH3. Notice that the change in x does not have to be equal on both sides of the equation. So do not think that somehow the x's you have on the left that are lost have to equal the x's on the other side that are gained. It was just a coincidence in this particular example that I'm using. Okay, so we're going to plug in the final row of the Rice table in terms of x into the equilibrium constant expression, and we know that Kc equals 51. So now we can solve for x. And I will tell you that on the AP chemistry exam, you do not need to use the quadratic equation. So therefore, I'm using an example in which you can just do simple algebra. The fact that I have a perfect square on the top and the bottom means I can take the square root of both sides and avoid any complicated math or the quadratic equation. So when I take the square root of both sides, I get 2x over 2 minus x equals the square root of 51, which works out to be 7.14. Now let's go ahead and continue solving for x so we can figure out the final concentration of each chemical at equilibrium. So we'll go ahead and multiply both sides by 2 minus x, then we'll distribute on the right, and then we'll combine like terms, so we get a total of 9.14x equals 14.28. When we solve for x, we get 1.56. So I can now plug in x into my final row of my Rice table. So 2 minus 1.56 equals 0.44, and then 2 times x equals 3.12. Now to show this graphically, like the diagram that was presented earlier from the homework problem, we start with 2 molar for hydrogen and iodine, and then that concentration decreases over time to a final value of 0.44. We start with 0 for our concentration of the product Hi, and that rises to a final concentration of 3.12. Now if you had to label where exactly on this curve is equilibrium achieved, at what point in time, it's not when the concentration of reactants and products are equal, it's when the concentration of reactants and products no longer change over time. So from that point on, equilibrium is reached because the concentrations are holding steady. Okay, so in that example we started with reactants only. Here's an example, same system. Let's start with product only and watch what happens. So we're going to start with 3 molar Hi. So we have 0 for the concentration of hydrogen and iodine find the reactants, and we have a concentration of 3 molar. So you'll see a similar pattern. We're going to do minus x and plus x. But if we're going from right to left, it's going to have to be minus for the product and plus for the reactant. So it's going to be plus x for the reactant because we had none to start with, and then minus 2x. Again, remember that the change is proportional to the moles from the coefficients. We're going to plug these numbers into the K expression like we did before and solve for x. Now, if I'm going too fast, feel free to pause the video because I am kind of, trying to cover a relatively large amount of material in a relatively short amount of time. So feel free to pause the video if you need to process all of the calculations that I'm doing for you. All right, I'm going to take the square root of both sides. So 3 minus 2x over x equals 7.14. Now we're going to solve for x. So we get 9.14x equals 3. X is 0.33. Let's put that into the values for the final row of our rice table. 0.33 and 3 minus 0.66 is 2.34. So now in this example, again graphically, we started with all products and no reactants. So the reactants increased from 0 to 0.33 and the product decreased from 3 to 2.34. As you can tell, equilibrium was achieved at this point when the concentration of reactants and products were not changing. All right, well, here's a third example. What if I start with a mixture of both reactants and products? So my concentration of HI is 3 molar and my concentration of H2 and I2 is 1 molar. It was obvious in previous examples that I was either going to proceed to the left or to the right. Now it's actually not so clear. If I'm going to reach equilibrium, how do I know whether I'm going to have the reactants go down or the products go down? So it's going to be a little confusing here. This brings us to another topic, another concept, which is called the reaction quotient. Okay, imagine you are at a mall or a shopping center and you see a map and you're trying to figure out where you would like to go to get to a particular store. Well, there's a particular part of the map that you're looking for, and that is where you are right now. Essentially, that's what the reaction quotient is. The reaction quotient is kind of a you are here symbol because it tells you where you are now and what needs to happen in order to get to equilibrium. So suppose you have a flask that contains a certain amount of reactants and products. This is your reaction vessel. This is where you are now. And at some point, the system will eventually reach equilibrium. So Q, the reaction quotient, it looks identical to the equilibrium constant expression. So these two look identical. The difference between Q and K is that with Q, you just plug in the values for what you have right now. And once you plug in the values for what you have right now, then you can compare the value of Q with the value of K and then determine in which direction you must proceed in order to reach equilibrium. So we're going to compare Q with K, and there are 3 possibilities. Okay, so the Q is where you are right now. The 3 possibilities are the following. Either Q equals K, which means you already are at equilibrium, so it's already arrived. But if for some reason Q is less than K, remember this is products over reactants. So if Q is smaller than K, it means you either have too many reactants or not enough products. The reaction would then proceed from left to right in order to reach equilibrium. But if on the other hand, Q is somehow greater than K, then the reaction indicates you have too many products or not enough reactants, and you would have to proceed from right to left. So comparing Q with K, this is a way of remembering it. I like this little mnemonic. This is a little memory device. So what I've done is I'm comparing Q with K, but I put K first, and there's a reason for that. You'll see in just a moment. So if K equals Q or Q equals K, you already are at equilibrium. Now, if Q is less than K, the reaction would have to proceed from left to right. And if Q is greater than K, then the reaction would proceed from right to left. So here's a little memory trick. Because I've done it this way, watch what happens. Look at that less than symbol. Q is less than K. It also indicates the arrow that the reaction would have to proceed from left to right. It's a little trick. If you write it this way with K first and Q second, it's kind of a little cheat sheet for yourself because it shows you that you can kind of make an arrow out of the inequality symbol. Okay, so if Q is less than K, you're going to go toward the products, and if Q is greater than K, you're going to go toward the reactants. Okay, well we have 3, 1, and 1. Let's go ahead and plug in the values that we have now and see where we are relative to K, which is 51. Well, we're going to plug them in. We have 3 squared divided by 1 times 1. That's 9. And since 9 is less than 51, that means that Q is less than K. The reaction would proceed from left to right toward the products. So the reactants are going to go down by X, and the product is going to go up by 2X. Again, that's the change based on the mole ratio and the coefficients. 1 minus X, and 3 plus 2X. Let's go ahead and plug this in, solve for X. So we'll do this math. We're going to take the square root of both sides, and then we're going to simplify the expression. And then once we simplify this expression and we solve for X, in this case, X works out to be 0.45. So 1 minus 0.45 is 0.55, and 3 plus 2X, which is 3 plus 0.9 is 3.9. So here we had a mixture of reactants and products. And since it was shifting, proceeding toward the right, the products increased to a final amount of 3.9, and the reactants decreased to a final value of 0.55. So I'm looking at equilibrium in 3 different examples here. You can see that we started with either all reactants. Now watch what happens when I plug these numbers in. 0.44 and 3.12, I get a K value of approximately 50. 50.3, that's close enough to 51. That's sort of approximately equal to K. If I started with only products and no reactants, I got a different set of numbers. But when I plugged them into the K expression, I still got the same value of K. And in our last example, I had a mixture of reactants and products. We got a different set of values. But when I plugged them into the K expression, I got the same value. So look at that. Look at the fact that I started with either all reactants or all products or a mixture of reactants and products, and I still achieved the same equilibrium constant. The only way you can change the value of the equilibrium constant is to change the temperature, which we're going to see a little bit later in this lesson. All right, here we have a discussion of Le Châtelier's principle, and I'm using a different equilibrium system. This involves nitrogen dioxide reacting to form dinitrogen tetroxide. It turns out that NO2 happens to be a brown gas, and N2O4 happens to be a colorless gas. So if you have an excess of NO2, then your mixture will look sort of reddish brown. And if you have an excess of the N2O4, it's going to be sort of a lighter shade. So that color change indicates you either have more of the reactants or more of the products. Suppose that a chemical reaction has already reached equilibrium. Okay. Now suppose that the rate of the forward reaction, which is equal to the rate of the reverse reaction, you're at equilibrium, and the concentration or the partial pressure of each reactant and product are no longer changing over time. What would happen if a system that's at equilibrium experiences some sort of stress? Now that is what the Châtelier's principle is all about. If a system that's at equilibrium is perturbed or experiences an external stress, then the position of the equilibrium may experience a shift, and the shift is in the direction that will somehow relieve that stress. So what exactly are we talking about when we say a stress? Either a change in concentration or pressure or temperature. Now remember that when Q equals K, the system is at equilibrium. So if the stress occurs, if a change occurs that causes Q to become less than K, then the equilibrium position will shift toward the products from left to right until Q equals K again, and equilibrium has been reestablished. If instead the change occurs that causes Q for some reason to become greater than K, then the equilibrium position will shift toward the reactants from right to left until eventually equilibrium has been reestablished and Q equals K again. So here are a variety of stresses that we'll talk about. So the first category is changes in concentration. What happens if I add more reactants? Well, if additional NO2 is added to the reaction vessel, and we're going to do all this at constant temperature, my concentration of NO2 is going to increase. And so I'm showing that by, you can see on my little graphic here. So I have an increased amount of the NO2 as indicated by this larger font. At this point, Q would become less than K. So the equilibrium position would shift toward the products if you add more reactants. Now, besides Q versus K, you could also use a kinetic argument. Remember that the more collisions you have, the faster the reaction rate. Well, if we increase the concentration of the reactant, there's going to be a greater number of collisions between reactant molecules, and the rate of the forward reaction would increase. Well, what about if we add more products? So if we add more products, now we're going to be adding additional N2O4. So what this is going to do with respect to our value of Q will now become greater than K. So adding more products will cause a shift toward the left. And again, you could use a kinetic argument and say, well, we're going to increase the concentration of N2O4. There'll be a greater number of collisions between N2O4 molecules, and that will increase the rate of the reverse reaction. Besides adding more of a chemical, you also could remove a chemical. So if we take away some NO2, that will cause the value of Q to become greater than K. So effectively, we are decreasing the concentration of NO2, and the equilibrium will shift toward the left. If instead we take away some products, so now we cause the value of Q to become less than K, then the equilibrium will shift toward the right. So So in terms of adding or removing chemicals, the Châtelier's principle tells us that the system will eventually reach equilibrium by responding to that change, by trying to counteract that change. And Q versus K is a great way to think about this and justify your answer. So on the AP exam, do not say because of Le Châtelier's principle and then that's it. That is not a sufficient explanation. But if you said because as a result of this change, Q now becomes less than K, which will shift the equilibrium position toward the right, that is a satisfactory explanation. Okay, so if they talk about discuss your answer in terms of collisions, then I would mention that the rate of the reaction is increasing or decreasing. So just read the question carefully. But the Châtelier's principle is a fine thing to discuss, but it cannot be a reason on its own. So be careful about that. Okay, another example would be besides change in concentration is a change in pressure. So one way to change the pressure is to heat up the mixture. Now we're not going to talk about a change in temperature until later. So there are two ways to change the pressure. You can either add more of a gas or you can change the volume of the container. Okay, so we're going to do this adding a gas, but we're going to add an inert gas such as helium or neon or argon. Now, is the total pressure going to go up? Absolutely. However, let's talk about Q versus K. Since helium or neon or argon are not featured in the equilibrium expression, then the concentration or the pressure of the individual chemicals, N2O4 and NO2, remain the same. So Q is still equal to K. There would not be any shift. So if you increase the pressure by adding a gas that does not participate in the chemical reaction at all, then the partial pressures and the concentrations of all of the gases that are involved in this reaction remain the same. So no change in the equilibrium position. Now, if we decrease the volume of the reaction vessel, well, that's going to increase the pressure of the gases. So for example, pretend that we have an equilibrium in which the concentration of N2O4 is 5 molar and the concentration of NO2 is 1 molar at equilibrium. So 5 divided by 1 squared is 5. What would happen to the concentration or partial pressure of each gas if the volume of the reaction vessel is reduced by half? So when you reduce the volume of a gas by half, according to Boyle's law, you double the pressure. So if I plug in new numbers for concentration, in this case, instead of 5 and 1, if I plug in 10 and 2, well, 10 divided by 2 squared, that's 2.5. So what happened is my value of Q is not equal to K. And hopefully you remember that when Q is less than K, equilibrium would shift toward the right. So we're going to shift toward the N2O4 if we reduce the volume of the reaction vessel in this case. What if we increase the volume of the reaction vessel? Well, now that's going to cause the pressure or the concentration to go down. So if I double the volume of the reaction vessel, now my concentration of N2O4 becomes 2.5 and my concentration of NO2 becomes 0.5. If you plug in these new values into the expression, notice that 2.5 divided by 0.5 squared is actually 10. So our Q has changed. Our Q is now larger than K. So we're going to shift the equilibrium position toward the left. Here's a way of understanding what's going on here in terms of particles. So I've got 12 molecules in this particle diagram. If you count, there are 1, 2, 3, 4, 5, 6 molecules of NO2 and there are 6 molecules of N2O4. So in this particle diagram, what happens when I decrease the volume of the reaction vessel? Well, those 12 particles are now occupying a smaller space. So the pressure goes up. So which side of the equation, the left or the right, will this equilibrium shift? Has to do with the way of counteracting this change. So how can the total pressure decrease slightly? We have to reduce the number of molecules of gas in the container. So when you decrease the volume of the reaction vessel, you're going to shift to whichever side of the reaction has fewer moles of gas. So what I've done in my final particle picture is I now have only 2 molecules of NO2 and I have 8 molecules of N2O4. That's a total of 10 molecules. So I have reduced the total number of molecules in the container, and that is because the equilibrium is trying to respond to this stress. By decreasing the total pressure, equilibrium shifts toward the side of the reaction with fewer moles of gas. Okay, but if we increase the volume of the reaction vessel, so I've got these 12 molecules again, 6 of NO2 and 6 of N2O4, I'm going to increase the volume. So now the pressure has gone down. So the volume has increased, the pressure goes down. So how can the pressure increase slightly? Well, the reaction would have to shift toward whichever side has a greater number of molecules. So what I've done now is I have decreased the amount of N2O4 and I have increased the amount of NO2. So I've increased the total number of molecules. Again, what happens when you increase the volume of the reaction vessel is equilibrium will shift toward the side of the reaction with more moles of gas as a way to sort of counteract the change and increase the total pressure. You can use Q versus K, or you can use this particle diagram to help you understand what's happening inside the reaction vessel. Okay, so again, decreasing the volume of the reaction vessel causes a shift toward the side of the equation with fewer moles of gas. Increasing the volume of the reaction vessel causes a shift toward the side of the equation with more moles of gas. What about this? Take a look at this equilibrium system. We have 2 moles of gas on the left and we have 2 moles of gas on the right. So what do you think is going to happen if we have the same number of moles of gas on each side of the equation? Changing the volume of the reaction vessel for a system like this would not cause a shift at all. Why? Because each side of the reaction has the same number of moles of gas. Now let me show you the Q versus K. Suppose, I'm just making up some numbers right now. I have the equilibrium system, HI squared divided by H2 and I2. I'm just going to plug in some numbers. So 5 for the concentration of HI and then 1 for the concentration of H2 and I2. Now 5 squared divided by 1 squared is 25. What happens if I double the concentration of each chemical? Well, 5 becomes 10 and 1 becomes 2. But 10 squared, which is 100, divided by the product of 2 times 2 is 4. It's still 25. So there's not going to be a shift because Q is still equal to K for this particular system. All right, so I talked about change in concentration and change in pressure. I now want to talk about change in temperature. Again, we go back to the NO2 and N2O4 system. Remember that if it is brown, it's going to have more NO2. And if it's lighter shade of brown or getting closer to colorless, it's going to be more of the N2O4. What happens when we place this reaction vessel that contains a certain equilibrium amount of each gas into a hot water bath? So we're talking about changes in temperature. Well, if we do that, it turns darker brown. And if we put it in an ice bath, the color actually fades and it gets lighter. So I'll show you a short video of this.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
So it's a great example of an experiment that we now have to draw some conclusions about this reaction. So increasing the temperature was a shift toward the brown NO2, and decreasing the temperature was a shift toward the colorless N2O4. So these observations can tell us information about this reaction. Is this reaction, which is as written, endothermic or exothermic? I'm going to give you another piece of data. For this reaction as written, the value of K is 160 at 15 degrees Celsius, and the value of K is 5 at 100 degrees Celsius. So changing the temperature will also change the value of K. We saw this with kinetics, with reaction rates, that the value of K, the rate constant, will change when you run the experiment at a higher or lower temperature. Otherwise, if you're just changing pressure or concentration or adding or removing a chemical, and you're not changing the temperature, then the value of K will stay the same. But here we are changing the temperature. So what does going from 160 to 5, as far as the equilibrium constant, what does that tell us about this reaction? Is this reaction endothermic or exothermic? Well, if we decrease the value of K, that implies that we have less products or more reactants. So it is a shift toward the left. And that happened when we increase the temperature. You can think of increasing the temperature like you're adding heat. So it indicates we have an exothermic reaction in this particular case, because when you increase the temperature, the reaction will shift in the endothermic direction, essentially to consume some of the heat that was added. So it's a way, according to Le Châtelier's principle, of counteracting the stress. So let me talk about this. We have an endothermic reaction at the top of the screen, and we have an exothermic reaction at the bottom of the screen. So for an endothermic reaction, if you increase the temperature, it's like you're adding more heat. It will shift toward the right, and K increases. If you have have an endothermic reaction, but you decrease the temperature, it is like you are removing heat. So the response to that would be the system would shift toward the left to kind of produce more heat as a result of that change, and K decreases. On the other side, if you have an exothermic reaction, increasing the temperature is like you're adding more heat, so it's going to consume some of that heat and shift back toward the left, and K decreases. And if you lower the temperature of an exothermic reaction, it will shift toward the right. So again, these are the kinds of statements you can make to justify your answer. If they indicate, justify your answer with respect to T, you can't really do Q versus K, it doesn't work in that case, but you can say that increasing the temperature will shift the reaction in the endothermic direction, and decreasing the temperature will shift the reaction in the exothermic direction. So in our situation, for the NO2 reacting to produce N2O4, when they placed it in the hot water bath, it turned brown because it was shifting toward the brown NO2, and when they placed it in the ice water bath, it was shifting toward the colorless N2O4. So when they raise the temperature, the value of K decreases, indicating a shift toward the left. That confirms that we have an exothermic reaction as written. All right, I want to talk about particle diagrams one more time, just briefly. I found this question on AP Classroom, and I thought it was very relevant to today's lesson. Now you can see we have 3 different chemicals in the box on the left. We have PCl5, which looks like this. We have some PCl3, which looks like this, and we have some Cl2. Now if you count, you're going to notice that we have exactly 3 of each kind of molecule in the box in this very simple particle diagram. What they have done is they've done a volume change. We still have a total of 9 molecules in the box, but the pressure has gone up. So in which direction are we going to shift the equilibrium? So immediately after the volume change, there's an increase in pressure. Remember that you have to alleviate that stress by shifting toward the side of the reaction that has fewer moles of gas. So if you were asked to draw the particle diagram, once equilibrium has been established, you would need to have not just 3 molecules of PCl5, but at least 1 more. And that's what I've done here. I could have drawn 2 more, but I was kind of getting crowded in this little box, so I have drawn an extra PCl5. Now because the reaction has shifted toward the right, there should be 1 fewer molecule of PCl3 and Cl2, and that's what I've done. So instead of drawing 3 molecules of PCl3, I have drawn only 2, and instead of drawing 3 molecules of Cl2, I've drawn only 2. So the total number of molecules is actually less. Instead of 9 molecules, we now have 8. And again, that was intended to show that there's been a shift toward the side of the equation with fewer moles of gas as a way of alleviating that stress of the increased pressure. All right, so we have talked about Rice tables, calculating equilibrium concentrations. We talked about the reaction quotient Q, Le Châtelier's principle involving changes in concentration, pressure, and temperature, and again, a good look at a variety of particle diagrams today. So for your homework, again, we're still talking about equilibrium tomorrow, but for your homework, I have picked some equilibrium questions that are relevant to today's lesson. So this is the first screenshot. If you want to pause the video, you can do that. We're talking about equilibrium between calcium carbonate and calcium oxide and carbon dioxide, and there is data given to you. And we're going to be answering parts A, B, C, and D. So again, if you want to pause the video or take a screenshot. And then I have a second AP practice question for you, also dealing with equilibrium. And this is the entire question. It was one of the short pre-response questions from an AP exam. So parts A and B, and that's it. All right, so tomorrow we'll go over the answers to these questions, and we'll wrap up our discussion of Unit 7, equilibrium. So remember that there are helpful chemistry resources in the link in the video description. Again, this has been Michael Faribault from Albemarle High School in Charlottesville, Virginia. Remember that the deadline is this Friday, April 24th. So again, they are working. The College Board is working on solutions to help students get what they need to show their best work on these online AP exams. So if you need mobile tools or connectivity, or know someone who does, go to cb.org/tech. All right, well, thank you very much for watching. Have a good day. Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. The topic of today's lesson, we are still in Unit 7, but this will be the end of Unit 7, so we'll talk about solubility equilibria today. I just want to remind you that if you haven't visited apstudents.org/exams2020, that is a good website to check out information about taking AP exams. And specifically, the AP Chemistry exam, the date on May 14th, you can see that there are a variety of different times. So depending on where you live, at the time at which you'll be taking the AP Chemistry exam. So again, more information coming from the College Board about the specifics, but you can tell for chemistry, there'll be 2 pre-response questions. Again, there's a lot more information on the apstudents.org/exams2020. Hopefully you have access to a periodic table and some scratch paper and something to write with. In today's lesson, we will wrap up Unit 7, and we're focusing on solubility equilibria. And so in today's lesson, I will talk about solubility and KSP, which is the solubility product equilibrium constant. We'll talk about the common ion effect and how solubility is related to pH, as well as how can we use a comparison of Q versus K for KSP to predict if a precipitate will form. Our warm-up problem is the AP problem that I had assigned for homework from yesterday's class. So we have a equilibrium situation, which you can tell up at the top here. You can see the double arrows. So this is our equilibrium system, and we have calcium carbonate. When heated, decomposes according to the equation shown above. In a study of the decomposition of calcium carbonate, a student added a 50-gram sample of powdered calcium carbonate, CaCO3, to a 1-liter rigid container. The student sealed the container, pumped out all of the gases, and then heated the container in an oven at 1100 Kelvin. So the total pressure that we're looking at is the pressure of the CO2 that's being formed. And it looks like right about here, somewhere between 10 and 15 minutes, that would be when equilibrium has been achieved. Because at that point, the pressure, not the concentration because we're measuring pressure here, but the amount of CO2 did not continue to increase, but rather level off and remain constant over time. So for this particular reaction, the decomposition of calcium carbonate, we have CaCO3 on the left, and then calcium oxide, CaO, and carbon dioxide on the right. So part A of this question, calculate the number of moles of CO2 present in the container after 20 minutes of heating. So we'll go back to our given information. So we have a volume, we have a temperature, and we have this number here, which is grams, but it would be a mistake to convert this from grams to moles because we have to go with the data, and the data indicates that we have a pressure of 1.04 atmospheres. So if equilibrium has been achieved, then it's possible that not all of this 50-gram sample was actually converted completely into CO2. And in fact, in a second trial, they used 100 grams of calcium carbonate, but they got the same final pressure, again, that 1.04 atmospheres, which is going to be the pressure of the CO2 as it leveled off. So if I've got a pressure and a volume and a temperature, then I'm going to calculate moles by using the ideal gas law. So we have rearranging this equation, N equals PD over RT. So on the equations and constant sheet, you can find the value of R, the ideal gas constant, which if we use atmospheres would be 0.08206. They gave us a pressure of 1.04 atmospheres in this problem. We have a 1-liter container and 1100 Kelvin. So we're all set up to calculate the number of moles of CO2 in the container. So I'm going to go ahead and round this off to 2 significant figures based on the 1100 for the temperature. So I'll call this 0.012 moles of CO2. Okay, so that was part A, to calculate the number of moles using the ideal gas law. On to part B. Now the student claimed that the reason why the final pressure in the container became constant is because all of the calcium carbonate had decomposed. Well, I'm pretty set up to disagree with this claim, but let's talk about what's going on here. Okay, so we had initially 50 grams. Now you can look on the periodic table and you can find the molar mass of calcium carbonate. So calcium's about 40, carbon's about 12, and oxygen 16. So we have about 100.09 if you use all the decimal places for the atomic masses for these elements. And then of course there is only 1 mole based on the balanced chemical equation, 1 mole of CO2 for every 1 mole of calcium carbonate. Now notice that in part A we had 0.012 moles of carbon dioxide, and that was after the pressure had leveled off for several minutes. So this is a good reason to disagree with this claim, because if all of the calcium carbonate had decomposed, then the reaction would have gone to completion and you would have produced 0.5 moles of CO2. So I disagree with the claim because we only have 0.012 moles of carbon dioxide in the container. Therefore, if all of the calcium carbonate had decomposed, as the student had claimed, then the number of moles of CO2 would have been higher. This suggests that, in fact, equilibrium was achieved, and that's why only some, but not all, of the calcium carbonate was converted into CO2. Another way you could have disagreed with this claim is based on the fact that in trial 1, they used 50 grams, and in trial 2, they used 100 grams, and yet they got the same final amount, the same final pressure. So if all of the calcium carbonate had decomposed, then we would have expected twice the amount of CO2 if we used twice the amount of calcium carbonate. But since we got the same pressure in both experiments, that suggests that the calcium carbonate is not being used up completely. So here are the official scoring guidelines. Again, there's two explanations. One, you can actually calculate the number of moles of carbon dioxide that would have been produced if the reaction had gone to completion and compare that with the actual amount from part A and say, no, that's less. Or you could have said that doubling the amount of the reactant did not lead to a double in the amount of product. Therefore, this reaction did not go to completion. There must have been an equilibrium achieved. All right, part C of this question says after 20 minutes, some CO2 was injected in the container. So this reminds you, hopefully, of the comment that I made yesterday about, see if I can spell his name right. So Le Châtelier's principle. Okay, Le Châtelier's principle has to do with what happens when we make a change. So if we somehow add more CO2 to this equilibrium, that should cause Q to become larger than K, and then a shift in the equilibrium position that go toward the left. So it says after 20 minutes, some CO2 was injected, raising the pressure to 1.5 atmospheres. With the final pressure in the container, assuming it would reestablish equilibrium, would it be less than, greater than, or equal to 1.04 atmospheres? So we got 1.04 atmospheres in two different trials using two different amounts of calcium carbonate. So it seems like the equilibrium pressure should still be 1.04 atmospheres. Assuming that temperature remains constant, equilibrium was reached in both experiments. Therefore, the equilibrium pressure of CO2 at this temperature should be 1.04 atmospheres. Now, after the addition of additional CO2 raising the pressure to 1.5, then there would be a shift toward the left, toward the reactants, and equilibrium would be reestablished with a final pressure of exactly 1.04 atmospheres. Again, all right, on to part D of this question. Do we have sufficient data from the information in this question to answer the value? What is the value of Kp? Now, normally an equilibrium constant is products over reactants. So take a moment and look at what I've written here. I've got products, so calcium oxide and carbon dioxide over calcium carbonate. Do you see anything wrong with my Kp expression? Well, if you look closely at the phases of matter, and just kind of use common sense here, you're not going to have the pressure for a solid. In fact, we never, in a heterogeneous equilibrium involving different phases, we never include pure liquids or pure solids in equilibrium expression. So our Kp is reduced to one term, and we already know that the pressure of the CO2 in each of these trials is 1.04. So yes, there are sufficient data to determine the value of Kp. All we really needed was that one measurement of 1.04, and that was obtained in both experiments. So we now have our value of Kp. All right, I gave you another AP practice problem, and I like this question a lot because there's something that students will do. I'm going to show you kind of the wrong way to do it and the right way to do it, but there's something that students will do with an equilibrium problem. So what I think should jump out at you when you look at this question right here, and I'm going to call your attention to something that was mentioned earlier in our discussion of equilibrium, and this is in topic 7, specifically topic 7.5 in the AP Chemistry course and exam description, the magnitude of the equilibrium constant. So some equilibrium reactions have very large values of K and then proceed essentially to completion. Other equilibrium reactions have very small values of K and barely proceed at all. So you may recall in an earlier lesson talking about acids and bases, and you can find information on the AP equations and constant sheet about what's called the KW. This K is extremely small, so 10 to the negative 14. So the predominant form in a sample of pure water is water molecules. So pure water does not conduct electricity. Now a student might think, well, wait a minute, aren't these ions present in solution? Not very much. If the fact that K is extremely small tells us that water is mostly just water molecules and very, very, very small amounts of these ions, pure water does not conduct electricity. Now on the other side, if I flip that equation around and put H3O plus, which is the sign of a strong acid, the hydronium ion, and then the hydroxide ion, which is the sign of a strong base, if I reverse a reaction, then you have the inverse of K. Well, what's the inverse of 10 to the negative 14? 10 to the positive 14. That reaction essentially goes to completion. Look at the large magnitude of that K. So when you have a strong acid and a strong base, they completely neutralize each other. So going back to this large value of K, this is going to show up in our discussion. So pay attention to that large magnitude that's coming up. Okay, and it even says this in the stem of the question in part A. Considering the value of K for the reaction, determine the concentration of the product. In this case, we're talking about this chemical formula Ba, that's barium, and then this ion, this polyatomic ion, which is abbreviated EDTA. So what's the concentration of this in 100 mils of solution? Let's go ahead and focus on the information that was given to us in the problem. We have 50 milliliters of a solution that contains EDTA at a concentration of 0.3 moles per liter. We have 50 milliliters of a solution that contains barium nitrate, and we're kind of focusing on the barium ions here and not the nitrate ions. So 50 plus 50 is 100. What is the concentration of the barium EDTA complex ion in 100 milliliters of the solution? I'm going to do some mole calculations to get started. I'm going to figure out the moles of barium. So volume times molarity equals moles, as long as I can get my units to cancel out. So I've written 1,000 milliliters on the bottom instead of 1 liter, but they mean the same thing. So when I cross off the units, I get moles of barium nitrate, which is the same as moles of barium. So do this math. We get 0.05 times 0.2, 0.01 moles of barium. I can do a similar calculation, volume times molarity for the other solution, which had a concentration of 0.3 moles per liter. So I've got moles of barium and moles of EDTA. Here I'm going to go down the wrong path, just to show you what some students did in solving this question on the AP exam. So what they did was they set up a rice table. So again, we are ignoring the large magnitude of K for the moment and doing a traditional rice table. I already calculated the moles of barium and the moles of EDTA. I'm going to go ahead and just keep this rice table in terms of moles as opposed to changing to concentration. Now the barium has to go down by a certain amount, X. EDTA has to go down by a certain amount, X. And again, that's a 1-to-1 mole ratio. So therefore the product has to go up by X. All right. So what students did is they set up the equilibrium expression. Now, if you're good at math, then you are going to follow me perfectly on this next slide. If you're struggling with math, you might find this is a little bit challenging. But what I'm trying to say in terms of the message is that this is not the required way to solve this. I'm actually showing you the wrong way to do it because I want to kind of take this wrong path, follow it to completion, and then we'll talk about why that was unnecessary. So we're going to go ahead and just do the math. Multiply both sides by the denominator. Looks like I have to FOIL because I've got two expressions there. So 0.01 minus X, 0.015 minus X multiplied. Okay, now I have to distribute that big number, that 7.7 times 10 to the 7. Oh my goodness. You may recall that I said in yesterday's lesson that the AP Chemistry exam is not going to require you to use the quadratic equation. I went ahead and did a quadratic solver with my A, B, and C from this ugly equation. And when I solve for X, this is what I got. Essentially, I got 0.01. So the message here is that you did not have to do that math. The value of K is very large, and as was mentioned in the course and exam description, you can assume that reactions with a rather large, I would say, around 1,000 or higher, value of K essentially goes to completion. So therefore, if X is equal to 0.01, essentially, this is a limiting reactant problem. You're going to run out of barium before you run out of EDTA because 0.01 is less than 0.015. So the reaction essentially goes to completion, producing 0.01 moles of the product. Okay, so barium is a limiting reactant, and so there's a 1-to-1 mole ratio between reactant and product. So the limiting reactant determines how much you produce. Now, the answer to this question, which we haven't gotten yet, is what is the concentration of barium EDTA complex, the product, in solution? And it was 100 milliliters or 0.1 liters. So our answer, 0.01 divided by 0.1 is 0.1. Now, watch how simple the official scoring guidelines look on this question. So it says based on the K value, the reaction that goes essentially to completion, and barium 2+ is a limiting reactant. So when you go from 50 plus 50 to 100, 100, you're essentially doubling the volume. And when you double the volume of a chemical, you cut the concentration in half. So 0.2 becomes 0.1. And so effectively, if the concentration of barium ions in solution is 0.1, then the concentration of the product, the barium EDTA complex ion, is also 0.1. So that was a much easier way to solve that question. But again, many students ignored the large magnitude of K and tried to use a Rice table. Whether they were successful or not, that was kind of a waste of time. Okay, there was another part of this question which will get us back to Le Chatelier's principle. Remember that in Le Chatelier's principle, a system that is at equilibrium experiences external stress and then will respond to that stress. Now, what is the stress? They added water. So by adding water, they went from 100 milliliters of solution to 1,000 milliliters of solution. So each concentration, the barium, the EDTA, and the complex ion, has been diluted by a factor of 10, going from 100 to 1,000. So here's our K expression. But now we have Q, and each of those concentrations has been diluted, reduced by a factor of 10. Well, there's a 1/10 on the top and on the bottom, so that will sort of divide out, cross out. But I still have an extra 1/10 on the bottom, which when I flip that, because it's on the bottom, it becomes 10. So effectively, my Q is equal to 10 times the value of K. So what did the dilution do? The dilution with water causes the concentration of each substance to decrease. And then as a result, Q becomes larger than K. And when Q becomes larger than K, equilibrium will shift in this direction. So the question is asking, after this equilibrium has been reestablished, is the number of moles of barium greater than, less than, or equal to the number of moles of barium that was present before the dilution? But because we are shifting as a result of Q becoming greater than K, we're shifting toward the reactants, toward the left, then the barium will be greater. Now I'm going to make a comparison to another example of Le Chatelier's principle, and that is gases. Here we have 2 moles of gas on the left and 1 mole of gas on the right. So a different number of moles of gas on each side. Suppose that we take our container, which contains these gases at equilibrium, and we increase the volume of the container. As a result, the pressure will go down, and the system will shift toward the side of the equation with a greater number of moles of gas as a way of counteracting this decrease in pressure. Well, there's a completely analogous system with aqueous species. While these aren't gases, by adding water, we've effectively increased the volume of the solution, and we caused not the pressure, but the concentration of each of these species to go down. So instead of shifting to the side which has a greater number of moles of gas, we're still going to shift to the side of the equation that has a greater number of moles of aqueous particles to counteract this decrease in concentration. So it's completely analogous to the situation that happens with gases. All right, so your official scoring guidelines say that the number of moles of barium increases, and you could have said because when you dilute a solution, that's going to increase the percent dissociation of the substance, in this case shifting toward the left. But another way to justify this is a Q versus K. It's a great argument that you can plug in those numbers, the 1/10 dilution, prove mathematically that Q becomes larger than K, and that will produce more reactants as equilibrium is reestablished. All right, so we're going to talk today about solubility and KSP. What you're looking at right now is a substance that is not very soluble in water. Now, I didn't say insoluble, I said not very. So we have to make a distinction between insoluble and very slightly soluble to talk about KSP. Suppose we have a beaker of pure water and a sample of solid is added to the beaker. The solution is stirred for several minutes, and then the solution is left undisturbed for several minutes. And now the solution looks like this. Now, some might classify that there's a white solid on the bottom of the beaker, indicating that this solid did not dissolve at all. Let's look a little closer and see what is actually happening at the particle level. Is this solid dissolving? Well, here we're looking at a close-up view of the crystal lattice. So these are all of the ions here. So this is the solid. And as you can see that we have some aqueous ions surrounded by water molecules. So we're getting both dissolution and we're also getting precipitation or crystallization is happening. So both the dissolution and the precipitation are happening at the same rate. That sounds a lot like equilibrium. So you're going to have a solid that is dissolving, but maybe not very much. So are you suggesting that the value of K for these types of solids is large or small? So think about that. Think about the value of K. Now we're going to have barium sulfate, which breaks up into barium and sulfate, magnesium hydroxide, which because there is a subscript 2 outside the hydroxide breaks up into 2 hydroxide ions along with 1 magnesium. Notice I'm putting the charge on the ions. Calcium fluoride breaks up into 1 calcium ion and 2 fluoride ions. And silver carbonate breaks up into 2 silver ions and 1 carbonate ion. Now if I were to write, let's say, barium sulfate and write the K, and again, not paying attention to phases of matter, I might think that's going to be concentration of barium times the concentration of sulfate divided by the concentration of barium sulfate. But if I pay close attention to the phase of matter here, remember, pure solids and pure liquids are not included in equilibrium expressions. You can't have the molarity of a solid, or again, a pure liquid. We're going to call this KSP, where SP stands for solubility product. So there is no denominator in these expressions. Now there's a coefficient of 2. I'm going to write an exponent. So I have that little superscript there. So these are the KSP, the equilibrium constants, the solubility product constant for these solids. Now is K rather large or small? Let's go ahead and look at some examples. I've got silver chloride, silver bromide, and silver iodide. Take a look at the magnitude of those KSP values. Okay, it's very small, indicating that these are practically insoluble. I say practically because they are slightly soluble. Now, solubility is not listed in this table because we are going to calculate that. But suppose you didn't have a calculator and this question were asked, which substance, silver chloride, silver bromide, or silver iodide, has the greatest solubility? If you didn't have a calculator and all you had was the KSP values, well, I would assume that the larger the KSP value, the larger the solubility would be. And that is a good assumption to make based on this comparison of very similar compounds with similar formulas. They have a 1-to-1 ratio between cations and anions. So I would assume that silver chloride is the most soluble without doing any math. Now, how would you do that math? Because again, solubility and KSP are related to each other, but they are not the same thing. So please don't say that the solubility of silver chloride is 1.8 times 10 to the negative 10 because that's not true. All right, I've written the expression for silver chloride dissociating into silver ions and chloride ions, and I've written the KSP expression. What I'm going to do is recognize there's a 1-to-1 mole ratio between the silver chloride itself and the silver ion. So the concentration of silver or chloride, use either one, is the same as the solubility. So if I can figure out the number of moles per liter for silver, then that is the solubility of the entire compound in terms of moles per liter. So how do I do that? I'm going to go ahead and write the KSP expression. I know what the value is. It was given to me in the table. And I'm going to call each of these concentrations, because they are the same, it's a 1-to-1 mole ratio, X. I mean, you could call it S for solubility. Some textbooks do that. I'm just going to go ahead and call this X. And when I solve for X, I'm essentially just taking the square root of the KSP. And when I do that math, I get 1.3 times 10 to the minus 5, and that's moles per liter. That is the solubility of silver chloride in water at that particular temperature. It's usually a standard temperature of 25 degrees Celsius or 298 Kelvin. If I take the square root of the silver bromide KSP, I'm going to get a smaller value. If I take the square root of the silver iodide KSP, I'm going to get a smaller value. So without doing any math, I could have predicted which one was the highest solubility, but if I had to actually calculate it, it was a simple square root of the KSP. So again, the concentration of the silver happens to be the same as the solubility of the entire compound. Here's a different chloride. This is not silver chloride, but lead chloride. Notice that the formula of lead is not PbCl, but rather PbCl2. So it's a slightly different KSP expression with the exponent chloride squared. So which ion, in your opinion, the lead or the chloride, would have the same value as the solubility of the entire lead chloride compound? Hopefully you can recognize we are looking for a 1-to-1 mole ratio between the formula of the solid and the ion. So it's going to be the lead, not the chlorine, that would tell us the concentration is going to be the solubility. There's a slightly different way of solving this problem, and that's because we cannot say it's X and X. For every 1 mole of lead that is produced in this dissolution, you get twice as much. For the concentration of chloride, it has to be twice as much. So now when I plug X and 2X into my KSP expression, and by the way, the KSP for lead chloride happens to be 1.7 times 10 to the negative 5, I am not going to simply take the square root of 1.7 times 10 to the negative 5 because the math works out a little bit differently. So while we have to take the concentration of chloride and square it according to the equilibrium expression, inside the brackets represents the concentration. Again, it's not X and X, but rather X and 2X. Some students struggle with this because they say, why are you doubling it and squaring it? The doubling it has to do with moles and mole ratio and stoichiometry, but the squaring, that's a separate event which is related to kinetics and rate laws laws and the equilibrium constant expression, those are two separate things, and they are not being done at the same time, and therefore we should somehow cancel one and only do one and not the other. These are two separate things that both are required for this expression to be true. So what goes inside the brackets is x and 2x, but when you do 2x quantity squared, that's 4x squared times x. This is what you get. Now, if I want to solve for x, which is going to be the concentration of lead and therefore the solubility of this compound, I have to take the KSP, divide by 4, and then take the cube root of that. So when I do that, I get 0.016, which represents the concentration of lead as well as the solubility of the lead chloride. So what's the concentration of the chloride ion in this saturated solution of lead chloride? It should be twice as much, so it should be 0.032. So for a saturated solution of lead chloride, we have these concentrations, and the solubility of the lead chloride would be 0.016 because that's the 1-to-1 mole ratio between the formula and the lead. Now, I'm going to ask you a question. It's a little bit different than the silver chloride, silver bromide, silver iodide comparison I gave you earlier. And here's the question. Which of these two substances has the greater solubility? Now, it's not really fair for a teacher to ask a trick question, but this is completely a trick question. Here's why. We had an earlier comparison, silver chloride, silver bromide, and silver iodide. They were all a 1-to-1 ratio between the cation and the anion. Here we have manganese and carbonate, and we have manganese and hydroxide. So that's a 1-to-2 comparison versus a 1-to-1 comparison. So that's not a good or fair comparison. Therefore, this is potentially a trick question. So I'm going to go ahead and solve, and this might surprise you and kind of confirm why it's a trick question, because you might think that the higher the KSP, therefore this would lead to a higher solubility for the manganese carbonate. But again, we're going to have to deal with an x squared versus a 4x cubed. So we're going to get a different solution here. When I take the square root of the KSP from manganese carbonate, I get 4.8 times 10 to the negative 6. But I am not doing a simple square root for the KSP of manganese hydroxide. In fact, I have to do what I did before for the lead chloride. Because of the x and the 2x and the 4x cubed that I get, I have to take the KSP, divide by 4, and take the cube root. So look at that. It turns out that the solubility of the manganese hydroxide is actually greater. This would not be an easy question to answer without doing the math. Therefore, I think that the important point I want to make is pay attention to how you set up your KSP problems. All right, moving along to another situation where we can calculate. I have barium sulfate and magnesium hydroxide. We're going to calculate the molarity and also the grams per liter. So if you have your periodic table handy, it might be a good idea to calculate the molar mass of both barium sulfate, BaSO4, and magnesium hydroxide, Mg parentheses OH2, because you'll need a molar mass to go from moles to grams. All right, so I have my barium sulfate, x and x, 1-to-1 mole ratio. Square root of the KSP gives me 1 times 10 to the negative 5. That's my solubility in terms of moles per liter. How do I take that 1 times 10 to the negative 5 and convert that into grams? Well, as I said, you have to calculate the molar mass of barium sulfate. And if we do that, the moles cancel out, and I now have grams per liter. Again, this is not insoluble, but slightly soluble. So about 2.3 milligrams of barium sulfate per liter at room temperature. All right, we'll do a similar calculation for the magnesium hydroxide. Again, watch out for how you set this up because it's not going to be a simple square root. It's going to be that 4x cubed that I talked about. It's a 1-to-2 mole ratio. So we end up with 1.1 times 10 to the negative 4 for our solubility. That is the concentration of magnesium, and that is the solubility of the magnesium hydroxide. I'm just going to go ahead and add parentheses. Oops, forgot my formula didn't have parentheses on that. All right, let's take our 1.1 times 10 to the negative 4 and convert that into grams per liter. So the molar mass of magnesium hydroxide is determined by looking at the periodic table. And now again, we're just confirming how small that solubility is. So about 6.4 milligrams of magnesium hydroxide for every 1 liter. If we've gone from KSP to solubility, we should be able to go the other way around. So now I'm going to give you the solubility of two different compounds. This is calcium fluoride, CaF2, and silver carbonate, Ag2CO3. Can we go from grams per liter to KSP? All right, let's again get our periodic table so we can figure out the molar mass of CaF2. So the molar mass of CaF2 is calculated, and this will take me from grams per liter to moles per liter. Now, does the 1.1 times 10 to the negative 3 moles per liter, does that refer to the concentration of the calcium ion, or does that 1.1 times 10 to the negative 3 moles per liter, is that the concentration of the fluoride ion? Think about that. Hopefully you can see based on the 1-to-1 mole ratio that the concentration of calcium is in fact the solubility of the entire compound. So the concentration of fluoride is not 1.1, but rather 2.2 times 10 to the negative 3. If I plug in those values into the KSP expression, I will get the value of KSP. We're expecting a pretty small number here, and sure enough, KSP for calcium fluoride works out to be 5.3 times 10 to the negative 9. All right, we'll do this again for the silver carbonate. We're going to start with grams, and again, we have to use the molar mass of silver carbonate. So the molar mass of silver carbonate allows us to go from grams to moles. Is this number that we get 1.3 times 10 to the negative 4? Is that the concentration of the silver or the concentration of the carbonate? So remember, you're looking for that 1-to-1 mole ratio between the compound itself and the aqueous ion. So that number, 1.3 times 10 to the negative 4, that is the concentration of the carbonate, which means that the concentration of silver should be not 1.3, but 2.6 times 10 to the negative 4. So plug in those values into the KSP expression. Again, we're expecting a pretty small number for KSP, and sure enough, 8.8 times 10 to the negative 12. So we have successfully done calculations using KSP to go to solubility and solubility to go to KSP. Hopefully you have a better understanding of those calculations. I now want to talk about a concept known as the common ion effect. And this has to do with Châtelier's principle. Now, the solubility of barium sulfate in pure water is 1.0 times 10 to the negative 5. So if I take barium sulfate and dissolve it in this solution, which already has some sulfate ions in it, then my question to you is, what is the molarity going to be? So if a sample of barium sulfate is dissolved in a solution that already contains 0.0015 molar sodium sulfate, do you predict that the solubility of barium sulfate in that solution on the right is going to be less than, greater than, or equal to 1.0 times 10 to the negative 5? So again, think about the Châtelier's principle. If we already have this additional amount of sulfate ions, that is going to affect the equilibrium. So with additional sulfate added to the equilibrium, we are going to predict a shift from right to left. And therefore, if we shift toward the solid, that will decrease the solubility of the barium sulfate in a solution that already contains sulfate ions. So let me go ahead and define for you. The common ion effect essentially says the following: that the solubility of an ionic solid is going to be less, it's going to be reduced when it is dissolved in a solution that already contains a common ion, as in one of the ions present in the solid. So if there is already barium, or if there is already sulfate in a solution, and then we try to dissolve some barium sulfate in that solution, we should have a lower solubility than it would be in pure water. So if you go ahead and do this, I'm going to write my KSP expression, but I'm not going to write x and x. What I'm going to do instead is put the concentration of sulfate that we already know, which is 0.015, into my KSP expression. That's going to cause the barium to be much less than it would normally be if I was just doing x and x. So as you can see, comparing the solubility in pure water with the solubility in a solution that already contains a certain amount of sulfate, it is less. When there's already sulfate, that shifts the equilibrium toward the left, making it less soluble. All right, I'm going to go ahead and extend this to pH a little bit. So what I now have is a situation 5 moles per liter, but now in a solution that already has sulfate ions, the concentration of the barium sulfate is less because of the shift according to the Châtelier's principle. All right, so I have pH of 12.0. Now that is a rather high pH, indicating that we have some hydroxide ions. So if there's additional hydroxide ions coming from a solution, then what's going on here is a shift toward the left. Our prediction is that the magnesium hydroxide should be less soluble in a solution that already contains a certain amount of hydroxide ions in it. So we're going to compare the value we get in the flask on the right with the value we would have gotten in pure water. You may have forgotten pH. I'll just remind you that pH plus pOH equals 14. And since the pH is 12, the pH would be 2 because 14 minus 12 is 2. Now 10 to the minus 2 would be the concentration of hydroxide. So that's how you go from pOH COH to concentration of hydroxide. And if I plug in 1 times 10 to the minus 2 into my KSP expression and I solve for the concentration of magnesium, again, we're going to see if it's going to be less than 1.1 times 10 to the negative 4, which is what it was in pure water. And sure enough, it is much less. So again, the common ion effect. The solubility of an ionic solid is reduced when it's dissolved in a solution that already contains a common ion. All right, so this is kind of related, solubility and pH. I have 2 acids, HCl and HF. Now, which one of these acids is strong and which one of these acids is weak? You may remember that HCl is on your list of 6 strong acids. That means that HF, which is not on your list of strong acids, is actually a weak acid. So therefore, the majority of the HF exist as molecules, not in the form of H plus and F minus ions. So now instead of making the solubility less, we're going to show you examples of making the solubility actually greater. So the solubility of calcium fluoride is actually greater in a solution of HCl than it is in pure water. So you don't see H plus or Cl minus in this equilibrium expression. So you might wonder, what effect would H plus and Cl minus have on this equilibrium? So if I have HCl, I've got a lot of H plus ions and Cl minus ions. Focus your attention on the fluoride for a moment. I mentioned that HF was a weak acid, and you can tell it's a weak acid because look at that value of Ka. It's rather small. What would happen if I reverse this equation? 1 over the Ka would be 1 divided by 6.8 times 10 to the negative 4, and look how large that K is. Remember how small Ks emphasize the formation of the reactants, whereas large Ks indicate the formation of the products. So any H plus ions that are present are going to react with F minus ions, essentially going to completion, and that's going to cause the concentration of F minus to decrease. Now, according to the Châtelier's principle, when you remove a product, then the equilibrium will shift toward the right, and that makes calcium fluoride even more soluble in an acidic solution like HCl than it would be in pure water. So to summarize, for solubility and pH, something like calcium fluoride, this reaction between the fluoride ion, which acts as a weak base, and the H plus ions or the hydronium ions from the acid causes the fluoride concentration to go down. Solubility increases as equilibrium shifts toward the right. Okay, here's another example. This is calcium fluoride. This is silver carbonate. It is observed that silver carbonate is more soluble in an acid solution like nitric acid than in pure water. So it's the carbonate. Okay, last time it was the fluoride. It's the carbonate that is reacting with H plus, producing initially carbonic acid, but that rapidly decomposes to give you water and CO2. This is like the classic vinegar baking soda reaction to produce bubbles. Okay, so that is going to cause the carbonate to go down, shifting the equilibrium toward the right, making silver carbonate even more soluble in an acid than in pure water. Okay, how about magnesium hydroxide? You find this in milk of magnesia. It's kind of a chalky solution, but it actually dissolves even more in an acid solution than in pure water. So if you add acid to something that looks chalky like magnesium hydroxide, it actually becomes even more soluble. So it's this negative ion, in this case the hydroxide, reacting with H plus to produce water. This causes the concentration of hydroxide to go down as it's reacting with the H plus ions, and when hydroxide decreases, we shift the equilibrium toward the right, making it more soluble. So with respect to solubility and pH, I'd like you to focus on the anion. So if the negative ion is hydroxide, fluoride, sulfide, carbonate, phosphate, these are all examples of bases, then what they will do is they will react with the H plus ions, and then that will cause the value of the concentration of that negative ion to decrease. The solubility will then shift toward the right because of the equilibrium shift. The ionic solid becomes even more soluble in an acid solution. All right, I'm going to talk about Q versus KSP, and then I will get to your homework problem. All right, here we have 2 flasks that are mixed together, and the 2 chemicals that we're mixing together here are barium nitrate, which contains barium ions, and sodium fluoride, which contains fluoride ions. So are we going to make a solid precipitate? It depends. It depends on Q versus KSP. We're going to predict if a precipitate will form. So when you combine 100 milliliters of barium nitrate with 100 milliliters of something else, that is a 2-fold dilution. So the final volume is now 200 milliliters. That's going to cause our barium concentration to be reduced by half. So now we have half of that number, which is 6 times 10 to the negative 4. Now for the sodium fluoride, we're also cutting that concentration in half. So our concentration of fluoride in this final solution is 1.6 times 10 to the negative 3. Now that we have our concentration of barium and fluorine in this final solution, we still don't know whether a precipitate would form or not. We have to do a Q versus K comparison. Let's plug in these values for the concentration of barium and fluoride into the KSP expression and see what happens. Now if the Q is greater than the KSP, then we have exceeded the solubility and we're definitely going to get a precipitate. If the Q is less than the KSP, then we have not reached the saturation point yet and no precipitate would form. So we have barium. Again, watch out for the fact that it's squared. Okay, so that's going to be barium times fluoride squared. We do that math and we get a number which is 1.5 times 10 to the negative 9. Now that is less than the KSP, so therefore no precipitate forms. All right, another example. This is lead nitrate, obviously contains lead ions, mixing with potassium iodide. So are we going to form lead iodide? Same kind of calculations as before. We're going to go from 100 and 100 to 200. So we cut our concentration of each ion in half. So the lead is actually half of 4.8 times 10 to the negative 3, and then the iodide is also half of 6.4 times 10 to the negative 2. So we've done that math. Let's plug in these numbers for the concentration of lead and the concentration of iodide into the KSP expression. That's lead times the iodide squared, and it looks like 2.5 times 10 to the negative 6 is our numerical answer, which is greater than the KSP. So yes, a precipitate does form. Now what if you have a solution that contains more than one ion? Here we have some silver and some lead. We're given the KSPs for each one, and we're going to add a sample of sulfate, potassium sulfate. Will a precipitate occur? There's our Q for silver, and they told us that the concentration of silver was 0.2. So there's my concentration of silver. This was the number of moles, but it was actually a 1 liter container, so that is also the molarity. So that is our concentration of sulfate. All right, let's see if we get a value for Q. All right, we'll come back to that in a moment. Let's do the same for the lead. They gave us a concentration of lead, which is 0.001, and that's also coincidentally the amount of sulfate that we have per liter. All right, let's compare it to our KSP. Well, for the silver sulfate, 4 times 10 to the negative 7 is less than the KSP, so no precipitate forms. And for the other one, the 1 times 10 to the negative 6 is greater than the KSP. So a precipitate of lead iodide would, lead sulfate would form, but a precipitate of silver sulfate would not form. All right, well, thank you for hanging in there. We talked about solubility and KSP and the common ion effect and the effect of pH on solubility, as well as Q versus KSP. So here is your AP exam practice homework problem, which I will go over in tomorrow's lesson. So take a screenshot of that. There's part A with Roman numerals I, and I. And we also have parts B and C and all the subparts there. All right, reminder to check out the link in the video description for helpful chemistry resources. Again, this has been Michael Fairbaugh from Albemarle High School in Charlottesville, Virginia. Tomorrow is the deadline. If you need mobile tools or connectivity or know someone who does, go to cb.org/tech. Let us know by tomorrow, Friday, April 24th. All right, thank you very much for watching. Have a good day. Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Fairbaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, the topic of today's lesson falls under Unit 9. Now, either we've talked about this before, you may remember this, but if not, I'll go ahead and give you the disclaimer that on the AP exam this year in 2020, it covers Units 1 through 7, but the College Board and colleges have decided that there are certain topics in Unit 8 and Unit 9 that are still worthy of study and focus, especially as you prepare for your next course in chemistry in college. So I will focus today on topics that are very important in chemistry, but will not be covered on this year's AP Chemistry exam. A reminder to students to go to apstudents.org/exams2020 to get more information about the format of the AP exam. For chemistry, the AP exam date is May 14th, and there's information here on the screen about the different time zones in which you'll be taking the AP exam, depending on where you live in the world. And there are 2 free response questions on the online AP Chemistry exam this year. So let's get into our lesson for today. Hopefully have access to a periodic table, scratch paper, something right with. We'll talk about in Unit 9, entropy, Gibbs free energy, thermodynamic favorability, and the connection between free energy and equilibrium and dissolution. And you can see not only the topics here, but also the skills and science practices. So in our overview today, we'll talk about entropy, free energy, and thermodynamic favorability, and as free energy relates to equilibrium and dissolution. Our warm-up problem for today's lesson is the AP Chemistry practice exam question that I've given you in yesterday's lesson for homework. And so this question relates to solubility equilibria. So we have a saturated solution of magnesium fluoride, MgF2, and that was prepared by adding 0.50 grams of solid magnesium fluoride to 100 milliliters of distilled water. Now again, it's a saturated solution, so we have to assume that not all of the solid dissolves, and at the end, the saturated solution most likely has some solid magnesium fluoride that is on the bottom of the beaker. Now, when the saturated solution is analyzed, it is determined that the concentration of the fluoride ion in this saturated solution is 2.4 times 10 to the minus 3 moles per liter. All right, so Roman numeral 1 of this question, write the chemical equation for the dissolving of solid magnesium fluoride in water. So we have our solid magnesium fluoride, and it dissociates into magnesium ions and fluoride ions. So make sure that you balance your equation and that you include the charges on the ions. You don't necessarily have to include the phases of matter, in this case S for solid and AQ for aqueous, but I just did that just to be complete. Definitely make sure you have the correct symbols, charges, and that the equation is balanced. The next part of this question asks us to calculate the number of moles of magnesium fluoride that dissolves. So we are not going to take the 0.50 grams of solid magnesium fluoride and convert that to moles. We have to assume that not all of that solid actually dissolves. Now we are given a number, and that number is the molarity, so the concentration in terms of moles per liter of the fluoride ion. But remember that there is a 1 to 2 mole ratio between the number of moles of the magnesium fluoride and the number of moles of the fluoride ion. So we have to make sure to include that 1 to 2 ratio in our conversion factor. Otherwise, if we calculate the number of moles of the fluoride ion, that will not be the number of moles of the magnesium fluoride. It would be twice as much, so we'll have to cut that number in half. So we'll start with the 100 milliliters, which is the volume of the saturated solution. We're going to use molarity as a conversion factor. So I could write 2.4 times 10 to the minus 3 moles of fluoride over 1 liter. I've chosen to write 1,000 milliliters instead of 1 liter, but that's because I wanted to get the milliliters to cancel out. Now, the second step is to convert moles of fluoride into moles of magnesium fluoride. There's that 1 to 2 ratio I mentioned. And so if we do this math, we get 1.2 times 10 to the negative 4 moles of magnesium fluoride. So that is considerably less than the amount of moles of magnesium fluoride that was added. That's how much actually dissolved. Now, the next part of this question, they want us to calculate the value of the KSP. So the KSP would be the concentration of the magnesium times the concentration of the fluoride squared. So remember that the concentration of magnesium is not 2.4 times 10 to the minus 3, but rather half as much. If we plug in these numbers into our KSP expression, that's 1.2 times 10 to the minus 3 times 2.4 times 10 to the minus 3 squared. Then we get our value for the KSP, the solubility product constant for magnesium fluoride, 6.9 times 10 to the minus 9. All right, so we have a part B of this question. And now we're done with magnesium fluoride, and we're going to talk about some other fluoride salts from the alkaline earth metal family. We have calcium and barium. So a beaker contains 500 milliliters of a solution in which both calcium ions and barium ions are present in a concentration of 0.1 moles per liter. The student intends to separate the ions by adding 0.20 molar sodium fluoride, 1 drop at a time, from a burette. And they're giving us the KSP value for calcium fluoride and for barium fluoride. You can see that they are different. So calcium fluoride's KSP is 5 orders of magnitude smaller than barium fluoride. And that we can take advantage of that difference in KSP because it helps us understand that there's going to be a difference in solubility. Which salt will precipitate first essentially is asking the question, which salt is less soluble in water? And hopefully you remember from yesterday's lesson, the smaller the KSP, the lower the solubility. So the value for KSP for calcium fluoride is smaller than that of barium fluoride. So therefore calcium fluoride has a lower solubility, and calcium fluoride is the salt that should precipitate first. Well, that was just qualitative. Now we'll actually do a quantitative calculation. Calculate the minimum concentration of fluoride necessary to initiate the precipitation of the salt. So we have 0.1 molar concentration of calcium and barium. And this is our KSP expression for calcium fluoride. Let's plug in 0.1 molar for the concentration of the calcium and then solve for the concentration of fluoride. This will tell us the minimum concentration of fluoride necessary to initiate precipitation of the calcium fluoride. So we'll go ahead and multiply both sides by 10, essentially dividing by 0.1. So now we have F squared, the concentration of fluoride squared is 3.5 times 10 to the minus 10, and then we have to square root this answer, or square root the number to get our answer. So the concentration of fluoride is 1.9 times 10 to the minus 5 moles per liter. That is the concentration of fluoride needed for the first grains of solid crystal calcium fluoride to appear. So now that we know that number, calculate the minimum volume of the 0.2 molar sodium fluoride that must be added. And again, we're assuming that the amount of sodium fluoride is so small, it doesn't change the total volume. So we still have essentially a 500 milliliter volume of solution, and then the concentration 1.9 times 10 to the minus 5 moles of fluoride per 1 liter, or 1,000 mils. So this number, 9.5 times 10 to the minus 6 moles of fluoride, that needs to come from a solution that has a concentration of 0.2 moles per liter. We're going to use the sodium fluoride molarity as a conversion factor, but this time putting moles on the bottom and volume on the top. So how much sodium fluoride do we need? A very small amount. In fact, less than 1 milliliter. So what I did was I multiplied volume times molarity to get moles, and the molarity was from Roman numeral 2 in this problem. Then I did moles divided by molarity essentially to get volume. So in the official scoring guidelines, you'll see a slightly different approach to what I did, and they still get the same answer. So they did m times v equals m times v, since the moles are not changing. So 0.2 molar, which is the sodium fluoride, times some volume we don't know yet, equals the 1.9 times 10 to the minus 5 molarity, which is the concentration of the fluoride needed, and then times the volume of the solution, the 0.5 liters or 500 milliliters. So as you can see, they got 0.047 or 0.048 milliliters. All right, there was a part C of this homework question, and it says there are several ways to dissolve salts that have limited solubility. Describe one procedure to redissolve the precipitate. So one way to redissolve a slightly soluble salt is to add more water. Another way would be to heat it up, increase the temperature. Any valid statement that implies a shifting of the equilibrium toward the products. So they also mentioned adding acid. So the fact that calcium fluoride dissociates into calcium ions and fluoride ions. I talked about this in yesterday's lesson. It turns out that since fluoride is a weak base, adding H+, it will react with the fluoride, causing this concentration of fluoride to go down as it forms the molecular version of HF, the hydrofluoric acid. So as it decreases that concentration of fluoride, then that will shift the equilibrium toward the right. So again, either adding more water, adding acid, or heating the solution would increase the solubility. All right, so for today's lesson, I'm going to start with entropy. Now, entropy is famous, or maybe I should say infamous, for being poorly understood by students. It's a difficult concept to teach. Many teachers try to use analogies, and the analogies sometimes create misconceptions. So one of the most common analogies for entropy is disorder, randomness, chaos, a messy room, a shuffled deck of cards that's dropped on the floor so that the cards are scattered. So the problem with saying entropy is disorder is it's actually more complicated than that. I'm not going to go into the great details today of things like microstates, but I'm going to go ahead and define entropy in a way that will help you earn credit when you answer a question on an exam. Now, it may not be on this year's AP Chemistry exam in 2020, but for any chemistry test in which you have to justify your answer, I'm going with the statements and phrases about entropy that I find in textbooks as well as the course and exam description for AP Chemistry. So you'll see on the screen definitions of entropy that I think are helpful. So entropy is a measure of how dispersed or spread out the energy of a system is at a specific temperature. Entropy increases when matter and or energy becomes more dispersed or spread out. And we're focusing on the particles of matter or the energy itself. Entropy increases when a substance changes phase from a solid to a liquid, from a liquid to a gas, or from a solid to a gas. And all of those phase changes would increase entropy as the particles become more dispersed and spread out. And entropy increases when individual particles become freer to move and generally occupy a larger volume. So for example, if you let air out of a tire, then the gas molecules spread out to a random, more wide spread out region. Entropy increases when a gas expands into a larger volume at a constant temperature. Entropy in a chemical reaction increases when the total number of moles of gaseous products is greater than the total number of moles of gaseous reactants. So if you go from 2 moles to 3 moles of gas, that would increase the entropy. And you may remember seeing Boltzmann distribution curves. I'll just try to sketch one here real quick. So we typically are talking about something like kinetic energy or sometimes molecular speed. So I'll just put number of molecules here. And then this could be either energy or speed. Speed or sometimes kinetic energy. I'll just say KE for short. So you'll notice that when you switch to a higher temperature, this would be a higher temperature, that the area under the curve stays the same, but there is a broader distribution of the energies. So again, entropy can be thought of as a dispersal of the energy. So when the temperature increases, the entropy of the system increases. Now where on your equation sheet do you find entropy? Well, again, this is our formula for calculating delta S. If you know the entropy of the products and the reactants, you may recall that we've already done work with this equation in Unit 6 talking about thermodynamics and thermochemistry. So the delta H of formation, the enthalpy of formation of the products minus that of the reactants. What's also interesting to note is that while the delta H of formation for an element in its standard state, a pure element in its standard state by definition is 0. Here, these values for elements are not 0. So the delta H has to do with enthalpy and the heat involved, the energy involved in the formation of 1 mole of a substance. Well, you're not going to form 1 mole of an element from an element. So these already are elements. So by definition, they would be 0. But since we're not talking about enthalpy, but rather entropy, the only thing that would have an entropy value of 0 would be a pure crystal that is at absolute 0. So you'll find that if you look up in a table, the entropy values, they will always be a non-zero number. There's a slightly different situation for aqueous ions. Aqueous ions are defined relative to H+, and so you will see a 0 for that. But for a pure substance, solid, liquid, or gas, as opposed to aqueous ions, you will never find a 0 in these tables. All right, so I have a equation, and this equation involves 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia, NH3. These are all gases. So think about what I mentioned earlier about the entropy change for a chemical reaction and make a prediction. Should the delta S, the change in entropy for this particular reaction, which goes from 4 moles of gas to 2 moles of gas, should that be positive or negative? So here's a hint. If entropy is increasing, the delta S is positive. If delta S is negative, it means the entropy is decreasing. So think about what happens when you go from 4 moles of gas to 2 moles of gas in terms of the change in entropy. All right, let's go ahead and do the calculation. So we'll do products minus reactants. That would be 2 times the number for NH3 minus the number for nitrogen, and then also minus 3 times the number for hydrogen. And then this math works out to be negative 198.3. So hopefully that agrees with what you had predicted, that when you go from 4 moles of gas to 2 moles of gas, the entropy decreases. And so that's why the delta S is negative. Let's take a look at a few more examples of this concept. Here we have the conversion of ozone, which is O3, to molecular oxygen, O2. Think about whether you should increase or decrease entropy. We're going from 2 moles of gas to 3 moles of gas. So 3 times the number for molecular oxygen, that's the products, minus 2 times the number for ozone. So now we get a positive value, but this should make sense to you. To contrast to the last example, now the number of moles of gas is increasing from 2 to 3, so the entropy increases and we have a positive delta S. All right, here's a phase change from liquid water to steam or water vapor. So think about whether entropy should increase or decrease for this change. Going from a liquid to a gas, think about what the particles are doing, whether they are more spread out or closer together or farther apart. So we'll go ahead and take the 188, which is the number for water vapor, minus 69.9, the number for liquid water, and we get a positive delta S. So as you go from a liquid to a gas, that is a phase change in which entropy is increasing. Here we have 2 moles of solid sodium reacting with 1 mole of gaseous chlorine to produce 2 moles of solid sodium chloride. So think about whether that entropy should increase or decrease and whether the sign of delta S should be positive or negative. So we'll take 2 times the number for NaCl minus 2 times the number for sodium plus the number for chlorine. So we're starting with 2 moles of solid and 1 mole of gas, and we're ending with 2 moles of solid. So hopefully your prediction came true and that the delta S is negative. This tells us that entropy is decreasing as we are converting from essentially a gas and a solid to just a solid. So there are less degrees of freedom and there are fewer arrangements of the molecules and the particles as you go from a gas to a solid. Okay, so I talked about entropy. I would like to also talk about free energy and thermodynamic favorability. Some textbooks, and depending on your teacher, the teacher might use this phrase, will use the term spontaneous. But the AP course and exam description tends to avoid the word spontaneous, and they instead prefer the phrase thermodynamically favorable. So what exactly is free energy? Well, the amount of energy that is free or available to do useful work. And so if I say a reaction is favorable or thermodynamically favorable, that typically means that it happens all by itself and that can be used to do work on the surroundings. Otherwise, if the reaction is not favorable, then the surroundings would essentially need to supply energy to the system to make that reaction happen. So the delta G is our symbol for the Gibbs free energy change, and we're talking about the little superscript 0 means standard conditions. That's typically 1 molar for aqueous species, 1 atmosphere or 1 bar for the pressure of gases, and standard temperature 298 Kelvin for thermodynamic standard conditions. Now earlier we said that delta S was positive, that meant it was increasing entropy, and if delta S was negative, then entropy was decreasing. So with free energy it goes like this. If the change in free energy is negative, then the process is favored to occur at standard conditions, so you actually would have a positive delta G indicating it's not favored. A negative delta G indicates that it is favored. Now this is not kinetics, this is thermodynamics. So whether it's favored or not says nothing about the rate of the reaction. It could be fast or it could be slow, but if the delta G is negative, this is where I talked about that word spontaneous before. We tend to avoid the word spontaneous because some people have the connotation that spontaneous means fast, and so we're not talking about the rate. So thermodynamically favored just means it's going to happen whether that takes 5 seconds or a year. One way to calculate the value of delta G is very similar to the equation I showed you earlier, products minus reactants, where you have a table and you'd be given the standard free energy change for individual chemicals, the free energy of formation. Another way to calculate delta G, and these equations are on your equation sheet, is the Gibbs free energy equation involving all 3 of these concepts: free energy, enthalpy, delta H, and entropy, delta S. These are all combined, and the T stands for the absolute temperature in Kelvin. All right, so free energy and thermodynamic favorability. Well, there are essentially 3 possibilities for delta G. It could be negative, positive, or 0. If delta G is negative, as I said, it means it's favored. The forward process, as in the reaction as it's written from left to right, is favored to occur. But if delta G is positive, then the forward process is not favored to occur. Instead, the reverse process would be favored. Or you could say that energy must be supplied from the surroundings in order to get the forward process to occur. Now, delta G is neither positive or negative. This often happens for a phase change, where, for example, you're melting ice and you're exactly at 0 degrees Celsius or 273 Kelvin. So neither the forward or the reverse process is favored if you have this perfect equilibrium situation, where essentially both the forward and the reverse processes are happening at the exact same rate. Otherwise, if K, the equilibrium constant, is large, you're favoring the products, and if K, the equilibrium constant, is very, very small, you're favoring the reactants. And we'll talk about the relationship between free energy and the equilibrium constant a little bit later in this lesson. All right, so here's some examples of products minus reactants. Notice that the delta G of formation for a pure element is 0, as it was for enthalpy, the enthalpy change of formation. So I have the synthesis of liquid water from the elements hydrogen and oxygen. Products minus reactants gives me a value of negative 474.4 kilojoules per mole of reaction. So what does this negative delta G tell me about the thermodynamic favorability of this synthesis of water? Well, you may have heard of the Hindenburg airship that burst in flames, and again, hydrogen was inside the ship. You may have done experiments in your chemistry class involving a little popping sound as a test for hydrogen gas. Hydrogen, the combustion of hydrogen, although it does need a spark or an ignition source to get started, it is thermodynamically favorable. So once you can get the reactants over the activation energy barrier, which is what that spark is doing, doing, then the reaction starts and it proceeds on its own. And one of the examples of free energy, how it can do useful work on the surroundings, is the launching of something like the space shuttle. So that's powered by hydrogen and oxygen. So obviously doing very useful work in that situation. What if I take the synthesis of water and write it backwards? If the forward process is favorable, then what do you think about the reverse process? Well, hope you understand if I take negative 474.4 and just flip it around, I now have a positive. So this is not the synthesis of water, but rather the decomposition of water. So the electrolysis of water can occur. It's not thermodynamically favored. It doesn't happen all by itself. So energy in the form of a battery or some power supply must be provided from the surroundings to the system for that reaction to occur. Here's another example of a decomposition equation reaction. This is hydrogen peroxide, H2O2. I'm going to go ahead and think about hydrogen peroxide in terms of what you might find in your medicine cabinet somewhere at home. I'll do the math of products minus reactants, and I come up with a negative value. Now, the decomposition of hydrogen peroxide is favored, however, without an enzyme. So when you pour hydrogen peroxide on a scrape or a cut and it fizzes and foams and sometimes stings, the enzymes in your skin called catalase are making that reaction go faster. You can also add various chemicals like potassium iodide or manganese dioxide to catalyze the reaction. Just because it's favored doesn't mean it's fast or slow. So remember that in general, thermodynamics will only tell you if it's favored or not, but it says nothing about the speed with which the reaction occurs. In general, if the activation energy tends to be relatively high, then the reaction will usually occur rather slowly. So if you are asked a question, explain why, although a reaction is favorable, it doesn't seem to occur at a very observable rate, you can talk about the activation energy being high, and that's why the rate of the reaction is slow. All right, here's another reaction. This is the decomposition of calcium carbonate, which is found in limestone, and it decomposes to calcium oxide and carbon dioxide. So we now have data for delta H and enthalpy of formation, and we have S, so entropy. We'll do products minus reactants for each of these sets of tables. So I have products minus reactants, and I get a delta H of positive 178.5. This indicates that the decomposition reaction is an endothermic process. We're going from 1 mole of solid to 1 mole of solid and 1 mole of gas. Now, gas has typically more entropy than solid because the particles are freer to move around. There's more arrangements of gaseous molecules than solid particles. So I would predict that the delta S is positive, and that's what happens when I do this math. So I did products minus reactants using the numbers in the table on the left. Entropy increases as 1 mole of solid is converted into 1 mole of solid and 1 mole of gas. Particles are freer to expand into a larger volume. Let's put these two things together. We have a delta H, which is positive 178.5 kilojoules per mole, and we have a delta S, which is positive 159.0 joules per mole Kelvin. Now notice what I did because I was worried about units. So I converted by dividing by 1,000. I went from joules to kilojoules because I wanted the units of delta H to be the same as the units of delta S. So watch out for that if you're solving problems. Pay attention to your units. All right, so delta G would be delta H minus T delta S. Is the decomposition of calcium carbonate thermodynamically favored to occur at 298 Kelvin or 25 Celsius? So there's our equation. We'll plug in our numbers, and again, notice I've changed my delta S into units of kilojoules, so it will match. The kilojoules are going to be present in my final answer. The Kelvin will cancel out, and so I did this math, and I got a positive value. So the answer to this question is no. The decomposition of calcium carbonate is not thermodynamically favored to occur at 25 degrees Celsius. Well, what if I choose a different temperature? It is an endothermic reaction, so maybe I have to heat it up. I'm just going to go ahead and make up a new temperature, and we'll do this calculation again. So is this decomposition favored to occur at 1,000 degrees Celsius, which would be 1273 Kelvin? I'm going to go ahead and assume that the delta H and delta S values are going to remain the same. That's my assumption. All I'm doing is plugging in a new number for the temperature. And now when I do this math, the delta G is negative. So it is favored to occur at 1,000 degrees Celsius, but it was not favored to occur at 25 degrees Celsius. So my next question is kind of related to these two results. Determine the minimum temperature that would be required in order for this reaction to become favored. So how do I switch from not favored to favored? Well, I have to heat it up, but at what point? What's the minimum temperature that would be? If delta G is equal to 0, then neither the forward or reverse process is favored. This would be the point at which it switches. So I'm going to go ahead and solve the equation. I set the delta G equals 0, which means that delta H equals T delta S. Divide both sides of the equation by delta S. Again, watch out for units. So we have kilojoules on both the top and the bottom. Now I'm going to get my answer in units of Kelvin. So around 850 Celsius would be the temperature that would be required at least to make this reaction occur. Okay, so I'm going to talk a little bit more about the connection between free energy and temperature. Now, focusing on our delta H and our delta S, there are 4 possibilities. We have in the first row of this table here what I'm going to call this a best case scenario. And then the next row of the table I'm going to call this a worst case scenario. And then in these examples, I would say in general, it depends. Well, it depends on what? It depends on the value of the temperature. So in terms of the T and the delta H minus T delta S, then that temperature is going to be important in certain situations. Okay, so best case scenario, if delta H is negative and delta S is positive, then delta G will be negative no matter what. So favored at all temperatures. Unfortunately, if we go the other way, delta H is positive and delta S is negative. Hopefully you can see by plugging those values into the free energy equation there at the top left, that's going to make delta G positive no matter what. So not favored at any temperature. Now, if they're both positive, delta H and delta S are both positive, then you would want this portion of the equation to get your focus. So if delta H is positive, that's not going to help our situation. We're trying to get delta G negative. So that would only be favored whenever the value of T is relatively high. And if instead delta H is negative, so that's a good thing. But now the delta S is positive. If T is rather large, if delta S is negative. If T is rather large, you have a negative times a negative. So that's actually going to make this term positive and is going to lead to a potentially positive delta G overall. You want the T to be low. So I'm going to go ahead and explain a little bit more about these last two scenarios. When I say favored at high temperatures or low temperatures, what does that mean? These are my it depends situations. Okay, so I want delta G to be negative. That means it's favored. This is not helping me. However, this is a good thing and therefore could potentially make the overall value of delta G negative as long as this T is large enough. So you want a high value for temperature because then this portion will be negative and make the overall delta G negative. You can also think of this in terms of the Châtelier's principle. So we have a positive delta H, which means we have an endothermic reaction. You may recall from an earlier lesson that as temperature is increased, the endothermic reaction will shift in the direction of the products that would make the reaction more favorable. So an endothermic reaction tends to be favored at high temperature. Now, if we do the same kind of scenario here, we have delta G is negative. We want this to be negative. So therefore this part, which is the delta H, that's a good thing. But unfortunately, a negative times a negative is a positive. So we do not want this term to overwhelm the delta H. So therefore, only at low temperatures would this reaction be favorable because if T gets too high, then the T delta S term might have a greater magnitude than the delta H. So low temperatures. And going back to the Châtelier's principle situation, if you raise the temperature too high, then what that can do by shifting the equilibrium toward the reactants, it can decrease and potentially make your reaction unfavorable at relatively high temperatures. All right, well, hopefully that helps you understand a little bit more about the temperature dependence of delta G. You might sometimes see a question that asks you about what drives a particular chemical reaction. Like what's the driving force? And there are 3 possible answers. The reaction is driven by enthalpy only, which is delta H. It is driven by entropy only, so delta S, or it's driven by both. Well, if you had a negative delta H and a negative delta S, again, the example being that we're trying to get delta G negative. So this would be a good thing, and this would not be a good thing. So focusing on the enthalpy only, if delta H is negative and delta S is negative. Now driven by entropy only, if you had a positive delta H, this cannot be the driving force because again, you're trying to get delta G negative. This positive delta S is helpful because again, that makes this T delta S term overall with that negative sign there, that can potentially be the driving force. So it can be driven by either a negative delta H or it could be driven by a positive delta S, or if you have both, that's your best case scenario, then it's driven by both. All right, let's talk about free energy as it relates to equilibrium. You should know that K is either more than 1 or less than 1, indicates something about products being favored or reactants being favored. So if the delta G is negative, then we are favoring the products and K is greater than 1. If delta G is positive, we are favoring the reactants and K is less than 1. And there is an equation on your equation sheet that looks like this. So if you look at the natural log portion of this equation, the natural log of a number that is less than 1 will be negative. So a negative times a negative is going to give you a positive positive delta G. But the natural log of a number that is greater than 1 will be positive. So you'll end up with a negative delta G. Now, as far as the R, that's the ideal gas constant, we're going to be using this particular value of R because it has joules attached to it. So pay attention to your units. When you have to use a particular value of R that involves delta G in this equation, you want to use 8.314, and that has units of joules per mole kelvin. All right, I want to talk about free energy of dissolution, then we're going to do some AP chemistry practice. Dissolution means dissolving in water. So I have a chemical called ammonium nitrate, NH4NO3, and I've got some delta H of formation data and entropy data on the left. So the dissolution of ammonium nitrate. What about the delta H or the enthalpy? If we plug in the numbers from the table, we get a positive value. Now you may know this. If not, it's a little fun fact to know. There are some things called instant cold packs. I might have mentioned them in an earlier lesson. Instant cold packs typically contain a substance like ammonium nitrate. And when dissolved in water, there's a little pouch of water on the inside of the bag. So you kind of twist the bag until that little pouch of water breaks. As it dissolves, everything gets cold. So an endothermic dissolution means that the surroundings are actually donating heat to the system and the surroundings get colder as a result. So there's our positive delta H. We're going from 1 mole of solid to 2 moles of aqueous ions. If I calculate delta S from the data in the table on the left, I get a positive delta S indicating that entropy is increasing. So we might say that the particles are freer to move around as they have broken off the crystal lattice and now can move more freely throughout the aqueous solution. So a positive delta H and a positive delta S. I'm testing you here. What's our value of delta G? I'll give you a hint. This is a soluble ionic compound. It's very soluble. So what would you predict your delta G to be? Positive or negative? If this reaction is going to occur, I'm going to go ahead and plug in the numbers. Again, watch what I did there is I divided the delta S by 1,000 so I can get my units in kilojoules. So pay attention to that. And the delta G is in fact negative, negative 4.3 kilojoules per mole. So the dissolution of ammonium nitrate is favored to occur. Is this process driven by enthalpy only, entropy only, or both? So consider the sign of delta H and delta S. Which one or both is driving the dissolution of ammonium nitrate? Well, as I mentioned earlier, when you have a positive delta H and a positive delta S, again, the positive delta H indicates it's endothermic. That can never be a driving force. But a positive delta S absolutely is a driving force. So this is driven by entropy only. So in terms of the dissolution process, you can think of the dissolution of an ionic solid in 3 steps. Now these steps all happen simultaneously, but let's break it down into 3 separate events. You have the solute, which is the crystal. So that's going to be breaking the attractions, and that would be an endothermic process. So delta H is positive. It's also going to create more freedom of movement, so more arrangements. So delta S is positive. Entropy and the free movement is increasing there. So entropy is increasing. You have to break up some solvent interactions. That will also lead to a positive delta H. Again, anytime you break an attraction or a bond, you're breaking attractive forces that requires the input of energy, so endothermic. And again, we're pulling the particles apart from each other. So again, positive delta S. Now, whenever the solute and the solvent form these ion dipole forces, there's actually slightly less degrees of freedom for the ions that are now hydrated. So that's actually going to result in a negative delta S. So a reduced degrees of freedom there for those particles that are bound to those water molecules. Again, when you form an attractive force, that is going to release energy. So breaking a bond absorbs energy, forming a bond releases energy. So negative delta H and negative delta S because of a slight decrease in entropy. All right, so I've got some AP practice problems to do, and then we'll wrap this up here. Okay, so here are some practice problems that relate to entropy, enthalpy, and free energy. We have an equation. A student designs an experiment to study this reaction, and in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering that the flask gets cooler as the reaction proceeds, what drives the chemical reaction here? So if it gets colder, like the ammonium nitrate dissolving in water, when it gets colder all by itself, that is an endothermic process. That would be a positive delta H. That is not going to be the driving force. But we know that it does occur. It definitely happens. There's formation of bubbles. So this reaction does occur, but it's driven by entropy only. So reactions are thermodynamically favorable when delta G is negative. Since the reaction is endothermic, the flask gets cooler, delta H is positive. The reaction is not driven by enthalpy because enthalpy does not help make delta G negative. Because there are no gases in the reactants and one of the products is a gas, delta S must be positive, which helps to make delta G negative. So driven by entropy in the formation of the gas, increasing entropy. All right, here's a new question. You might have a little deja vu on this question. We did talk about this in an earlier lesson in Unit 6. This is calculating the delta H by doing bonds broken minus bonds formed. So you may have to watch that earlier lesson because I'm going to go ahead and just cut to the solution there that I'd already shown you in an earlier video. So it's a conversion from fulminate acid to isocyanic acid. That's 1 mole of gas going to 1 mole of gas. And we have now calculated from the bond enthalpies that the reaction is exothermic, so negative delta H. A student claims that the reaction has a delta S close to 0. Explain why the student's claim is accurate. So we're not changing phase here, and we're not changing number of moles. So the change from fulminate acid to isocyanic acid is a rearrangement of the atoms, but there's no change in phase and no change in the number of molecules. So delta S should be pretty close to 0. Which species, the reactant or the product, is present in higher concentration? This is our connection between delta G and the equilibrium constant. Well, we know that delta G equals delta H minus T delta S. We've already established that delta H is negative, and delta S is pretty close to 0. So therefore, delta G is essentially equal to delta H. So we have roughly negative 246 kilojoules per mole for our delta G. That means that the reaction is favorable. Since delta G is negative, that means that K, the equilibrium constant, is greater than 1. There should be more products than reactants. So the product, isocyanic acid, will be present in higher concentration. We made the connection from delta G to the equilibrium constant being greater than 1. All right, here's a new practice problem. We have an equation between NO and NO2, so nitrogen monoxide reacting with nitrogen dioxide to produce N2O3. We have to calculate the value of the equilibrium constant, and we are given the delta G in the table. So we're going to calculate the value of the equilibrium constant by rearranging this equation, which is given to you on the equation sheet. I'm going to divide both sides by the negative RT, and then I have to do the opposite of a natural log, which is the E raised to that power. Now be careful that you have to focus on your units because this delta G is in kilojoules, but the R, the ideal gas constant that we're pulling off the equation sheet, is in joules. So watch out, you don't put in 0.87 on the top there, but rather 870 because that would have units of joules. Alternatively, you could have divided 8.314 by 1,000. So either one, just pay attention to your units. I did this math, and I got that my K happens to be a little bit less than 1, so it's 0.7. Next part of this question says, if the pressure of the nitrogen monoxide is 1 atmosphere, and the pressure of the nitrogen dioxide is also 1 atmosphere, will the pressure of the N2O3 be 1 atmosphere at equilibrium? Look at that value of K. Is that relatively large or small? K is less than 1. That means that this reaction does not go to completion. The only way the pressure of the N2O3 would be 1 atmosphere at equilibrium is if the reaction went to completion. Since K is less than 1, this indicates that there will still be a certain amount of reactants present at equilibrium, so we disagree with that particular question there. A student hypothesizes that increasing the temperature will increase the amount of N2O3. Okay, so if you raise the temperature, are we going to shift this equilibrium toward the formation of N2O3? Well, that would be true if we have an endothermic reaction, but we don't. We have an exothermic reaction, so I disagree with this hypothesis. This reaction will be exothermic because delta H is negative, so therefore with an exothermic reaction, increasing the temperature will actually shift the reaction toward the left. The reactants, this would cause the amount of N2O3 to go down, not up. All right, so some more practice problems. Here we have the dissolution of a chemical. This is called urea, and it's featured right up here. And it says calculate the concentration of the urea. So we're given information about grams. We can definitely convert from grams to moles, and then moles divided by volume in liters. So that problem gives us 17.9 moles per liter. The student also determines that the concentration of urea at 25 degrees Celsius, not 20, but 25 degrees Celsius, is 19.8. So what just happened is we raise the temperature and we increase the concentration. That results in a shift toward the products. That indicates that the reaction must be endothermic because when we raise the temperature, we increase the concentration of the product. That's the Châtelier's principle. This is about a procedure for making the reaction. Well, actually not really a reaction, but a dissolution. And it says list the specific measurements that are required. So you don't actually have to write a procedure. I'm sorry. You have to actually write the measurements. And the measurements would include, let's measure the mass of the urea area, the mass of the water, initial and final temperature. There were students on the AP exam that got this question correct, but they wrote an entire procedure. Didn't have to do all of that. Just simply list the measurements. Delta T, by the way, is not a measurement. So initial temperature, final temperature, those are measurements. All right, so we have an entropy. Delta S is 70.1. That's products minus reactants. So we have 70.1 equals the product, which we don't know right now. That's the question mark in the table, minus the reactant, 104.6. And we just solve and we get 174.7. I'm going to tell you right now that looking at the clock, I know I wrap this up pretty quick, so I want to thank you for hanging in there with me. The good news is there's not going to be any homework in today's lesson. So I'm going to explain that in just a second. But feel free to pause the video because I am going kind of fast through these last few slides to finish up our discussion of free energy, entropy, and thermodynamics. They're asking for a particle level explanation for why the delta S is positive. It has to do with the fact that the particles are more free to expand and move around. Definitely want to talk about the particles in this case being more free to expand and move around or have a greater number of possible arrangements. So delta S is positive for the dissolution of urea. And student claims that the delta S contributes to the favorability. We already know that this is an endothermic process. That was mentioned earlier in this question. I'm not sure if I talked about that, but anyway, it is an endothermic process. But we're talking about delta S specifically here. So a positive delta S will lead to a negative delta G. So when delta S is positive, yes, this does contribute to the favorability of the dissolution. Now the reason why there is no homework is that next week, Mr. Byrne and I will be teaching lessons focused primarily on AP practice. So that means that our practice will happen in the lesson. So no AP chemistry questions to practice because we'll be doing a lot of FRQ practice. So today's lesson was on Unit 9, Entropy, Free Energy, and as it relates to thermodynamic favorability. I want to remind you to check out the helpful chemistry resources in the video description. And this has been Michael Faribault from Albemarle High School in Charlottesville, Virginia. Today is the deadline. If you have not contacted the College Board about your need for mobile tools or connectivity, let them know by filling out the survey at cb.org/test. So next week we'll do lots of FRQ practice in preparation for the AP chemistry exam. Thanks for watching. Have a good weekend.